Hello everybody, and welcome to the free code camp Blockchain and Solidity Beginner to Expert Full Course Python Edition. We're going to go through everything you need to know for developing on a blockchain using Solidity and engaging in the future of finance. We're going to cover topics that will teach you all the skills you need to become a smart contract expert that you can take with you no matter which blockchain you're developing on. Blockchain engineers are in extreme demand, and they're building billion-dollar applications almost every day at this point. At the time of filming, protocols like Aave, Finance, and Synthetics have billions of dollars of locked value in them, allowing people to engage in decentralized finance, or DeFi. This allows people to make censorship-resistant moves and so much more. Some of these protocols with billions of dollars are even less than a year old. So whether or not you're brand new to this space or you've been in here a while, hi, my name is Patrick Collins and I live in the smart contract world. I'll be taking you through your journey to becoming a blockchain and smart contract expert. A little bit of background on myself. I'm an engineer and developer advocate on the Chainlink protocol. And I also have my own blockchain infrastructure company called AlphaChain, where I run different nodes and different infrastructure for blockchains, including one of the main technologies we're going to be talking about today, which is Ethereum. I love being a pioneer in the smart contract ecosystem, and I love taking new users like yourself along to the journey with us. And we are going to teach you to become a smart contract expert. Building blockchain and Solidity applications is building a world of more trust and accountability. It means building a financially free future, and we get to be the ones that will go down in the history books as the pioneers of this space. Additionally, blockchain and smart contract engineering skills are some of the most sought after in the world, with an average salary of a Solidity developer being between $150,000 and $175,000. In this video, we're going to teach you how to become one of these developers and go out into the world and participate in the world of smart contracts and the world of blockchain. This course is ideally for engineers who know a little bit of Python programming, and you can have any level of smart contract engineering. Whether you're a complete beginner to blockchains and you don't even know what one is, or you're an advanced Solidity engineer and you're looking to learn more, this is the perfect place for you. Having a little bit of experience in other object-oriented programming language like JavaScript as well will be helpful here too. And if you're brand new to coding in general, that's all right, because we're going to take you step by step through everything. If you do want a little bit more in-depth Python coding video, there is a fantastic free code camp video in the description. If you do prefer JavaScript, we will also be releasing a JavaScript edition of this video as well. But everything that you learn here will be applicable there, and if you watch both, you'll learn even more.
You can find the entire itinerary for this entire course along with all of the code associated with everything that we do, and additionally discussions and support and everything else in this Smart Contract Kit / full blockchain Solidity course Pi GitHub repository. It has a table of contents and then the entire itinerary of everything that we're going to go over in this course. And like I said, with helpful tips, resources for getting support, and resources for getting help.
Now, for your convenience, every single piece of code that we're going to go over in this video has a GitHub repository associated with it. So be sure to grab the link in the description, grab that GitHub repository, and look through all the different repos that we're going to give you. If you ever get lost or need to refer to some code or want to copy paste some code, all of it will be there for you. It'll also be a great place to reference in the future when you're working on some project and you want to remember how to do something. So be sure to start and refer back to it as you watch this video. So let's talk a little bit about some best practices for watching this video. This space moves really quickly. So if we show you some documentation, it might be a good idea for you to open that documentation up as well, read through it as we do, so you can stay up to speed. Now, we've packed a ton of information into this video, and studies have shown if you try to digest a massive amount of information in a short period of time, your retention isn't as good. So it's highly recommended that every 25 minutes to half an hour, you take a 5-minute break, and then every 2 hours, maybe you take an additional 30-minute or an hour-long break. You can pause, bookmark areas, and come back later and learn at your own speed. There are timestamps in the description that will help you come back to where you left off. And you don't even have to go in order. If you want to bounce around from topic to topic, you're absolutely free to do so. We're also going to get really technical with the fundamentals of blockchain, and if you want to just jump right into Solidity, you can jump down the timestamps below and get right into it. And if you're watching this on YouTube, you can adjust the speed that I talk and that I give this presentation. So if I'm talking way too quickly for you, you can slow it down. Or if I'm talking too slowly for you, you can have me speed up. So be sure to set me at the pace that you like best. You are highly encouraged to pause, come back, and ask questions. The blockchain and smart contract world is a very collaborative community. So if you have questions, some of the best places that you can go, going to Stack Overflow and tagging your question with the specific technologies that you're working on, make an issue on the GitHub repo that we're working with, go to Stack Exchange ETH and make a question there as well, jump into the Discord of the technology that you're working with, or even on GitHub discussions if those are there. Learning to become a blockchain and Solidity engineer is actually a lot more than just learning Solidity. Becoming comfortable with all the tools in the space is going to be just as essential as becoming familiar with Solidity itself. And continuing the conversation on maybe Twitter or Reddit or any of these other channels, and maybe even showing your stuff in the next Ethereum or Chainlink hackathon are going to be majorly beneficial to increasing your skill as an engineer. Now, before we get actually coding, a lot of people want to understand what is actually happening with all this blockchain stuff. What is blockchain? What is a smart contract? How did this all get started? And understanding these core fundamentals will actually shape the way you code and architect your smart contract applications. So learning these is really, really critical. However, if you're already familiar with blockchain and you just want to jump into the Solidity, feel free to grab a timestamp from the description and jump to that section. Now, since you're here though, you've probably heard of Bitcoin before. Bitcoin was one of the first protocols to use this revolutionary technology called blockchain. The Bitcoin white paper was released by the pseudo-anonymous Satoshi Nakamoto, and it outlined how Bitcoin could be used to make peer-to-peer transactions in a decentralized network. This network is powered by cryptography and allows people to engage in censorship-resistant finance in a decentralized manner. Due to some of the features of Bitcoin, a lot of people took it to be as a superior store of value over another asset like, let's say, gold. And that's why it's commonly referred to as digital gold. Similar to gold, there is a scarce and set amount of it on the planet, and people use it to buy and sell, similar to other assets. You can read more about the original vision in the white paper, and there's a link to it in the description. Now, this was a fantastic breakthrough, and in a little bit, we're actually going to look through how blockchains can actually work and how all of this is possible. But some people took this and saw this technology and thought that they could do even more. A few years later, a man named Vitalik Buterin released a white paper describing a new protocol called Ethereum, which used this same blockchain infrastructure, but with an additional feature. And in 2015, they released this project called Ethereum. Him and a number of other co-founders took this blockchain technology and applied it in ways that people can make entire decentralized applications, decentralized organizations, and build smart contracts and engage in agreements without a third-party intermediary or centralized governing force. Their idea was to take the same pieces that made Bitcoin great and add smart contracts to it. And in fact, this technically wasn't even a new idea. Back in 1994, a man named Nick Szabo proposed a technology called smart contracts. A smart contract is a self-executing set of instructions that is executed without a third-party intermediary. They come to life on a blockchain. And these smart contracts are really going to be the core thing that we're going to be working with and we're going to be developing. Smart contracts are similar to regular traditional contracts that people make between each other. But instead of writing these contracts down on pen and paper or typing them on the computer, it's entirely written in code. The terms of the agreement are written in code and automatically executed by the decentralized blockchain network instead of being written in pen and paper and executed by the 2 parties or 3 parties or however many parties involved. This was one of the main differentiators between the Ethereum protocol and the Bitcoin protocol. Now, technically, Bitcoin does also have smart contracts. However, they're not Turing complete, meaning that they don't have the full range of capabilities as a Turing complete application like Ethereum. This was actually an intentional move by the Bitcoin developers. They view the Bitcoin network as an asset, whereas Ethereum and the Ethereum developers viewed that asset as an asset and also a utility for people to build these smart contracts. Now, these smart contracts are revolutionary technologies, and we're going to talk a little bit more about what their advantages in a little bit. But they actually come with a fatal flaw with what's known as the oracle problem. These blockchains are deterministic systems, and we'll learn why they're deterministic very soon. And this determinism means that they're a walled garden, meaning that everything that happens in these smart contracts and on this blockchain happens in this little box. Now, of course, if we want these smart contracts to actually be these digital superior agreements, then they need some way to interact with the real world and get real data and external outside the blockchain computation. This is where oracles come into play. Oracles are devices that bring data into a blockchain or execute some type of external computation. So great, so oracles are the solution. Now blockchains can talk to the real world, right? Well, not quite. Our blockchains and smart contracts are these decentralized applications. And in order for them to stay decentralized, that means they would also need to get their data and external computation from a decentralized manner as well. Your on-chain logic will be decentralized on the blockchain, but you'll also need your off-chain data and external computation decentralized as well. Combining these on-chain logic settlement layers and these off-chain data and external computation builds what's called hybrid smart contracts. And a large majority of DeFi applications and the largest applications today are these hybrid smart contracts. This is where the protocol Chainlink comes into play. Chainlink is a decentralized modular oracle network that allows you to bring data into your smart contracts and do external computation. And it's these hybrid smart contracts that can have this on-chain settlement and interact with the real world in some meaningful way. Chainlink is an incredibly powerful oracle network because it allows us to get data, get randomness, do some type of upkeep, or really customize our smart contracts in any way we want and elevate them to do anything that we want them to do. Now, throughout the course, when we're talking about smart contracts, oftentimes we are also talking about hybrid smart contracts. Smart contracts is used a little bit interchangeably with hybrid smart contracts, but just know that when we say hybrid smart contract, we're talking specifically about smart contracts with an off-chain component. Now, throughout this video, you'll hear people say smart contract, you'll hear people say decentralized protocol, decentralized application, or DApp, and they kind of all are a little bit interchangeable. A decentralized application is usually a combination of several smart contracts, and when we start coding some Solidity, you'll see what a singular smart contract or singular contract looks like. Smart contracts are going to be what we code, write, and deploy for the majority of this video. And learning some of these fundamental concepts will allow us to be better smart contract and better Solidity developers. Now, since its inception, the Ethereum protocol has given rise to many new paradigms and industries, including DeFi, NFTs, DAOs, or decentralized autonomous organizations, layer 2s, and so much more. And a couple of other protocols have taken this Ethereum vision and gone in a different direction with it, like Polygon, Polkadot, or Avalanche. If we learn the core basics of smart contract development on the Ethereum platform, all of these skills translate to these other chains as well. So don't worry about learning a specific tool or chain because most of them work together pretty seamlessly. Now, there are a few exceptions to this rule, and there are some smart contract platforms, aka blockchains, that don't use Solidity. However, learning the fundamental skills here will still translate to every single other blockchain. And Ethereum is by far the most popular and most used smart contract blockchain or smart contract protocol. You'll also hear those words used a little interchangeably as well. Sometimes I'll say blockchain, or sometimes I'll say smart contract platform, smart contract protocol, and the like. Similarly, Chainlink is the most popular and powerful decentralized oracle network, and is going to be the one that we're going to focus on here. Chainlink is also blockchain and smart contract platform agnostic, meaning it'll work on Ethereum, Avalanche, Polygon, Polkadot, or really any blockchain or smart contract platform out there. Whew. Even in this introduction, we've already learned a lot. So let's do a quick summary of what we've talked about. Bitcoin was the first application to take the blockchain technology into the limelight and into a meaningful way. Bitcoin is a sort of digital gold, able to make transactions between users as almost a sort of currency. Ethereum takes this blockchain technology one step further, but you can also build smart contract or decentralized applications, decentralized autonomous organizations, and more, because you can code with smart contracts. These smart contracts can then access external data and external computation outside the blockchain using what's called oracles. Chainlink is the most powerful decentralized oracle network and allows us to build these hybrid smart contracts, which is a combination of decentralized on-chain logic settlement layer and any decentralized external off-chain data or computation. Hybrid smart contracts and smart contracts are often used interchangeably. Now, you're probably asking yourself a lot of questions right now, like what makes Bitcoin so interesting? What makes it like a digital gold? And how are these smart contracts going to add any value to the real world? And that's what we're going to go into now. So before we get into the nitty-gritty of how these blockchains and how these smart contracts actually work from a low level, let's go high level and talk about some of the features and massive advantages that blockchains and smart contracts have over our traditional environments. The first feature that these have is they are decentralized, and you'll hear this term used a lot because it has a massive benefit. Blockchains are decentralized, meaning there's no centralized source that controls the blockchain. The individuals that make up blockchain are known as node operators, and they are the independent individuals running the software that connects the whole blockchain together. It's all these different independent individuals that make the blockchain and blockchain-like networks decentralized. We'll dive deeper into that concept later. A great example of why this is so fundamentally groundbreaking is if we go back to what happened recently, even with Robinhood and GameStop. GameStop shares were no longer allowed to be bought because a centralized entity didn't want them to be bought anymore. So they flipped a switch and nobody could buy that stock anymore, essentially having a single entity controlling the entire financial market. The fact that a single entity has the power to make these choices for us is a travesty, and blockchain is here to solve that. There's a narrative here called the bankless narrative, where users can actually live in a world where they don't have a bank. Banks, while good in their own right, have a history of doing some shady things. They also have the power to potentially freeze your funds, not letting you withdraw or move or do anything, because they are a centralized entity that again can flip a switch and control how you interact with your life every day. Being free of these centralized entities have this much power and this much control over your life has widespread positive ramifications. Transparency and flexibility. Everything that's done on a blockchain and all the rules that are made can be seen by everyone. There's no backdoor deals, there's no shady happenings. Everything that happens on chain, you can see. This means that there's no special information that a few have. Everyone has to play by the same rules, and everyone can see exactly what those rules are. Now, additionally, this doesn't mean that everything you do is tracked. The blockchain is pseudo-anonymous, so you can create different accounts and you can interact with it in many different ways. This leads me to my freedom point, but I'll get there in a second. Speed and efficiency. Have you ever tried to make a withdrawal from the bank and it took 3 to 5 days? All the bank is doing is adding and subtracting numbers. Basic first grade math. So why does it take so long? Because blockchains are verified by a decentralized collective, the settlement or withdrawal period in this case is substantially faster. And depending on the blockchain that you're using, it can be from 10 minutes all the way down to just a couple of seconds. In the stock trading or hedge fund world, it can actually take up to a week for your buy or sell of a stock to go through. Security and immutability. Blockchains are immutable, which means they can't be changed. And because of this, it means that they can't be tampered with or corrupted in any way, shape, or form. This allows us to have massive security on our data, on our transactions, and anything of the like. If your computer goes down and your backup computers go down, in the regular world, your data is gone. If all your data is on those two computers, you're out of luck. On a blockchain, if several nodes go down, it doesn't matter. Because as long as one node in the entire system is running, the data is safe and secure. There are thousands or hundreds of thousands of nodes running these blockchain softwares, meaning that everything that happens and is immutable and won't change. Hacking the blockchain is nearly impossible and substantially harder than hacking a centralized entity. And this is also much more secure in the asset sense as well. Instead of having gold in a vault or a contract written on a piece of paper or on your computer, you have an asset that is locked on the blockchain forever. And all you need to do to access it is have a private key or mnemonic, which is essentially a password. So you don't have to lug your gold around or lug your contracts around with you. It is always on the blockchain. Smart contracts in particular remove a massive conflict of interest. In the traditional world, when we engage with users or individuals, they don't always have our best interests at heart. A lot of them are usually self-motivated in some sense. And there's nothing wrong with that. That's how a lot of people are. However, when we make an agreement with them, This agreement can have a massive conflict of interest with the user who's supposed to execute that agreement. Let's take insurance, for example. If I pay an insurance provider $100 a month, I'm paying them $100, and in the event that I get hit by a bus, we've made an agreement or a contract that they're going to pay my medical bills or bail me out. However, they have this massive conflict of interest. Insurance companies aren't in the business of giving out money. They're in the business of making money. So even though they've signed this agreement, when this event occurs, they still don't want to pay this money out to me. And if they can find a loophole in the contract, they will, because that is what they are motivated to do. So they sign this agreement, but it's not in their best interest to do so. So they have this massive conflict of interest, and this is native in all of the agreements that we make today. They are the ones who decides whether or not they're going to execute their agreement. Giving execution power to the party that doesn't want to execute something has often led to frustration. Now, the follow-up is you can always sue them and go through these processes, but now you're wasting all this time going through this long process to get something that you should have originally gotten in the first place. This leads me to one of the biggest value adds of smart contracts. Smart contracts allow us to engage in trustless and trust minimized agreements. We currently live in a world of brand-based agreements. If I engage in some agreement and I don't like the service that I'm provided, my alternative to this is to waltz down the street to another brand, to another service who's going to make the exact same set of promises to me. And then I have to trust them that they're going to execute faithfully. Smart contracts allow us to move from this brand-based agreements to math-based agreements. These math-based agreements, we don't even have to trust that they're going to do the right thing, hence the name trustless. 1 + 1 is always going to equal 2 in a math world. Whatever the code determines is the input-output, that's exactly what's going to happen every single time. Now, for me, these really all add up to 2 major pieces: freedom and trustless. All these pieces allow us to live in a world that's more accountable, more trusting, more friendly, and just better. It allows us to work in an environment and a universe where things just work. It allows us to do the freedom to engage with other people how we wish, because there's no centralized controlling body influencing every action that we make. All the rules are the same and nobody's getting special treatment. This brings out this new world of economic opportunity as well. And as our lives become more and more digital, we're constantly being bombarded with centralized services that want us to use their interface so they can profit on how we interact and force us or push us to making the decisions that they're motivated for us to make. Smart contracts, decentralized applications, and blockchain allows us to be free of these repressors and live in an environment that's truly free and trustless. So with all that high level being said, let's do a quick summary of what we just learned. Blockchains are decentralized, meaning that they are not controlled by a single centralized entity. It is run by a network of independent users. Transparency. Blockchains are transparent. Everything that happens on a blockchain, everybody else can see and everybody else can work with and see that everyone's playing by the same rules. Blockchains are quick and efficient, especially when it comes to monetary policy. Settlement on blockchains are fast and easy. Immutability and security. Blockchains can't be changed or tampered with or corrupted and are incredibly, incredibly secure. Smart contracts remove the massive conflict of interest traditional agreements have. Smart contracts allow us to move away from political brand-based agreements to secure math-based agreements. Smart contracts allow us to engage in trustless and trust-minimized agreements. Smart contracts are a set of instructions which, when placed on a blockchain, are self-executing pieces of code not run by any centralized intermediary. In addition, smart contracts are typically paired with some type of oracle to get some information about the real world. When smart contracts are paired with an oracle, they're called hybrid smart contracts. Chainlink is a secure, decentralized, modular oracle network used to bring data into your smart contracts and also make some type of external computation. I also briefly want to mention DAOs, or decentralized autonomous organizations. You'll hear this referred to a lot as well. Decentralized autonomous organizations are organizations that live online and live in these smart contracts. They're similar to a regular organization in the traditional world. However, they have people who maybe hold governance tokens to make voting decisions, or they do all their governance on chain, on this decentralized settlement layer, giving us the freedom to engage with each other as we please. So now that we've taken our first dive into blockchains and smart contracts, and at least from a high level understood why they're so advantageous, let's jump in, let's get an Ethereum wallet, and let's make our first transaction on a live blockchain. Are you ready?
Now let's jump into Ethereum. We're going to make our first interaction with the Ethereum blockchain. And once we do this interaction, once we make this transaction, then we're going to go back and look at what actually happened. What were the technical implications that allowed this transaction to go through? So in order for us to interact with the blockchain, the first thing that we're going to need is an Ethereum wallet. So I'm going to go ahead and go to MetaMask because it's one of the most popular wallets and one of the easiest to use. We're going to go ahead and download it. I'm using the Brave browser, but it works for Chrome, Firefox, or really any other browsers. And it's just going to be a little extension in the top right hand of your browser. This way, we can really easily see at any time what we have in our wallet. This will store all of our Ethereum-based currencies. So I'm going to go ahead and install MetaMask for Brave, add to Brave, add extension. And now we can go ahead and get started with working with Brave. This is the first step you absolutely need to take when starting your journey and one of the easiest steps to take. So we're going to go ahead and get started. And we're going to create a brand new wallet. So we're going to go ahead and hit create wallet. If you already have a wallet, you can actually import it via I have a seed phrase. And we'll talk about this seed phrase or secret phrase in a little bit. So let's go ahead and create a new wallet. And sure, we'll agree to help out MetaMask. Now we will create our password. Make sure that this is really secure. For the purpose of this demo, my passwords are just going to be password, but please don't have that be your password. Now, when I'm doing my testing and when I'm doing my coding, I actually use a separate account from the account that I actually have real money in. However, if you want to use this account and actually put real Ethereum and put real money into it, you absolutely 100% need to back this up. So we're going to go ahead and click reveal secret words. I'm showing you guys here because this is just a demo and I don't really care. However, if you show this secret phrase to anybody else, they will have access to all the funds in your application. So everything that we're going to do in this tutorial, we're going to use fake money. We're going to use not real money, so it doesn't matter. However, if you're going to actually put money in here, you absolutely need to have this written down because if you lose access to this and or your private keys, which we'll talk about in a little bit, you will lose access to your wallet and you will lose access to all your funds. So they give some tips like store this phrase in a password manager like 1Password, write this phrase down on a piece of paper, put it in a secure location, memorize it, whatever you want to do, just make sure you have this backed up somewhere. I'm just going to go ahead and hit download this for now, and I'm going to save it on my computer. It's not best practice to save it to your computer. It is much better to use a password manager or write it down on a piece of paper or something. But again, because we're just demoing here, I'm going to show you it here, and we're not going to put any real funds into this. So we're going to go ahead and hit next, and it's going to ask us to make sure and it's going to ask us to verify that we actually have it written down. And we're going to go ahead and hit confirm. And great. And it gives us a couple other tips. Remember, definitely take these tips very seriously, especially if you're going to use this for real money. Like I said, for this demo, we're just going to use test money. So it's not as big of a deal, but if you put real money in, you absolutely need to back up this seed phrase or secret phrase, or we're going to refer to it as our mnemonic phrase. Awesome. Now we can see the user interface of this wallet. And depending on your browser, if you actually go ahead and look in your extensions, you can pin it to your browser. And you can even just click it and get the same interface here. Let's take some inventory of what is actually going on in here and what we actually have. Our mnemonic phrase, that secret phrase that we got, has given us access to a new account. And here's the address of our account. We can use a tool like Etherscan to view different addresses and what's been going on with them. So if we look at this address that we just created on Etherscan, we can see that no transactions have happened. It's empty. It has 0 Ether in it. It has $0 worth of value in it. And this address here is our unique address. This address represents exclusively this single account that we just created. We'll talk a little bit more about Etherscan in a bit, as it's a tool that we're going to use more and more. Now we can even click this circle here and we can even create more accounts and give it a different account name. We'll call it account 2. This one has a different address. So if we go ahead, go back to Etherscan and look this up, this one has a different address here. So we can have multiple addresses in here. And now if I click this, I have 2 accounts, account 1 and account 2. The mnemonic that we've been given gives us access to create multiple accounts with that same mnemonic. So having that mnemonic will give us access to every single account that's ever created with that mnemonic. This is why securing your mnemonic is so crucial, especially if you create multiple different accounts. Now each account has a unique identifier with them as well. So this right here is the public address. When we copy this, this is the public address of that account. However, there's also a private key to work with this account, a secret key. And we can go ahead and view it by clicking these 3 dots, go to account details and export private key. Put our password in and confirm. So this is going to be our private key. So this is a single password associated with this account. If you give somebody else access to this private key, they will have access to my account 2. They won't have access to my account 1 because the private key of account 2 is only associated with account 2. The mnemonic, however, is associated with all accounts. And this is why when people say store your private keys in a safe place or store your keys in a safe place, they're usually referring to both your mnemonic and your private keys. If you lose your private key, you lose access to this account. If you lose your mnemonic, you lose access to all your accounts. So long story short, back up your mnemonic since it has access to everything, and back up your private keys too, but just keep in mind they only have access to the individual accounts. And great, those are some of the main security pieces here. Now, what else is going on in MetaMask is we can see this section here that says Ethereum mainnet. If we click it, we actually see a bunch of other networks in here. So when you buy ETH and when you work with ETH, you're working on the Ethereum mainnet. When you interact with smart contracts or DeFi or any things that we're going to talk about later on mainnet with real value, you're going to be working on the mainnet. However, since we're engineers, oftentimes we're going to want to test our applications or do some type of integration tests or just make sure our code actually works. So there's also what's called testnets. These are networks that resemble Ethereum and work exactly the same way as Ethereum does. However, they're not with real money and it's just for testing your applications. So we can even go to Etherscan and look up Rinkeby Etherscan. We can see the Rinkeby Testnet Explorer. We look up at our address and it's the exact same information here. Nothing has gone on Rinkeby, and this is totally different. So when we make a transaction, these are all different networks. And if it says test network, it's made to be made without real money. Later on, we're actually going to show you how to work with other EVM compatible chains. Don't worry about what EVM compatible means for now, but we can work with Avalanche, Polygon, and other applications through this network's interface as well. So remember, a testnet blockchain is a blockchain where the currency doesn't have any real value, but it resembles and acts exactly like the Ethereum mainnet so we can test our applications. So we can test and practice our applications. In fact, what we're going to do right now is make our first transaction on the Rinkeby testnet. And this will simulate exactly what it's like to make a transaction on the Ethereum mainnet. So we're going to go to this application called the Rinkeby faucet. This is where we're going to make our first transaction. Rinkeby is going to be one of 2 testnets that we're actually going to work with. The other testnet that we're going to work with is going to be Coven. It's important to know how to switch between testnets and EVM compatible chains, which is why we're going to be working with both. For now, we're just going to be working with Rinkeby. A faucet is a testnet application that gives us free test Ethereum. Hence why it has no value, because anybody can get it for free from one of these faucets. So to get testnet Ethereum with this application, we actually have to post a tweet or a Facebook post with this tweet. So I'm going to sign in real quick. And now that I'm signed in, I can post this tweet requesting faucet funds into, and this is where I'm going to put my address on the Rinkeby Ethereum test network. I'm going to go ahead and tweet that out. Now that I have this, We're going to copy a link to tweet, and we're going to place it in here, and we're going to hit give me ether. And we're going to say 18.75 ether for 3 days. And it said funding request accepted for Patrick Alpha C into this. And what we can do then is if we take this address again, we go over to Rinkeby Etherscan. We now see that the balance is 18.75. And we can even see that in our wallet. On the Rinkeby network, we have 18.75 ETH. But again, if we look at mainnet, we have nothing there. If we look at Robson, we have nothing there. If we look at Rinkeby, we have 18.75, right? So these are very different networks. And we just made our first transaction. We've been given 18.75 ETH. And if we refresh this page, we also see that this is our first transaction that was made. Some account sent us 18.75 Ether from this account to us. And we can actually even look at the details of this transaction. Etherscan is what's known as a block explorer. Block explorers are applications that allow us to see details of things that happen on a blockchain easily. We can see the transaction details of this transaction here. And whenever we work with smart contracts, we will also see them in a transaction similar to what we're seeing right here. And again, we'll talk about that soon. Now we can see a number of information here. We see a unique transaction hash. This hash, or this unique identifier, uniquely identifies this transaction as the key of what this transaction is. We see that it was a successful transaction. This is the block number, which we'll talk about in a little bit. We see it was from this unique account, which looks like they've done a ton of transactions because this is the faucet account, to our account that we created. Value was 18.75 Ether. And then we have these transaction fees, gas price, gas limit, and gas used. Now, gas refers to the fee paid to node operators for successfully including a transaction in a blockchain. Now, exactly how this works is actually going to change pretty soon, but the concept is basically anytime you want to change the state of blockchain, whether this is sending some Ethereum or making any type of transaction, you actually have to pay a little bit of Ethereum or a little bit of that native blockchain token to actually execute that transaction. Whenever we do something on the blockchain, it costs gas. And if we do something that would take a lot of energy for the blockchain to do, it will cost more gas. So if I send a single transaction, that's going to cost 21,000 gas. However, if I were to send a transaction that called the smart contract function and did a whole bunch of other stuff, it would cost more gas. So we see here, when we got sent 18.75 ETH, whoever sent us that ETH also paid the blockchain miners or the blockchain validators a little bit of Ethereum to include our transaction. Now, we actually get to pick how much of a fee we want to send with our transactions. So let's look at another example. So in our accounts in MetaMask, let's even expand the view here. We have two different accounts. We have account 1 and account 2. Account 1 has 18.75. Account 2 has 0. We can actually send money from account 1 to account 2. And again, remember, this is all fake money. So we're going to go ahead and hit transfer between my accounts. So we're going to send money to account 2. And here's where we can see some transaction details. And we see the asset that we're going to send, which we only have Ethereum in this wallet. So we're only going to send Ethereum. Later on, we'll learn how to get different assets into this wallet. We're going to choose an amount. I'm just going to choose to send 1. And then we have these pieces here associated with the transaction fee. So we have a gas price in Gwei and a gas limit. So when we send a transaction, we can choose a gas limit. We can say, hey, if this transaction is going to spend more gas than 21,000 gas, we're not going to do it. We also get to set a gas price in Gwei, but here's the quick example of Gwei versus Ethereum. 1 Ether is this many Gwei, and 1 Gwei is this much Ether. Because if we just said, hey, could you send me 0.0000001 Ether, that would be kind of really obnoxious. So we just say, send me 1 Wei or send me 1 Gwei. So I know we've been throwing this gas term around for a little bit, but here is it basically simplified. Gas is going to be the measurement of how much computation something uses. The gas price is going to be how much it costs per unit of gas. A gas limit is going to be the maximum amount of gas that can be used in a transaction. So for example, if we make a transaction that uses 21,000 gas and each one gas is 1 gwei in price, that means we're going to pay 21,000 gwei in transaction fee. So back in our transaction, we're saying the gas price is going to be 1 gwei. So the transaction fee is going to be the gas that we use, which will be up to this gas amount, times the gas price. So it'll be 21,000 gwei will be the transaction fee. So then the question is, well, why would we ever bump it up? Why would we want to pay more gas price? Why do I even have the option to pay more? Well, and this comes down to block space. We'll talk about this a little bit more when we get into how the blockchain actually works, but the blockchain can only process so many transactions at a time, and nodes and blockchain nodes can only process so many at a time. So when I make a transaction, a node has to decide why they want to include my transaction into the block. And if there are a ton of people looking to make these transactions, then the nodes are going to be highly incentivized to pick the transactions that are going to give them a high price, that are going to give them a lot of money for including that transaction. So this is what's called ETH gas station, and it is a gas estimator of the blockchain. It currently says that if you want to get your transaction in right away, it's going to cost you 31 gwei to do so. If you want to get it in less than 5 minutes, it's going to take you maybe about 21 gwei. So the gas prices of Ethereum fluctuate with how much people use it. And the gas prices of all these blockchains fluctuate with how much people use it. So this is an important concept. So typically when you're setting your gas price in a transaction, you can take a look-see at ETH gas station and say, okay, if I want mine to go in right away, I'm going to do ASAP. If I want to go in fast, maybe I'll do this fast amount. Standard, I'll do this standard amount. But it all depends on how many people are looking to work with this blockchain at the same time. And as you can see, it fluctuates pretty quickly, right? It just went all the way up to 46. So maybe more people are using the blockchain. Now, this is obviously for the ETH mainnet, and on the testnet, there's not going to be that same competition, but we can still change it anyway. So if I go ahead and do 100 for the gas price, and I hit next, and I hit confirm, if I go to activity, I now have this transaction in my MetaMask. But I can go ahead and view this on Etherscan as well. And we can see this is what it looks like when it's still processing this transaction. And now I can see that it's passed. And now if we look at the gas price, we see it's 100 gwei. And this is what we set it as when we were working with it before. So gas price is 100 gwei here versus our first original transaction was just 1 gwei. And now if we look at our MetaMask, we can see that the funds have indeed been subtracted from this account and they have been added to this account. Now there's 1 ETH in this account. Awesome. And you can see the activity. There's 1 ETH in here. So again, the reason that these gas prices exist is because nodes can only put so many transactions into a block. So they're highly incentivized to input the transactions that are going to give them a higher fee. So in times when a lot of people are looking to use a blockchain, prices will get very high. And when very few people are using a blockchain, prices will be very low. This Etherscan tool is incredibly, incredibly powerful, and we'll be using it more and more as time goes on. Now, here's something that's incredibly exciting. With just this little bit of information, you now know how to interact with blockchains and interact with the Ethereum protocol. So if you don't want to learn how to code anything, you can go and you can start interacting with Ethereum and interacting with protocols with just this much information. However, I know most of you guys are here to learn how to code. So let's look under the hood of Ethereum and what is actually going on with these transactions and with these gas and with these blockchains and what's really going on. Let's learn all the fundamentals of a blockchain. Now, if you want to just go ahead and jump into the coding, go ahead and grab a timestamp from the description. However, learning exactly how the blockchain works is going to make you an incredibly powerful developer. So let's take a look at that first. So we're going to be going through this blockchain demo on this site right here. Now, the creator of the site has a fantastic video and a fantastic walkthrough, Blockchain 101. It is right on their site. So if you're looking for another explanation, definitely check out his video. It is absolutely fantastic. But the first thing that we really need to do in order to understand blockchain, in order to understand really anything and everything that's going on here, we first really need to understand this SHA-256 hash or hashing just kind of in general. Let's first understand what a hash is. A hash is a unique fixed length string meant to identify any piece of data. They are created by putting some piece of data into a hash function. In this example, the hashing algorithm used is SHA-256. Now, Ethereum actually uses this right here for its hashing algorithm, which isn't quite SHA-256, but is in kind of this SHA family. But it's really just another way to hash things, and the specific hash algorithm doesn't matter so much. So this example uses SHA-256, but you can imagine it's the same as the Ethereum hash. They're just going to result in a different hash. So what's going to happen in this application here is whatever data or whatever information we put into this data section here, as you can see below, this hash changes. So what's happening is this data is running through the SHA-256 hash algorithm, and it's outputting this unique hash. So this hash is a unique fixed length string that's going to identify like a blank data piece here, right? So if I put in, my name, like, Patrick Collins, this is the hash that's going to represent Patrick Collins, right? And you can see, even when I put, tons and tons of data in here, the length of the string doesn't change, right? So it's always going to be the same amount. We can put almost any amount of data in here. There is an upper limit on the max size of the data, but for all intents and purposes, we can pretty much put any length in here. And you'll see too that, every time I type in Patrick Collins, this hash is always going to be this 7E5B, right? I'm going to delete it. I'm going to do Patrick Collins again, 7E5B. It's always this unique hash is always going to be unique, right? It's always going to be this fixed length string here. So now we can take this idea, right, of putting this data in here, and we can move on to this concept of a block. So with this block concept, we're going to take the exact same thing with this hash, this data section, right? But instead of having everything just being this singular data area right here, we're going to split this data up into block, nonce, and data. So what we're going to do is we're actually going to hash all three of these to get this hash, right? We're going to put all three of these. We're going to say all three of these are combined together. We're going to put all three of them into this hashing algorithm to figure it out. So if I type a bunch of stuff here, we can see that block one with nonce, this nonce and this data, we're going to get this hash. And as you can see, actually, the screen turns red. This block turned red. Now, what happens when I hit this mine button? When I hit this mine button, it's actually going to take some time. It's going to think for a little bit. And we can see that the nonce here actually changed, right? The nonce is different from what it was before. And this hash now starts with 4 zeros. Okay, and then the back turned green. When we're talking about mining, we're talking about miners solving some type of very difficult problem that takes a lot of time to do. Now, in this example here, the problem that the miners had to solve was they had to find a nonce or a value in this nonce section that when hashed at block number 1 with this data, it would start with 4 zeros. So the problem here the miners had to solve was to start with 4 zeros. And the only way for them to really do that is kind of this brute force, trying stuff. So they tried 1, okay, 1 didn't work. Okay, 2, nope, 2 didn't work. 3, no, 4, 5, 6, okay, 5, well, that started with 1 0, but that's not 4. And they have to keep trying all these numbers until they get to this one where, let's hit mine again, where it has 4 zeros at the start. Now, this specific problem changes blockchain to blockchain, right? Ethereum has a different problem for miners to solve. Bitcoin has different problems for miners to solve, but this concept is going to be the same. So they have to take one block is going to be this concept is going to be all this data. It's going to be the block number, and it's going to be this nonce, right? And so this nonce is the solution. Is going to be the number that they use to get like the solution to the problem, right? So if I go to 1. Here, and I do this again, I'm going to hit mine, and the nonce has changed, right? It went from 1 to 33,128 because this is the nonce that allowed this hash to start with 4 zeros. And so that's what's happening when blockchain miners are mining. They're going through this process, this very computationally intensive process of trying to find a nonce that fulfills whatever the problem is. So that's really it, actually. So that's a block, and that's really what's happening when miners are mining. They're just looking, there's trial and error, brute force, trying to find this nonce. So now that we know what a block is, let's go to the next step and figure out, okay, well, what's a blockchain? So here we have an example of what a blockchain is going to look like. right? We have a combination, we have back here in the block section, we have what one block looks like. Now here we have multiple different blocks, right? Each one of these represents a different block, but we have an additional column here, or we have additional variable here. So like before, we have block, nonce, and data, right? We have block, nonce, data, but we also have this thing called previous, right? And so this is actually going to be pointing to the previous hash of the last block. So for example, if we go to the last block in this blockchain, it says previous is 00AE8. And if we look at the hash of block number 4, it's 0000AE8. And then we look at its previous, it's 40B9. We have 40B9 and so on, all the way back to our first block, which has previous of just all zeros, right? And so the block with the previous of all zeros is going to be known as the Genesis block. So you've probably heard that before, the Genesis block. It's the first block in the blockchain where the previous hash points to a hash that doesn't actually exist. Now, as you can imagine, kind of the same as how this block worked, how the block, nonce, and data all go through the hashing algorithm. In the blockchain, the block, nonce, data, and previous hash all go through this hashing algorithm to figure out, what the hash is, okay? So if we go to over here, for example, if I type in, Patrick, obviously this is now no longer valid, right? Because this nonce combined with the block, the data, and the previous hash aren't going to solve, our problem of having 4 zeros at the start, right? So I'm going to go ahead and fix that, and that's kind of an easy way to see it being broken. But let's take a look. If I break this block right here, what happens if I break the data in here? If I do like trick in here, you can see that both of these are now red. Both of these are now invalid, right? Because the block hashed with the nonce, hashed with the new data, which is my name Patrick, hashed with the previous block, is now a brand new hash, right? And this block is still pointing to this previous hash right here, right? Is pointing to this previous block, and now it is wrong and it is messed up, and now its nonce with this previous hash is also wrong, right? And this is where, when we talk about blockchains being immutable, this is exactly how it's immutable, right? Because if I go back and I change anything, if I just typed A right here, the entire blockchain is now invalidated, because none of these are going to have nonces that solve this equation anymore. So this is why blockchains are immutable, is because anytime you change one thing, you ruin the rest of the blockchain, okay? So however though, if an A was here originally, we can go ahead and mine these. We can mine all these, but as you can see, this is going to start getting very computationally expensive, because I have to go redo basically the entire blockchain. And the farther and farther down the line you get, the harder and harder it becomes to, rehash and redo all these different blockchains here. Now this makes a lot of sense, right? So we have this blockchain. It's really hard to change something in the past, but if we do, we can just go ahead and remine it. Now, if I'm the one who controls the blockchain, right? If I'm the one who controls this, and I want to change something in the past, well, okay, great. All I got to do is change this data here, and then, mine each one of these. Obviously it's going to be very computationally expensive, but it's something that I can do, right? If I'm the one who owns the blockchain. Now, here's where the decentralized nature or the distributed nature really makes it incredibly powerful. So we're going to go to the distributed tab here, which I also refer to as the decentralized tab here. And it's going to show us what a blockchain looks like in a decentralized manner. So we have this exact same initial setup here. We have distributed blockchain. We have our first blockchain, which is kind of exactly as the one from here. But we also have more than one. So we have peer A, peer B, and peer C. And when people are talking about peer-to-peer transactions, they're really talking, this is kind of that concept that they're talking about, right? So we have a number of different peers who are running this blockchain technology. They're all weighted equally, right? Each one of these peers, or each one of these nodes, each one of these entities running a blockchain has the exact same power as anybody else, right? So the way that we can tell very easily which blockchain is correct or which ones are correct are by looking at this end hash here, right? Or by looking at where we are in the blockchain. Because again, remember, this hash that this in this last block here is going to encompass all of the blocks from before, right? Because this last hash is going to have the previous hash here, which includes the previous hash here, which this hash includes the previous hash here, so this last hash encompasses everything in here, right? And we can look We can look at the hash of peer C, which is 4 zeros and then E4B. We can look at the latest hash of peer B, which is 4 zeros E4B, and then peer A, which is 4 zeros E4B. So all of these peers, all of these nodes, all of these decentralized, these independent, all these independent users running this blockchain software, they're all matched up. It's very easy for their nodes to look at each other and say, hey, great, we are all matched up. Now, let's say that A decides that, something happened on the blockchain that they didn't like and they wanted to go back and change something, right? So let's say they change here, obviously the rest of their blockchain is invalidated and they have to spend a lot of computational power to catch up to speed. So let's go ahead and humor it. Let's say that they did. They ended up catching up. They ended up mining everything. And now they have a valid blockchain, right? It solves the equation. Awesome. However, in block number 3, there's something new, right? This is here and it shouldn't have been here. This is something that peer A put in by themselves. All that happens now is we look at all the blockchains that are running the software and we're looking at all the hashes at block number 5. So peer A has this new hash now, 0009BC, but peer B has a different hash, 000E4B, right? So who's right? Is it peer A with their new stuff or is it peer B? Well, that's where the decentralizer comes in, because then we can look at peer C, and peer C also has E4B. So peer B and peer C both say, hey, peer A, you're wrong, get out, right? And peer A will stop being able to participate in the mining rewards because they have essentially forked the blockchain and started their own little blockchain, right? With their own history, because they're the only ones with this piece of data in block 3, whereas peer B and peer C have nothing in there. So that really shows why in these blockchain worlds, in this decentralized world, there really is no centralized entity. Peer A, might have been maliciously motivated to change, this block number 3. However, democracy rules, right? The majority rules in the blockchain. Peer B and peer C both say, hey, that's cute and all, peer A, but you're wrong, right? That's not right. Now, it might be a little abstract to just look at data and, us typing kind of random stuff in here and think, okay, yeah, that's data, right? That makes sense. Just kind of random strings in here doesn't really do anything for us. So if we actually go over to the token section here, this is where everything really starts to make a lot of sense. So we have the exact same setup here with peer A, peer B, peer C, except the difference is instead of having kind of this data section, we have this TX, this transaction section, right? And this represents all the transactions that are happening in this block, right? So we're sending $25 from Darcy to Bingley, $4.27 here, 1922, right? And it's the exact same thing. So all these transactions are going to get hashed in the exact same way that the data is going to get hashed. And this is why it's so powerful, because again, if I want to be malicious, right? If I want to say, hey, I really wanted to give Jane a lot more money from Elizabeth, so I'm peer A, and I go back and I change it to 100. Well, now, not only does my whole blockchain get invalidated because that was so long ago, but I'm not going to match any of these other chains, right? And so my blockchain is going to be excluded from the overall blockchain. So, and let's go ahead and fix this. And it's the same thing. If down here, if I become malicious and I want to send, I want Miss Audrey to have less money, maybe I want to send $1, and I go ahead and mine it. The same thing here. This hash now, this 2A1 is not going to match peer B's hash of BBA, and it's not going to match peer C's hash of BBA as well. So the two of them are going to say, hey, your blockchain is invalid. It's not matching the majority. You're out, right? So that's really how these blockchains work at a low level. And it all goes back to this understanding this hash idea and using it in this very sophisticated manner to kind of cryptographically prove, where stuff lies.
Now, the way the blockchain works is instead of random stuff put in this data section, it's actually going to be Solidity code in here, defining ways to interact with different blocks and different protocols that are on chain, or, as we've said before, different smart contracts.
Now, the next question that you might be asking is, okay, well, how can I be sure that I'm the one, let's say I'm Darcy, right? How can I be sure that Darcy was the one to actually send this money here? How do we know that Darcy sent $25 to Bingley? Well, this is where we get into private keys and public keys, and that's what we're going to go into now. Let's just do a quick recap of what we've learned in this section so far, right? We've learned that Ethereum actually runs on this Keccak 256, but we used SHA 256 for this demo. It doesn't really matter. We're just talking about hashing algorithms. So again, a hash is a unique fixed length string meant to identify any piece of data. A hash algorithm or a hash function is a function or algorithm that computes any type of data into a unique hash. Mining is the process of finding the solution to the blockchain problem. In our example, the problem was to find a hash that starts with 4 zeros. Whenever a node mines a block, they get paid a little bit of that gas we were talking about earlier for doing so. A block in a blockchain is basically a combination of a block, nonce, transaction, and a previous hash to create this unique hash for this block. And again, depending on the blockchain implementation, this might have a couple other fields or might have different fields, but this is essentially what's going on. Blockchains are decentralized and distributed because many independent users are going to run this blockchain software, and it will check and they will compare against each other to see which blockchains are acting honestly and which ones are acting maliciously. In the blockchain world, majority rules. The nonce here is the answer used or the number used to get this hash. Now, nonce is kind of an overloaded term. It's actually used for a number of different reasons. In this case, we're using it to solve this problem of getting 4 or 5 zeros at the stop of the hash. However, in Ethereum, it'll also be often used as the number of transactions from a given address. So now we're going to talk a little bit about signing these transactions and private keys and some other cryptography pieces, right? Because in this blockchain demo here, we can see we have all these fantastic transactions, right? All these things went through, but how do we know that it was Darcy who was the one to send $25 to Bingley, right? How do we know that actually happened? And this is where all those pieces that we just learned about in our testnet, in our MetaMask account, are really going to start to come to life here a little bit here. So here we have an example of public and private keys. Okay, at the top we have this private key, right? That was randomly generated. A private key is as it kind of states, is a key that you really want to keep secret because you're going to be using this as kind of your secret password for all your transactions, right? I can really pick any private key, anything that I want, and with it, this algorithm, they're going to use an algorithm. For Ethereum and Bitcoin, they both use this elliptic curve digital signature algorithm. It's a variant of just a digital signature algorithm, and it's going to create this public key, right? I'm really not going to go at all into kind of this digital signature algorithm, but just know it does use some of these some of the hash knowledge that we just learned, combined with some other pieces. To kind of get this public key here. So I'm not going to go too deep into it, but we have this private key that we create and we get this public key. Now this public key, we want everybody to have access to, right? This is, whole world can see this private key. We really want it to be private. We don't want people to see this. We're going to use this private key as like a password to quote unquote digitally sign transactions. And then people can verify them with this public key. So let's see what this actually looks like. Let's pick a random key, a more secure key, right? Because the longer it is, the more secure it's going to be. And if we go to signatures now, right? Let's say we have this this message that we want, right? We'd say hi world, right? We want this to be the message. What's going to happen is this private key that we've created, we can use to sign this data, right? Remember how in the blockchain demo, we were hashing stuff, right? We're using this SHA-256 hash to get this hash. Well, we're doing something similar, but instead of hashing, we're using this digital signature algorithm to create this message signature. Now, what's really powerful about how this algorithm works is that you can create this message signature with your private key, but somebody else can't derive your private key from the message signature. And that's what makes this really, really powerful. However, if we go to verify using this public key, right? And so this is that 0403. This is that same public key. Using this public key, anybody can verify. Oh, let's go ahead and sign it again. Anybody can verify that this signature is yours, right? So you have a private key just for you, so you can sign things, and a public key so that anybody can verify something, right? So anybody can verify this. And let's say somebody tries to fake a transaction from you. They say, hey, you know, this is their transaction. All they have to do is verify that this signature against your public key, and very easily this whole thing turns red because it isn't verified, right? The algorithm says, hey, that's wrong. So we can go ahead and take that into transactions in this exact same way. So if I want to send money, if I want to send $400 from, my address to another address, using my private key, I can sign that transaction. And anybody else in the world can then verify this transaction, right? And this is why when people say, hide your keys, protect your keys, this is what we're talking about. In our accounts here, right? If we go to settings, and again, the only reason that I'm showing you guys my mnemonic and my private key is because this is a dumpster account. I'm going to throw this away at the end of this video, or I'm just not going to put any real money in it. But when we look at our MetaMask here, we have this mnemonic phrase which allows us to easily get these different private keys, right? So mnemonic phrase combined with whatever account number will get us a private key. So mnemonic phrase combined with 1, we're going to get this private key. And this is when we look at account details, export private key, password confirm. This is going to be the private key that we're going to use to sign our transactions, right? This, if anybody else gets access to this private key, they then can sign transactions for us, and they can send transactions for us. And that's why we want to keep these private. So it works the exact same way, right? And so this is why it's so important to hide your private keys and hide your mnemonics. Now, your Ethereum address is actually a piece of your public key. Now, to get our address in Ethereum, all we have to do is take this public key that we've created with our private key, hash it using that same Ethereum hashing algorithm, and then take the last 20 bytes. And that's how we'll actually derive to our address here. Now, knowing the exact methodology of how to get the address doesn't really matter because it could change blockchain to blockchain and could even change in ETH2. But just know that that is essentially how kind of these addresses are derived, right? There's some derivative of the public key, right? Because the public key is public, and using the public key in kind of any public way is totally fine, but not the private key. So that is how we sign our transactions. Note though, this isn't how we send the transactions. So this is just going to sign it, create a transaction for us to send. We'll learn later on how to send these transactions. Whew, so that was a lot of information there too. Let's do a quick recap. Your public key is derived by using a digital signature algorithm on your private key, right? And you want to keep your private key private at all times because you're going to use your private key to sign transactions. Signing transactions with your private key, you are the only one who can actually do this because you can't get the private key from a message signature. However, using your public key, anybody can very easily verify that a signature that's signed by you is in fact signed by you. In our MetaMask, our private keys are located in this account details section. You just hit show private keys and type in your password, and you'll get your private key here. A quick note here is oftentimes when using your private key somewhere, they want it in hexadecimal form. So if we're going to use our private key for something like Brownie, which we'll go into later, we need to actually append a 0x to the front, but we'll get into that later. And the address of your account is derived from this. So if you think about it, your private key creates your public key, which then can create your address. And there's a little barrier here, or a big barrier here, because your private key you want to keep private, and your public key and your address can all be public information.
Awesome. So now that we know all the cryptography pieces and all the little nitty-gritties of how the blockchain actually works and how our signatures work and how everything sticks together, let's talk a little bit about how this works in actuality and what's really going on. Now, for a lot of this, each different blockchain has slightly different algorithms and slightly different metrics and criteria for doing a lot of this stuff. So when we're talking about these specific implementations, keep in mind the exact algorithm might be a little bit different, but the concepts are all still going to be exactly the same. Hashing and a hash function is going to be the same no matter where you look. A decentralized blockchain is going to be the same no matter where you look. How it's actually implemented is going to be a little bit different. Now, traditionally, when you run an application, be it a website or something that connects to some server, you are interacting with a centralized entity. And unlike how we saw with the blockchain with multiple different peers, it's going to be run by a single centralized group. Now, it still could be run on many different servers, but all those servers are still going to be controlled by the same centralized group. Blockchains, as we saw, run on a network of different independent nodes. When we saw peer A, peer B, peer C, those were different examples of different independent users running the blockchain technology on their own node. Now, when I use the term node, I'm usually referring to a single instance of a decentralized system. So when I say a single node, when I'm talking about a blockchain, I'm talking about one of those peer A's, peer B's, peer C's running that blockchain software. I'm talking about one server running this technology. And again, it's this network, it's this combination of these nodes interacting with each other that creates this entire blockchain. What makes these so potent too is that anybody can join the network, and that's why there's decentralized. The barrier to entry is a little bit of hardware requirements, you getting the correct materials to run the software, and then you running the software. Anybody can join these networks and participate, and that's what makes it truly decentralized. In fact, you can go to GitHub right now and run your own Ethereum node in a few seconds. Now, in the traditional world, applications are run by centralized entities, and if that entity goes down, or is maliciously bribed, or decides that they want to shut off, they just can't, because they're the ones that control everything. Blockchains, by contrast, don't have this problem. If one node or one entity that runs several nodes goes down, since there are so many other independent nodes running that it doesn't matter. The blockchain and the system will persist so long as there is at least one node always running. And luckily for us, most of the most popular chains like Bitcoin and Ethereum have thousands and thousands of nodes. And as we showed in our demo, if one node acts maliciously, all the other nodes will ignore that node and kick that out or even punish it in some systems, because they can easily check everybody else's node and see, okay, this one is out of sync with the majority. And yes, majority rules when it comes to the blockchain. Each blockchain keeps a full list of every transaction and interaction that's happened on that blockchain. And we saw if a node tries to act maliciously, then all their hashes are going to be way out of whack and they're not going to match everybody else. This gives blockchains this incredibly potent immutability trait where nothing can be changed or corrupted. So in essence, we can think of a blockchain as a decentralized database. And with Ethereum, it has an extra additional feature where it also can do computation in a decentralized manner. Now let's talk consensus, proof of work, and proof of stake, because you've probably heard these before and they're really important to how these blockchains actually work. When we went through that blockchain example and we did that mining feature, this is what's known as proof of work. Proof of work and proof of stake fall under this umbrella of consensus. And consensus is a really important topic when it comes to blockchains. Consensus is defined as the mechanism used to reach an agreement on the state or a single value on the blockchain, especially in a decentralized system. I briefly alluded to this consensus mechanism in our blockchain example when I said if one changes something and the other two don't, then majority will rule and kick that one out. This is part of that consensus mechanism. Now, very roughly, a consensus protocol in a blockchain or decentralized system can be broken down into two pieces: a chain selection algorithm and a Sybil resistance mechanism. That mining piece that we were doing, or the proof of work algorithm, is what's known as a Sybil resistance mechanism. And this is what Ethereum and Bitcoin currently use. Please note that depending on when you're watching this, if ETH2 is out, then it's no longer proof of work. Now, proof of work is known as a Sybil resistance mechanism because it defines a way to figure out who is the block author. Which node is going to be the node who did the work to find that mine and be the author of that block, so all the other nodes can verify that it's accurate. Sybil resistance is a blockchain's ability to defend against users creating a large number of pseudo-anonymous identities to gain a disproportionately advantageous influence over said system. And in layman's terms, it's basically a way for a blockchain to defend against somebody making a bunch of fake blockchains so that they can get more and more rewards. Now, there are two types of the Sybil resistance mechanisms that we're going to talk about here, namely proof of work and proof of stake. Let's talk about proof of work a little bit more in depth first. In proof of work, this is Sybil resistant because a single node has to go through a very computationally expensive process called mining, which we demonstrated earlier, to figure out the answer to the blockchain's riddle of finding that correct nonce or whatever the blockchain system has in place. In proof of work, this works because no matter how many pseudo-anonymous accounts you make, each one still has to undergo this very computationally expensive activity of finding the answer to the proof of work problem or the proof of work riddle, which again, in our demonstration, it was finding a nonce with that first 4 zeros. But again, each blockchain might change the riddle or change the problem to be a little bit different. In fact, some of these blockchains make this riddle intentionally hard or intentionally easy to change what's called the block time. The block time is how long it takes between blocks being published, and it's proportional to how hard these algorithms are. So these problems actually can change depending on how long they want the block time to be. If a system wants the block time to be very, very long, they just make the problem very, very hard. If they want it to be very short, they make the problem a lot easier. We'll talk about Sybil attacks in a little bit and how they can affect the system. But with proof of work, it's a verifiable way to figure out who the block author is and be Sybil resistant. Now, you need to combine this with a chain selection rule, create this consensus. Now, there's some consensus protocols that have more features, but very, very roughly, these are the two pieces that we're going to look at. The second piece is going to be a chain selection rule. How do we know which blockchain is actually the real blockchain and the true blockchain? Now, on Bitcoin and Ethereum, they both use a form of consensus called Nakamoto consensus. And this is a combination of proof of work and longest chain rule. The decentralized network decides that whichever blockchain has the longest chain or the most number of blocks on it is going to be the chain that they use. This makes a lot of sense because every additional block that a chain is behind, it's going to take more and more computation for it to come up. That's why when we saw in our transaction, we actually saw confirmations. The number of confirmations is the number of additional blocks added on after our transaction went through in a block. So if we see confirmations as 2, it means that the block that our transaction was in has 2 blocks ahead of it in the longest chain. Now, I do want to point out that a lot of people use proof of work as a consensus protocol, and I do want to say that this is a little bit inaccurate, but sometimes people use it interchangeably. Proof of work is a piece of the overall consensus protocol, which in Bitcoin and Ethereum 1's current case is Nakamoto consensus. Nakamoto consensus is a combination of proof of work and this longest chain rule, both equally and very, very important. Now, proof of work also tells us where these transaction fees and these block rewards go to. Remember how when we made this transaction, we had to talk about gas and a transaction fee. So who's getting paid? Who is getting this transaction? And this transaction fee is going to the miners or the validators. In a proof of work network, they're called miners, and in the proof of stake network, they're called validators. They are a little bit different, and we'll get into that when we talk about proof of stake. In this proof of work system, all these nodes are competing against each other to find the answer to the blockchain riddle. Remember, in our example, it was to find a hash that has 4 zeros at the start. And again, depending on the blockchain implementation, that riddle is going to be a little bit different. But all the nodes are trying as many as possible to try to get this answer first. Why? Because the first node to figure out the answer to the blockchain riddle is going to get that transaction fee. They're going to get paid from that. Now, when a node gets paid, they actually get paid in 2 different ways. One is going to be with a transaction fee, and another piece is going to be the block reward. Remember how we talked about alternating the gas price or the GUI on our transaction? Well, that's the transaction fee that we're going to pay to these blockchain nodes for including our transaction. The block reward is given to these nodes from the protocol, from the blockchain itself. You've probably heard of the Bitcoin halving before. The halving is referring to this block reward getting cut in half, and it's supposed to be cut in half roughly every 4 years. This block reward increases the circulating amount of whatever cryptocurrency that is being rewarded. For example, on Ethereum, the block reward is giving out Ethereum, and on Bitcoin, the block reward is giving out Bitcoin. So these nodes are competing against each other to be the first one to find this transaction, to be the first one to find the answer to this problem, so that they can be the ones to win both this block reward and your transaction fee. Some blockchains, like Bitcoin for example, have a set time when they're no longer going to give out block rewards, and the miners or the nodes are only going to get paid from transaction fees. Now, this gas fee, again, is paid by whoever initialized the transaction. When we got our funds from the faucet, there was some server and somebody else was paying the transaction fee for us. However, when we sent Ether from one account to another, our first account actually paid some transaction fee to send that Ether. In proof of stake, there's also a gas fee, but it's paid out to validators instead of miners, and we'll talk about that in a little bit. Now let's talk about 2 types of attacks that can happen in these blockchain worlds. Let's talk about the first one being the Sybil attack. The Sybil attack is when a user creates a whole bunch of pseudo-anonymous accounts to try to influence a network. Now, obviously, on Bitcoin and Ethereum, this is really, really difficult because the user needs to do all this work in proof of work or have a ton of collateral in proof of stake, which again, we'll talk about in a bit. The other more prevalent attack is what's known as a 51% attack. Now, as we saw as part of our consensus protocol, these blockchains are going to agree that the longest chain is the one that they're going to go with, so long as it matches up with 51% of the rest of the network. This means that if you have the longest chain and you have more than 51% of the rest of the network, you can do what's called a fork in the network and bring the network onto your now longest chain. Now, Sybil attacks obviously are when a single node or a single entity tries to affect the decentrality of the network by pretending to be multiple different people, although they're just the same person or entity. And like I said, it's really difficult to do in proof of work and proof of stake. So you can see now that blockchains are very democratic. Whichever blockchain has the most buy-in and is the longest is the blockchain that the whole system is going to corroborate. When nodes produce a new block and add it to the longest chain, the other nodes will follow this longest chain that the rest of the network is agreeing with, add those blocks to their chain, and follow up. So very small reorganizations are actually pretty common when a blockchain picks a block from a different longest chain, puts it on, and then has to swap it out for another block and continue with a different blockchain. However, if a group of nodes had enough nodes or enough power, they could essentially be 51% of the network and influence the network in whatever direction that they wanted. This is what's known as a 51% attack, and it's happened on blockchains like Ethereum Classic, which is not Ethereum. This is why the bigger a blockchain is, the more decentralized and the more secure it becomes. So after you watch this video and you become a blockchain engineering expert, I definitely recommend you run a node as well because you are going to increase the security of the network as a whole by running a node. So proof of work is fantastic because it allows us to very easily protect against these Sybil attacks and keep our blockchains decentralized and secure. However, it has some drawbacks as well. Proof of work costs a lot of electricity because every single node is running as fast as they can to win this race to get the rewards. This leads to, obviously, an environmental impact. Now, since proof of work and Nakamoto consensus, a lot of other protocols have taken this idea and gone in a different direction with a different Sybil resistance protocol. A lot of them with the intention to be a lot more environmentally friendly. And the most popular one right now is proof of stake. There are some chains that are already using this proof of stake protocol and that are live and thriving. Some of them are like Avalanche Solana, Polygon, Polkadot, and Terra. And additionally, Ethereum has decided to upgrade to ETH2, which will have this proof of stake algorithm as well. It'll also have some other features which we'll talk about in a bit. Now, as a quick aside, all the tools that we're going to learn here are still going to work in ETH2. So depending on when you watch this, everything here is still valid. So let's talk about proof of stake now. Again, this is a different Sybil resistance mechanism. Instead of solving this difficult problem, proof of stake nodes put up some collateral that they're going to behave honestly, aka they stake. In the example of Ethereum 2, nodes put up some Ethereum as a stake that they're going to behave honestly in the network. If they misbehave in the network, they are going to be slashed or removed some of their stake. Obviously, this is a very good Sybil resistance mechanism because if you try to create a whole bunch of anonymous accounts, then each one of those accounts, you have to put up some stake. And if you misbehave, you're going to run the risk of losing all the money that you put up as collateral. In this system, miners are actually called validators because they're no longer mining anything. They're actually just validating other nodes. Now, unlike proof of work, which every node is racing to be the first one to find the block, in proof of stake, nodes are actually randomly chosen to propose the new block. And then the rest of the validators will validate if that node has proposed the block honestly. As we saw with our cryptography lesson, it's usually very easy for other nodes to verify if a proposal or a transaction is honest. Now, randomness is a really important topic when we're talking about blockchains, because keep in mind, these blockchains are deterministic systems. They're walled gardens from the rest of the world. And as you know, a deterministic system, by definition, can't have random numbers. So how do we choose the random validators in the system? Well, it changes from blockchain to blockchain, and actually choosing the node will change blockchain to blockchain. But in ETH2, they're using what's called RANDAO, at least for the original implementation. This is a decentralized autonomous organization that collectively chooses the random number and collectively chooses which node is going to run next. We aren't going to dive too deep into this because there's a good chance that this might change in the future. But we will go into randomness solutions in blockchain later on in this course. Now, proof of stake obviously has some pros and cons as well. Pros are that, again, it is a great Sybil resistance mechanism and a great way to figure out who the author of a block should be. The other pros are that it's way less computationally expensive to figure out the new block, because instead of every single node on the network trying to do this, only one node needs to do this. And then the rest of the nodes just need to validate it. The cons are that it's usually considered a slightly less decentralized network due to the upfront staking costs it costs to participate. Now, this gets into a little bit of a philosophical battle on how decentralized is decentralized enough, and I think that's up to the community to decide. And as we progress, I think we'll learn more and more about how decentralized is decentralized enough. The general consensus amongst blockchain engineers, though, is that proof of stake is very, very decentralized and very secure. This massive environmental impact improvement is one of the two main reasons why ETH is shifting to ETH2. It reduces the environmental impact by up to 99%. Now, these are the main pieces of proof of work and proof of stake, but I did want to talk about another concept that's really important in these ecosystems, and that is scalability. When we were talking about gas prices, we were saying that the gas prices can get really high if a lot of people want to send a transaction, because a block only has so much block space and the nodes can only add so many nodes. So when a lot of people want to use a blockchain, the gas price skyrockets. This is not very scalable, because if we want to add more and more people to these blockchains, it's going to cost more and more to use the blockchains because more people are going to want to get into these blocks. This means that there's kind of a ceiling to how many people can use the system because of the financial constraints that'll get imposed as gas prices keep rising. Ethereum 2 is not only attacking the environmental impact of proof of work by switching to proof of stake, but they are also implementing this new methodology called sharding. And sharding is a solution to this scalability problem. A sharded blockchain really just means that it's going to be a blockchain of blockchains. There is a main chain that's going to coordinate everything amongst several chains that hook into this main chain. This means that there's more chains for people to make transactions on, effectively increasing the amount of block space that there is. Sharding can greatly increase the number of transactions on a blockchain layer 1. Now, there's another term that might be the first time you heard it, a layer 1. We're going to talk about layer 1s and layer 2s in terms of scalability really quickly as well. A layer 1 refers to any base layer blockchain implementation. Bitcoin's a layer 1, Ethereum's a layer 1, Avalanche is a layer 1. These are the base layer blockchain solutions. A layer 2 is any application that is added on top of a layer 1, added on top of a blockchain. Some examples of layer 2s are going to be Chainlink, Arbitrum, or Optimism. Arbitrum and Optimism are very interesting because they are layer 2s that also look to solve this scalability issue. Arbitrum and Optimism are what's known as rollups, and they roll up their transactions into a layer 1, like Ethereum. We're not going to go too deep into rollups and how they actually work, but all you really need to know is that a rollup is kind of like a sharded chain. They derive their security from the base layer, from the layer 1, like Ethereum, and they bulk send their transactions onto the layer 1. They solve some of the scalability issues by being another blockchain that people can make transactions on, still on kind of this base Ethereum layer. Now, they're different from side chains because side chains derive their security from their own protocols. Rollups derive their security from the base layers. So Arbitrum and Optimism, for example, is going to be just about as secure as Ethereum. There's some fantastic guides in there that go a little bit deeper into rollups, and I've left a link in the description for you. All right, so we just talked about a lot of stuff. So let's do a quick recap before moving on. Ethereum and Bitcoin are currently both proof of work blockchains that follow Nakamoto consensus. However, Ethereum is moving to Ethereum 2, which will be a proof of stake sharded blockchain. Sybil attacks are prevented due to protocols like proof of work and proof of stake. 51% attacks grow increasingly harder with the size of blockchain, so you should run a node. Consensus is the mechanism that allows a blockchain to agree upon what the state of the blockchain is. Sharding and rollups are solutions to scalability issues on layer 1s. A layer 1 is any base blockchain implementation, like Bitcoin or Ethereum. A blockchain scalability problem is that there's not always enough block space for the amount of transactions that want to get in them. This leads to very high gas prices. And again, gas prices are how much it costs to interact with a blockchain. Whew. So we've learned a ton in this video so far. Everything that you went over is going to make you 10 times better as a developer. Because yes, being a good developer means you understand the code at a very technical level. But if you can understand the overall architecture as well, you can make informed decisions about how to architect your design or how to build your software in however you want to do so. So with all that being said, it's finally time to jump into some Solidity and jump into some code. So let's do this.
Now again, in the description of this video, there is a link to this GitHub repository. That's going to be the home base for all the code that we work with in this tutorial. We scroll down to this main section, this README, there's a table of contents in here. We can go to lesson 1, simple storage, and we'll have links, helpful tips, the itinerary of what we're going to learn, and everything else that you need to work with here. All the code that we're going to be working with is located in this simple storage link that we can go ahead and click. It's in its own different repository. We can go ahead and click the file to see all the code that we're going to be working with. So let's jump into it. Additionally, back in our full blockchain Solidity course, right at the top, there's this resources for this course section. If you have questions, engaging in GitHub discussions, Stack Exchange Ethereum, and Stack Overflow are going to be great places to get help and get support. I highly recommend making a Stack Overflow, Stack Exchange Ethereum, and a GitHub account so you can participate and engage with the community. Welcome to the Remix IDE, or the Remix Integrated Development Environment. This is going to be where we're starting to teach you how to work with Solidity and work with smart contracts and deploy to blockchains. We're going to use Remix to get us up to speed, as it has a lot of nice features that allow us to really see and interact with blockchains and really see what's going on. But eventually, we're actually going to move off of Remix to another platform. But all the Solidity that we're going to learn here obviously is going to apply everywhere as well. When you come to Remix, there's a whole lot of different plugins like Solidity, Learn ETH, Sol Hint Linter, and a whole bunch of other plugins as well. I'm going to go ahead and start by clicking the Solidity plugin, but we're not going to use any of these plugins for now, but later on you can kind of go back and learn a little bit more about what these plugins do. So let's start perusing. Let's start coding some things. On the left-hand side over here is where we're going to interact with everything. So let's go ahead and click the files up here. Now you can always go back and peruse this a little bit more. And in fact, I highly encourage you to, because that's how you're going to learn the most, the quickest. But for us, we're actually just going to go ahead and start with our own brand new file. We're going to create a little application that can store information on the blockchain for us. And this is our first project that we're going to do in Solidity. So we're actually going to create a new file, and we're going to call it simple storage.sol. All Solidity has an extension of .sol at the end. It stands for Solidity. Now let's take inventory of what we're going to be working with here. This is the Solidity compiler tab. It compiles all the Solidity code down to machine understandable code, or machine language here. There's a whole bunch of different parameters we can choose when working with Solidity. We can choose the compiler version, we can choose the language, which we're only going to be working with Solidity, the EVM version, don't worry about this for now. So let's code our first Solidity contract here. Now we are going to use something a little bit special here. When we actually deploy these, we're going to use a JavaScript virtual machine. So we're going to use a virtual machine that's going to simulate actually deploying to a testnet or a real network. We're not actually going to deploy on a real network. We will in a little bit. But just to get started, we're going to work with a JavaScript VM, which is kind of a fake environment for now, okay? Testing locally and understanding how to test locally will make your coding experience a lot faster. As you saw, when we sent some transactions, some of them actually took a lot of time to actually deploy. We don't want to have to spend that much time waiting around for our tests to actually finish. So we're going to use a JavaScript VM to kind of dummy it for now. But let's just start coding and go from there. So the first thing that you're going to need in any Solidity program is the Solidity version. So that's always going to be at the top of your Solidity code. It's defined by doing pragma, Solidity, and the version. We're going to be using some version between 0.6.0 and 0.9.0. So we're saying we want to use anything between 0.6 and 0.9. And as a force of habit, I just automatically hit Command S whenever I write anything. So that's why you saw some of this pop up here. Hitting Command S or Control S, depending on if you're Windows or not, we'll hit this compile button and we'll compile everything for us. Now, if we want a specific version of Solidity, we can also do 0.6.0. And if I go ahead and hit Command S or compile, our compiler will automatically revert to 0.6.0. However, if I try to do 0.8.0 with my Solidity at 0.6.0, it's going to give us an error. It's going to say the source file requires a different compiler version. We're using 0.8.0 and this is 0.6.0. So we're going to go ahead and hit compile and it's going to automatically move down to 0.6.0. We can also do caret 0.6.0 and this will allow us to work with really any version of 0.6. It'll work all the way up to 0.7, where if we hit Command S or Control S there, it'll give us an error. So this only works with any version below 0.7 and above 0.6. We're going to be using version 0.6.6. However, in future contracts that we work with, we're actually going to work with different versions of Solidity. The reason we're going to be changing versions throughout this course is that Solidity is a constantly updating language. Being good at switching between versions is going to make you an incredibly powerful smart contract engineer. The next thing that we're going to do is we're going to define our contract. So contract is a key word in Solidity, which stands for our smart contract that we're going to create. You can think of a contract similar to a class in Java or any other object-oriented programming language. So we're going to give our contract a name here. We're going to call it simple storage. And we're going to add this little curly bracket to say, this is the contents of our contract simple storage. And I went ahead and hit Command S, and we can see it is compiling successfully. You could hypothetically deploy this right now, and this would be a valid contract. So great job for making it this far. Now in Solidity, there are many different types that we can work with. Let's go into some of the types of Solidity. We can have integers, aka whole numbers. They can be uint, as in an unsigned integer, meaning they're not positive or negative. We can also have an int, and we would define a variable by doing uint 256 favorite number equals 5. So we have an unsigned integer. Uint 256 means this is an integer of size 256 bits. So we can have this number be up to 256. You can also do uint favorite number equals 5, but if you want to be a little bit more precise, a lot of protocols and a lot of smart contracts will do the whole name like uint 256. We can also have booleans. Booleans are true, false. So we can have boolean favorite bool equals true. So this favorite bool would be true. It could also be false. We can have strings. String favorite string equals string. A string is a string of text here, right? It's going to be some word or phrase or really any of these keystrokes here. Similar to the unsigned integer, we can have an int 256. Favorite int equals -5. So it could be positive or negative. We can have an address, which is going to be some type of Ethereum address. So we could do address, favorite address equals, and then we can even copy right from our MetaMask and just paste it right in here. This is going to be a valid address here. You'll also notice that we end all of our statements with a semicolon. We can have a bytes object, size 32 bits, favorite bytes. For our example, we're just going to use the word cat because cat is a string which can be converted down into a bytes object. Byte 32 means that there's 32 bytes in this variable favorite bytes. We can also do bytes 2, bytes 3, bytes 5, etc. with a maximum size of bytes 32. For example, we can't do bytes 64. We're going to be talking about some other variables as well, like arrays and mappings, but let's just stick here for now. If you want to learn more about the different types and the different variables that you can use, head over to the Solidity documentation, and there's a link in the GitHub and the description to show you this section. For now, for our simple storage, let's say we only want to store numbers. We don't want to store anything else. So we're just going to go ahead and delete everything and just have uint 256 favorite number at the top. Now in Solidity, if I do this, favorite number actually does get initialized even though I didn't have it initialized to 5. If I leave it blank, it gets initialized to the null value. In this case, it would be initialized to 0. So for now, let's just not initialize it to anything. That way it'll get automatically initialized to 0. This means that when we deploy this contract, as of right now, favorite number will start off as 0. If you get confused, you can also make a comment on this. You could say, this will get initialized to 0. This double slash here is the way to make comments in Solidity, and it won't get executed as code. So we can write whatever we want as long as it's preceded by 2 backslashes. Now let's go ahead and create our first function. Functions or methods are self-contained modules that will execute some task for us. And in Solidity, it's the exact same thing. They're defined by the keyword function. Let's make a function called store that will change the value of this favorite number here. So we're going to call store, and we're going to allow it to be passed a variable. So we're going to allow it to be passed a variable of type unsigned integer 256, and we're going to call it underscore favorite number. We're going to make this a public function, which we'll get to in a minute. And all we're going to do is we're going to set favorite number equals to whatever variable we passed in, favorite number. So this, in its simplest form, is how you can define a function. Now, just to visualize what we're working on so far, let's go ahead and deploy this contract so we can actually start to interact with it. So if we hit this button, this will bring us to the deploy tab and will allow us to deploy our smart contract here. Using our JavaScript VM, it's given us a fake account with some Ethereum in it. It has 100 Ethereum in it to start. And same as before, anytime we want to interact with the blockchain, we have to pay a little bit of gas, even in our fake virtual machine here. And we want to simulate that. So you'll see it has some of the same parameters here as making a transaction, like gas limit, for example. When we deploy a contract, it's going to cost a little bit of Ethereum or a little bit of gas to do so. So let's go ahead and hit this deploy button and see what happens. So once we deployed with this virtual machine, a few things happened. We have Remix kicking out this section down here saying, great job, you've deployed something. And if we scroll down, it says transactions recorded 1. We can look at all the transactions we recorded, and we can see it says deployed contracts, and we have a contract here that we've deployed. Now let's zoom out just a hair here so we can see everything a little bit better. In this simple storage contract, we see this big store button because there's one public function that we can actually interact with. So we can add this number here and we'll hit store, and you'll see again, we have a completed transaction. And if we look at our contract, we'll have paid a little bit more gas, right? We'll have paid a little bit more to interact with this function because again, anytime we want to make a state change on the blockchain, we have to pay a little bit of gas. The reason MetaMask isn't popping up is because we're kind of doing it in this simulated environment. So this is great. However, it looks like we can't actually see what our favorite number is. We can't actually look at it. So how do we actually make sure that we can view this favorite number? Well, let's add another parameter to this as well. If we add public to our favorite number, we recompile by hitting Command S or hit the compile button. We delete this contract and we redeploy and scroll down. Now we'll see 2 buttons pop up. This blue button to show us favorite number, which again is initialized to 0, and we have this store function. So let's talk a little bit about why this public variable allowed us to see this new button, this new favorite number button. This public keyword defines the visibility of the variable or the function. There are currently 4 different types of what's called visibility in Solidity. There's external, public, internal, and private. We're mostly going to be working with public for now, but it's important to note how the rest of these work. Public functions can be called by anybody, including variables. So oddly enough, variables are a function call to just look at them
and return whatever that variable is.
An external function means it can't be called by the same contract. It has to be called by an external contract. So if in this contract, I had this be external, I couldn't call the store function. I couldn't call the store function inside this function because the function is external. It means somebody outside of the contract has to call this function. Internal functions, however, can only be called by other functions inside of this contract or in its derived contract. And then private is the most restrictive as private functions and state variables are only visible for the contract they are defined in and not derived contracts. Now, the reason that we didn't see favorite number show up in our original contract deployment is that if we don't give a state variable a visibility, it will automatically get set to internal. So if we want other people to be able to read it, we have to change it to public. Now, let's see how this interaction actually works. If we hit the favorite number button right now, we'll get this call thing that shows up, and it'll show us right here that the value of favorite number is 0. Now, this function, however, is set so that whatever value we pass it is going to change the favorite number to whatever we pass it as. So if we pass 1, 2, 3, hit store, that transaction goes through, and then hit favorite number, we can see the value is now 1, 2, 3. Now, I will also be using transactions and smart contract interactions and function calls a little bit interchangeably. That's because on a blockchain, whenever you call a function or whenever you make some state change to the blockchain, you're actually also making a transaction. That's what makes this whole thing so powerful. And again, that's why making a function call or deploying a contract costs a little bit of gas. Now, the reason we can access this favorite number variable inside this function is because favorite number has this global or contract scope. So even if we made uint 256 test equals 4 or equals 4, we wouldn't be able to use this variable outside of this function, right? Because it's self-contained. It's self-contained inside this bracket. And if I were to make another function, store2 perhaps, public, store2 doesn't know that this test variable exists. Functions only know about the variables that are in the same scope as them. So favorite number is in this global scope because the only bracket that's above them is simple storage. And test is in this store scope because it has 2 brackets above it. It's inside of this store function and inside of this contract simple storage. Store2 isn't inside of this store function or this store scope, so it can't access this test variable. So let's go ahead and make this back to public, and we'll compile. Again, I'm hitting Command S to compile, but you can go ahead and click the button if you like. And let's get rid of this and get back. Now, as you saw, when we deploy this, there's this button here that we can click called favorite number. We can also make a function called retrieve and make it a public function that is of type view and returns uint 256. And all this is going to do is return favorite number. So we're going to talk about views and returns here. So I'm going to go ahead and compile. I'm going to go ahead and delete this contract. I'm going to go ahead and deploy it now. And we can see now we have 2 functions or 2 blue buttons here. We have retrieve and we have favorite number. And if I change favorite number by calling the store function, favorite number and retrieve will both now say it's 1, 2, 3. So then the question might be, well, why is this one orange and these 2 are blue? And the key relies in this view function or this view keyword. There are 2 special keywords that define functions that you actually don't have to make a transaction on. And those keywords are view and pure. A view function means that we want to read some state off the blockchain. So we're just reading off the blockchain. If we're reading off the blockchain and we're not actually making a state change, then we don't need to make a transaction. These blue buttons are blue because they are view functions. Public variables also have view functions. That's why both of these are blue. This technically is a view function. And when I click it, I get to view and I get to read the state off the blockchain. Retrieve is the same way. We could have this without a return, but it wouldn't do anything. Pure functions are functions that purely do some type of math. We could have uint 256, favorite number, public pure, and just have favorite number plus favorite number. So we're doing some type of math here, but we're not actually saving state anywhere. We're going to do this math, but we're not going to save this favorite number anywhere. We're not going to save anything. Deploy this now, this pure function. We would have this retrieve function, 1, 2, 3. It's blue as well because it's, again, not going to change the state of the blockchain. So view functions and pure functions are both going to have this blue color. Now, the reason that nothing shows up at the bottom is because we didn't return anything. All we're doing is we're saying, add these two numbers together, and that's it. In order for this function to give us something back, we need to have it return something. So if we go back to this retrieve function, we have to define what we're going to return when we're defining this function. So we're going to say this is a public function. It's a view function because we're going to read some state, and it's going to return a uint256. So favorite number is a uint256, so that's what we're going to return. Our public variable favorite name is also a view function that returns a uint256. For now, let's just remove that so we can work with this retrieve function. So let's go ahead and deploy. So now we see we don't have this favorite number button anymore because it is no longer a public function. Because again, it gets initialized to internal, so we can't actually view it. Now keep in mind, later on, we're going to talk about how everything on chain you actually can see, and we'll talk about that a little bit later though. So retrieve is going to do 0, we can call store, and now retrieve is going to be 1, 2, 3. Now, this application is great so far. It allows a single person to store a favorite number and then go ahead and retrieve it later, which is fantastic. But what if we want a list of people or a group of people and store their favorite numbers? Or what if we want to associate a favorite number with a single person? Well, what can we actually do? Now, we have a whole number of different choices, but the one that we're going to talk about is using a struct. Structs are ways to define new types in Solidity. They're almost like creating new objects as well. So we can create a struct called type people and allow it to start storing a favorite number associated with a certain people. So inside of our struct, we can have different types as well. So we can have a uint256 favorite number, and we could also have a string name. Now we have a new type of type people that has a favorite number and a name inside of it. Now what we could do with the struct is we could say people public person equals people, and then inside we add the variables. So we could say favorite number, favorite number is 2 and name is Patrick. And of course the semicolon at the end. And again, I'm hitting Command S to save, but you can also go ahead and compile in the compile tab. So let's go ahead, delete this contract, and see what this looks like now. So now we've deployed this new contract, and we have this person struct, which at the 0th index is the favorite number, and the variable stored in the first index is going to be the name. Storing variables in Solidity always works in this numeric index fashion. In fact, in contract simple storage, uint256 favorite number is at index 0. If we were to add another object here, like boolean favorite bool, this would be at index 1. If we were to add bool favorite bool 2, this would be at index 2. 0, 1, 2. And it works the same in structs. This is at index 0 inside the struct. This is at index 1 inside the struct. So we can see the variables associated with this person. We're going to go ahead and delete this for now, because instead of just creating one person, we actually want to create a whole list of people. So how do we create a list of people? Let's delete that contract. And what we can do is we can make what's called an array. An array is a way of storing a list or a group of some object. So as you're starting to see, the way the syntax works for defining any type of variable is going to be the type of the variable, the visibility of the variable, like public, or if you don't declare it, it gets initialized to internal, and then the name of the variable. It works the same with arrays. So we'll make a people array. The people array is the type. We'll make it public, and we'll call it people. Now if we deploy this contract, we go ahead and see we now have a people array. But if we click this button, you'll see that nothing shows up. And the reason is because it's an empty array to start with, right? We don't have anything inside of it. Now, this type of array that we've created is what's known as a dynamic array. It's a dynamic array because it can change its size. Right now, it's of size 0, and if we added something to it, it's of size 1. You can also create arrays of a fixed size. So if I were to do people 1, public people, this array could only have a maximum of 1 person inside of it. So we're going to work with a dynamic array though, because we're going to want to add an arbitrary number of people into here. So let's go ahead and create a new function called addPerson, where we can add a person to this array. So we'll do function addPerson string memory name, and I'll talk about this memory keyword in a minute. uint256 favorite number, and then we'll make this a public function. And inside we'll add this person to our array. The way to add a person to your arrays is using the push method. So we're going to push a new people or a new person, and we're going to give it those variables again. So we're going to give it favorite number is this variable that we passed in here. Oops, this needs a bracket. And then we're going to give the name, going to be this underscore name, and then end bracket. Oops. Zoom out again here just so I can see stuff. This needs a semicolon, and perfect. Now, in that last clip, we saw this little red box pop up. Whenever a little red box like this pops up after you compile, it means you have a compile error. This means that there's something wrong with your Solidity code or your Solidity syntax, and it won't compile and deploy properly. Red is going to be this compile error. Now, we're going to see a bunch of yellow warnings in the future. If you get a little yellow pop-up, these are okay to ignore, but they usually have some helpful tips about something that might be going wrong in your code. So to summarize, if it's red, it's broken. If it's yellow, you might want to check it out, but it could be okay. So we can see we have our new function addPerson, where we pass a string memory name and a uint256 favorite number. And then we create this people person, this people object here, and then we push it onto our people array. And I'm going to show you another way we can actually create a people person is just by passing favorite number and name. And getting rid of this other bracket by passing favorite number and name. Because we know that the 0th index of people is favorite number, and the first index of people is name. So we can also create a new person by adding it like this. Now let's talk about this memory keyword here. Now in Solidity, there's more or less 2 ways to store information. You can store it in memory or in storage. When you store an object in memory, it actually means that it'll only be stored during execution of the function or of the contract call. If we hold it in storage, that means that that data will persist even after the function executes. A string in Solidity is actually technically not a value type. A string is actually an array of bytes. A variable of type string is actually a special type of array that we can append text to. So because it's technically an object, we have to decide where we want to store it, in memory or in storage. And since we only need this name during the execution, we can have it be string memory name. And then when we create this new people object, we will create a new copy of this name variable into storage. Memory means that after execution, delete this variable, and storage means keep it forever. If this is a little bit confusing for you, just know that for now, when you use a parameter that's going to be a string for one of your functions, you need to call it string memory. So let's go ahead and deploy this contract and see what happens now. Now we have this new function, addPerson. And since we are making a state change here, we can see that this indeed is a orange button instead of being a blue button. So we can add in here a string name. We'll add Patrick, and we'll say his favorite number is 2. Again, right now, if we look at people, we see people 0, there's nothing in here. If we retrieve, there's nothing in here. So we're going to add person Patrick, and now if we hit people of 0, we can see that the person at the 0th index in this people array is going to be string Patrick. If we try at 1, there's nothing in here. Let's add another person. We'll add Becca, and her favorite number will be 24. Let's add her. Now if we hit 1, we see favorite number 24, string name is Becca, and retrieve is still showing up blank because we haven't touched favorite number. Awesome, this is great. We can just keep adding people. However, there is kind of an issue here. What if I'm looking for a person? What if I'm looking to find Becca and find her favorite number in this array? What if I know her name, but I don't know her favorite number? Is there an easy way for me to find that favorite number without having to triage the entire array? There's another data structure called a mapping. So let's create this new data structure. So this data structure is going to be of type mapping. A mapping takes some type of key and spits out whatever variable it's mapped to. So in this case, if we're saying we want to use the name Becca to find her favorite number, we would say the string Becca is going to be mapped to the uint 256 favorite number. And similar to all the other variable declarations, the first part is going to be the typing. So this is going to be a type mapping of string mapped to uint 256. We're going to give this public visibility, and we'll call it name to favorite number. And without adding any other functions that work with it, if we deploy this, we can see we have this blue button because we're not making a state change, name to favorite number. And if we type in Becca in here, obviously nothing's going to happen because we haven't added this mapping in yet. So in our add person down here, let's even have this add person also add to the mapping. So we can do name to favorite number. And then the key is going to be this name. So of Becca, we're going to say we're going to map the name Becca to the favorite number. Now we're going to go ahead and compile. Again, I'm hitting Command S, deploy. We can scroll down here. If we look up Becca in here, we're going to get nothing. However, if we add Becca and her favorite number being 24, this add person is going to add it both to the array and to this mapping. Now, if we look up name to favorite number, we see that Becca returns 24. Now, one other thing I want to show you guys, just because compilers are going to yell at you if you don't have them, is typically at the top of these contracts, you'll want to add an SPX license identifier. Basically, Solidity and the Ethereum community found out that trust in a smart contract can be better established if source code is available. And in terms of legality and copyright, it just makes life a lot easier if you add that license identifier right at the top of your Solidity. We're going to use the MIT license identifier because it's the most open license out there. It means, hey, anybody can use this code and we don't care. So you'll see a majority of Solidity contracts have this SPX license identifier, MIT at the top, and compilers will yell at you a lot less. Awesome. We now have a contract that we've decided that we liked. It's got mappings. It enables us to actually store people and their favorite numbers. This is fantastic. We've done all of our testing in this JavaScript VM, and we've decided, you know what? We want to deploy this to an actual testnet or an actual mainnet. How do we actually deploy this so that other people can interact with this contract? We are again going to use Rinkeby because that's what we use to make our first transaction. Now, again, you will need some type of test Ethereum in your testnet wallet. So again, if you get lost, you can always just Google Rinkeby faucet or Rinkeby testnet faucet and find a faucet. Or a better alternative would be to come to the link token contracts in the Chainlink documentation at docs.chain.link and scroll down or just look up Rinkeby. This link token contracts page has the most up-to-date faucets for any testnet that it supports. So for example, we get a testnet ETH faucet right here, which also just happens to be that exact faucet that we used earlier. The only thing you need to change in Remix is we need to change from JavaScript VM to injected Web3. And MetaMask will actually pop up and say, hey, would you like to connect to this application? Anytime you're working with a Web3 application or a web application that wants to access your funds or work with your MetaMask, MetaMask will pop up and ask for authorization first. This is really good so that we know which applications we're actually connected to. So we're going to go ahead and say next, connect, and we can see here that we've even connected here and that our account on the main network has 0 ETH. And Remix even tells us, hey, you're on the main network. So let's go ahead and switch to the RinkB network, and we can now see we're on the RinkB network, and we have 17.74 ETH on this RinkB test network. Injected Web3 means we're taking our MetaMask and injecting it into the source code of the browser here. And that's the difference between injected Web3 and JavaScript VM. Web3 provider is if we want to use our own blockchain node or our own Web3 provider. When we do injected Web3, we're saying our Web3 provider is our MetaMask, which will work perfectly for what we're trying to do. So since we already have some tests on Ethereum, let's go ahead and deploy this and see what this would actually look like if we deploy to a mainnet. The process is going to be exactly the same, right? The only difference is we would be on the mainnet instead of RinkB. So let's go ahead, hit deploy. We'll uncheck published IPFS, hit deploy. MetaMask will pop up asking if we want to do this transaction, because remember, we are deploying a contract. We are changing the state of the blockchain, so we have to pay a little bit of gas fee for it. So we're going to go ahead and hit confirm, and we get a link to RinkB Etherscan, similar exactly as we saw before when we made a transaction. The difference here is that instead of sending Ethereum to somebody, we're actually making a transaction on the blockchain to create a contract. After a short while, it will show up here on Etherscan with a success, the number of block confirmations, which again is the number of blocks appended to the block that included our transaction. We see from, which is our account here, and we see to is this new contract that we just created. And we can even click it, and we see that there's this unique transaction hash that created a new smart contract. And same as working with the VM, we have all the exact same functions in here. And you can see if I hit retrieve, these three functions, since they're not making a state change, you can just click them and no transactions will be made. However, what do you think is going to happen if I hit store? If you guessed MetaMask will pop up, you guessed correctly. Again, we see the familiar pieces here. We have a gas price, gas limit. Go ahead and hit confirm. We get another transaction here. And once this transaction goes through, we should be able to call our retrieve function and see a new number. If we call it now, nothing shows up because our original transaction hasn't succeeded. But I bet if we look at it now, okay, it's still indexing, but it looks like it's been included. If we hit it now, we do indeed see this value here. And we can do the same thing with adding a person. We'll add Becca. We'll say her favorite number is 24. MetaMask will pop up. We'll go ahead and confirm the transaction. And if I look up Becca and then name to favorite string right now, it's going to show nothing because our transaction hasn't gone through yet. But if we wait a little bit, I should probably spell her name right, we do see 24. And if we look at the 0th index, we also see Becca's been added here as well. Now, all this Solidity code that we wrote, and when we interacted with this blockchain here, all this Solidity was compiled down to the EVM, also known as the Ethereum Virtual Machine. A lot of the blockchains out there today are what's called EVM compatible. And that means that all this Solidity and all these functions that we're creating can still compile down to EVM and deployed on their blockchain. You'll find out a little later when we look to work on a non-Ethereum based chain that we could still deploy our Solidity smart contracts to these other chains as well. But that's a term you'll hear more and more, the Ethereum Virtual Machine, or EVM. Now, take a break, give yourself a high five because you just deployed your first smart contract and you learned the basics, the fundamentals of Solidity. So huge congratulations on how far you've gotten. Now, in our second project, we're going to take the fundamentals a step further and start going into the more of the intricacies of Solidity. But just as a quick recap, the first thing you always got to do in your smart contracts is name the Solidity version. Then you'll have to name your contract. A contract in Solidity is like a class and defines all the functions and parameters of your contract. There's many different types in Solidity, like unsigned integer, 256, Boolean, and bytes. We can create structs in Solidity. We can create arrays in Solidity. We can create mappings in Solidity. We can create functions in Solidity. View functions don't make a state change. Memory and storage are two different ways to initialize where a variable is going to be saved. All the Solidity code that we're working with gets compiled down to the Ethereum Virtual Machine. And last but not least, congratulations on taking your first step in learning Solidity. Let's move on to the next project. All the code, tips, and links that we're going to be working with can be found in our course repository. We can scroll down, to lesson 2, storage factory, click it here, and we can see all the code we're going to be working with. Good luck. All right, so we've done it. We've got our first contract out of the way. We're understanding some of the basics of Solidity. Now let's move onward. Let's get a little bit more advanced with what we're going to do with our smart contracts. And let's build what's called the factory pattern of smart contracts. So we have our simple storage contract here, which is great. It allows us to store numbers and store favorite numbers associated with different people, and this is great. What if, though, I want to have a lot of these simple storage contracts deployed? I want to give people the ability to generate and deploy their own lists based off of this contract. This is where the factory pattern comes into play. So let's go ahead and create a new contract. So in this contracts folder, I'm going to do new file. We're going to call this storage factory.sol. And now we'll have a storage factory.sol. Now, the way that we're going to do this is that you need simple storage and storage factory in the same folder. I have both of them in this contracts folder, but if you have them outside or in a different folder, that's okay. Just make sure wherever they are, they're in the exact same folder. So let's figure out how to get a contract to actually deploy another contract. We're going to add those basic pieces that we added in that simple storage.sol. We'll add the SPDX license identifier, which will be MIT. We'll choose our Solidity version, which will be Pragma Solidity. And we'll say anything in the 6 range. And then we'll create our contract. We'll say contract storage factory, and we'll create our brackets here. And I'm going to do Command S or compile, whatever you want to do. Things are looking good here. Great. So how can this contract deploy a simple storage contract? Well, the first thing that we're going to need to do is actually import this simple storage into our storage factory contract. We need to import it so that our storage factory contract knows what a simple storage contract even looks like. The way that we can import it is by doing the command import and then the file path that the simple storage is located. So the file path for this is going to be at ./simple storage.sol. This means that simple storage is in the exact same directory as storage factory. Doing this line is equivalent to copying everything in this contract bit, coming over to storage factory and pasting it above. You can even save and compile and have 2 contracts in the same file. Now, what's interesting about having 2 contracts in the same file is that when you go to deploy, you'll actually have a choice of which one you want to deploy. And it's the same thing if I do that import statement. So if I delete all this and I go back to import./simple storage.sol, in our deploy tab still, you'll see that we still have our choice of which contract we actually want to deploy. So this is how we actually import a contract or import any type of file that we want so that our contract knows what that contract looks like and can do. So if we want this contract to then be able to deploy a simple storage contract, we're of course going to have to create a function that can do that. So we'll do function. We'll call it create simple storage contract. We'll make this a public function. We'll do our little open and close bracket in here. The way we can generate a contract of simple storage type is by using a new keyword. So let's create a simple storage variable. We'll say a variable of type simple storage contract. We'll name this variable simple storage with a lowercase s equals new simple storage. What this line is saying is we're saying we're going to create an object of type simple storage contract. We're going to name it simple storage with a lowercase s. And we're going to say this is going to be a new simple storage contract. And we're saying this simple storage contract takes no input parameters. Of course, if we deploy this contract as is by going to our deploy tab, choosing the storage factory, staying on a JavaScript VM, deploying, scrolling down, we have this function that doesn't return anything. So we're creating new contracts, but we can't really read where those contracts are being created. We'd have to look on a block explorer like Etherscan or something. So let's make a way for us to keep track of all the different simple storage contracts that we deploy. Let's put them in a list or in an array. So what we can do is we can say simple storage array of visibility public, and we'll call it simple storage array. We'll initialize this simple storage array. And every time we deploy, we create one of these new simple storage contracts, we'll add it to our simple storage array. So we'll do simple storage array dot push, and we'll push this simple storage variable. So again, I'm compiling or hitting Command S, delete that most recent contract. We'll choose the storage factory and not the simple storage, and we'll hit deploy. Now, if we scroll down to our storage factory, we have this blue button, which stands for our simple storage array. If we try to see what's at index 0, we get an error, of course, because we haven't added anything to it yet. If I click this create simple storage contract orange button here, now I've created a transaction that's going to create a new simple storage contract and push it onto our simple storage array. Now, if I try to access the 0th index or the first index of this array, I'm going to get this address here. This is the address that this simple storage contract was deployed to. So we've successfully deployed a contract to the blockchain from another contract. And this, of course, is really exciting. Now, we can actually do more than just deploy the contracts. We can actually deploy contracts from another contract and then call those functions as well. So let's create a new function where we call this store function, and we'll also create a function where we call the retrieve function from our storage factory. So we'll do function storage factory store. We're going to shorthand it by saying SF store. We'll have it take uint256 simple storage index and a uint256 underscore simple storage number. We'll make this a public variable as well in our little brackets here. And the reason I'm choosing a simple storage index is because we're going to choose which simple storage contract in our list that we want to interact with. And then we're also going to pass a simple storage number to call on the store function, which of course we need to pass a favorite number to. Anytime that you interact with a contract, you need two things. You need the address of the contract you want to interact with, and you also need the ABI. For us, we figured out that we're going to push and get this address from this simple storage array. We can get the ABI, or the application binary interface, from this import. We'll explain the application binary interface a little bit more later. For now, just know that in order for us to interact with this simple storage contract, we can just do simple storage, and then we'll pass this simple storage the address of that simple storage contract. To get the address of that simple storage contract, we'll say grab the address inside the simple storage array at index simple storage index. This will return that contract that we want to interact with. So we could even say simple storage equals simple storage at that address in the array. Once we get this contract, we can then call any and all of its functions. So we could call simple storage dot store this simple storage number. Now, if we compile this, we go to our deploy tab, deploy the factory, hit deploy, open this up. We can see we have a couple different functions here. We, of course, have our create simple storage function, which creates the contract and adds it to our array. We now have this SF store, which stores a number to one of those contracts on this array. And then we have a lens into that simple storage contract. So if I create a simple storage contract, I can now store on that 0th contract, on that first contract, any number that I want, like 55. Of course, I can't really see that 55 because we didn't add a retrieve functionality. We didn't add a way to actually listen or read or retrieve that favorite number that we got. So let's add that now. So we'll create a new function called sfget, and this will take a uint 256 simple storage index and as a parameter, and we'll choose one of these contracts on this array and return its favorite number, calling the retrieve function on that contract. So since we're just going to be reading state, this can be a public view function that will return a uint 256. To do this, we need to access that contract once again. So we'll say simple storage equals simple storage at that address of simple storage array at index underscore simple storage index, and call. And we can return simple storage dot, we call this retrieve function. I'm just going to copy paste it so I don't spell it wrong. Simple storage, we'll put the semicolon here too, and here. Now, if we compile this, go to our deploy tab, delete the most recent, choose the storage factory, and hit deploy, we can see we now have an sfget function. So let's go ahead, create a simple storage contract. We'll store a function on the 0th contract. We'll store 55 as its favorite number, and we'll hit that. And then for sfget, we'll see if we can get the favorite number of the 0th contract. And we do indeed get 55. Awesome. We can actually even refactor this code to be a little bit simpler here. We don't need to save this simple storage contract as a variable here. We can actually just call retrieve on this whole section here, paste retrieve at the end, and just return like this. The same goes for our SF store. We can delete, saving it as a variable. We can copy this dot store, paste it at the end here, and delete this as well. Now we'll compile, delete the most recent, we'll deploy the storage factory. And if we go into it, create a simple storage, store the number 55, see what's at the 0th index, and we do indeed see 55. So this is really cool. This is a way for us to actually deploy contracts and interact with contracts from another contract. Now, to deploy a contract, we do need all the functionality of that contract imported. However, to interact with a contract, we don't need all of the functionality. We'll learn about interfaces in the next lesson, which will allow us to actually interact with a contract without having all of the functions defined. And now I'm going to show you something really cool. Simple storage has got a lot of really cool functions, and maybe I want all these functions inside my storage factory. I want my storage factory to be able to create simple storage contracts, and I want it to be a simple storage contract itself. Well, what I can do is my storage factory can actually inherit all the functions of simple storage. without me having to copy paste all these functions and all these variables over to Storage Factory. What I can do is I can do Solidity's version of inheritance. I can say contract storage factory is of type simple storage, or is of contract simple storage. And just by doing this line right here, my storage factory contract now will have all of the functions and variables of simple storage. So it'll have a store function, a retrieve function, an add person function, a people array, a name to favorite number mapping. It'll have everything because I will inherit it with this is syntax. So if I go to my deploy tab now, let's look at what our last storage factory was. All we did to change this was add is simple storage. And we can see just the 4 functions that we originally added. If I delete this now, if I save and compile the storage factory, let's go ahead and deploy storage factory. If we open this up now, we can see not only do we have all the functions originally defined in our storage factory, but we additionally have all the functions from our simple storage. And awesome, you've completed the second lesson. We've learned about some incredibly powerful tools here. We've learned how to import entire chunks of code from other files into our files. We've learned how to do inheritance. We've learned how to deploy contracts from our contract. And then we've learned how to interact with different contracts from outside of our contract. Well done. Now is a great time to take a breath, take a breather, and review what you've learned. The GitHub repository associated with this course also has all the code for this lesson. So let's jump into it. So we're back in Remix now, and we're going to go to contracts, and same as before, we're going to create a new file. We're going to call this fundme.sol. Now, same as last time, we're actually going to add this SPDX license identifier, MIT right at the top, and then we're going to choose our Solidity version. So we're going to go pragma, Solidity, and for this, we're just going to do greater than or equals to 0.6.6 and less than 0.9.0. And great. This should look pretty familiar. Now, we're going to do contract fundme, and we're going to start working. So what again do we want this contract to do? We want this contract to be able to accept some type of payment. So let's create a new function that can accept payment. We'll call it fund. So we'll do function, fund, public, and we'll add a new keyword in here called payable. When we define a function as payable, we're saying, hey, this function can be used to pay for things. When you call a function, every single function call has an associated value with it. Whenever you make a transaction, you can always append a value. This value is how much way or gwei or finny or ether you're going to send with your function call or your transaction. As we mentioned before, way, gwei, and ether are just different ways to talk about how much ether you're going to send. So if we look at a way to Ethereum converter, 1 ETH is this much way. 1 way is the smallest denomination of ether. You can't break up Ethereum into anything smaller than 1 way. This is why when you're talking about how much something costs, everything always defaults to way, or the smallest unit of measure in Ethereum. So again, for us to test, we're going to stick with the JavaScript VM for now. If we hit deploy, we get a new contract, and this button is now red. It's red because it is a payable function. So now if I hit this fund button, I can add a value associated with it. So what do we want to do with this funding? What do we want to do when people send us something? Well, let's keep track of who sent us some funding. So what we can do is we can create a new mapping between addresses and value. So let's do a mapping of address to uint256, which will represent the value. We'll make this a public mapping, and we'll call it address to amount funded. Now, in this fund function, let's keep track of all the people who sent us money, or all the addresses that sent us some value. To do this, we can use some keywords that go along with every transaction. So we'll say address to amount funded of message.sender equals or plus equals message.value. Message.sender and message.value are keywords in every contract call and every transaction. Message.sender is the sender of the function call, and message.value is how much they sent. So whenever we call fund now, somebody can send some value because it's payable, and we're going to save everything in this address to amount funded mapping. So if we deploy this now in our JavaScript VM, we now have, again, a new view function called address to amount funded, and we can even hit the drop down to see the full name. Now, if I hit fund, nothing's going to happen, right? Because my address is going to be sending 0. In order for me to send something, I have to add some value along with my transaction. So let's send, for example, 1 gwei, which is going to be equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, this much wei. So before I hit fund here, if I copy this fake account, which is up here, and I put it in this address to amount funded, it's going to return 0. But now, if I add 1, 2, 3, 4, 5, 6, 7, 8, 9 in here, and we go ahead and hit fund now, we've now just called this fund function with a value of 1 gwei associated with it. So if I call this address to amount funded now with the same address, I can now see how much we've funded this smart contract. And we can even add more gwei. We'll add 11 gwei, for example. We'll call fund. And if we call this now, we can see that even more has been added. When we send our funds to a contract, this actually means that this contract, wherever this is deployed, now is the owner of this amount of Ether. So this is fantastic. We now have a way to fund our smart contracts. Now, here's the thing. In this smart contract, in this funding that we're doing, we want to create a minimum value for people to be able to fund our endeavors, which, whatever they may be. We want to set some minimum value here. And Ether is great, but for whatever reason, we want to work in USD, or maybe we want to work in some other token. So how are we going to get the conversion rate from that currency to a currency that we can use in this smart contract? Well, the first thing that we're going to need to do to set this value is we're going to need to know what the ETH to USD conversion rate is. Because if I want to accept Ethereum as the token, but I want it in its USD currency, well, then I'm going to need to know what that conversion rate is. So how are we going to get this data into our smart contract? Where are we going to get this data from? Now, remember how we talked about blockchains being deterministic systems and oracles being the bridge between blockchains and the real world? Well, this is exactly where oracles come in. When we're talking about these systems, these blockchains, they can't connect to real world events. They can't connect to external systems. They can't do external computation. They're intentionally these deterministic systems, these walled gardens. So in order for us to make this connection, we need a blockchain oracle. We need some type of network here. Now, just to get a little bit more technical for you, if we look at a blockchain can easily say 1 + 1 = 2, and every other node can easily verify this. However, a blockchain can't easily say, okay, let's all grab the same random number, because each node is going to get a different random number. They also can't say, hey, let's make an API call, because if one node calls the API at a different time, another node calls it, or specifically like an HTTP GET, there could potentially get very, very different results. And if another node tries to replay these transactions by calling these APIs again, maybe 10 years in the future, there's a good chance that that API is going to be depreciated. And they could be hacked, they could be malicious, etc., etc. The other reason that blockchains intentionally can't make API calls is because then they would be making assumptions about the real world. And layer ones typically don't want to have an opinion on any political or geopolitical issue, whereas an oracle network, on the other hand, can make those assumptions. The other main thing we need to talk about here is centralized oracles being main points of failures. If you or I say, hey, I'm just going to be the oracle, I'm going to be the one to put this data on chain, we now have this massive centralized point of failure. We've done all this work to make our decentralized computation decentralized and on-chain, but we ruin all the decentrality by having a single point of failure. Remember, one of the whole purposes of blockchain is so that not a single entity can flip a switch and restrict our freedom to interact. With a centralized oracle, a single entity can flip a switch and restrict our freedom to interact with each other. We also need to get data from many different decentralized sources or do any type of computation in a decentralized manner. This is where Chainlink really shines. Chainlink is a modular, decentralized Oracle infrastructure and Oracle network that allows us to get data and do external computation in a highly Sybil-resistant, decentralized manner. It can be as customizable as you want, as you can run with one node or many nodes, or do as many nodes as you like. Now, currently, one of the most popular features of Chainlink is their data feeds or their price feeds. We can even go check them out over at data.chain.link. We can see a number of different price feeds and the networks that are providing the prices for these specific pricing points. We can see here by looking at the UI, there's a whole number of decentralized different oracles returning data for different price feeds. This one, for example, is ETHUSD, and it's also exactly the price feed that we're looking for. Having a decentralized network bring this data on-chain and have it as a reference point of definitive truth allows users to all collaborate and use this common good, and it will be cheaper, more secure, more efficient than anybody even running their own centralized oracle. So these price feeds are incredibly powerful. Additionally, they're being used by some of the top protocols in the DeFi system right now, like Synthetics, which at the time of recording is securing around $2 billion. SushiSwap for leveraging trades, Set Protocol, Commodity Money, Aave for understanding the price of an underlying collateral. Now, this is an example of an out-of-the-box decentralized solution that's already been packaged in a decentralized manner for you to consume and for you to use. This makes going to production 1,000 times easier than building everything yourself. However, if you want to make API calls and build your own decentralized network, you absolutely can with the Chainlink API calls. We're not going to go into that here because using the Chainlink price feeds, Chainlink VRF, Keeper Network, and all these other pre-boxed decentralized services are going to make going live and going mainnet a lot easier. You can always make a Chainlink HTTP GET call as well. We're not going to go over this though because putting this into production is a little bit trickier, and working with Chainlink VRF, if you ever want to try them out by themselves, you can always head over to docs.chain.link and head over to get the latest price feed. There's usually a remix button actually that we can click, and it will kick us out to a remix edition with all the code already ready to go for us. If we just hit this gist right here, this will include all of our code, which we'll go into in a second. But let's go ahead and compile it. We're going to deploy it to a real network here. This one looks like it's actually for Kovan, so we're going to go ahead and switch to Kovan. Looks like I don't have any Kovan Ethereum, so we're going to grab a Kovan faucet. We can usually find different faucets in the Chainlink documentation. Let's look up Kovan here. Aha, there is a Kovan faucet here. It looks like in order for us to get some Kovan Ethereum here, we have to log in with GitHub. Then we can add our address in here and get the Ethereum. In the interest of time, I'm going to skip ahead from me doing that. Great, it looks like I've got some Kovan testnet now. Being able to switch between testnets is going to make you a lot more effective as an engineer as well, because you're going to be able to understand how each network actually works. So now we've compiled this. Let's deploy this. Again, MetaMask is going to pop up. And let's go ahead and click the get the latest price, and we can see that this function does indeed return the latest price of Ethereum. Now you might be asking, why does this number look so big? Well, remember how we talked about Wei and Gwei and Ether? Well, the reason that those exist is because decimals don't work in Solidity. So we actually have to return a value that's multiplied by 10 to some number. So this value is actually 2,614 times 10 raised to the 8th. Now, the next question you might ask is, well, why did we work with this on a testnet? Why couldn't we do this on a local network? And the answer to this is because there is a network of nodes looking at this testnet and delivering data onto this testnet. When you spin up a local network or do a simulated VM, there are no nodes actually doing that. We'll learn later how to actually mock these interactions and mock a Chainlink node returning data onto our blockchain. But for now, let's head back over to the contract that we're working on so we can learn how to implement this in any contract that we ever want to. Another contract in this case called price feed, has a function called latest round data, which returns a lot of data. It returns a round ID, which defines how many times this price feed has been updated. It returns a price, which is the actual conversion rate between the two assets. It returns a started at, which defines when this was last updated. It returns a timestamp, and it returns an answered in round. Don't worry about answered in round for now. If you want to dive a little bit deeper into what these rounds mean and what answered in round means, you can definitely check out the Chainlink documentation and some of the FAQs to learn more. Now, how do we implement this data feed into our FundMe application? Well, the first thing we're actually going to need to do is we're going to need to import the Chainlink code. So we're going to do import at Chainlink/contracts /source /v0.6 /interfaces /aggregator v3 interface.sol. Now let's talk about what this is actually doing. Oops, looks like I spelled aggregator v3 interface wrong. All right, great. Now it's actually compiling. So let's talk about what imports actually do. As we know, an import will take whatever code you're importing and stick it at the top of your project. So when we import from @Chainlink/contracts, we're actually importing from the @Chainlink/contracts npm package. We can look up @Chainlink/contracts in npm, and we can see and read more about this repository. This links us back to the GitHub, which will tell us a little bit more about what's really going on. If we follow that import path that we got from the documentation, we'll end up on this file. In front of me now, we have what's called an interface. You can see these contracts don't start with the contract keyword, but they start with the interface keyword. They have the exact same pragma solidity at the top, but the main difference is that you can see that their functions aren't completed. They just have the function name and its return type. Now, just to be a little bit more explicit here, I'm actually going to go ahead and delete this import statement on the top and replace it with that interface code from GitHub, just to show you exactly what's going on. However, if you've already typed that @import syntax, feel free to leave it in there. And just remember that it's going to be the exact same as me copy pasting the interface code in. In our code here, Solidity doesn't natively understand how to interact with another contract. We have to tell Solidity what functions can be called on another contract. This is where interfaces are actually going to come in. Similar to structs, what we can do with interfaces is define a new type. So if we copy all of this code from this section and place it at the top of our code here, above where we're declaring a contract, we can actually then interact with contracts that have these functions. If we go ahead and even compile this, we can see that this does indeed compile correctly. Remember how we said before, we talked a little bit about ABIs. Well, interfaces actually compile down to what's called the ABI, or the Application Binary Interface. The Application Binary Interface tells Solidity what functions can be called on another contract. We need Solidity to know what functions it can use and what functions it can call other contracts with. And if that was a little bit confusing, just know anytime you're going to interact with another contract in Solidity or smart contract programming in general, you're going to need that contract's ABI. We'll go into what these ABIs look like a little bit later. Anyways, to simplify it, interface compiles down to an ABI. We always need an ABI to interact with a contract. So how do we actually work with this contract here? To interact with an interface contract, it's going to work the exact same way as interacting with a struct or a variable. Let's define a new function called getVersion, and we're going to call this version function on this other contract. So we'll start out doing function getVersion public. Remember, it needs to be a view since we're just going to be reading this state, and even in the interface, it even defines it as a view returns. So we'll even grab this whole bit right here, view returns uint256. Now, the exact same way we define variables and structs, we define working with other contracts and interfaces. So the first thing is we name the type, which in this case is aggregator v3 interface. Then we'd name the visibility. But since again, we're inside of this contract, we're going to skip it. Then let's give it a name. We'll call it price feed, since this aggregator v3 interface is going to be giving us a price feed. Then we can do equals, and this is where we're going to initialize the contract. So how do we actually choose where to interact with this contract? Well, we just type aggregator v3 interface, and then we put in here the address of where this contract is located. In order to find where this ETHUSD price feed contract is located on the RINKB chain, we can look at the Ethereum price feeds Chainlink documentation. It has a ton of different price feeds and even more not price-related data. Let's scroll down to RINKB because, again, on each different chain, the contract address that has all this price feed information is going to be different. Let's scroll down and find ETHUSD, which is right here. And we'll copy it and we'll paste it into here. Now, what is this line saying? It's saying that we have a contract that has these functions defined in the interface located at this address. If that's true, then we should be able to call pricefeed.version. And we should be able to return it. Whoops, looks like we forgot to add those here. And we need a semicolon here. I hit Control S or Command S, compiles. It looks like we're compiling successfully. And we do need to deploy this on a testnet. Remember, this address here is located on an actual testnet. It's located on an actual network. It's not going to be located on our simulated chain here. So we do need to deploy this to injected Web3. We do need to deploy our contract to RINKB because the RINKB chain has this address. We'll learn later on how we actually can work with a simulated chain and work with these price feeds, but that's much later in this course. So let's go ahead and save. We'll deploy. Make sure we're on injected Web3. Now we can go ahead and hit deploy. MetaMask is going to pop up per usual. Confirm. We're going to get a transaction link to Etherscan showing us our contract. And once it actually is confirmed, we can see we have our contract right here. Now we have our familiar functions with one additional function. We have our fund button, which is red because it's payable. We have our address to amount funded mapping, which is blue because it's a view. And we also have this get version button that's also blue. If we go ahead and click it, we can see that the version of our aggregator v3 interface is version 3. This is the third version of the aggregator interfaces, hence the name, aggregator v3 interface. So we just made a contract call to another contract from our contract using an interface. This is why interfaces are so powerful, because they're a minimalistic view into another contract. So this is great. We have a get version function, but this still isn't the function that we want. We want to call the get price function, which if we look at our interface, we can see there's a latest round data function that returns an answer. This is the function that we're going to want to call on this contract. So let's go ahead and make a function that calls that instead. So we're going to do function get price public view returns uint 256. This latest round data function though returns 5 variables. So how do we actually work with that? Well, let's find out. To work with this contract, we're going to do the exact same thing. We're going to do aggregator v3 interface because this is the type of the contract. Price feed equals aggregator v3 interface. We'll do this same address in here because this is the ETHUSD address. Then we'll do price feed dot latest round data. Now, since this is going to return 5 different values, we can actually have our contract also return these 5 different values. We can copy paste like this and literally do this these 5 values equal price feed.latest round data. And you can see that even compiles correctly. Let's adjust the formatting a little bit here so it looks a little bit nicer. A tuple is a list of objects of potentially different types. This is the syntax for getting a tuple. We can define several variables inside one of these tuples. Although our compiler is going to give us some warnings. It's saying unused local variable because we're not actually using these for anything. We'll come back to this. Now we can go ahead and do return, and we can pick one of these variables that we want to return. Answer is going to be the price. So we're going to do return answer. But we're going to run into an error. Return type argument int 256 is not implicitly convertible to expected type. Answer is an int 256, and we want to return a uint 256. So how do we rectify this? We can fix this by using what's called typecasting. If we just return answer, we're going to be returning the wrong type. However, integers in Solidity are really easy to cast into each other. So we can just do uint 256 and wrap it around this answer, and then compile and save that instead. As you can see, now our compiler is happy because we've changed this answer into a uint 256. Awesome. So now this get price should return the latest price of Ethereum in terms of USD. Let's go ahead and deploy this new contract with this new function. So same thing, we're going to come to our deploy section, hit the deploy button. Remember, we got to go to the fundme.sol. Let's deploy it. Confirm with MetaMask here. And let's scroll down to our newly deployed contract. As you can see, we have our get version function, which still works exactly the same, but we have a new function too, called get price. And this should return a uint 256 answer. Let's go ahead and click it. Amazing! We've actually returned an answer. Now, again, if you're a little confused on why this number looks so big, you have to remember that this actually has 8 decimals. We could call this decimals function on the contract to learn that. 1, 2, 3, 4, 5, 6, 7, 8. And we know that the current price of Ethereum in terms of USD is 2,482. Awesome. So now that we have the price, we can actually get the conversion rate. But let's clean up this function a little bit before we go on up there. As you can see, one thing that the compiler is complaining about is we have a lot of unused local variables. But latest round data returns 5 different variables. So how do we actually return the 5 variables, but make our compiler happy with us? Well, we can actually just return blanks for each one of these sections with commas in between each other to say, hey, there is a variable here, but we're not going to use it. This will also make our code look a lot cleaner because now this function's a lot smaller. We say, something's here, we're ignoring it. In 256 answer, we're going to use something's here, ignore it, something here, ignore it, and ignore this too. And we can even test this out by compiling it, deploying it, checking on RinkB, scrolling down, hitting this, and hitting get price. And you can see, indeed, it's the exact same as before. Awesome. So now we're all done cleaning things up, right? Not quite yet. See, the other thing that's really annoying here, we have this massive chunk of code at the top that is probably a little redundant. There's a good chance that a lot of our contracts are going to want to use this aggregator v3 interface. So let's just go ahead and add that @chainlink/contract syntax backend because it's going to look a lot cleaner here. And do @chainlink/contracts. If you ever get a little bit confused with what you should be importing to work with their contracts, we can see right in the documentation at the top, this @syntax is what this is going to use. Now you can also go ahead and browse that npm package of @chainlink/contracts to see what other applications are in there and what other files are in there, or you can just peruse around the GitHub. Now, the third way we can actually do imports is we can import from contracts that are in the same file system as our contracts. Well, awesome. Our contract is starting to look more and more put together. Now, one other thing that I usually like to do with these is I usually like to put everything into the GUI way standard. So as we saw, this get price had 8 decimal places. However, the smallest unit of measure, aka way, if we look at it, has 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. So typically in these, I like to try to make everything have 18 decimals as well. You don't have to do this, and it'll save some gas if you don't, but I usually like to multiply everything so that everything has 18 decimal places. So since I know this has 8, I can just do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now this will return the price with 18 decimal places instead of 10. Now we have the price of Ethereum in US dollar, which is fantastic. So we could set the price of our funding function to anything that we want here. For example, let's say $50. We could convert whatever value that they send us to its US dollar equivalent and see if it's greater than or less than $50. All we have to do is make a new function that converts that value that they send to its US dollar equivalent. So we could do function get conversion rate, and it'll take a UINT256 ETH amount. Let's get this out of the way for the rest of this. It'll be a public view function, since again, we're not actually going to have it make any state change. We'll do returns UINT256, and then in this function, we can do UINT256 ETH price equals get price. And we can call this get price function up here. Now we have the price in here. What we want to do is we want to convert whatever value that they send as ETH amount. Let's say they send 1 gwei, or again, that's going to be this much wei. How do we convert this to ETHUSD? Well, we can now do UINT256 ETH amount in USD equals this ETH price times the ETH amount that they sent. This is actually going to result in a much bigger number than we're looking for. And then, of course, we're going to return it. Let's test this out and see why we have to do one more thing here. So let's, again, fund me. We'll deploy RINKB. And we'll scroll down, and we have this new function called get conversion rate. Let's grab this 1 gwei and put it in here. Whoa, this seems like it's a really big number. We're saying that 1 gwei is equal to 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This many dollars. Now, I don't know about you, but I don't think the price of even 1 Ethereum is that many dollars. Maybe in the distant future, but definitely not right now. The reason that it's off is we have to then actually divide by this number. The reason that we have to do this is because both ETH price and ETH amount have an additional 10 raised to the 18th tacked onto them. So now we have to divide it out in order to get the right number. So we're going to compile, deploy, confirm. We can scroll down, and now let's try this 1 gwei. We'll get the conversion right here, and we can see we get a number that makes a little bit more sense. Now remember, this has 18 decimals as well. So the real number is 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we know that this number is actually accurate because we can go ahead and pull up a calculator, pop that into here, and we know that this is 1 gwei in US dollar. If we get the conversion rate, we're saying that this many gwei equals 1 ETH. So we can check it back by multiplying this number by that, and we see that we do actually get the price of 1 Ethereum in US dollar. So our math here checks out. Awesome. Now, since we're on the topic of math, I do want to talk briefly about some of the pitfalls of Solidity, especially when it comes to math. Prior to Solidity 0.8, if you added to the maximum size a UINT number could be, it would actually wrap around to the lowest number that it would be. And in fact, you can even demo this with a contract here. Now, you don't have to follow along with this contract, but just watch to see the example. We're going to call this overflow.sol. Now in here, we're going to add all kind of the normal stuff, contract overflow, and we're going to add a function called overflow. We'll make a public view, and we'll have it return a UINT 8. I'll show you why in just a minute. A UINT 256 is a really, really big number, and it's hard to kind of imagine going over the maximum cap of a UINT 256. But a UINT 8 is a lot smaller, with the maximum number actually being 255. So if we create a UINT 8 and we call it big equals 255, and then we just do return big, what do we think we're going to get here? For this, we can go ahead and use JavaScript VM because we're not interacting with any other contracts. Let's deploy this, and we'll see in our contract, if we call overflow now, we're just going to get 255. However, what happens if we add 1 to this number or try to add 1 to this number? If we do it just like this, Solidity actually knows that there's an issue here and says, hey, try not to do this. But if we typecast this as a UINT 8, Solidity gets a little bit more confused and goes ahead and lets us do this. Now, what do we think big is going to be? It should be 256, right? But big is a UINT 8, and this is the maximum size that it could be. So what happens when we deploy this? We look down. We actually get 0. What happens if we do 100 and we deploy that? We actually get 99. And this is because integers can actually wrap around once you reach their maximum cap. They basically reset. This is something we need to watch out for when working with Solidity. If we're doing multiplication on really big numbers, we can accidentally pass this cap. Luckily, as of version 0.8 of Solidity, it actually checks for overflow, and it defaults to check for overflow to increase readability of code, even if it comes a slight increase of gas costs. You can use this unchecked if you want to have it keep that wrapping functionality. So just be aware, if you're using a lower version than 0.8, you're going to have to do something to make up for this. And we could write a whole bunch of code here basically to check all of our math, or we could just import something called SafeMath from another package. Similar to how we imported Chainlink, we can go ahead and import a package called SafeMath from a tool called OpenZeppelin. Now, OpenZeppelin is an open source tool that allows us to use a lot of already pre-built contracts. We can go ahead to their documentation and go to their utilities and see SafeMath. And they even have a little sticker here saying, SafeMath is no longer needed, started with Solidity 0.8. SafeMath is a tool and a way for us to avoid some of these problems with doing math in Solidity. Now, I'm not going to spend too much time on the contracts that actually fix this, but we can actually import right from the Chainlink directory as well a Solidity file called SafeMath Chainlink. And what we can do is right after our contract, we can do using SafeMath Chainlink for UINT 256. And what this will do is it'll use SafeMath Chainlink for all of our UINT 256. And SafeMath Chainlink doesn't allow for that overflow to occur. Libraries are really similar to contracts, except that they're isolated code that can be run in a reusable context. In this case, we're attaching the SafeMath Chainlink library to UINT 256 so that these overflows are automatically checked for. Just keep in mind, if you're using anything less than 0.8, you're going to want to use some type of SafeMath just to check for your overflows. Now, this is for those of you who are familiar with SafeMath and integer overflows and underflows. We are not going to be calling the functions that SafeMath provides us, like div, add, mul, all those functions. Simply because in 0.8 moving forward, we no longer have to use those, and we can just use our regular operators like plus and minus. So this is great. Our contract is coming along really well. We now have a way to get the conversion rate of whatever ETH is sent and turn it into US dollar. Now we can set a threshold in terms of US dollar. But how do we guarantee that whatever amount that the users send when they call fund is going to be at least $50? Well, first we might want to set a minimum value. So we can do UINT 256 minimum USD equals, let's say, $50. And again, since we're using everything in GUI terms, we want to then multiply this by 10 raised to the 18th. And just wanted to take a pause for a second because this line is actually wrong. This should be raised to the 18th. So this line should really look like this, where it has the double star. So apologies, the rest of this has that single star, but it should be the double star here. If you do have the single star though, the rest of the contract will still work fine. So this will be the minimum value. It'll be $50 times 10 raised to the 18th so that everything has 18 decimals. Now that we have a minimum amount, how do we actually make sure that this minimum amount is met in the value that they send us? Well, if you're familiar with if statements, we could do something like if message.value is less than minimum USD, then revert. Or we could do something a lot easier and better practice and much cleaner. We could do what's called a require statement. When a function call reaches a require statement, it'll check the truthiness of whatever require you've asked. So in our case, the converted rate of message.value needs to be greater than or equal to our minimum USD. This line says that if the conversion rate of message.value to USD, if they didn't send us enough Ether, then we are going to stop executing. We're going to kick it out. We're going to say, hey, this doesn't count, and we're going to do what's called a revert. We're going to revert the transaction. This means that the user is going to get their money back as well as any unspent gas, and this is highly recommended. We can also then additionally add a revert error message, something like, you need to spend more ETH. So now let's try this out. As we saw, 1 GUI is going to be way less than $50. So if we send 1 GUI along with this fund contract call, it should kick out and say, you need to spend more ETH. So let's actually try this. Let's go to the deploy tab. We'll get rid of our overflow. We use injected Web3 because again, we are working with the Chainlink aggregated contracts that are on chain. We're going to move to fund me and we're going to hit deploy. MetaMask is going to pop up and we're going to hit confirm. Now, if I try to hit fund, let's see what happens. We're getting a gas estimation failed. It says gas estimation error failed with the following message. Execution reverted. You need to spend more ETH. So the contract isn't even letting us make the transaction. We can go ahead and try to send the transaction, but here's what's going to happen. On Etherscan, once this goes through, you can see that once this transaction finished, we got this status, fail with error. You need to spend more ETH. We don't want to force these transactions to go through. If we look in our MetaMask, we can even see this failed bit here. So whenever you see these gas estimation failed errors, usually that means something reverted or you didn't do something that was required. However, if we go to value here and we spend a lot more, let's say 0.1 Ether, which if we take out our calculator, 2500 times 0.1 is going to be $250. This should easily be well and beyond past our $50 threshold. So let's add 0.1 Ether. And remember, we got 0.1 by adding it in the converter and grabbing the way. Again, the way is the smallest denomination. Now, if we change this to way and hit fund, this should go through. We go ahead and hit fund now. You'll see MetaMask pops up because MetaMask goes, oh yeah, this transaction isn't going to revert. And that's what we want. So we can go ahead and hit confirm. And now we'll finally have sent some funding to our contract. And now that this is confirmed, we can go ahead and grab our address here, pop it into our address to amount, and we can see that indeed our funding has gone through. Now we can be part of this crowdsourcing application with our minimum value, which is fantastic. Awesome. Great job. Awesome. So now we can fund this contract with a certain minimum USD value. In this case, it's going to be $50. Now, you'll notice though that right now we don't do anything with this money. So we're going to fund this contract. However, that's it. And we don't have a function in here to actually withdraw the money. So there's no way that even though we just sent this contract some money, there's no way for us to get it back. So how do we fix this? Well, we can add a withdraw function in here. So let's go ahead and add that. Function withdraw. And this is also going to be a payable function because we're going to be transferring ETH. We'll make this public. And we can do message.sender.transfer. Transfer is a function that we can call on any address to send ETH from one address to another. This transfer function sends some amount of Ethereum to whoever it's being called on. In this case, we're transferring Ethereum to message.sender. So all we need to do now is define how much we want to send. Well, we're going to send all the money that's been funded. So to get all the money that's been funded in this contract, we can do address this dot balance. Now, there's a couple of special things going on with this line. First, we're saying address of this. This is a keyword in Solidity. Whenever you refer to this, you're talking about the contract that you're currently in. And when we add address of this, we're saying we want the address of the contract that we're currently in. Whenever you call an address and then the balance attribute, you can see the balance in Ether of a contract. So with this line, we're saying whoever called the withdraw function, because whoever calls the function is going to be the message.sender, transfer them all of our money. So let's go ahead and try this. Let's deploy FundMe. And now let's fund this with a lot of Ether so that we can see it. We'll fund it with one whole Ether so that we can see it go into the contract and get pulled out of the contract. We'll hit the fund button and you'll see we're sending one whole Ether into this contract. Now, if we look at our balance, it's gone down from 17 to 16. Or if you're still at 18, it went down from 18. So let's try to get it back. If we call this withdraw function now, confirm, once this transaction goes through, we should get all of our Ether back. Let's look at our MetaMask and boom, indeed, we have got all of our ETH back. However, looking at this contract, we can see that, well, maybe we don't want anybody to be able to withdraw all the funds in this contract. That seems like it might be a really bad idea. Maybe we only want the funding admin to be able to withdraw funds. So how do we set this up in a way that only the contract owner can actually withdraw funds? Well, we learned before that the require function can actually stop contracts from executing unless some certain parameters are met. We can do the same thing here with require message.sender equals the owner. But we don't have an owner to this contract yet. So how do we get an owner to this contract the instant that we deploy it? Well, we could have a function called create owner. But what happens if somebody calls this function right after we deploy it? Well, then we wouldn't be the owner anymore. So we actually need a function to get called the instant we deploy this smart contract. And that's actually exactly what the constructor does. So typically at the top of your smart contracts, you'll see a constructor. And this is a function that gets called the instant your contract gets deployed. We don't even need to do add function here. We can literally just call it constructor because it's what constructs the smart contract. So we'll make constructor public and whatever we add in here will be immediately executed whenever we deploy this contract. So one thing that we could do is we could have an owner be set the instant we deploy the smart contract. So in the top, we could add address owner. And in our constructor, we could say owner equals message.sender because the sender of this message is going to be us. It's going to be whoever deploys this smart contract. We can even test this out in the JavaScript VM to be a little bit quicker because we're not actually going to be calling the fund or the get price function for now. Oops, let's also make this public so that we can interact and see this owner variable. So now if we go to FundMe, we deploy this in the JavaScript VM, we should be able to see who the owner of this contract is. And it should be our address because this constructor function should have been immediately called the instant that we deployed the smart contract. Awesome, we can see the owner of this smart contract is indeed our wallet. Because remember, when we're working with the JavaScript VM, our wallet is these fake wallets that they kind of give us. We can even try this with an injected Web3 with deploying this. And the owner should be this OX757, etc. address. Let's go ahead and look at FundMe, see the owner, and we do indeed see the owner is us. Okay, great. Now we have an owner. We can go down to our withdraw function and use that same require. So we can call require message.sender equals equals owner. Equals equals is the way that Solidity understands true false. We're saying that message.sender has to equal owner. Now let's go ahead and try this, and we'll try it with the JavaScript VM again for speed reasons. Let's deploy this FundBee. And if we go down here, we can try to call the withdraw function. And it looks like it is successful because currently this is the address that deployed the contract, and it's also the address that is calling withdraw. However, if we switch to a different account and call withdraw, you'll see that Remix actually freaks out down here. It says, uh-oh, something wrong happened. And this is essentially the require statement kicking out. If you want to try it with injected Web3 as well, we can absolutely do that too. And remember, the way to switch accounts in MetaMask is to either create account right here or just switch like this, and then we'll connect with account 2. So if I try to withdraw from this second account that didn't call the contract, and I hit withdraw now, it's going to give us gas estimation failed because the require statement is going to kick out. But again, if we switch back to account 1 and we call withdraw, MetaMask is going to pop up and it's going to allow us to withdraw. Now, obviously, there's nothing in this contract right now, so we're going to withdraw nothing, but we can still call it. It's going to do message.transfer 0. So this is great. We can now require this withdraw function is only callable by the owner. Now, what if we have a ton of contracts that want to use something like this? They require the message.sender to be some owner, or maybe it's more complicated than this. Is there an easier way to wrap our functions in some require or some other executable? Well, this is where modifiers come in. We can use a modifier to write in the definition of our function, add some parameter that allows it to only be called by our admin contract. Modifiers are used to change the behavior of functions in a declarative way. Let's create our first modifier. We'll call it modifier, which is a keyword, only owner, and we'll add this require statement in here. Require message.sender equals owner. Then after this, we just add an underscore and a semicolon. What a modifier is going to do is it's going to say, hey, before you run this function, do this require statement first, and then wherever your underscore is in the modifier, run the rest of the code. So we could also do a modifier where the underscore is up here, and then this is afterwards, but we want to run the require first. So now what we can do is we can make this function withdraw payable only owner public. And what's going to happen is before we do this transfer, we're actually going to check this modifier. We're actually going to run this require message.sender equals owner. And then again, where this underscore is, that's where we'll add the rest of the function. So again, for speed reasons, and since we're not actually going to be interacting with the Chainlink data contract, we can go to JavaScript VM, switch to FundBee, deploy, and we can call withdraw. Obviously, we can call withdraw from our account, but if we switch accounts and try to call withdraw, we're going to get an error, which is perfect, because that means our modifier is working correctly. Awesome. Now we have a fantastically succinct FundBee contract here. The only thing that we're really missing is that when we withdraw from this contract, we're actually not updating our balances of people who funded this. So even after we withdraw, this is always going to be the same. So we need to go through all the funders in this mapping and reset their balances to 0. But how do we actually do that? We can't actually loop through all the keys in a mapping. When a mapping is initialized, every single key is essentially initialized. Now, we obviously can't go through every single possible key on the planet. However, what we can do is create another data structure, an array, something we're already familiar with. So let's go ahead and create a new funders array. That way we can loop through them and reset everyone's balance to 0. We'll do an address array because it's going to be an array of all the funders' addresses. We'll make it public and we'll call it funders. Now, when somebody funds a contract, what we're going to do is we're going to do funders. Now, whenever a funder funds this contract, we can go ahead and push them onto our funders array. So we can do funders Push message.sender. Now, if somebody funds multiple times, the funders array is going to be a little bit redundant, but we're going to ignore that for now. Now that we have an array of funders, when we withdraw everything, we're going to want to reset this to 0. When we withdraw everything, we want to reset everyone's balance in that mapping to 0. So we're going to do what's called a for loop. A for loop is a way to loop through a range of numbers to do something. So we're going to say for Uint 256 funder index equals 0, because we want to start with the 0th index. We're going to give it a max size to go to. We're going to say the funder index has to be less than funders.length. .length is how we get the length of our array. And then we're going to say funders index plus plus. This means that we have an index variable called funder index, and it's going to start from 0. This loop is going to finish whenever funder index is greater than the length of the funders. Every time we finish a loop, we're going to add 1 to the funder index. That's what that funder index plus plus does. It adds 1 to the funder index. And every time whatever code is in this for loop executes, we're going to restart at the top. And all we're going to do in here is we're going to grab the address of the funder from our funders array. Funders. So the funder at the index in our funders array, we're going to use this as the key in our mapping. So we're going to take address to amount funded of funder, and we're going to set it equal to 0. So now our mapping is going to be all updated to people having 0 funded in there. We do have to do one more thing as well. We have to reset our funder array as well. Now there's a couple ways to do this, but a really easy way is just to set funders equal to a new array. So we could do funders equals a new blank address array. So all right, it looks like we've got everything in here we need. Right away when we deploy this, we are set as the owner. We can allow anybody to fund whatever public good that we're doing. And they have to fund it with the minimum USD value that we actually set. Whenever they fund, we'll keep track of how much they're funding and who's been funding us. We can get the price of the Ethereum that they send in the terms of USD. And we can convert it to check to see if they're sending us the right amount. We have our only owner modifier so that we're the only ones who can withdraw from the contract. And when we do withdraw everything from the contract, we reset all of the funders who have currently participated in our crowdsourcing application. Awesome! Let's see if everything works end to end. So we're going to go to Fund Me. We're going to deploy it. We're going to confirm from MetaMask. And remember, if you're ever confused about what's going on or something weird is happening in your transactions or your deployments, you can always go into Etherscan and read more about your transaction and what's going on. Now that our transaction has been deployed, let's go ahead and just take inventory as what's going on. We have our owner, which is our address right here. We have the aggregator v3 interface version, which is version 3, which we can kind of ignore. We have the price of Ethereum in terms of USD with 18 decimals instead of 8. We have a function that allows us to get the conversion rate of any Ethereum amount to its US dollar equivalent. We have an array of funders, which right now starts out as empty. We have a mapping of addresses, which also right now starts out as empty. Let's go ahead and try to fund this contract. We'll use Way, just so that we're always on the same page, and we'll fund it with 0.1 Way. Remember, everything has 18 decimal places. So if we want to do 0.1, we just do 17. So we can do 1, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9. And that'll be 0.1 Ethereum. Now we can go ahead and hit fund, and we're going to send 0.1 ETH to this contract. Great. So if we look at the 0th index of funders, we can see that indeed we have funded this contract. Let's even have our second account fund this contract. So all we got to do is switch to this contract in MetaMask. We can go ahead and put 0.1 ETH back in here for value and hit fund. Now, as you can see, we're deploying this from account 2. Let's go ahead and hit confirm. Funder at index 0 is going to be our admin, and the funder at index 1 is going to be our second account. And if we go ahead and we add this funder in here, we can see we've indeed sent 0.1 Ether with this account. If we go back to our account 1 and put this in here, we can see that that address also has 0.1 Ether. Fantastic. So let's try to be malicious. Let's try to have account number 2 actually withdraw all the funds in here. Let's hit this withdraw function. Uh-oh, the transaction has failed. We're relentlessly malicious. We want to send this transaction regardless. So even though I'm not the admin of this contract, I've gone ahead and still tried to send this withdraw. So what happens now? We can see that Remix is saying, hey, something went wrong. And again, if we look at Etherscan, we can see that there was a fail here. Since in our modifier, we didn't give a reason here, nothing shows up. But we could have always put a reason in there and something would show up. So, all right, let's go ahead back to the actual admin. And now let's try to withdraw everything. So if we hit withdraw now, we can go ahead and confirm. What should happen is everything in here should be back to 0, and this array should be back to 0 as well. And if we watch our address, we can see it literally just went from 0.4 to 0.6 because it got 0.1 from the original funding that this account put in and the 0.1 that our second account put in. So now if we look at funder 0, we can see it actually errored because it is now a brand new array and there is nothing at index 0. If we try to see how much this address now is funded, it's back down to 0. Awesome, you've now learned how to deploy a relatively simple yet effective crowdsourcing application where users can fund and an admin can withdraw those funds to go spend them on things. Now, we've been working with Remix so far to start our smart contract and our Solidity development journey. Remix is an incredibly powerful, what's known as a web IDE, or an integrated development environment. And in my opinion, Remix should always be the starting ground for anybody looking to start their smart contract journey, because it is a wonderfully friendly way to really show what's going on behind the scenes. And it's really easy to see everything we're doing with Ethereum, with Chainlink, and with our smart contracts. Now, it does have some limitations though. It's really hard to integrate other parts of different projects. It has some limited support for testing or custom deployments. It's a little tricky to save files locally. You need an internet connection to actually interact with it, and it doesn't have Python. So in order for us to deploy, test, and automate everything about our smart contract development cycle, we want to connect our Solidity and our smart contracts with a more traditional programming language like Python. This way, we can customize our entire development environment in any way that we like. We're first going to teach you all how to work with what's known as web3.py, which is an incredibly powerful Python package for doing everything that we want to do with smart contracts. Then once we learn some of the basics of web3.py, then we'll move on to Brownie, which is a smart contract development framework built on top of web3.py, which makes our lives even easier. However, it's still really important to learn web3.py first because this will teach you what's going on behind the scenes of Brownie. Now, for the rest of this course, I'm going to be working with Visual Studio Code, which is an incredibly powerful text editor that will give us a lot of formatting and a lot of really nice tools to work with deploying and interacting with our smart contracts. If you've already got VS Code and Python and your entire coding setup set up the way that you like it, feel free to use the timestamps in the description to skip ahead to the next section. You'll often hear people referring to this as VS Code or Visual Studio Code. But just to point out, this is not what you're looking for right in front of you here. Visual Studio is a different application. Make sure you're on Visual Studio Code. If you want to be a total hardo and just work with Vim or Emacs or whatever else you want to do, you absolutely can, but I'm going to go through setting up Visual Studio Code the way that I like it. And if you guys want to follow along, I highly recommend it because it's going to make your life a lot easier. There's a link to download Visual Studio Code in the GitHub repository. Basically, all you have to do is come to the site right here and you can hit this big download button. It should recognize what operating system that you're on, be it Windows, be it Mac, or some other operating system. And if it doesn't, you can go ahead and hit this little drop down and pick one there. So let's go ahead and download Visual Studio Code and open it up. Awesome. Once you've downloaded Visual Studio Code, this is approximately what you should be seeing. There's a fantastic getting started section here where if you're brand new to VS Code and you want to learn a little bit more quickly, you absolutely can. And we have some links as well in our GitHub repository, giving you a crash course in VS Code if you want to learn more. Let's set this up though, so it's going to be really friendly for us to be doing our smart contract development here. So first, we want to go to this extensions tab. It looks like these little blocks thing right here. And first, we're going to look up Python, and you want to install this Python extension right here. This is going to make our lives a lot easier for interacting with Python and doing a lot of things with Python. Then you're going to want to go ahead and download this and install this Solidity extension. This is going to make formatting our Solidity a lot easier. Now we want to download Python if you haven't already. So go ahead to python.org. Let's go to downloads, and it should recognize what operating system that you're on. And you can just go ahead and hit the download button and then follow the steps to download this. I've already got it downloaded, so I'm not going to walk through this. Okay, great. Now that we have Python installed, one of the other amazing things about VS Code is you can actually open a terminal up inside of Visual Studio Code. The way you can open your own terminal, if this is your VS Code, you can go over on this top bar to Terminal and select New Terminal. And you'll see something that looks like this. It might be a bash, it might be a ZCH, it might be a PowerShell. There's a lot of different types of terminals that you'll be able to see by looking right here. We can now test to see if Python is installed correctly. If we type in Python space -- version, we should get something that looks like this. The exact version of Python doesn't really matter here, but ideally you're at least on Python 3.8. If Python -- version doesn't work, you could also try Python 3 -- version. Now, if neither one of those works, we actually have a number of troubleshooting tips in the GitHub repository for this course. And oftentimes, a quick Google search on whatever error that you have, you'll get a link which will lead you to the answer. But if that Google search doesn't lead you to the answer, then just go ahead and drop an issue or a conversation associated with your issue on the GitHub repo associated with this course. In particular, there are a couple of common errors that I've definitely seen a number of times. So if you see an issue on your instance that matches something on the screen here, definitely 100% be sure to check out those troubleshooting tips. Sometimes just installing some of these applications is really the hardest part of doing the entire coding journey here. So please make sure you have Python and VS Code installed correctly before moving on. And don't be discouraged if this doesn't work exactly the way that it should right away. Now, if you're on a Mac, you can actually hit Control backtick and it will toggle back and forth between having the terminal open and closing it. I find this really helpful and I use it all the time instead of hitting the buttons. A key tip for productivity is going to be using keyboard shortcuts instead of clicking around all the time. You'll be much faster. Okay, great. We have Python installed. We have Python and Solidity extensions of Visual Studio Code installed. Let's start working on a new project. So in our terminal, we can create some folder. I've already created a demos folder here. You can create one as well if you'd like by doing mkdir demos. Since I've already done it, the file already exists, and then cd into demos. You can type clear, or if you're on a Mac, Command K to clear the terminal. Now, here's what we're going to be doing. We're going to be working with simple storage, again, the exact same contracts, but instead we're going to be using web3.py. So we're going to make a new directory inside of our demos folder / directory called web3.py simple storage, and we're going to cd into this new folder right here. Now, again, all the completed code is going to be in our GitHub, and there's going to be a link to everything that we do in this folder in this GitHub. So you can always refer to that if you get lost. And the next thing that we want to do is we want to have our Visual Studio Code know that we're in this folder. So we can go ahead and click this files icon and hit open folder. And I'm just going to go to this web3.py simple storage and hit open. And another VS Code will actually pop up. We can see on the left-hand side here, we have a folder. This will show all the different files and folders in our web3.py simple storage directory. Let's go ahead and create a file .sol. We can right-click on this area and select New File and do Simple storage.sol. And then we can go back to our simple storage.sol and remix, copy everything, and then paste it into here. If you don't have it up, remember you can always refer back to the GitHub repository, which will have it in there for you. Awesome. Now we have our Solidity in its own file called simplestorage.sol. You'll notice that some of the words are actually highlighted different colors. This is known as syntax highlighting, and it's due to the fact that we added the Solidity extension in. It makes reading this code a lot easier. Now that this file is in here, we'll see that we have this little dot here. Whenever you see this little dot, this means that your VS Code file isn't saved. So we want to always save it. Otherwise, when we compile or we go to run a script, things might not work correctly. So we can save it by going up to File and then selecting Save. Or again, you're going to want to learn how to do the keyboard shortcuts because you're going to want to hit Save often. For Mac, it's Command S. And for Windows, it's Control S. Now, the other thing that you'll see is you get this red line here. This is VS Code's way of telling us it thinks that there's an error at this position. So this is really just the extension being a little bit confused here. And we can safely ignore this. And normally when I'm coding, I do just ignore it. We're often going to be flipping back and forth between compiler versions. So oftentimes this isn't really a helpful warning here. But if it is really bothersome, you could right click it and do something like Solidity change global compiler version, or we can go to Code, Preferences, Settings. Let's close this so we can see some more things in here. We'll look up Solidity and we'll come to this Solidity extension config. What we can do then is scroll down and we can see Solidity compile using remote version. This will allow us to choose what version we want to compile with. If we do 0.6.0 and hit save and go back to simple storage, you'll see the red line is now gone. While we have this up, another really helpful piece that we can do here is we can add what's called a formatter. So if we scroll down to Solidity formatter, you'll see that this enables/disables the Solidity formatter. We can go from none to prettier. Then we'll also look up format on save, and we want to make sure we have this editor format on save checkmarked. What we can do then is we can come over to simplestorage.sol, and maybe I've got some bad formatting in here. We'll move over favorite number, string name, and put a whole bunch of new spaces in here or something. Now, if I hit save, it automatically reformats our file to look a lot nicer. So to recap, we want to turn on format on save. And if you get issues with the red line under Pragma Solidity, you can just change the compiler version in your settings here. Now, while we're in here, we're also going to go ahead and set up our Python formatting as well. So the first thing that we're going to do is we're going to install the black Python formatter. So we're going to open up our terminal here. And whenever you install Python, it comes pre-installed with this package called pip. To check to see if you have pip installed correctly, run pip -- version. Now we can install the black formatter by running pip install black. I already have it installed, so it's going to be pretty quick for me. Then we'll come to our settings and we'll look up Python formatting. And we'll scroll down to Python formatting provider. You might have AutoPep8 or none in here. You're going to want to change it to black. This way, whenever we save our Python files now, they will also get automatically formatted to be very readable and really nice. And just to note, for my demos in Solidity, I don't always have format on save for Solidity. I do have format on save for my Python, but I'm still going to highly recommend you have format on save for both your Python and for your Solidity anyways. So how are we going to actually deploy this? Well, this is where our Python is going to come into play. Let's go ahead and create a new file on the left here, and we'll call it deploy.py. Now let's go into this deploy.py file, and let's start actually figuring out how we can deploy this in Python. And this is the part of the course where we start using Python here. If you're unfamiliar with Python or a little bit weaker on Python, there is a fantastic free code camp course that goes through all the basics of Python. If you want to learn more, I definitely recommend checking it out. However, we are going to walk you through all the scripts that we write anyways, so don't be afraid to just jump in and follow along with what we're doing here, even if you have no experience. So the first thing that we're going to want to actually do is read this simple storage Solidity file. We need to get this into this deploy script so that our Python file knows what it's going to deploy. So how do we do this? Well, we're going to type with open quote / simplestorage.sol, comma R, as file, simple storage file equals file.read. Now, what is this actually doing? Well, it's saying that we're going to execute some code inside this indented area after the colon. And then once this code is finished, we're actually going to close this file. Because right now we're opening it, we're going to close it once it's done. The file that we're going to open is going to be this simplestorage.sol, which is located right here in this same directory that we're in. We're going to only read from it, and we're going to call it file. And then we're going to read all the contents of this file and place it in a variable simple storage file. So then we can go ahead and write a print statement, print simple storage file. And if you hit save here, you'll see that it automatically gets formatted, which is really nice. If you want to run black yourself, you can just type black dot, and it'll automatically format all the Python files in your folder here. You'll know that you're doing it right if you add a whole bunch of new lines and then save it. Anyways, enough on formatting. Let's head on down to the terminal and let's call python deploy.py. And we can see our terminal printed everything in simple storage file, which is perfect. Now, our Python script has what it needs to actually get started working with our Solidity. Now, something you'll see I do a lot is I save a lot. And if you're looking for some keyboard shortcuts, you can always do Command P, add a little bracket here, and look up keyboard shortcuts reference, and click this. And it'll bring you to this keyboard's reference page based off of what operating system that you have. All right, great. So now that we can actually read from our simplestorage.sol file, we actually have to compile it. Because remember, back in Remix, every single time we did anything with our files, we had to compile them first. So we need some compiler in Python. Luckily, there is a fantastic Python package called pysulkx that does exactly this. Now, I also want to point out, though, that pysulkx is actually a fork of this package called pysulk. Now, you can still use pysulk. However, I'm going to highly recommend that you use pysulkx instead, as pysulkx is a lot more actively maintained than Ethereum pysulk. We can install it with pip install pysulkx. We could even hit this little copy button, move back on over here, paste it in, and hit enter. Again, I've already installed it, so it's pretty quick for me. The way that we can use it now is by importing it into our Python here. So we'll say from sulkx import compile standard. Compile standard is going to be this main function that we actually use to compile this code. So let's go ahead and compile our Solidity. We're going to save our compiled code to a variable called compiled sol. And this is going to be equal to us calling this compile standard function, but we're going to add a lot of variables and a lot of parameters into this function here. First thing we have to add is a language, which in this case is Solidity. We're going to add in some sources, which we're going to say our sources is going to be simple storage.sol, and it's going to have some content, which is equal to this simple storage file variable that we made. Oh, excuse me. This all has to be in a bracket piece as well. And see, if I hit save here, it auto formats, which is really nice. And another quick tip, you can see how even my brackets are highlighted in these fun colors. If we go down to extensions and look up bracket, you can add this bracket pair colorizer, which will help make the brackets look a little bit nicer, kind of as you see here. You can go ahead and install that as well. Anyways, then we'll add some settings. And a lot of this is a little bit lower level stuff than what you're really going to have to know or use. So I'm not going to go too deep into everything that's actually going on here for now. But in our settings, we're going to choose an output selection, which is going to choose what we output when we compile this. We do a little star here. And in the star, we're going to do another star. We're going to choose our output list. We're going to get an ABI out. That's incredibly important, which we've talked about before. We're going to get some metadata. We're going to get an EVM.bytecode. We're going to get an EVM.source-map. That's pretty much it. Again, I'm not going to go too deep into what this output selection and what these settings are actually doing. But if you want to learn more, you can go to the homepage of pysulkx, scroll down to the documentation section, and read more in the docs on what you can actually put and all the different features that this actually has. The last thing we're going to do is we're going to add a Solc version or Solidity version. We're going to say Solc version equals, and then we'll choose the version that we want to use. So we'll put in 0.6.0. And then what we should be able to do is print out this compiled sol, and we'll see just a whole bunch of really, really low level stuff. So let's go ahead and run this. We'll run Python deploy.py, and you'll see we get this massive object here, which has a whole bunch of basically unreadable pieces. But this is a lot of the low level code that actually gets compiled whenever we use the compiler in Remix or now in Python. Remix actually does the exact same thing. Once we compile something on Remix, you can actually copy the bytecode. If you hit this little copy button and copy the bytecode and come back to your VS Code and create a new file, a keyboard shortcut to create a new file is Command N, and we paste everything, we can see there's a whole bunch of stuff in here. These opcodes are the low-level code that our contract is actually doing, that actually governs how this code works. This is what our written code is getting compiled down to, so Solidity can actually read it and understand what's going on. You'll also see this thing called ABI, which is in Remix, and we're even going to output it right here. We have this ABI thing. Now in Remix, if you hit copy the button on the ABI, come back, create a new file, paste it, you can see we have this long JSON object. This is that application binary interface that we've talked about so much. You can see that it's actually describing all the functions and variables. So for example, we have a function called addPerson, and it takes two parameters, a name and a favorite number. So we have this input section for the function, and we have this section that describes what the function is actually doing. So the name is addPerson, it doesn't have a return type, it's non-payable, and it's a function. And we can see that for pretty much everything in here. This is the lowest digestible way to say, hey, here's where all the functions are, here's what the parameter types are, here's what the return types are going to be, and everything like that. So we're going to close it out for now, though. So this is fantastic. We've now compiled our Solidity. Typically, I usually also like to output it and print it out to a file as well. So to do that, we'll do with open compiled code.json. And this time, instead of reading, we're going to write, and we'll call this as file as well. Instead of doing file.write, we're going to do what's called a json.dump. Compiled sol file. We do need, of course, to import JSON. Also, just a note, I know it says we're using Solc here, but please use Solc X still. I ended up filming a little bit of both versions, so I did a little bit of a mix and match, but please use Solc X even if you see Solc. What this line is going to do is it's going to take our compiled sol JSON variable and just dump it into this file here. But it's going to keep it in the JSON syntax, so it's still going to be JSON-y. So now if we run Python deploy.py, we'll see we have a new file in here called compilecode.json. The other reason that I wanted to do this was because if I hit Control S, it actually formats this into a readable way. Now again, we can go into these settings here. We can look up JSON, and we can do enable JSON formatter. And this will automatically make it so that we format this JSON so it's a lot more readable. Again, the reason I like to output this is because this ABI is so important and we're going to use it so much that I like to kind of be able to see it and read through it really quickly. The rest of this lower level stuff like EVM and bytecodes and opcodes, we don't really work with so much. However, as you learn more and more about Solidity, you'll probably see more and more of opcodes. So if you really want to learn a lot of really low level stuff, look into opcodes, but for the purpose of this tutorial, we're not going to be going too deep into it. Okay, awesome. So we've compiled our Solidity. We've even stored our Solidity code to this compiled code.json file. Now what do? We probably want to deploy it and test it out. So how do we actually do that? Well, first, we actually have to get the bytecode. We need the bytecode of the file so that we can actually deploy it. So we're going to do bytecode equals compiled sol contracts simple storage.sol simple storage EVM bytecode object. All right, great. There we go. So now we have our bytecode. we also need to get our ABI. So we need to get the ABI. So what we're doing here when we're typing in all these words like contract, simple storage, is we're walking down the JSON here. So when we say we want to get the bytecode, in this compiled Solidity JSON, we want to go to contracts, simple storage, EVM, bytecode. So contracts, inside this contracts JSON, we got to go to simple storage. Inside this simple storage.sol, there's another simple storage. Inside that, there's an ABI, but that's not what we want. We want the EVM. So we're going to scroll down. Aha, we're going to get the EVM. Then what do we want? Then we want the bytecode. Great. And then we want the object. So this is the bytecode of our contract. It's the really low-level stuff that the Ethereum virtual machine, or the EVM, is going to understand. Now, we also need the ABI. When we deploy this to a chain, this is what we're going to need. We're going to need the bytecode and the ABI. The ABI we can, of course, get from this kind of same method here. So to get this, we can do ABI equals compiled sol, same thing, contracts, simple storage.sol, simple storage, and as you can see, we're right here, and then we can just grab this ABI object. ABI. And we can even do print ABI, we'll do Python, develop.py, and indeed, our ABI is printed here. Awesome. So now that we have our two main pieces to deploy this, now all we have to do is deploy it. But the question then becomes is, where are we going to deploy it to? Which blockchain are we going to deploy it to? In Remix, when we were first playing around, we were using a JavaScript VM, or a fake or a simulated environment. We absolutely could, and we absolutely will, learn to deploy this to a testnet, because that's going to be the same way that we're going to deploy it to a mainnet. But before we do that, we should learn how to deploy this on a simulated environment or something similar to that JavaScript VM, so it's much faster and easier to test things. And this is where Ganache is going to come to the rescue. Ganache is a simulated or a fake blockchain that we can actually use to deploy our smart contracts to and have it interact like it's a real blockchain. Ganache is going to allow us to spin up our own local blockchain. And it'll look something like this. Now, the user interface is really nice because it allows us to kind of do this one-click blockchain to create our own local blockchain. That means that this blockchain isn't connected to any other blockchain out there, but it'll act like a blockchain. But it'll be a lot faster than us having to interact with a testnet, and we control the entire blockchain because it's only one node. We're the only node. So Ganache, great way to test things quickly. Now, we're going to mainly be working with the user interface, but I'm also going to show you how to work with the Ganache command line. You can really use either one depending on what you want to do, but a lot of the tools actually have built-in Ganache command lines, so it's definitely really useful to learn that as well. So again, Ganache is going to be our simulated environment here. So what we're going to do, once we get into Ganache, we can just go ahead and hit Quick Start. This will automatically upload and get started with our own local fake blockchain. You can even see it gives us some accounts. This should look pretty familiar. It should look very MetaMask-y, right? We have an address here, and each one of these addresses has a private key. In your Ganache, you can go ahead and just click the key and hit Show Keys, and it'll show you the account address and the private key. But of course, these are for development purposes only. Each one of these accounts has a balance associated with it. We can see a mnemonic or your secret phrase. You can see blocks, transactions, and a whole lot of other really useful features here. And it even tells us how to connect to this blockchain. And these are the connecting features that we're going to want to use. Let's learn how to connect to this Ganache blockchain from this user interface first, and then we'll learn how to do the command line version. This is when we finally start working with web3.py. You can just do pip install web3. And now we can start working with web3.py. Right at the top, a little confusingly, we're going to do import web3 from web3. Whoops, and this should be from web3, import web3. Sorry about that. Now, to connect to this blockchain, we choose what's called an HTTP provider. If we look at this Ganache instance, we have this RPC server, which has this URL, HTTP 0.0.0.854. This is the URL that we're going to use to connect to this blockchain. In Remix, we're actually using our MetaMasks directly to connect to the blockchain. However, we want to connect directly to our simulated, our fake blockchain right here. So what we're going to do is we're going to do W3 for connecting to Ganache. W3 equals web3 web3.http provider of HTTP 0.0.0.0, and it was on port 845. Port 845. Now, with everything that we show you, you're probably going to want to get really familiar with the documentation, because even after being a pro, you're going to want to use it more and more. If you want to learn more about other providers, you can go to the providers page of the documentation. The next thing that we're always going to need as well is we're going to need the chain ID or the network ID. What is the ID of this blockchain? And for Ganache, it's 1337. It's supposed to be a funny leet reference. So we'll do chain ID equals 1337. Now, we're also going to need an address to deploy from. We can go ahead and grab one of these fake addresses in here to work with. Similar to how in Remix, when we were working with the JavaScript VM, we were given a bunch of fake addresses. We're doing the same thing, but with Ganache. And then we're also, of course, going to want a private key. We need the private key, of course, to sign our transactions. So we'll do private key equals this. Now, just note, whenever you import a private key in Python, you need to add an OX to the front. Python is always going to look for the hexadecimal version of the private key. Awesome. Now we have all the parameters that we need for interacting with and connecting to our Ganache local chain. It's time to finally deploy our simple storage.sol contract. Let's do it. So to create a contract that we're going to deploy with web3.py, we're going to do simple storage. We're going to call this variable w3.eth.contract. And we're going to give it ABI equals ABI and bytecode equals bytecode. Great. Does this mean we've deployed it? Well, no. This just means we have a contract down. So we can do print simple storage, and you'll see if we run python deploy.py, you'll see we have a new type here, class web3.utils.datatype.contract. This is another type that, if you want to learn more, you should definitely check out the web3.py documentation. So we have a contract object. Awesome. How do we actually deploy this? Well, we need to actually build our transaction. Because again, whenever we interact with the blockchain, whenever we make a state change, and in this case, we'd be deploying a contract, we're going to make a state change. So we first need to build a transaction, sign a transaction, and then send a transaction. And to do that, we need to talk about that nonce thing again. Remember way back in our blockchain demo, when we used a nonce to solve the answer to that really difficult mining problem? Well, the definition of nonce is just a word coined or used for just one occasion. And in cryptography, it's an arbitrary number that can be used just once in a cryptographic communication. So this nonce that's used to find the answer is going to be different from another nonce that we're actually going to need to make our transaction. See, if we look at our MetaMask and we look at our activity, and we look at one of the transactions we've made recently on Etherscan, if we scroll down, we'll see nonce here as well. This nonce is the number of transactions that our account has actually made. Every time we make another transaction, our transaction is hashed with a new nonce. This is what's going on behind the scenes with our transaction. And we need this to send our transaction. We can actually get our nonce by just grabbing our latest transaction count. Get the latest transaction. We can do nonce equals w3.eth.get transaction count. And we'll put in my address. This will give us the number of transactions, and it'll effectively give us our nonce. We can even test it out with a print. Python deploy.py. We can see that the answer is 0, because on our local blockchain, this address that we're using hasn't been used before. We can even go to the transactions tab, and we can see that there are no transactions that have ever occurred on our local blockchain. Now, to deploy this contract, we need to make a transaction. Remember, everything that we do, every time we change the state of a blockchain, we're going to do it in a transaction. Let's create a transaction object. To do this, we can do transaction equals symbol storage, which again is this contract object, dot constructor dot build transaction. Now, as you might have pointed out, our symbol storage.sol doesn't actually have a constructor. Every contract technically has a constructor. This one's is just blank. We're not telling our symbol storage.sol to do anything. We saw back in our fundme example that the fundme example does have a constructor. So now we want to put in some parameters for this transaction. In web3.py, we always have to give at least a couple of parameters. We always have to give the chain ID, which we already got from above, which is 1337. So we can just do chain ID. We need a from address, in this case, my address. And then we need a nonce, which in our case is just nonce. Great, now we have a transaction object. Let's even print this out and see what it looks like. Whoa, what's this? We can see there's even more parameters in here than just what we made. So we have value, which is the ether or the Ethereum that we're going to send. We have gas. We have our gas price, which we could arbitrarily set if we'd like. We have the chain ID. We have from address. We have the nonce. And then we have this giant data object. And then 2 is just empty because it's sending it to the blockchain. This giant data object here is encompassing everything that's happening in this simple storage.sol. Now, that's just a transaction, and anybody could actually send this transaction as long as it's signed by them. So we have this transaction, but we need to sign it from somebody. Since we're sending it from our address, our private key is going to be the only key that's going to work to sign this. Remember back when we were talking about public and private keys, we right now have a message that is defining how to deploy simple storage, but it's not signed yet. So we're going to need to use our private key to sign it to create this unique message signature that we're the only ones that can create the private key, but anybody else can verify that it was us who signed it. So now signed transaction equals web3.eth.account.sign transaction, and the parameters it takes are going to be transaction and then private key. We're going to say the private key equals private key, because above we've actually gone ahead and added our private key in here. Now guys, a really, really important note about putting your private key in your code. This is really bad practice. If you push this to source or you push this to GitHub, somebody else can see your private key and steal all your funds. So we don't want to hard code our private keys in our code like we're doing here. So let's take this time to talk about environment variables and how to set them. Environment variables are variables that you can set and that we set in our terminal and in our command lines. The following is a way to set an environment variable in macOS and Linux only. Don't worry, we'll show a way to make an environment variable in Windows as well. You can set an environment variable by running something like export private key equals, and then adding whatever variable that you want. Now, if you type echo $, private key, this variable actually shows up. To set environment variables with Windows, the process that we're going to do is actually a little bit different. I've left a link in our GitHub to actually set environment variables in a Windows setting. And we've left a couple of really helpful links for working more with environment variables. You should definitely check them out. It's important to note that this export method that we're doing here for creating environment variables only works for the duration that our shell is live. So if we were to close out of our shell and then reopen it, our environment variable that we set would be gone. So we'd have to rerun that export command. We're going to show you a way to set environment variables so that you don't have to keep doing that. Now, it's also not great to have it in plain text on your computer. However, it's a lot better than hard coding it into our script here. Now, remember, if you're using an account that has real money in it, which I highly recommend you do not do, don't send this environment variable or this private key or any of this code anywhere, because then people can steal all your funds. Once we move to Brownie, we'll show you a more effective way for private key management. But for now, be cautious here. But if you followed along and set up a brand new account that has no real money and only test that money in it, then great. Who cares? Because it's test and it's fake money anyways. I think I've talked about it enough. Anyways, let's get back to it. We can actually access this environment variable in Python using os.getEnv. We just need to import OS. And now we can access our private key in our script without actually hard coding it in. Let's see what happens if we do print private key, Python deploy.py. You can see our Python script was able to pull our private key from our environment variable. The other thing that we can do is create a .env file. A .env file is typically where people store environment variables. It's important to not push these to source if this is what you're going to do. In this .env file, in Python, we can just do export private key, and then same as what we did before, add the 0x at the start, and then private key. So we could put 100 environment variables in here. Export some other var equals 7. If you're going to do it in this way, please, please, please always set a .getignore and make sure .env is in here. This will help make it harder for you to accidentally push your .env folder or your .env file to GitHub. Python actually has a way of loading directly from a .env file without having to export our environment variables or run source.env or export or really anything. And we can do it with this python.env package. If we close our shell and then reopen it, if we run echo some other var, we're going to get none here. And in fact, if we run python develop.py, when we print this environment variable, we're going to get none. However, we can use this .env to have it pulled directly from our .env. So we just do pip install python.env. I've already downloaded it, so it just says requirement already satisfied. And then what we can do at the top of this, we can do from .env import load.env, and we can run a load.env function right at the top. This load.env looks for this .env file and automatically imports it into our script. So if we run this now, you'll see that the environment variable was successfully imported into our script. And now we can use it. So let's use it, for example, with our private key. Private key equals os.getEnv. Private key. Now we can even print it out just to test. We'll run our script, and awesome. We can see our private key is being successfully pulled in, and we didn't hard code it into our application. All right, let's get back down to our signed transaction here. Now let's go ahead, print this out, and take a look at what this looks like. Now we can run our script, and great. What we see here is an example of a signed transaction. Remember, this is exactly what's happening when we were looking back at public-private keys. We are signing a transaction that is actually deploying a contract to the blockchain that anybody can easily verify. All right, so we finally have our signed transaction. Now we want to send this to the blockchain so it actually can deploy. Let's send this signed transaction. We can do transaction hash equals web3.eth. Here's a little helpful tip. If you see this little box underneath with suggestions show up and you just hit tab, it'll auto-complete the rest of your text here. .send raw transaction, and we'll give it our signed transaction raw transaction. This will send our transaction to the blockchain. Now, if we look at our local ganache and we look at transactions right now, it'll be empty. But let's see what happens when we run this script. Okay, so we didn't print anything out, but if we go to our ganache, we can see that a transaction actually did go through. It was from the address that we put in here. We created a contract at this address. This is how much gas it used, and this is how much value was sent with it. We can even click on it to see more information about this. Now, this is the other advantage of doing this locally, is that the transaction automatically went through. We've sent our first transaction to a local blockchain, and this transaction is deploying a contract. Great work. You can already see how much faster this is than working with a testnet. One other thing that's really good practice whenever sending a transaction is we wait for some block confirmations to happen. So we can do transaction receipt equals web3.eth.wait for transaction receipt tx hash. This will have our code stop and wait for this transaction hash to go through. Awesome. So I just ran it again. And if we go to transactions, we can now see that there are 2 transactions here. and our code waited a little bit longer for this one to complete. So, of course, we've deployed a contract, but how do we actually interact and work with the contract? Let's start doing that. So, when working with contracts and we're working with on-chain, whenever we work with a contract, we always need two things. We need the contract address and the contract ABI. Oftentimes, if you're looking for a specific ABI of a type of contract, you can usually just Google it. So we need to make a new contract object to work with contracts. Let's go ahead and create this simple storage contract so that we can actually interact with it. So we'll do simple storage equals w3.eth.contract. Now we need our address, which we can get from Ganache, but that might be a little bit hard to always be checking the blockchain for a transaction. It's actually also in this transaction receipt. Address equals transaction receipt dot contract address. And then, since we've compiled this, we also have our ABI already. ABI equals ABI. Sometimes you'll see people have a file called abis.py or abis.json or something like that, and they'll load ABIs in directly from there. And great, now that we have the address and the ABI, we can start interacting with this contract exactly as we did in Remix. So let's do a print statement to get that initial value that is returned from our retrieve function. Remember, it should be initialized to 0. So if we do print simple storage dot functions dot retrieve, let's see what happens here. Huh? What's this? We get this function retrieve bound to in these parentheses here. So what's going on? When making transactions on the blockchain, there's actually two different ways that we can interact with them. We can interact with a call, or we can interact with a transact. When we use a call, this is just to simulate making the call and getting a return value. Calls don't make a state change to the blockchain. And it's similar to how in Remix, we would call these blue buttons and nothing on the blockchain would actually change. We can actually also call these orange buttons or these non-view functions and just not actually make a state change. Remix defaults these blue buttons to be calls and these orange buttons to be transacts. In Python, we can actually pick which one we want to do. A transact call is when we actually make a state change. And this is when we actually have to build a transaction and send a transaction. You can always just call a function no matter what that function is, but just keep in mind you won't make a state change. You can also always transact on a function even if it's just a view, and this will attempt to make a state change. Something like retrieve, even if we transact on it, it won't make a state change. So for something like retrieve, where we don't actually want to make a state change, we just use the call function. So we'll just do .call. Now, if we try to run this, you'll see we do get the 0 because now we're actually calling this transaction. Awesome. So now we have our initial value for our retrieve function. Let's keep going. Let's try to update this favorite number using this store function. This, we'll just keep in mind, is our initial value of favorite number. We know that this store function is orange and will actually make a transaction, but if we wanted to, we can even just use call on it. We'll do simple storage .functions .store. We'll put that 15 in here, .call. Let's see what happens when we send this. You can see it returned a blank. That's because this store function has no return type. If we give this returns uint256, and then we say return favorite number, and now we go back here, and we run this again, you'll see now that we get a 15 back. If we go to Ganache, you'll see that we keep making a whole bunch of different contracts, but none of these are contract interactions. That's because when we call a function, we just simulate working with it. If we call retrieve again right afterwards, you'll see that it's still 0. It's because calling is just a simulation. Now let's delete all that. So let's actually build a new transaction to actually store some value into this contract. Since we want to make a transaction, we got to go through the same process as when we deployed this contract. Let's first create a transaction. We'll call it store transaction equals simple storage dot functions dot store, and we'll give it some number, in this case 15, and then we have to do dot build transaction, and we'll put those same pieces in here from before. We're going to have chain ID be the chain ID. We're going to need from, going to be my address. Nonce is going to be the nonce plus 1. We're going to need to do nonce plus 1 because we actually used this nonce already when we create our initial transaction. Remember, a nonce can only be used once for each transaction. So this transaction is going to have a different nonce than the nonce we use to deploy the contract. Now that we have the transaction, let's go ahead and sign it. We'll do signed store tx, and we'll do web3.eth.account.sign transaction store transaction, and then private key equals private key, and we'll go ahead and save. Then, of course, we need to send it. So we'll do transaction hash equals w3.eth.send raw transaction signed store transaction dot raw transaction. And let's grab that transaction receipt again by doing transaction receipt equals w3.eth dot wait for transaction receipt, and actually let's call this send store tx. That wait for receipt, send store tx. Awesome. It looks like we're following the same steps here as we did above. We created the transaction, we signed the transaction, and then we send the transaction. Down here, we create a transaction, we sign the transaction, we sent the transaction, and then we waited for the transaction to finish. So let's run this. All right, great. We still have this print function printing out the current value of retrieve. Let's go over to Ganache and see if there's anything different here. There is. Instead of all these contract creations here, we now have a contract call. We can see there's some transaction data that was sent, a different amount of gas, same gas prices. However, this actually updated and sent the transaction to our blockchain. Now, if we call this retrieve function again, this should print out our newly updated value, which in this case was 15. Let's go ahead and run Python deploy.py, and we can see it started at 0 and then it turned to 15. Awesome. We've made our first state change to a contract that we've deployed on our local blockchain. Great work. Sometimes it's nice to put some lines in here to tell you what's going on, to make it a little bit more clear. So I'll put something like deploying contract, ... right before we deploy our contract. After we do it, I might do deployed. Then, right before we update our contract, we'll print out something like updating contract. And then, right after it's done, maybe something like updated. Now, if we run this now, you'll see as this goes along, we'll get these things printed out saying deploying contract, contract, deployed, updating contract, updated. This will make those moments when waiting for these contracts to actually finish a lot easier. You're doing fantastic. So Ganache user interface is really nice because we can see a lot of things that are going on here. However, it's a little tricky to do a lot of programmatic stuff. Oftentimes, engineer will use what's called a command line interface of Ganache instead of the UI. So we're going to go ahead and close this out, and we're going to use the Ganache CLI instead of that user interface that we just saw. And this is what Brownie is going to use on the back end when we move to Brownie. Let's learn how to actually do that. So in order to use the Ganache CLI or command line interface, the first thing that we need to do is download Node.js. Yes, I know this is a Python video. However, we do need to install Node.js to work with the Ganache CLI. You can come to this download page and choose your operating system and download it accordingly. We have a link to a video showing you how to do this in the GitHub. You'll know you've done it right if you can run node -- version in your command line and you get a version. It might be 12, might be 14, might be something else, depending on what version you downloaded. Next, we're actually going to install Yarn. Yarn is a package manager similar to pip and will allow us to actually download pieces and packages like the Ganache CLI from the package repository. We can install it with npm install -- global yarn. And you'll know you've done it right if you can run yarn -- version in your command line and you get the version outputted here. Then we want to install the actual Ganache CLI. We're going to be installing it with yarn. So to install this, we're going to do yarn global add Ganache CLI. This will install our Ganache CLI as a global command in our terminal. We can test to see if we've done it right. If we can run Ganache CLI -- version. Perfect. We now have the Ganache CLI. Let's spin up a Ganache chain with the CLI. If you have your Ganache UI open right now, please close it. Otherwise, it'll conflict. So to run a local blockchain from the command line, all you need to do is run Ganache CLI. And the node will start running directly in your terminal. If you scroll up, you can see a lot of familiar pieces. We see the available accounts, just like on the UI. These are the different addresses. And then we see a whole bunch of different private keys. This Ganache spins up with a bunch of random addresses and random private keys. If we wanted to always spin up with the exact same private keys so we don't have to update our private key every time, we can do Ganache CLI -- deterministic. This way, we'll always get the exact same private keys and the exact same addresses. You can check out the documentation to see a bunch of other flags that you can use to run this. And you can see it's listening on 127.0.0.1. 127.0.0.1 is also known as the loopback address or localhost. Now to work with Ganache in the command line, all we need to do now is update our private keys and our addresses. Let's also update the HTTP provider, since now we're going to be looking at the loopback address. For my address, we'll scroll up to this top address here, and we'll place it in. And for our private key, we're going to copy this and put it into our .env file. It already has the OX at the top here. Great, now let's open up a new terminal. You can open up a new terminal by hitting this plus button here. And you can flip back and forth by hitting this drop down and flipping back to the Ganache terminal. Now let's go ahead and run Python deploy.py. We can see the exact same output as we got when working with the UI. And if we flip over to the command line, we can see we've made a whole bunch of different calls to our blockchain. Each one of these calls is a specific JSON RPC call to our blockchain that we're making to interact with it. We can see information about the transactions that we sent. This one creates our simple storage contract. This one updates our simple storage contract. And great, you now know how to work with the Ganache CLI and the Ganache UI. Fantastic. So how do we actually deploy this to a testnet or a real network? When we were working with Remix, all we had to do was switch to injected Web3, and we used our MetaMask as our blockchain connection. Well, in our script here, we don't have MetaMask natively with our script. So we need some way to connect to the blockchain. We can see that when we're connecting to our own local blockchain, we just use an RPC URL that connects to our local blockchain. To connect to a testnet or to a mainnet, we can actually do the exact same thing. All we have to do is swap this out with the URL that connects us to a mainnet or a testnet. We can also run our own blockchain node, similar to how we're running our own local blockchain node. We can run a node that actually connects to a real blockchain. However, it's not always practical or really easy to do this. So sometimes we want to use an external or a third-party client that actually will run our blockchain for us. Let's learn a little about Infura. Infura.io is an application that will give you a blockchain URL for you to connect with, for you to run whatever you want to run. And you can get started for free. Let's go ahead and register. Then we just check our email, confirm email address, and awesome. Now we're inside of Infura. There's a couple other services out there that you can also check out, like Alchemy, which is another fantastic blockchain as a service platform. Infura is a freemium service. It starts out as free. If you make too many API calls or too many calls to the URL, they'll start charging you. But we can create a project for free for now. Let's go ahead, hit the Ethereum tab, hit Create Project. We'll call this Free Code Camp Brownie. Hit Create. Now we'll have a whole bunch of project keys and project secrets. We also have this endpoint section as well. This is how we're going to be deploying to the different networks. We can see we have an Ethereum mainnet connection, as well as Ropsten, Kovan, Rinkeby, and Gorilli testnets. There's also Polygon in here as well. Since we want to test and deploy to a Rinkeby chain, we can go ahead and move to Rinkeby. And then we can copy this URL. Back in our application, all we have to do is swap this out for the new URL. We also have to change the chain ID, our address, and the private key. If you ever are confused as to what is the chain ID of the chain that you're working on, you can always check this chainid.network, or you can usually ask somebody. Let's look up Rinkeby. We see the chain ID is 4. So we'll grab 4 and we'll place that in our script. Now, this address and the private key that we gave it, aren't going to have any testnet Rinkeby in them. So we need to go in our MetaMask and grab the address, place that in for address, and then account details, export private key, type in our password, and grab the private key. Go into our .env file, leave the 0x, and replace the rest with our private key. Since I have my private key stored as an environment variable, I need to then run source.env so that my private key is now updated. The reason we're using this is because, again, since we're making transactions to a testnet, we need some testnet ETH. All right, so now we have everything updated for deploying to Rinkeby. Let's go ahead and run this now. As you can see, it's going a lot slower. This is because we actually have to wait for the contracts to get mined and for everything to happen on the testnet. Deploying to a testnet will result in nearly the exact same experience that you'll get when deploying to an actual mainnet. So it'll take a lot longer, but you can see we got the exact same responses here. Now, if we take this address and we go to the Rinkeby Etherscan, we can verify what just happened. We can see that 38 seconds ago, we made this transaction, and then 23 seconds ago, we made this transaction. We can look at all the different details of this transaction that we just made from our Python script. We can see it even tells us we created a smart contract, and then we made this call, which called this store function on this contract. Whew, we've learned a lot so far. This is fantastic. Now is a perfect time to take a break and take a quick breather and reflect back on what we've just learned. We've learned a lot about Python, deploying to our own local blockchain, deploying to a testnet, and deploying to a mainnet, working more with private keys, creating transactions, signing transactions, and then sending transactions. Now, as you can see, there's going to be a lot to actually managing all the contracts that we work with. Having to write our own compile code, our own storage code is going to take a lot of work. And what if we wanted to interact with one of the contracts that we deployed in the past? Well, we'd have to keep track of all those addresses and manually update our address features here with an address. Maybe we didn't want to deploy a new contract every single time. Maybe we wanted to work with a contract that we've already deployed. What if we want to work with a whole bunch of different chains? What if we want to work with Rinkeby and mainnet and our own local network? There seems to be a lot to manage here, and we still haven't even talked about writing tests. This is where Brownie is going to come into play. Brownie is currently the most popular smart contract development platform built based on Python. It's used by DeFi giants like Yearn.finance, Curve.fi, and BadgerDAO, each having billions of dollars currently locked in value. And the reason that we learned a little bit about Web3.py first is because Brownie heavily relies on Web3.py. So let's do all this again, but in Brownie, and we'll see how much easier it is to actually interact with. In our shell, let's go back one directory And let's make a new one. We'll call it Brownie Simple Storage. Now, another really cool trick that VS Code has is instead of us having to go to File and open up this folder in this Explorer here, what we can do is we can type code and then type the directory that we want to work with. In our case, this directory. So we can just type code dot. And we'll get a new VS Code pop-up inside of this Brownie Simple Storage folder. Let's get learning about Brownie, and this is where you're going to spend the majority of your time moving forward. Brownie is incredibly powerful and makes our lives fantastically easier. So get ready to learn one of the most powerful tools in the smart contract developing ecosystem. Let's go ahead and open up our terminal, and let's get started installing Brownie. It's recommended to install Brownie via pipx. Pipx installs Brownie into a virtual environment and makes it available directly from the command line. Once installed, you'll never have to activate a virtual environment prior to using Brownie, which is really good. To install it with pipx, we can go ahead and run python -m pip install --user pipx. Once we've run that, we can then run python 3-m pipx ensure path. Then we'll want to close the terminal by hitting the little trash can and then reopen it. And then we just need to run pipx install brownie. I've already got it installed, so that's why we see this here. And then just one more time, we're going to close and reopen the terminal. You can tell you have Brownie installed correctly if you run brownie --version. And you get some output that looks something like this. Or you just run straight up Brownie, and it'll output a bunch of commands that we can run. Let's create our first Brownie project. We're going to be using the exact same simple storage code that we just went through, except for we're going to use it in Brownie. This is going to make our lives a lot easier when working with simple storage. To create a sample folder with everything we need with Brownie, we can just run Brownie init, and we will get a new Brownie project initialized in the directory that we're currently in. If you type ls, you'll be able to see all the folders that are created, or you can just see them on your side panel in VS Code. Let's talk really quickly about what each of these folders is going to do. The build folder tracks a lot of really important low-level information. It's going to track any interfaces that we're working with or deploying. It's going to keep track of all of our deployments across all of the different chains, so we no longer have to manage that ourselves. And it's going to store all of the compiled code. Remember how in our simple storage code, we actually saved everything to this compiled code.json? Well, Brownie is actually going to do all of that for us into this contracts directory, so we can always reference it later. This contracts directory outside the build folder is where we're going to put all of our contracts. Brownie knows to look inside of this folder when looking for new contracts to compile, deploy, or anything else. Interfaces is where we can save and store different interfaces. Remember how when we were working with Chainlink, working with interfaces makes it really easy to interact with a blockchain application. Reports are to save any type of report you run. Scripts are we can automate tasks like deploying, calling different functions, or really anything we want. And then we have a test folder, which is incredibly powerful and we're going to be using a lot. We also have git attributes and git ignore, which are helpful when working with version control like Git. So let's go ahead and start working with Brownie and really understand what's going on here. So let's go ahead and add our simple storage contracts to the contracts folder. So in here, we're just going to make a new file. We'll call it simple storage.sol. And I'm just going to copy and paste the code I have from the simple storage that we've been using this whole time. Let's go ahead and save that with Command S. Okay, great. Now that we have our contract in here, we can already start working with Brownie and even compile this code without even having to write or work with our own compiler. All we need to do is run Brownie compile. Brownie will automatically read the version of Solidity and then store all of the compile information in this build folder. So if we go to contracts, we can see we have a simple storage.json, and there's a lot of familiar pieces in here. For example, we see the ABI, opcode section, which is the low level language. We'll see a PC map and we'll see a lot of useful information. And great, obviously deployments and interfaces are still empty. So great, we've already compiled our smart contract. So how do we actually deploy this to a blockchain? To do this, we do have to write a script, which will allow us to do whatever we want. So we're gonna create a new file, and we're just gonna call this, similar to last time, deploy.py. This is where we're gonna define working with and deploying our code. Brownie can run scripts by running Brownie run. In fact, if you want to take a quick minute to familiarize yourself with all the different commands that Brownie has, just run Brownie and you'll see we can do a lot of different things. We can do Brownie init, which will create a new Brownie project. We will do Brownie bake, which allows us to pull from the Brownie mix, which we'll talk about later. We can compile, we can go into a console, test run, we can do a lot of wonderful things in here. If we do Brownie run, it'll run a script for us, and we can define that we want to run this deploy. All we have to do is add a def main. So def in Python is the way to define a function. We're gonna call this function main. And for now, let's just say print hello, and we can run Brownie run scripts deploy. And as you can see, it automatically does this launching thing. So Brownie defaults to always working with a local Ganache CLI blockchain. It's running the exact same command that we ran earlier, and it has a bunch of different flags, like accounts 10, a certain hard fork, a certain gas limit, etc. So at the beginning of all of our scripts, if we don't give Brownie a network to use, it'll spin up a local Ganache, and at the end of the script, it'll tear it back down. Typically, what I like to do is actually put all of the logic of our deployment in its own function. Def, deploy, simple storage, and we'll do pass for now. And then our main function, we can just call deploy simple storage. Now, in order to deploy our contract, let's look back at our Web3 Pi version of deploying this and see what we did. So first, we compiled it. Great, Brownie does that automatically. Then we dumped it to a file. Great, Brownie does that automatically. We got a bytecode and an ABI. Great, Brownie does that automatically. We added a local blockchain to use. Great, Brownie automatically spins up a local Ganache. We'll learn how to do testnets in a little bit. Aha, we do need an address though and a private key. So how do we actually get our private key, get our account into Brownie? Brownie has an accounts package that actually natively understands how to work with accounts, and we can import it into our script here. So we can do from Brownie import accounts. And with this accounts keyword, we can add an account a number of different ways. If we're gonna work with our local chain, as you see here, the Ganache CLI will spin up 10 fake accounts for us. And Brownie automatically knows that we can work with that account. So we could do something like account equals account 0, and then just do something like print account. So we're gonna take the account that's spun up at the 0th index, because this accounts object is just an array. So if we run this now, Brownie run scripts, deploy, it's gonna spin up us an address and a private key that we can just work with without having to define a private key or do anything. It does all of that for us, which is fantastic. We do, of course, still want to know how to add our own private keys so that we can work with a testnet. So this is great and works when we're working with a development network or working with Brownie's automatic Ganache CLI. If we want to work with a testnet though, we have to do something else. Another way to add your accounts in Brownie is to use the command line and actually add them natively into Brownie. We can do Brownie accounts new, and we'll give it a name, free code camp account. This will then prompt us and say, enter the private key that you wish to add. Let's go ahead and grab our private key from MetaMask, account details, export private key, put your password in, grab the private key, and then we just add OX and paste it in. Brownie will actually password encrypt your private key in this way. So we'll give it a password. And now we have a new account natively integrated into Brownie. To see it, we can do Brownie accounts list, and you'll see that we have a free code camp account with this address and also a testing account. I made this a little bit earlier. We can get rid of it by running Brownie accounts delete testing. Helpful terminal tip time. So if you hit up or down on your keyboard, you can actually toggle through the history of the commands that you've written. So if you hit up, it'll actually bring you to the most recently run command, which can allow you to run previous commands a little bit faster. And if we run Brownie accounts list again, we'll see it's now just free code camp. If we want to work with this free code camp account that we've added to Brownie via the command line, we can get it with account equals accounts.load free code camp account. And then we can do print account. Let's run this script again. This time when we run the script, it's going to ask us for the password. We need to enter the password to decrypt the account because right now it's password encrypted. So we're going to type in the password and it's going to go ahead and execute with our unlocked private key. We can see the address it printed out was right here. And if we copy the address and we go back, we can see that that is correct. Now, if we're going to talk about safety and you want to safely secure your keys, this is one of the safer ways to do it because it's not going to store it in Git. You're not going to accidentally push it up to GitHub or show it to anybody, and it's going to be password encrypted. This is going to be one of the ways that I highly recommend you store your keys. Oftentimes, you're going to want to do a mix of working with the local Ganache ones and your own keys, and we'll learn how to flip back and forth between them in a little bit. Now, the third way that I like to use is still, again, using an environment variable script. Oftentimes, it's really easy just to have your private key be an environment variable. This way, you won't have to keep putting the password in every single time you run a script. So it's a little bit less secure. And just another tip for myself, I never put my private keys associated with wallets that have real money in them as environment variables or in a .env file, just in case I accidentally do something really stupid. I don't trust myself enough. So I'm going to highly recommend that whatever private key that you use and you store as an environment variable here, always have it be just kind of a test account that you're going to use to test things. And then for some of your more serious accounts, that's what you'll use the encryption for. So let's go ahead and create an environment variable file. So we'll do a new file, call it .env, and we'll do export private key OX this. Now we have a private key set as an environment variable. So Brownie has an additional feature that allows us to easily work with environment variables in an environment variable folder. We can tell Brownie to always pull from our .env file in a Brownie config.yaml. This is a special file that Brownie always looks for to grab information about where you're going to build, where you're going to deploy, and where you're going to grab things. In this config, all we need to do is add .env and set.env. This is telling Brownie, hey, when you run scripts, grab the environment variables from the .env file. And what we can do is after we import OS, we'll do account equals accounts.add os.getEnv. This is how we get that environment variable private key. Then let's just print out that account and see if we did it right. Brownie, run scripts, deploy.py, and great. All right, great. So this seems to work perfectly, but I like to make this method even more explicit. So we're going to take this version that we just learned and improve it. In our Brownie config, we can actually add more information about what wallets we want to use and when we want to use them. What we can do is we can add a wallets section and add in here a from key section and then add that environment variable, private key. In your YAML file, if you surround a string with $ and some curly brackets, it will automatically get transformed into the environment variable. So if we go back to deploy, we can actually change this. We can grab right from our config file. So we'll do from Brownie import accounts, config, and instead of using OS, we can do accounts.add config, and then we'll do wallets, since that's what we're defining right here, and then from key, wallets, from key. And this will do the exact same thing as our os.getEnv. The reason that this is better is because now we have one canonical place where we're always going to pull our private key from, instead of having to go through all of our scripts and update it based on whatever we change an environment variable. Now let's try this out. Brownie, run, scripts, deploy. And great, we see our address printed here. For now, let's just stick with using accounts 0, since we want to just use the account that Brownie makes for us with Ganache. Now, Brownie is really intelligent, and we can actually go ahead and import a contract directly into our script. In a web3.py version, we opened a contract and read from it, and that's how we were able to interact with it after we deployed it. In Brownie, what we can do is from Brownie, import, and then just the name of the contract. Simple storage. Then we can do simple storage.deploy. And this is how we're going to deploy it to a chain. Anytime you deploy to a chain or you make a transaction, you always need to do a from. And then say who you're going to be deploying from. What's the account that's going to be deploying this? As you can see, this step of just deploying is much quicker than what we did in web3.py. In web3.py, we had to get the bytecode and the ABI, then we had to get the nonce, we had to create the contract, we had to create the transaction, sign the transaction, and then send the transaction. Remember how I said before, you could either make a transaction or a call? Brownie is smart enough to know whether or not what you're doing is going to be a transaction or a call. In this case, since we're deploying a smart contract, Brownie's smart enough to know that, we want to make a state change, so let's make a state change. It'll return a contract object. So we can just add print simple storage, and we'll see what prints. So let's run this. Brownie run scripts deploy.py. Awesome. So what happened was Brownie, again, per usual, it launched a local Ganache chain, and then it sent a transaction to deploy simple storage. And it says simple storage deployed at, and then the address it was deployed at. And we can see how much quicker this is to actually deploy. Now let's go ahead and do exactly what we did with web3.py. Let's call this initial retrieve function, and then we'll update it with a new value of 15. But we'll do it in Brownie now. Remember, here's how we did it back in web3.py. In Brownie, what we're going to do is first, we're going to do stored value equals simple storage dot retrieve. Now, since this is a view function, we don't have to add from account in here. Again, Brownie is intelligent enough to know if this is a call or a transaction. And we know that retrieve is a view function, so we know we don't actually have to make a transaction here. Then we can print out the value of stored value. Print stored value. Let's go ahead and try this. Great, we get 0 right here. Perfect. Now let's try updating this. So we can do transaction equals simple storage dot store. And in here, we'd want to do 15. But remember, since we're doing a transaction, in Brownie, we always have to add who we're going to transact from. In this case, we're going to do from account. Similar to web3.py, we can do transaction.wait for how many blocks we want to wait. And then let's call that retrieve function again to see if it's been updated. So we can do updated stored value equals simple storage dot retrieve. And then we can print the updated stored value. And if we run this, we now see we have two transactions here. One that deployed our original simple storage contract, and we called the retrieve function and we returned 0 here. Then we updated with our store function, and then we call retrieve again, and we see we did indeed update it to 15. You see how much smaller and easier and more intuitive this is in Brownie, and how much our lives are going to be much better. Awesome. Now you've learned how to deploy to a local chain. Now running these scripts is fantastic, but we need a way to actually automate that our contracts are doing what we want them to do. We don't want to always have to manually check that all of our stuff is doing what we want it to do, right? We don't want to have to manually check that 15 is actually updating appropriately. This is why running tests are so important, and automating your tests is going to be crucial to becoming a successful smart contract developer. Now, I do want to point out that you actually can write tests directly in Solidity. And this is a great way to actually test your smart contracts, is to learn how to do it right in Solidity. However, a lot of the professional developers code their tests in the smart contract development framework language, like Python or JavaScript. Doing it in this way allows you to get a lot more flexibility and customization with what you're doing with your smart contracts, and not being confined to whatever only Solidity has. So let's go ahead and learn how to actually write our smart contract tests in Python. This is what this test folder is for. So we're going to create a new file called test simple storage.py. Make sure you do add test to the front of these, because this is the syntax that PyTest is going to be looking for. And then in our test, we can actually set it up the exact same way we set up our deploy function. We can do from Brownie import simple storage and accounts. Then we can start defining our tests. We want to test to see that when we deploy our smart contract, that it gets started off with 0 in that retrieve function. So we'll create our first test. We'll do def test deploy. And typically, testing in smart contracts, or testing really in anything, is going to be separated into 3 categories: arranging, acting, and asserting. We're going to bounce around and be a little bit loose with this definition for the duration of our tutorials here. However, keep in mind that typically this is the setup that you want to use. Later on, in one of our later smart contract examples, we're going to go through a much better testing setup. So in our arrange stage, we're going to set up all the pieces that we need to get set up. So first, we're going to grab an account. We're going to say accounts equals account 0. And this is really all we need to do to start getting set up. Now, for our acting stage, we're going to deploy a simple storage contract, exactly as we did with deploy. So we're going to do simple storage equals simple storage dot deploy from account. Then we're going to get our starting value. Starting value is going to be equal to simple storage dot retrieve. And we're expecting this to be 0. So then all we have to do in our assert stage is we have to run assert starting value equals expected. So let's recap this. In our arrange stage, we're just getting our account so that we can actually make contracts. Then in our act stage, we're going to deploy this simple storage smart contract. We're going to call the retrieve function to see what its starting value is. And we're going to compare to see if that starting value is what we expect. And we expect it to be 0. We can then test this with Brownie test. And per usual, Brownie is going to kick off a Ganache CLI, and then it's going to test this. For every test you have, you're going to get a little green dot. And we're going to say 1 pass in 1.86 seconds, which is perfect. If we had expected to be 15 and we ran Brownie test, we should get a fail here. Awesome, and that's exactly what we got. Now let's go ahead and test updating this with 15 and see if it works as we want it to. So we can do a new test in here. We'll do def test update storage. And we'll do those 3 phases: arrange, act, and assert. In our arrange, all we need to do is get our account from account 0. And in this one, arranging is also going to be deploying our smart contract. Since this is really just part of the setup and not the act that we're really testing. Now in our act, we're going to add expected to be equal to 15, and we're going to run simple storage dot store expected and then from account. You'll notice this is nearly exactly the same as this deploy function here. Now, same as last time, all we have to do is assert expected equals simple storage dot retrieve. We're saying we want to store 15 in our smart contract, and then when we call our retrieve function, it is stored correctly. So let's go ahead and run Brownie test. Awesome, we can see 2 dots here. This means 2 have actually passed correctly. That's great. Now I do want to quickly show you a couple of useful tips that I pretty much always do when I'm running my tests. If you want to test just one function, you can do -k. Brownie test -k, test updating storage, and we will only test this test updating storage. We can run Brownie test -pdb and add something wrong in here, like 5 equals simple storage.retrieve. And what will happen is once this kicks out and is wrong, we'll actually get put into a Python shell. And now we can check to see some variables in here. Like if I see what expected is 15. If I try to run simple storage.retrieve, expected is 15. If I run simple storage, I'll see this is the simple storage contract. PDB is a really useful way to mess around and see, okay, well, what did I really go wrong? Why is my test failing? Another important flag is going to be -s. So you'll notice that no print lines actually get sent out when you're working with these tests. If you do -s, it'll be a little bit more robust in telling you exactly what's going on. And if we had any print lines, it would print the lines out as well. Everything that you can do with Brownie test actually comes directly from PyTest. So if there's some flag you want to use or some awesome debugger you want to use, you can use it with Brownie just by looking at the PyTest documentation. All the tools are exactly the same. All right, we're coming along fantastically. We have a script to deploy. We have some tests. We have our contract. This is great, but now we actually want to deploy to a testnet. How are we going to do this? Let's look at back how we did it with web3.py. Back in web3.py, to deploy this to a testnet, we just needed to add our HTTP web3 provider, which was our Infura account, and that was pretty much it, and add our address and our private key. In Brownie, our lives are even easier. Brownie comes prepackaged with a list of networks that it's already compatible with. You can see all of the networks by running Brownie networks list. Now, mine has a couple more actually because I've been playing around with this for a long time. But if you want to see all the different networks, you can look at this list here. Something important to note is that there's a difference between the development networks and the Ethereum networks. Whenever we deploy to a network, we default to this development network. Any network that you see under this development section is going to be a network that is temporary. These are networks such as the temporary ganache network that Brownie automatically spins up when we run any of the scripts we've written so far. So this is really important to note. Remember, anything in this development section is going to get torn down after it's deployed. However, the Ethereum ones are going to be our persistent networks. Anything under this Ethereum tab, Brownie is actually going to keep track of our deployments and keep track of everything in there. These networks under here represent persistent networks like mainnet, Rinkeby, Coven, etc. Now in our web3.py, we used an RPC URL or an HTTP provider from Infura to connect to a testnet. We're going to use that exact same methodology here. So how do we actually get this RPC URL, this blockchain URL into our Brownie smart contract package? Well, one of the easiest ways is with an environment variable. So Brownie actually already knows that Infura is the thing and can look natively right away for Infura. Web3 Infura project ID and use our project ID from Infura. If we go to our project back in Infura and we go to settings, you'll see the project ID is a little bit different than the whole URL. It's just going to be this ID right here. We can then copy this and paste this right into our .env. Now that we have our Web3 Infura project ID directly in our project, if we do Brownie networks list, any network that Infura has access to, you'll see a little Infura in colons here. These are networks that Brownie will automatically know about if we're working with Infura. So we can see here that Rinkeby is one of these Infura keys. If we wanted to deploy to Rinkeby, we could then just run Brownie run scripts deploy.py and then select the network with -- network Rinkeby. Now we're going to get an issue here because remember, account 0 only works when Brownie works with a ganache CLI. We have to use our actual private key here. And that's where some of those other versions of working with private keys is going to come into play. Sometimes I'll even add a get account function. So down here, we'll do def get account. And then in here, I'll just natively check. If we're working on a development chain, we'll use account 0. And if not, we'll use the method that pulls from our config. So we can check by saying if network.showActive equals development, then return accounts 0. Network is another keyword that Brownie actually has. This network keyword allows us to interact with different networks. Now, if it's not on the development network, we're going to pull directly from our config. So we'll return accounts.add config wallets from key. And instead of doing account equals account 0, we can just do account equals get account. Now if we run Brownie run scripts deploy.py network Rinkeby, it should pull directly from our config file. And great, we can actually see transactions being sent directly on the Rinkeby chain. If we pull up Etherscan, the Rinkeby Etherscan, and we take this transaction hash and post it into the Rinkeby Etherscan, we can see this transaction actually going through. We've deployed our simple storage contract and it's initialized to 0. Then we're going to go ahead and update it, and it gets updated to 15. Now, once we've deployed to a blockchain, you'll see our build contract will actually change. Our deployments folder will have a new deployment. Every time you deploy to a blockchain, Brownie will actually save that deployment so you can always go back and say, where did I deploy that, or what happened with that deployment? You'll notice that it's separated by chain ID. Remember, the chain ID of Rinkeby is 4. You'll also notice that none of our development deployments are in here. Again, anything that's in this development section isn't going to get saved to the deployments area. However, anything up here and these ones will get saved. And that's going to be really powerful because we can actually interact with contracts we've already deployed onto a chain. So let's go ahead and even add a new file in here called read value. This function is going to read directly from the Rinkeby blockchain, and it's going to read from a contract that we've already deployed. Remember, we did something similar in web3.py by using the address and the ABI. We're going to do the exact same thing, but in Brownie. So in Brownie, again, we're going to do from Brownie, import, simple storage, accounts, and config. We'll do def, read contract, and we'll just do pass for now. And then we'll do def main is going to be read contract. Whoops, didn't mean to do that down here. And if we run, Brownie runs scripts, read value.py, network Rinkeby, obviously right now, nothing's going to happen. So how do we actually interact with this simple storage contract that we've already deployed? Well, this simple storage object is actually just an array. If we were to print simple storage, let's see what we get. See, we get this brownie.network.contract.contract container object at here. This object works the same as an array, and we can access the different indexes inside of it. So what if we do print simple storage at position 0? You'll see we get this address here. And if we check on Etherscan, we can see that this is indeed the contract that we just deployed. Brownie knows that we just deployed it because, again, in our build section in the deployments on the Rinkeby chain, which has the chain ID of 4, we have this contract that we've deployed. Now we can actually just directly interact with this contract. We can do simple storage equals simple storage of 0. Or if you're always looking to get the most recent deployment, -1 is a little bit easier. If we always do 0, we're just going to get the first deployment that we made. And if we make deployments later, we're never going to get past it. I want to always work with the most recent deployment, so I can just do -1. Remember how I said, whenever we work with a smart contract, we need to know its ABI and its address. Well, Brownie already knows what the address of this contract is. It's got it saved in this deployments folder. It also knows what the ABI is, because when we compile it, we get this big JSON file, and one of the first inputs that it has is the ABI. So Brownie automatically knows what the ABI is and what the address is already. So then we can just go ahead and run simple storage .retrieve and print it out, and we should see 15 since we already updated it. Brownie runs scripts, read value.py -- network Rinkeby. And great, we do indeed see 15. Now that we know how to write some scripts and actually deploy things with Brownie and work with Brownie, I'm going to show you one of the most powerful features to also work with Brownie. Typically, we write our scripts when we want something to be reproducible, and we want to do something over and over again. Deploying a simple storage or reading a value is something that we're probably going to want to do over and over again. However, maybe we want to work with some of these contracts a little bit ad hoc and get into a shell where we can actually interact with these contracts. This is where the Brownie console is actually going to come into play and make our lives a lot easier. So what we can do is we're going to Brownie console, and what will happen is Brownie will actually kick us off into a console. It has all of our contracts and everything already imported. So if I run simple storage, it gives me back an array. It's saying, great, that's your simple storage contract. Since we're working on a brand new local test environment, there are no simple storage contracts deployed. So what I can do is I can say account equals account 0. And we now have our account that we can work with. Accounts is one of these keywords that's automatically imported into our Brownie console. Everything that is imported via Brownie in our script is automatically already imported into this little shell here. So with that being said, we can go ahead and even deploy our simple storage contract. So we can literally take this line, copy it, paste it in here, and you'll see exactly the same thing that happens as if we ran our script. We get a little transaction hash here, and we get a simple storage. Now, if I type simple storage, the simple storage variable now has a storage contract here. If I type simple storage, you'll see I now have a contract in here. The length, a simple storage, is now 1 because I've deployed one simple storage contract. If I were to deploy it again, the length is now 2. Brownie now knows I'm holding on to 2 simple storage contracts, and I've deployed 2 simple storage contracts. I can then even do things like simple storage.retrieve. We can see we start with 0. I can go ahead and even run simple storage.store 15 from account, and we'll see we'll get a transaction. Now if I rerun simple storage.retrieve, a nice little hack here is in these shells, if you just hit the up key, you'll actually be able to go back in the history of the shell. So if I just hit up twice here, I can go back to this command, and I hit enter. Now we see the 15 is here. So the Brownie console is a great way to interact with these scripts in a more ad hoc manner. Maybe we want to test some weird functionality, or maybe we have some experiment that we want to try. It's a great way to really interact with anything that we have in Brownie. And the other thing is we can do everything that we normally do in Python in here. So for example, I could write print hello, and it'll print out hello. I could do cat equals 1 plus 2, and I type cat, and I get 3. So this Brownie shell is a Python shell with all of our smart contract features already natively integrated, and it's incredibly powerful here. We can go ahead and quit it by doing quit. So I know we've learned a lot so far. I'm sure you're starting to see why working with Brownie is so much easier and makes our lives as smart contract developers a lot easier for testing them, deploying them, and working with them. All right, let's move on to our next project. We're going to take the FundMe contract that we made recently in Remix and actually import that one into Brownie. With this, we're going to go over a lot more of the advanced features that Brownie has to offer us. And we're going to get into some more sophisticated testing and deployment mechanisms for this. So I'm going to make a new directory, Brownie, FundMe. We're going to cd into Brownie FundMe. And remember, if you hit tab, it'll autocomplete. And we're going to open this up in a folder. Again, if code period doesn't work, you can always go up to File, Open Folder, and do it like that. We're in our Brownie FundMe project, and we're going to initialize a new project by running Brownie init. And we're going to create a new contract called fundme.sol. And this is going to be exactly what we had before for our FundMe contract. So if you have Remix up, great, you can go ahead and grab it, or you can check the GitHub repository associated with this course and just copy paste the code. Now, typically, this is where in our last project, we just ran Brownie compile. But what happens if we run Brownie compile here? Brownie is going to give us this error. It's going to say, hey, this source wasn't found. So what's going on here? Well, Remix understands that at Chainlinks/contracts is an NPM package that it can import from. However, Brownie isn't aware of NPM packages, and Brownie can't actually download directly from NPM. However, Brownie can download directly from GitHub. So we have to tell Brownie where it should be downloading these third-party packages from so that we can use them in our contracts here. And while I'm in here, I might as well change the global compiler version to 0.6.6. And we'll just change the compiler version to caret 0.6.6 so that our linter is happy. So we need to tell Brownie where to import these contracts from GitHub instead of from NPM. Luckily, there is a package out there specifically created for downloading Chainlink contracts. The way that we can tell Brownie where to get these from is in our Brownie config. So let's create our Brownie config, And in here, we're going to create a dependencies section. And this is where we tell Brownie the organization / repo name at version that we want to download from. So to get these Chainlink contracts, we can look up Chainlink Brownie contracts, and we can use this repository to get it. So instead of downloading from npm, we're just going to download directly from this GitHub repo. So we need to tell Brownie the organization, which is going to be Smart Contract Kit, the repository name, which is going to be Chainlink Brownie contracts, and then the version. You don't always have to use the latest version here. And in fact, we can go to the past 9 versions by clicking on the version history. We're actually going to be using 1.1.1. And yes, it does look like the latest version went backwards, but as of a recent release, as a 1.2.0 version of this package, all the releases of Chainlink Brownie contracts is going to match exactly the @Chainlink contracts npm tag. So that's why it looks like this is an earlier version. So we'll say 1.1.1. So great. So now Brownie knows to download this repository from GitHub. Once we do that, everything in this contract section will be available for our Solidity code to import and use. However, that's not the final story here. We also need to tell Brownie what this @Chainlink thing means, because we're downloading from Smart Contract Kit / Chainlink Brownie contracts. Brownie's going, okay, cool. Well, what's this @Chainlink thing? So we need to tell Brownie whenever we're using @Chainlink, we're actually referring to this import. So we need to tell the compiler this. So let's add a new section. We'll say compiler. When it compiles Sulk, we need to remap @Chainlink. We need to say whenever you see @Chainlink here, it means we're referring to this package. So compiler Sulk remappings @Chainlink is equal to this package up here. Now, let's go ahead and try to compile. Perfect. We see here that it compiles successfully. And if we look in our build folder in the contract section, we now have this new folder called dependencies. And if we even expand this a little bit, we can see it says dependencies, Smart Contract Kit, Chainlink Brownie contracts at 1.1.1. And this is what it downloaded from that GitHub repository. It downloaded Aggregator v3 interface and Smart Math Chainlink because we're using both of those files in our Solidity code. All right, great. So let's write our first script to deploy this to a development ganache chain, to Brownie's built-in chain. Let's do this. So in scripts, let's go ahead. We'll create a new file. Let's go ahead and build a simple deploy script to work with Rinkeby, and then we'll actually learn how to deploy this to our own local ganache development chain. So let's build our deploy script. So in scripts, we'll do new file, deploy.py, and we'll start by doing def deploy fundme. Then we'll do pass for now. And then we'll do our entry point of def main, and then we'll call deploy fundme. In this file, of course, we're going to do from Brownie import fundme so we can actually use this. And let's go ahead and build this deploy fundme function. So first, we're going to need to get an account. And same as last time, we used a function called getAccount, which would know to switch back and forth between if we were on development or if we were with an actual testnet that we could pull from our config. We can actually, once again, copy that function and use that in our script here. So once again, we can use that getAccount function that we had before. What I like to do with this getAccount is add it into its own file called helpful scripts. So what I'll do is create a new file called helpful scripts.py. And in here, I'll add that getAccount function, right? So literally just pasted it from our last project. And just a quick recap on what this is doing is we're saying if the network is in development, we're going to use the accounts 0 syntax. Otherwise, we're going to pull from our config. And of course, we're going to have to from Brownie import network, config, and accounts. And then of course, in our Brownie config, we're going to have to add wallets and from key. So let's go to our config. We'll do wallets from key. And we'll add our private key environment variable setup, which of course means that we're going to have to set .env to .env, and we're going to have to create a new file, .env, and we'll paste the exact same values from our last .env. So it's going to be our private key and our project ID. Kind of just a lot of the basics of the setup here. But now that we've added this get account to its own script, how do we actually use that in our deploy script? Depending on the version of Python that you're in, you might actually have to create a new file first, named __init__.py. You might not, but just in case, let's make it here because it doesn't hurt. And with this, now Python knows that it can import from other scripts and other packages in this project. So now we can do from scripts.helpfulscripts import get account. So we're importing that get account function from our helpful script here. And we're going to make this get account function a little bit more robust a little bit later, but for now, it'll work perfectly for what we're looking to do. Now we can just run our typical deploy function. We'll do the fundme contract equals fundme.deploy. And of course, we'll do from account. Because again, since this deploy is going to make a state change to the blockchain, we always need to do a from account section here. Then we can even do a little print. We'll do a printf here. So we'll say contract deployed to fundme.address. This is how we'll get the address of our fundme. And great, we can even go ahead and try this out right now. Remember you'll need some testnet RINKB Ethereum in your MetaMask. Brownie runs scripts, deploy.py, -- network, RINKB. And perfect. Contract deployed. Here it is. We can even go to RINKB Ether, scan again. And we can see the contract right here. Now, this is great and all, but if we look at our contract, it's kind of this blank jarble of bytes here, right? Nobody can actually see this contract and easily interact with it. And we want to make our contracts easy to interact with. What we can do on Etherscan is verify and publish our smart contracts. To verify our smart contract, all we have to do is hit that verify button. We'll choose our Solidity compiler type, which we know is going to be 0.6.6. And we know we're working with the MIT license here. Now, to continue, we would then have to add in all of the rest of these pieces. We'd have to do optimization, which is going to be yes. We'd enter our Solidity contract code below, which importing fundme like this wouldn't actually work because Etherscan doesn't know what @chainlink/contracts is. So we would have to copy paste the code from these imports to the top of our contract here. Removing these imports and copy pasting the code associated with these files is known as flattening. And this is an important concept for verifying our smart contracts on platforms like Etherscan. However, Brownie has a really nice way to get around this actually. What you can do is go to their main site, etherscan.io. You can sign in and sign up and get an API key. I've already signed up, so I'm going to go ahead and sign in here. Log in. And what we can do is we can go to my profile and scroll down to API keys. And this is where we can create an API key for us to interact with and programmatically verify our smart contracts on Etherscan. I've already got one here, but all we need to do is hit add. We'll give it a name. I'll call it verify Brownie. Continue. And we've created this new API token that will allow us to verify our smart contracts. What we'll do to use this in Brownie is we'll copy this API key and we'll move back to our scripts here. We'll set this API key as an environment variable. So we'll do export. The name of this is Etherscan token, and we'll set it equal to that key that we just got. Now, to verify this, all we have to do then is once we deploy this contract, we'll tell Brownie whether or not we want to verify the contract. So after our dictionary here, we'll do comma, publish, source equals true. we're saying, yes, we would like to publish our source code. Now, if we rerun this script, let's see what happens. Again, remember, we'll do Brownie, run, scripts, deployed up high, dash, network, space, Rinkeby. And says fund me has been deployed to here. Now we're going to say waiting for API rinkeby.etherscan.io to process contract, and we're submitting our code for verification here. And it'll say verification pending, verification complete, pass verified. And it'll say where the contract has been deployed and what's been done with it. Now, if we go back to Etherscan, again, we're going to have to go back to Rinkeby Etherscan, because we deployed this to Rinkeby, and we paste this in. We now have this little check mark associated with our contract. And if we click contract, we can see all of the code in here for our contract. We have contract fund me, payable, you need to get more ETH, everything that we defined in here. And if we scroll up, we can see that they did indeed flatten this contract, right? They pasted that aggregator v3 interface import, and they also pasted that library SafeMath Chainlink. Now that's verified, we can even read the contract, see the different public variables in here, such as the owner, get version, get price, and all the exact same buttons that we saw in Remix. This read contract section is for all these view functions, right? The ones that aren't going to be making a state change. Write contract is going to be for when we want to call something like fund or withdraw. And we could even go ahead and interact with this. So for example, we could connect to Web3, MetaMask, okay, and it would automatically get connected to our MetaMask here. Then we could call fund and withdraw just like we did in Remix. If you want to give it a shot, go for it. All right, we're back in our code editor after successfully verifying one of our smart contracts on Etherscan. Now, just a quick note, sometimes the verification process can be a little bit touchy. And for version of Solidity 0.8.4, there's currently a bug that makes verifying a little bit tricky, but it's being worked on, so don't be discouraged if it gets a little bit funky. So this is great that we've written a deploy script for deploying directly to Rinkeby. However, as you know, we're always going to want to be able to deploy to our own local blockchains or Brownie's built-in development chain so we can test a lot quicker. And so that we can write some tests. But we have a little bit of an issue here. The first issue being that our FundMe contract currently has an address hard-coded to work with the Rinkeby chain. So in fact, the way it's written right now, it's going to be hard to work with any other chain other than Rinkeby. The second bit is that these price feed contracts don't exist on a local Ganache chain or a Ganache chain that Brownie spins up. There's two ways we can get around this. We can do what's called forking and work on a forked simulated chain, or we can deploy a mock or deploy a fake price feed contract on our Ganache local development chain. Deploying mocks is a common design pattern used across all software engineering industries. And what it applies doing is deploying a fake version of something and interacting with it as if it's real. So again, right now, if I run Brownie, run scripts, deploy.py, and I don't set this network flag, we're going to actually have a default spinning up a Ganache chain, and it's even going to try to verify it, which it's going to run into an issue because we can't verify on a Ganache chain. So we have a couple issues that we need to address here in order for us to get this to work on a Ganache chain. Similar to how in this get account function in our helpful scripts, we do a little bit checking. We say, hey, if we're on a development network, use this development accounts version. Otherwise, pull from our config. We can do that exact same mentality, but with working with these mocks. So the first thing that we need to do is we need to parameterize our FundMe Solidity smart contract so that we don't have this hard-coded in here anymore. So what we can do is right when we deploy this contract, we'll tell it what price feed address it should use, right when we call our deploy function here, instead of having it hard-coded. And we can add this parameter to our constructor. We'll say address price feed as an input parameter, and whatever input parameter we use here is going to be our global price feed address. So instead of us creating these aggregator v3 interface contracts right in the functions here, we're just going to create a global one. So we'll say aggregator v3 interface public price feed, and right in our constructor, right when we create this, we'll set price feed equals aggregator v3 interface price feed. And now what we can do is we can just delete this part, because as you can see, this is doing the exact same thing as up here. This is doing aggregator v3 interface price feed equals aggregator v3 interface, and then the address here. And we're going to do the exact same thing, but in our constructor, meaning right when we deploy this contract. So we can delete this, and we can delete it here as well in our get price function. We can even verify this with Brownie compile. And great, looks like it's compiling perfectly. Now, our deploy function is going to need to look a little bit different. We're going to need to pass the price feed address to our fundme contract. To do this, all we'd have to do is paste that address before we have our from account variable here. So this is how you can actually pass variables to constructors. Anything inside this constructor function, you can pass through Brownie in our deploy script here. So great. So we could 100% always just pass this RINKB address here, but that's not really going to solve our problem, obviously, right? The problem right now is that we always have this RINKB address here. We need to say if we are on a persistent network like RINKB, use the associated address. Otherwise, deploy mocks. And I know we've been talking about mocks. We'll get into them in a second. But let's first set this one up here. So we can check what network that we're on, again, by importing from Brownie this network bit. And we can say if network.show active does not equal development, then we'll say price feed address equals this address here, and we'll just pass this price feed address. Now this still doesn't solve our issue because we're just always passing this, the RINKB hard-coded piece here. So what we want to do is parameterize where we get these addresses from. So instead, what we can do is in our Brownie config, we can add different addresses for different networks. So right underneath our .env, we'll add a new section called networks, and we'll do one called RINKB, and we'll say the ETHUSD price feed address is going to be this price feed address. Now what we can do in our deploy script is we can say, if we're not on a development network, let's grab the address from our networks section. This way we can define different addresses for this price feed across different networks. So we could add a Coven section, we could add a mainnet section, any other networks that we want to work with. All we need to do is add these flags for those contracts. So back in our deploy now, we can say the price feed address is going to get pulled from the config instead. So we'll say config, and this means we're going to have to import config from Brownie. We'll say config of networks based off of the network.show active, and then we'll use the ETHUSD price feed flag here. Perfect. So this little if statement is going to say, hey, if we're not on a development network, pull the address right from the config. And this will make it so that we can deploy to really anywhere that we want to deploy to. But what if we are on a development chain? Well, what do we do then? We can say else, if we're not on a development chain, we're going to have to deploy a mock. So right now, on all these live networks that we're working with, there is a version of this price feed contract, this price feed address. On our development chain, obviously, there won't be one because it's going to start off as blank. So what we can do is we can deploy our own version of the price feed contract. This is known as mocking, and we can interact with it accordingly. In order for us to deploy a price feed contract ourselves, we're obviously going to need to have the Solidity code associated with it. So what we can do is in our contract section, we'll create a new folder called test. When you create a test folder in your contracts folder, this is typically where mock contracts are going to go. And we'll create a new file called mock v3 aggregator.sol. And this is where we'll add the code for us to deploy our own price feed. Now I'm going to show you another repository pretty soon called the Chainlink mix that we're going to work with. For now, if you're looking for one of these mocks, I highly recommend just pulling it from this Chainlink mix repository. So we can grab it by going to contracts, test and grabbing mock v3 aggregator.sol. And we can just copy this whole code and paste it into our mock v3 aggregator.sol. This has all the same exact functions as a real price feed contract, such as decimals and latest answer, which are going to be two of the ones we use the most. We can also see its constructor here. These are the variables that it takes whenever this contract is deployed. It takes a decimals and an initial answer. Decimals is of course going to be how many decimals that this contract should have, and initial answer is going to be its starting value, like 2000 for example. Once we have this contract in our test section, we can of course run Brownie compile, and Brownie will go ahead and compile this mock v3 aggregator as well. Because remember, Brownie compiles any contract in this contracts folder. Let's go back to our deploy script now that we have this mock v3 aggregator in here. Now what we can do is we can do a little else here saying, okay, well, if we are on a development chain, let's do something. Let's deploy these mocks. So let's do a little print statement here, a little printf saying the active network is, we'll do network.show active. Do another print statement, printf saying deploying mocks, Oops, I need a little closing there. And this doesn't need to be printf. It can just be a regular print. And then now, the same way we import fundme, we can import mock v3 aggregator. We can just deploy this contract the same way we deploy all of our other contracts. So we'll do mock v3 aggregator dot deploy. And as we just learned, we have to add the parameters the constructor takes, which is going to be decimals and initial answer. So maybe we'll set decimals to 18, and then maybe we want to set the initial answer to 2000. So 2, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, comma. And of course, since we're deploying, we've got to do a from, and we'll use our account here. Then we'll do another print saying mocks deployed. And of course, we're going to need to get this mock v3 aggregator's address. So we'll do mock aggregator equals this, and we'll set price feed address to equal our mock aggregator dot address. And now we're development or live network agnostic. If we deploy this on a live network, we'll use the address from our config. Otherwise, we'll use a fake aggregator contract that we've deployed. Let's go ahead and even try this on a development network. So we can do Brownie, run scripts, deploy.py. We don't need a network flag here. We'll hit enter. It'll spin up the ganache. And we even will deploy a mock aggregator contract first, and then we'll do our fundme part. Of course, we are running to an issue because we're trying to verify a contract on a chain that doesn't exist. Etherscan doesn't know about our local ganache chain. So to fix this, instead of doing publish source equals true, we can have this publish source be, again, based on what chain that we're on. So we'll go back to our Brownie config, and for RinkB, we'll say verify will be true. But for development, we'll say verify will be false. And back in our deploy script, we now say publish source is going to be pulled from our config. So again, we'll do config, networks, network.show active, and then we'll do .get verify. This .get verify will make our lives a little bit easier if we forget to add verify in here. You could still do like this, like verify, but you'll run into some index errors if you forget to actually put the verify. So sometimes I get lazy, and it's just a little bit nicer like this. Now, if we run this again, deploy.py, we'll spin up our local ganache, we'll deploy a mock price feed contract, and then we'll deploy our fundme contract, and it completes successfully. So this is awesome. We have a way to PD our fundme contract that uses a price feed contract to our own local development environment with a mock, aka a fake price feed contract. This is awesome. Now this is great, but our deploy script is starting to look a little big and a little clunky. So let's actually clean this up to make it look a lot nicer. The first thing that we want to do is we want to fix this big 2000 number. Just looking at it right away, I'm not exactly sure how many zeros it has. So to make this look a little bit nicer and more readable, we can once again call on our friend web3.py. from Web3, import Web3, and down here we'll do Web3 dot two-way 2000, comma, Ether. This two-way function will just add 18 decimals to this 2000. So now this is much more readable that the initial value for this is going to be 2000. The next bit is that we're always deploying this mock v3 aggregator here. And if we already have a mock deployed to whatever network that we're working on, we don't need two mocks here. So what we can do then is right before we deploy this mock is we can do a little if statement. We can say if the length of our mock v3 aggregator is less than or equal to 0, only then will we deploy this mock v3 aggregator. Remember, we can check the length of our v3 aggregator because this v3 aggregator is just going to be a list of all the different v3 aggregators that we've deployed. Now, instead of using mock aggregator.address, we can just use mock v3 aggregator -1.address. So we're just saying, okay, great, just use the most recently deployed mock v3 aggregator. And then of course we no longer need to set this as a variable. And that looks a little bit cleaner and will make this a little bit more efficient. So this deploying mocks bit though is going to be something that we're actually going to do relatively frequently. Let's even move this print statement up here. So instead, what I like to do is put this whole mock deploying bit in its own function in our helpful scripts. So let's open back up our helpful scripts. We'll do a new function called def deploy mocks, and we'll just paste that code in here. Of course, this means that in our helpful scripts, we're going to have to import mock v3 aggregator. We'll also have to do from web3 import web3. And instead of account, we'll just use this getAccount function. Now, back in our deploy script, we can just delete this whole part, replace it with deploy mocks, and then import deploy mocks from our helpful scripts. And then we can also delete this import now. Let's remove some of these comments if you'd like. This is starting to look a lot more sophisticated. And this is great because now we have a way to deploy based off if we're on a live chain or a development chain. And then one more thing I like to do so that everything is parameterized, I like to set these as static variables in the top of our helpful scripts. So I'll set decimals equals 18, and then I'll set starting price equals 2000. And then I'll have mock v3 aggregator to deploy to decimals, web3.2way to starting price here. So let's say now that I wanted to deploy this to my own Ganache instance. Well, what we could do is we could open up our Ganache here. We'll do quick start, and we'll just quickly create our own Ganache blockchain. In our script, let's go ahead and just run this deploy script again. Let's see what happens. Instead of Brownie spinning up its own Ganache here, it says attached to local RPC client listening at, and then this address here. Brownie is smart enough to detect if you're running your own Ganache instance here and will automatically attach itself to it, knowing that that is going to be a development environment. If we go to our Ganache, we'll see we have two transactions, which are going to be contract creations. We're going to create the price feed contract and then also our fund fee contract. So this is great. This is great for testing quickly and locally, but there is an issue with this. For development networks, again, Brownie doesn't keep track of those. So in our build folders, if we go to deployments, we only are saving stuff from the Rinkeby chain here. So we would need to tell Brownie, hey, there's another network that we want you to work with, and we want you to remember the deployments to that chain. So what we can do is we can add a new network to our Brownie networks list. Remember, in Brownie networks list, we have all these different pieces in here. These are the ones that Brownie's going to not remember, and these are going to be the ones that Brownie remembers. So let's say we want to deploy to a Ganache chain and we want Brownie to remember those deployments. Well, we can add a network here. And this is going to be how we add any blockchain that we want, any EVM blockchain, like Avalanche, like Polygon, etc. To add a new network to the Brownie networks is we'll run Brownie networks add. We'll choose development or Ethereum. We're going to choose Ethereum because we want this to be a persistent network. We'll do Ethereum. We'll give it a name. I'm going to call this Ganache local. We need to give it a host, aka an HTTP address, which we know is right here. And then I'm just going to make this lowercase. And then a chain ID, which for this we know is 1337. Hit enter. Now, if I do Brownie networks list, I see a new blockchain called Ganache local. And this is going to reach out to our Ganache UI or our Ganache command line, depending on what we're running. Now, just a note, we are going to be deploying to this Ganache UI or Ganache CLI a lot for the rest of this lesson, so please keep your Ganache instance running. Now, what I can do is I can run Brownie, run scripts, deploy.py, -- network, Ganache local. Let's see what happens. Of course, we run into our first issue. Ganache local isn't development. So it's going to go ahead and try to pull from our config file. We don't want this. We want to actually deploy a mock for our local Ganache if a mock hasn't been deployed. So what we can do is we can extend our definition of what a development environment is. In our helpful scripts, we can add a flag in here. We'll say local blockchain environments equals, and this will be a list. We'll say development, of course, will be one, but we can also say Ganache local will be another. And now we can import this local blockchain environments into our deploy. So from at the top, from scripts.helpful scripts, do a comma here, paste that and save. Mine gets reformatted, which is really nice. And instead, we'll say if network.showActive not in local blockchain environments, then go ahead and pull from the config. What this is saying is it's saying if whatever network that we're on, if it isn't development or Ganache local, then go ahead and use a config. If it is one of these two, we're going to go ahead and deploy a mock here. Now that we have that, let's try this again. Brownie run scripts, deploy.py, -- network, Ganache local, and we run into a different issue. We're saying, hey, you don't actually have enough gas. Well, why is this? Let's look at our get account function. Aha! This one is also looking directly for this development chain. This one will say if network.showActive is in local blockchain environments, then return accounts 0. So we're saying if the network we're working on is development or our Ganache local, then just return accounts 0. So let's try this. Okay, we're getting closer. Now we're running to this key error, Ganache local. Well, we do know how to fix that as well. In our config, we'll add this new network. We'll say Ganache local, and we'll set verify to false. So let's try this one more time. Perfect. Now mocks have been deployed and our FundMe has been deployed. And if we look in our build folder in deployments, we now have a new chain ID for 1337 for saving these deployments. And it looks like in our Ganache chain, we have these actually saved in here, which is great. Now, an important thing to note, if you were to close this or delete this Ganache chain, all of your contracts will be lost. So you won't be able to interact with them again. To account for this, you can always delete 1337 and delete the entries in 1337 from your map.json. Or if you're fine deleting the whole build folder, you could delete the whole build folder. So now that we've deployed this, let's actually write a script to interact with this. So let's create a new file. We'll call it fund and withdraw.py. And this will be the script we use to fund and withdraw. So let's create a function called fund. We can say fundme equals the most recently deployed fundme. We're going to have to do from Brownie import fundme. We're going to have to get an account since we are going to be making some state changes. And we just have this equal to get account. And we can do from scripts.helpful scripts import get account. Let's get the entrance fee so we can figure out how much we want to fund. Since this is going to resemble that FUSD price feed, it actually only has 8 decimals. 2, 1, 2, 3 for 2000, and 1, 2, 3, 4, 5, 6, 7, 8. The reason we want to do it like this too is because In our get price function, we know that it only has 8 decimal places, so we're multiplying it by an additional 10 here. We want it to resemble that as well. So we'll do 8 decimals, starting price of 2,000 with 8 decimals here. And for our mock V3 aggregator, we're just going to use those exact values, and we're not going to do the Web3 converting. We're just going to make it exactly those hard-coded values. Now we're going to want to get the entrance fee. So I've gone ahead and actually added a function called get entrance fee to our contract to make our lives a little bit easier here. I'm going to recommend that you take a look at this and then type it in yourself, or you just copy paste it from the GitHub repository so that we can use this get entrance fee, because it's just a whole bunch of math here. So back in our fund and withdraw, what we can do then is we can do entrance fee equals fundme.get entrance fee. Excuse me, get entrance fee. And we can even print out this entrance fee just to see if we're doing it right. But first, we're going to want to run Brownie, run scripts, deploy, network ganache local, because we changed our fundme.sol. All right, great. And now we can run Brownie, run scripts, fund and withdraw, network ganache local. And whoops, I need a main function. So we'll do def main, fund in here. And let's rerun this. And great, we can see this is the entrance fee. We'll do a little print statement here, a printf saying the current entry fee is entrance fee. We'll do a little print saying funding. And then we'll call fundme.fund. And of course, we're going to have to do a from account. And we're also going to send a value of entrance fee. Any low-level transaction data that we want to send with our transactions and function calls, we'll add in this little bracket piece here. Let's hit up. Let's do Brownie run scripts, fund and withdraw again. And great, it looks like it's going through perfectly. Awesome. Let's also do a withdraw function for the owner to withdraw. We'll say fundme equals fundme -1. Do account equals get account. And then we'll just call fundme.withdraw from account. And then right after fund is called, we'll have withdraw be called in our main function here. Let's go ahead and try this. Brownie run scripts, fund and withdraw, network ganache local. This is our funding script, our funding transaction going through, and then our withdraw transaction going through. Perfect. So it looks like our approximate functionality here works great. And this is a script that we can run on a main network if we'd like. Now, again, it's still much better for us to run. So now we're going to move into actually writing those tests. And for these tests, we're going to want to quit our Ganache UI. Let's go ahead and write some of these tests. Create a new file called test fundme.py. We'll quickly speed through this test because we're not going to learn too much new here. Keep in mind, when we run this test, we're going to want it to be able to work independent of the network that we're working on. So let's just keep that in mind. Let's do a test just to see if we can fund and withdraw. So we'll do def test can fund and withdraw, and we'll do basically exactly what we've done before. Do account equals get account. And of course, we'll do from scripts, that helpful scripts, import get account. Then we'll want to deploy fundme, and we can even just use our deploy fundme script in our deploy.py. So we can do from scripts dot deploy import deploy fundme. In our deploy fundme at the bottom, we'll just say return fundme so that our test can now have this fundme contract for it to work with. So now we'll say fundme equals deploy fundme. We'll grab the entrance fee, which will be equal to fundme.get entrance fee. And then let's go ahead and fund it. So we'll do transaction equals fundme.fund. And we'll call from account. We'll do value entrance fee. We'll do tx.weight1. We'll do an assert here. We'll do assert fundme.address to amount funded. It's going to be account.address. It's going to be equal to the entrance fee. So we want to check that our address and the amount that we funded is being adequately recorded. And then we'll do transaction 2 will be fundme.withdraw from account. We'll do tx2.weight1. And then we'll assert fundme.address to amount funded account.address equals 0. And let's go ahead and run this test. So we'll do Brownie test. And perfect. Looks like it's doing well. Now you may be wondering why sometimes we use the -- network flag and sometimes we don't. In our network section, Brownie automatically picks a default network to use. And the default is always set to development. However, we could set this to be anything that we wanted. We could set the default to be Ganache local. We could set it to be Rinkeby, whatever we want here. Whatever you set for the default in your Brownie config is what the network will be defaulted to. So right now, when we run Brownie test, this is equivalent to running Brownie test -- network development. We can even go ahead and run that too. Now, we could also run this test on Rinkeby, and we will in a second, but oftentimes we don't want to test all of our functionality on Rinkeby and on live networks because it's going to take a long time for them to run. So sometimes we only want to run tests on our local chains. Well, how do we do that? We can use PyTest's skip functionality to do so. To work with PyTest, we're going to first need to install it. So go ahead and run pip install PyTest. To demonstrate this, let's create a test that makes sure only the owner can withdraw and nobody else can. So we'll call this def test only owner can withdraw. To skip this test, if we're not on a local network, we'll first check the network. We'll say if network.showActive is not in, and yep, probably would have guessed it, we're going to pull this local blockchain environments in from our helpful scripts. So we'll do comma, local blockchain environments. And we're going to say, if the network.showActive is not in this list of local blockchain environments, we're going to do pytest.skip and say only for local testing. Now, of course, we're going to have to import network. And we're also going to have to import PyTest. Now, if I try to run this test here with Brownie test -k --network Rinkeby, it should skip. Perfect. And we do see with this S here, meaning that it skipped this function. If we run this with --network development, it should go ahead and run this and it'll pass because nothing happens in this function. And it does. Perfect. Let's keep going. So now we'll say account equals get account. We'll say fundme equals deploy fundme. And now let's get a different account to try to call the withdraw function. So we'll say bad actor equal, and this will just give us a blank random account, but we do have to import accounts from Brownie here. Now, we want to test to see that them calling this withdraw function actually reverts them and causes an exception. Because if I try to do fundme.withdraw from bad actor right now, what do you think will happen? Well, we know in our fundme.sol, our withdraw function has the only owner modifier. So technically, only the owner should be able to call this function. So what happens, actually, we don't even need this get account bit. Let's just go ahead and delete that. So what happens if somebody else tries to call this withdraw function? Well, let's go ahead and test this. We'll do Brownie test -k, test only owner can withdraw. And you can see we're getting this error here. We're getting brownie.exceptions.virtualmachineerror revert from this fundme.withdraw. Well, we want this to happen. We're expecting this to happen. So how do we test that we want this to happen? Well, we just need to tell our test that we want this to happen. So first, we're going to have to import from Brownie this exceptions package. This way we can tell our test exactly what exception we're expecting to see. Then we'll say with pytest.raises exceptions.virtualmachineerror fundme.withdraw, and then we'll just copy this line down here. Now, what this is telling our test is that if this reverts with this virtual machine error, that's good. We're saying we want you to revert when you try to call this line. So if we delete this line and hit up and try to run this again, we can see that it now passes. And this is exactly what we're expecting. So this is awesome. All right, we've learned a lot of fantastic tools for working with Brownie here. Now, the last version of testing that I want to show you how to use is mainnet forking. Mainnet forking is incredibly powerful when we're working with smart contracts on mainnet that we want to test locally. So let's talk about forking for a minute. So on the left here, I have a blockchain, right? An example of a blockchain. This is going to be like a testnet, like Rinkeby, or something like mainnet, right? This is going to be a blockchain that we actually deploy to. Now, there are a whole bunch of blocks in here, right? And there's a huge chain that we can actually work with. All of this information is public information, right? This block is going to have like transaction. It's going to have, each one of these blocks is going to have a whole bunch of transactions, and all this information is here. In addition to all these transactions, it's going to have price feed contracts, Aave contracts, etc. It's going to have all these different contracts in it. So hypothetically, if it's all already there, we should be able to basically copy this whole blockchain and do some simulations ourselves. And that's exactly what forking does. A forked blockchain literally takes a copy of an existing blockchain on the left here and brings it into our local computer for us to work with. We actually have control of this blockchain since it's going to run on our local computer, similar to Ganache. Now, all the interactions that we do on this local blockchain are not going to affect the real blockchain because it's our local chain, right? It's a simulated blockchain. But because it's simulated, we can go ahead and interact with price feeds. We can interact with Aave. We can interact with all these different contracts that are already going to be on chain. Mainnet fork is a built-in part of Brownie and also pulls from Infura the same way it works with Rinkeby and Coven and everything else. We can start to interact with the mainnet fork contracts the exact same way, therefore. So we can take this whole Rinkeby section, copy it, paste it, and we'll just change this FUSD price feed address to its mainnet address. So we'll go to docs.chain.link, Ethereum price feeds. We'll get FUSD here, copy that, and we'll paste it into here, and we'll change this to mainnet fork. And since this is going to be a fork, of course, for verify, we're going to do false. Now, if we try to run one of our scripts, like Brownie runs scripts deploy.py -- network mainnet fork, you'll see we'll actually run into an issue here. It's saying insufficient funds for transfer. In our deploy script, when we do our get account and our helpful scripts, right now we're using accounts.ag config wallets from key. Yes, it's going to be our account, which right now has 0 money in it on mainnet. So Brownie's right away going to say, hey, you don't have any money on mainnet. What's the deal? So we need to tell Brownie that when we're working with mainnet fork, it should create us a fake account with 100 ETH in it. However, we don't want it to deploy a mock because the price feed contracts already exist. So we don't want it to deploy a mock, but we do want it to get us an account here. So typically what I like to do is I'll add another variable here and I'll call it forked local environments. And I'll add mainnet fork in here. And I'll use this now as part of my if statements. So I'll say if network.showActive in local blockchain environments or network.showActive in forked local environments, then we're going to go ahead and return account 0. However, in our deploy.py, mainnet fork is not going to be in this local blockchain environment, so we will just get our price feed from our config. So now, if I run this mainnet fork again, now if we run this, you'll see we'll still get an error. We'll get list index out of range. So Brownie's built-in forking mechanism doesn't actually come with its own accounts here. However, it has these issues. So what normally I like to do is I like to create my own custom mainnet fork right in Brownie. The way we can create our own development custom network is by using the Brownie networks add key. So we can do Brownie networks add. We'll make this a development network instead of a persistent network. And we'll call this mainnet fork dev. To set this up, we'll do a ganache CLI. So we'll say the command to run this fork is going to be ganache CLI. The host is going to be the same as always, http://127.0.0.1. Fork is going to be equal to, and this is where we just put https mainnet.infura.io/v3/web3 infura project ID. Now don't hit enter quite yet. I'm going to explain a couple things. So this single quote means run this as is. If we ran this without the single quote, our environment variable would get actualized here, and we'd always have to use whatever our current environment variable is. So we want to have this little semicolon here. Then we would do accounts equal 10. This tells Brownie for us to set up 10 fake accounts for us. We'll give it a mnemonic of Brownie. So we'll say, great, make those accounts, just have a mnemonic of Brownie. And we'll do port equals 8545. Now, once again, don't hit enter quite yet. I do want to explain one other thing. So this is great for working with Infura and forking from Infura. However, I have to note that performance-wise, forking from Infura has pretty much always given me an issue. So I prefer actually to fork from this application called Alchemy. And in fact, if you'd like, you could set up all of your networks to work with Alchemy by modifying them. I'm going to go ahead and sign in here, and we're going to give it an Alchemy URL instead of an Infura URL. So I'm going to go ahead and create an app. I'm going to call this Fund Me Demo. Description will also be a Fund Me Demo. Be a development environment on the Ethereum mainnet. Let's create this. We can now view the details of this. We'll go to View Key, and we'll copy this HTTP address, and we'll move back over here. And for forking, we can just delete everything next to this fork, and we'll just paste that in here instead. And let's go ahead and hit enter. You'll know you've done this right if you can see something like this. Mainnet fork dev has been added. Oftentimes, in my example, I will actually just delete mainnet fork and have mainnet fork dev be my default for mainnet fork. But for us, we're going to go ahead and do mainnet fork dev. So in our config, we're going to change mainnet fork to mainnet fork dev. And so since we're giving this a different name, that means in our helpful scripts, we're going to have to do a comma here and say mainnet fork dev. All right, great. Now our get account should return account 0 for mainnet fork dev, and it should actually work. So let's run our script again. Brownie runs scripts. Deploy -- network mainnet fork dev. And perfect, we're running our mainnet fork dev, and it is running successfully. Now we should also be able to test exactly the same way. Let's look at our test real quick. Test fund me and see, okay, cool. We're going to be skipping this one since mainnet fork dev isn't in the local blockchain networks. But this should work perfectly. And then oftentimes in my tests here, I'll actually do like a little plus 100 or something for entrance fee, just in case I need like a little bit more money for whatever reason. So now if we run Brownie test -- network mainnet fork dev, we'll see that this does indeed pass. And this is awesome. So this is fantastic. Incredibly powerful project here. Now we're going to teach you how to actually share your code and enter the world of open source and decentralized code. The way the world works when sharing code and sharing ideas and collaborating together is they use what's called open source Git repositories. GitHub is an example of one of these Git repositories that we can use to share our code. And it's one of the dominant ways that smart contract engineers share ideas and share code. We are now going to learn how to add our code to GitHub, and then we can even share the code and show the world what we've built and what we've done. This isn't going to be a full end-to-end Git course. However, there are some links in the course repository that will show you how to work with Git, work with GitHub, and work with version control. So the first thing that we're going to do is we're going to come to GitHub and we're going to sign up for a service. Add our email, create a password, enter your username. No. Now we'll go to our email to verify it. We'll continue. We're going to be working with some collaborative coding. We're going to choose the free edition, and perfect. We are now in GitHub. Now that we're in GitHub, we're going to create our own first open source repository. So we're either going to hit this plus button here or create repository. Let's choose a repository name for this. We'll give it the same name as our main folder. So we'll call this Brownie Fund Me. We'll give it a description, maybe smart contract, application, and we'll hit create repository. This is where we're going to upload our code to share with the world. Back in our VS Code now, we're going to send this folder to that repository. First thing we need to do is installing Git. There are a couple different ways to install Git depending on the version that you're on. We'll put this link in the description to our course to actually install Git. Once you have it installed, you should be able to run git -- version and see a Git version here. Now we're going to initialize our repository in here by doing git init. We're going to choose a branch name. We're going to call it main. We'll go ahead and add our username and email to our git config user.name quotes free code camp video git config user.email free code camp video at gmail.com. Now we're going to do a couple things to push all of our code to GitHub here. However, remember, we do not want to push our .env pieces up here. So we can do a couple of things. We can go ahead and delete this, of course, but we can also add in our .gitignore file a .env. This will help us so that we don't accidentally push our .env file to GitHub. We can choose what files we want to push by doing git add and then a period. And if we do git status, it'll now show us all the different files that we have staged to push to GitHub. If we look in here, we see we have git attributes, git ignore, Brownie config, fundme, some contracts, some scripts, but we do not have that .env file. If you were to remove .env from .gitignore and you ran git add .again, and then we did git status, we now see the .env in here. We do not want this in here, so we can do git remove -- cached .env. We'll add .env back to our .gitignore file, and then we'll run git status again. And then we'll run git add period, and then git status. And great, we do not see that .env in here, so that's very good. Now we'll commit this by git commit -m first commit. And now we can add this folder to our GitHub. Back in our GitHub, there's a little line here which even tells us how to do it. We're going to copy this line right here. Git remote add origin, HTTPS free code camp Brownie fundme. I'm going to copy that, paste it in here, hit enter. And now we can just do this second line. Git push -u origin main. We'll do git push -u origin main. We get an output like this, and if we go back, we'll now see all of our files and folders in here. Now, I've already added my email and password in here, but instead of this, you'll probably get GitHub asking you for authorization. You can just go ahead and put your GitHub username in and your password in there. If your username and password doesn't work, you can come into GitHub, go down to settings, scroll down to developer settings, personal access tokens, and generate new token. We'll call this Brownie, and we'll want to give it at least repo authorization here, and we'll hit generate token. And instead of using your password, you can go ahead and use this GitHub token. Amazing. And you now have your first GitHub repository. We could even come in here, add some topics like Solidity, Chainlink, Python, Brownie, etc., so that we know what our file is about. And this is incredibly exciting. Now, I'm going to even encourage you to pop onto Twitter and share your excitement. I just made my first at GitHub repository, thanks to at Free Code Camp, at Solidity, Lang, at Brownie Eth, at Chainlink. If you want to tag me, you can also tag at Patrick Alpha C, and then pop your repo in there. Go ahead and hit tweet. The community absolutely loves hearing about all the fantastic things people are doing in this ecosystem. So be sure to reach out, have fun, and engage. I know we've gone over a lot here, but let's talk a little bit about some testing pieces here. Now, a big question you might have is, well, okay, so I learned a ton of stuff. We learned about mainnet forking. I can do stuff on Ganache. I can use Brownie's Ganache. I can use Brownie's mainnet fork. I can do a test net. There's all these places to do stuff. Where do I need to run my tests? The default for every single one of your contracts is as follows. You always 100% need to have tests that pass on a local Brownie spun up Ganache instance. That should be priority number one to get all your tests to pass on this. This means that you will need to deploy mocks. After that, the other place you absolutely need to have tests or do some type of development is on a testnet. These are going to be what's known as your integration tests, and we'll talk more about those later. So those are the two places you always need to have tests, development and a testnet. I think testing on mainnet fork and your own local Ganache are optional. Testing on mainnet fork can be done and probably should be done whenever all of your contracts and all of your interactions are going to be on-chain, on one chain without any external off-chain components. Testing on your own local Ganache is really more meant for tinkering and kind of exploring and seeing things yourself. So that's going to be the setup here. So great, now let's move into our most challenging example. Once you pass and once you complete this example, you basically will have all the tools to be an incredibly powerful smart contract developer. Then after that, we're going to show you the Chainlink mix package and how to do what's called a Brownie bake to automatically open up this package with all these scripts and all these contracts pre-built in. This is going to make our lives substantially easier and faster for deploying our smart contracts. However, let's go through the process of understanding all the pieces that are going to be inside of this Brownie mix. Are you ready? You should be. Let's get excited and jump in. Okay, so let's get into our most advanced smart contract project that we've made so far. This is going to be the best example of a full-scale application. And by full scale, I really mean end-to-end, full suite of our Brownie. All of our smart contracts are really solid here. What we're going to want to do is create a lottery application where anybody can enter the lottery and a random winner is selected. So let's get to it and let's get started. So first, of course, we're going to make a new directory. We'll call it Smart Contract Lottery. CD into Smart Contract Lottery, and then open that folder. And great, we are now in our lottery application. So let's go ahead and start a new project. Brownie init, we've got our project here. Now let's create a quick readme.md to explain what we're going to be trying to do here. So number one, we're going to say users can enter the lottery with ETH based on a USD fee. So for example, let's set the price to be like $50 and the users actually pay with Ethereum. So we're going to have to get that conversion rate. Number two, an admin will choose when the lottery is over. And then three, the lottery will select a random winner. Now, something important to note here is since we have an admin here, this means that our application isn't necessarily going to be truly decentralized because we have a single person chooses when the lottery is over. We could scale this out to have maybe a DAO being the admin or something like that, or we could have the lottery automatically open and close based off of some time parameters. But for the moment, this is the setup that we're going to have. Keep in mind, even though this is much less decentralized, it's still going to be a great use of smart contract technology. So first thing that we're going to get started with, of course, is our lottery contract. So create a new file called lottery.sol. And let's begin with our initial setup here. So let's choose our version, Pragma Solidity caret 0.6.6. And this will be the version that we want to work with here. We'll do contract lottery, little bracket here. Now let's think for a second on what some of the functions that are going to be, what our main functions are going to be here. We'll probably have a function enter. That'll be public. We'll probably have a function get entrance fee to get the entrance fee of the lottery. We'll probably have a function start lottery that only the admin can call. This will be public as well, which means we'll also probably have an end lottery function. And those are really going to be the main functions. The user can enter based off the entrance fee. We can start the lottery, and then of course we can end the lottery. So let's get started with this enter function, just because this is most likely going to be the entry point. As we know, since we're going to want them to pay using this entry function in Ethereum, we're going to need to make this function payable. And in here, we're going to need to keep track of all of the different players, everybody who signs up for this lottery. To keep track of all the players, we're going to make an address payable array. We'll make it public, call players. And anytime somebody enters, we'll just do players.push message.sender. However, right now, we're not checking to see how much value that they're actually sending. We want to set the price of this to be at least $50. So we'll say $50 minimum. So here we're going to have to do a require statement requiring them to do at least $50. In order to do that, we're probably going to need to have some function to get the entrance fee to check whether or not how much they're sending is actually $50. So let's go ahead and make that get entrance fee function now. Since we're just going to be returning a number for get entrance fee, we can probably go ahead and make this a public view and have this return a UN256. To get this entrance fee, we're first going to have stored somewhere what the entrance fee is. We're going to have to store this $50 minimum somewhere. This is something we'd probably want to set right when our contract is deployed. So where can we put stuff like that? Well, in our constructor, we'll do constructor public. We'll create a new variable outside of here. We'll call it UN256 public USD entry fee. And in our constructor, we'll say USD entry fee equals 50. Now, because I like to have units of measure always in way, we'll also do times 10 raised to the 18th. Now we have some USD entry fee. Let's go ahead and get this entrance fee. As we know, since we're going to try to get a conversion rate here, we're going to want to use a Chainlink price feed. So we can head on over to docs.chain.link. We'll scroll down to get the latest price. And we can even just go ahead and copy paste this again. But for the sake of robustness, let's just walk through again how to actually set this up. We're going to need to pull from the price feed to convert $50 to $50 in ETH. So let's go ahead and create an aggregator v3 interface. Internal ETH/USD price feed. And in our constructor, we'll go ahead and set this. We'll say ETH/USD price feed equals aggregator v3 interface. And we're going to want to grab an address from our contract addresses. But of course, as you know, as we've learned from last time, we're going to want to parameterize this. So we're going to want to pass the address of our price feed as a constructor parameter. So we'll do address price feed address, and we'll have our aggregator v3 interface be passed that price feed address. Then of course, since we're using an aggregator v3 interface, we're going to have to import this from Chainlink. So we can just go ahead and copy this from the documentation and paste it right at the top. Or if you want to rewrite it out yourself, feel free to do so. And of course, since we're doing this import here, new file, Brownie config.yaml, we're going to want to add this as a dependency. So we'll do dependencies, SmartContract kit / Chainlink Brownie contracts, and we'll do add 1.1.1 again. and then compiler, soak, remappings. We'll say at Chainlink equals this right here. We'll pull up our terminal and we'll try this out. Do Brownie, compile, see if we're doing everything right. We forgot an SPDX license identifier, which is just a warning, but let's add it in anyways. SPDX license identifier, MIT. And I should probably spell remappings right. We'll do remappings. And let's try to compile again. All right, lovely. So we at least know that we are compiling correctly here. Awesome. So now that we have a price feed, let's go ahead and set up this entrance fee. So we're of course going to need to get a price from this price feed. So we can even check the documentation on how to do that. We can call this latest round data function. So we could copy paste it. I'm just going to go ahead and rewrite it. But again, we don't need round ID, started at, timestamp, or answered in round. We only need price. So we can go ahead and ignore these variables on our call. So what we'll do is we'll do blank comma, int price, and then comma, 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 equals ETHUSD price feed dot latest round data. And this means we're just going to get the price here. Now we're going to want to do a little bit of quick math. Typically, if we're setting the price at $50 and we have a price feed of $2,000 per ETH, we would just want to do 50 divided by 2,000. But of course, since Solidity doesn't work with decimals, we can't actually just do this. So we'll have to do 50 times some big number divided by the 2,000. So we're going to go ahead and do it like that. But first, let's go ahead and convert this price from int 256 to uint 256. So we'll say uint 256 adjusted price equals uint 256. Uint 256 price. And then, since we know we're going to be using an Ethereum USD price feed that has 8 decimals, let's also just convert it to having 18 decimals as well. So we can also do times 10 raised to the 10th. So now we can have 18 decimals. Now that we have this adjusted price, we'll do uint 256 cost to enter is going to equal USD entry fee times, again, we're going to want to times it by some big number here. So we'll just times it by 10 raised to the 18th. This way, USD entry fee has 18 decimals, but it has an additional 18 decimals here that'll get canceled out with our price feeds, and the math will work, divided by price. And then we'll return cost to enter. Now, of course, since we're doing some interesting math here, it's recommended to use safe math and use safe math functions. We're going to skip over the safe math functions here, again, because in the newer versions of Solidity, you don't really have to use them. But I think it's important to note here that sending this code, this exact code to production would be a bad idea for at least the reason of the safe math functions. But in any case, we have a function here. We think our math is pretty good, but I know for a fact that my math is usually not very good. So let's go ahead and do some testing as we code, just to make sure our getEntranceFee function is working properly. So based off of our last lesson, let's talk about how do we want to test this? Well, we could do a mainnet fork here because we're only working with some on-chain contracts and some math. We will at some point have to do our development with mocks and of course our testnet. I kind of want to just do a quick and dirty way. So let's try our mainnet fork just for now, just to see if this is really making any sense. If the current price of Ethereum is $2,500 or this much here, and we want the price of this to be $50, we can do 50 divided by this, and we get 0.019. So this should be approximately what we get for our ETH value. So if we were to write a test lottery.py, we were to test this function, we would expect to get 0.019, or in way, it'll be 19, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6. We'd expect to get approximately this. So let's go ahead and create a function that tests this. So we'll do test get entrance fee. And in here, we'll deploy lottery. And in here, the first thing we need to do is deploy this lottery function, of course. So we'll do from Brownie import lottery. In order to deploy this, we're going to need to get an account. We are going to import our helpful scripts from the last project to this one too, so we can get our get accounts, but for the time being, we can actually just use accounts 0 from Brownie. So we'll say accounts 0. Let's just start with def. Then we'll do lottery equals lottery.deploy from account. And of course, we have a parameter here of our price feed address. So we're going to have to add some type of parameter here. For now, let's just hard code it from our config. And we'll go into our config and we'll start our networks flag. We're going to be working, like I said, on the mainnet fork for this quick and dirty here. And we'll call ETH-USD price feed. We'll grab the ETH-USD price feed from mainnet, since we're going to be doing a mainnet fork here. Pop that in here. Now we can just say from config network.show active ETH-USD price feed. Of course, we're going to need to import network here. And now we can do our kind of quick and dirty test. We can do lottery dot get entrance fee. Am I spelling that right? Get entrance fee. Yes. Assert lottery.get entrance fee should be greater than, let's just go down one, 18. Or if we wanted to make sure we're actually doing this right, we'll do from web3 import web3. We'll do web3.toWay 0.019 comma ether. Should be greater than, and then we'll even do 0.018 just to make sure. And it should be less than 0.022. Now these numbers are of course going to be a little bit different for you. And if you want, you can go ahead and skip this part so that you don't have to do the math. But it is kind of nice to do a quick sanity check saying, okay, like based off what things are right now, what would this price end up to be? Now in our last section, we made a mainnet fork dev network. I'm going to just go ahead and customize our mainnet fork the way that we showed you guys how to do mainnet fork dev. This way you can use accounts and we can be a little bit more robust here. To do this, we're first going to have to delete Brownie's internal built-in mainnet fork. So we'll do Brownie networks delete mainnet fork. Mainnet fork has been deleted. And now let's go ahead and add our own mainnet fork using Alchemy as our Ethereum connection. So you'll want to create a new app. I've already created one here called SmartContract Lottery. We'll view the key, and this is the HTTP endpoint that we'll use. So to do this, we'll do Brownie networks add. This will be a development chain. We'll call this mainnet fork. It'll be a ganache CLI. The host is going to be our local host, so 127.0.0.1. And the fork is going to be equal to our Alchemy HTTP here. We'll do accounts equal 10. That way we can use the accounts. We'll do the mnemonic equals Brownie. Port is going to be 8545. And great, mainnet fork has been added. Now that we have this here, we can go ahead and run our test. Brownie test dash dash network mainnet fork. Whoops, looks like we got a little compile error on our math here. Whoops, it looks like we're divided by price when we need to be divided by adjusted price. And we forgot the parentheses on latest round data. Let's try this again. And I put an extra comment in here. Let's try this one more time. Lovely, and it looks like we're forking correctly. And awesome, it looks like our test indeed passes here. Of course, we know that we're going to want to change this because this isn't a great way to actually test our contracts here, but it can be a nice sanity check. And we know we're going to have to refactor this as well for mocks and for accounts, but we'll get to that in a little bit. Awesome, sanity check complete. Let's get back to our contract here. So we are getting the cost to enter correctly. Perfect, we're getting this entrance fee. What that means we can do in our enter function, we can do require message.value. It's got to be greater than or equal to our get entrance fee function. And if it's not, we'll give an error of not enough ETH. We have a way for them to enter, and we have a way to get the entrance fee. But we want to make sure that we're not ending the lottery before the lottery even starts, right? Or we're not entering a lottery when a lottery hasn't even begun. So we're going to want a way to iterate through the different phases of this lottery. And we can do that with what's called an enum or an enum. According to the Solidity documentation, enums are another way to create user-defined types in Solidity. We saw an earlier version of doing this with a struct. Enums are a little bit different in that they're explicitly convertible to and from all integer types. So what does that actually mean? Well, we can have an enum like this, action choices, go left, go right, go straight, and sit still. They're just more readable ways to say go left is going to be represented as state 0, go right is going to be state 1, go straight, state 2, sit still, state 3. So for our lottery contract, we're going to want to create this new type that represents the lottery state. So to do this, we'll do enum lottery state open, closed, and calculating winner. This means that we have a new type called lottery state with 3 positions, open, closed, and calculating winner. These different states are actually represented by numbers. So open is actually a 0, closed is actually a 1, and calculating winner is actually a 2. Now that we have this new type, we can create a variable of type lottery state. So we'll say lottery state, public, lottery state. And right when we initialize our contract here, we're going to want to set our lottery state to being closed. So in our constructor, we'll do lottery state equals lottery state dot closed. Now, since these are represented by numbers as well, we could also just do lottery state equals 1, because 1 stands for closed. However, it's much more readable to do lottery state dot closed. Now that we have a lottery state, in our enter function, we can require that the lottery state is going to be equal to lottery state dot open. So we can only enter if somebody's started this lottery. And that's exactly what we're going to do in our start lottery function. We're going to do a require in here that the lottery state is going to be equal to lottery state dot closed. And we can even add a failure function in here saying can't start a new lottery yet. And when we do start this lottery, we'll say lottery state equals lottery state dot open. Now, when somebody starts the lottery, they'll be able to enter. Of course, this start lottery bit here needs to be called only by our admin. So this is where our only owner modifier is once again going to come into place. We could write our own only owner modifier, or we can once again use OpenZeppelin's access control and OpenZeppelin's ownable function instead, which is what I'm going to use here. So we're going to go ahead and grab this, copy this, paste it in, import at OpenZeppelin/contracts/access/ownable. And of course, since we're doing this, we're going to have to add this dependency into our config. We're going to be using OpenZeppelin/OpenZeppelin contracts at 3.4.0. We're going to remap at OpenZeppelin equals this. Oops. And then we'll say our lottery is ownable. Perfect. Now we'll try to compile this. Awesome. Looks like Brownie grabbed everything correctly and we're good to go. Great. Now we can finally move into our end lottery function. This is where we're actually going to choose a random winner here. We only want the admin to be the one to actually end the lottery, so let's add the only owner modifier here. And let's talk a little bit about randomness, because this is what we're looking to do now. We're looking to get a random winner here. Now, as you know, the blockchain is a deterministic system, right? And this is super advantageous because it allows us to do all these smart contracts and have this system that can actually reach consensus very easily. Random numbers are much harder. If, let's say, you had a blockchain with a whole bunch of different nodes and each node responds and gives their own random value, well, each node is never going to be able to sync up and say, hey, we all agree on a random number. What you could do is you could base the random number on some other attributes in the system, but then it's not really random. It's actually going to be pseudo-random. So getting truly random numbers in a deterministic system is actually impossible. And if you know a lot about computer science, you actually know that even when you call like math.random in your JavaScript, what your computer is really doing is it's looking at some place in memory, grabbing some value and saying, hey, this is probably random enough. Here, go ahead and use this. Now in smart contracts, especially when working with any type of financial application such as a lottery, having an exploitable randomness function means that your lottery is at risk of being hacked or destroyed. And this isn't even a fairy tale. At the time of recording, about 2 weeks ago, I did a rundown on an exploit where a protocol used insecure randomness and got hacked for $700,000. So I am going to show you this insecure way first. And the reason that I'm going to show you is that it is a quick and dirty way to get a pseudo random number, but please do not use this in any production use cases. I'm going to show you a method that's often used to teach people how to get random numbers, and then we're going to explain why it's so vulnerable and not a good method of randomness. And what some insecure protocols will do is they'll use a globally available variable and hash it. So in your smart contracts, there's actually a number of globally available variables. One of those, as we saw above, is going to be message.value, right? It's going to be the value that's sent with a transaction. Another globally available variable is going to be message.sender. You can actually see a whole list of these different globally available variables in the Solidity documentation here. So since there are all these globally available variables, a lot of times someone will see something like block.difficulty, which returns the current block difficulty. Now, one of these globally available variables is going to be block difficulty or block.difficulty. It's the current block difficulty. Remember how I said that the time between different block generation is called the block time? Well, you can always keep that block time as is by changing the block difficulty over time. The harder the problem or the harder the proof of work algorithm, the longer it's going to take, or the more nodes you're going to need to solve that problem. There's this constantly recalculating metric called Ethereum difficulty or block difficulty, depending on the chain that you're working on, that constantly changes. So you might think this would be a great use of randomness, right? Because it's a somewhat hard to predict number. So what a lot of people do is they think that, hey, those sound pretty random. Let's use them as a unit of randomness. And what you'll see like something like uint Kachak 256, which is, again, this hashing algorithm. And they'll do something like abi.encode packed nonce message.sender, block.difficulty, block.timestamp, mod, players.length. So I know there's a whole lot going into this line, and let's talk about it. So first, as we can see, is that we're casting, or we're converting everything in here to being a uint256. The reason that we're doing this, of course, is because we're going to want to pick a random winner based off of an index, right? We're going to want to pick some random winner in our players array or our players list. So we say, okay, whatever number that we're going to use, that's going to be the index of the winner that we're going to randomly pick. Then they use kachek256, which is, again, our hashing algorithm. So they hash a whole bunch of variables together. And they do this abi.encode_pact. ABI is another keyword for some low-level work. They'll add maybe a nonce in. They'll add the message.sender, block.difficulty, and block.timestamp. Basically, what they're trying to do here is take a bunch of seemingly random numbers, mash them all together in a hashing function, and then say, yeah, this is pretty random. But the issue here is that the hashing function itself isn't random. The hashing function is always going to be exactly the same. Kachek256 is always going to hash everything exactly the same way. So we're not actually making it more random by hashing it. All these numbers inside are the pieces that actually determine how random it is. So if the block.difficulty is random, then this will be a random method. If the block.difficulty isn't random, then this won't be a random method. And the block.difficulty is not random. Difficulty can actually be manipulated by the miners. And timestamp is predictable. Nonce is predictable, aka transaction number, because in this regard, they're using the nonce as some transaction number. And message.sender is predictable. When using a random number in this way, the hashing algorithm is always going to be the same. uint256 is always going to be the same. We have a predictable number, a predictable address, a predictable timestamp, and then a manipulatable value. So all this is really doing is giving the miners the ability to win the lottery or win whatever lottery that you're working on. So this isn't going to be an effective way to get a random number. This is an unacceptable way to get a random number in our applications. Yes, we do have this only owner modifier here, which means that we are the ones who are going to choose when to call this. So it is still centralized in that regard. But let's just teach you the best practices for working with random numbers right from the get-go so you don't run into any issues. I'll explain what this part is doing in a little bit. In order to get a true random number, we are going to have to look outside the blockchain. The blockchain itself, like I said, is a deterministic system. So we need a number outside the blockchain. But what we can't do is we can't use just an API that gives a random number, right? If that API becomes corrupted, if they're malicious, if they go down, if something happens, etc. What we need is a provable way to get a random number. And Chainlink VRF is actually that solution. Chainlink VRF stands for Chainlink Verifiably Randomness Function. And it's a way to get a provably random number into your smart contract. It has an on-chain contract that checks the response of a Chainlink node to make sure the number is truly random. Using some cryptography magic, it's able to check a number of the parameters that the Chainlink VRF started and ended with to make sure that it's truly random. It's already used for protocols like Avagochi, Ether cards, Pool Together, and a whole bunch of other protocols as well, because it is a secure, reliable, truly provable way to get a random number, which is incredibly powerful in a decentralized system. So that's how we're actually going to get our random number here. So let's work on getting that. What we can do is we can go ahead and head right over to the Chainlink documentation to actually learn how to work with one of these. Let's go over to the Chainlink documentation just to make sure that we get it right. So if we go to the get a random number here, we have all the documentation you could ever want. So if you ever get lost or confused, you can always come right back here to work with it. What we're going to do is we're going to deploy their simple version in Remix version of working with the Chainlink VRF. And we're going to walk through a minimalistic contract to see how it actually works in a contract. So once again, we'll hit this Remix button, Remix pops up, and we immediately get this random number consumer.sol in our files that we can check out. So awesome. So here is our files right here. We can see that this is actually using a different chain than what we've been using. We've been mostly working with Rinkeby, but For this demo, it's actually on Coven. So we can do some work with Coven here. And remember, if you do want to stay with Rinkeby, you can always go to this contract addresses section of the VRF and grab these addresses to use. So what's going on in this contract? How do we actually use this? Well, as you can see, the first thing that happens is we're importing some code from the Chainlink package. And our contract is inheriting the abilities of this VRF consumer-based contract. So we're going to see what functions we're actually going to use that are inherited from this contract. And the first thing that we notice is we can see that our constructor in here does some weird stuff. It looks like it almost has two constructors. So what's actually going on here? Well, let's look at this VRF consumer-based.sol contract in the Chainlink GitHub. So we can come to the Chainlink GitHub here. We'll go to EVM contracts, or depending on when you're watching this, it's migrating to contracts at some point. We'll go to EVM contracts. We'll go to SRC. So once we're using v0.6, we'll go there. And we'll look at this VRF consumer-based.sol. As we can see, this VRF consumer base that we're importing has its own constructor. And it takes an address for the VRF coordinator. This is the on-chain contract that actually checks to make sure our numbers are random. And the address of the Chainlink token, which we'll talk about ERC20s in a little bit. What we're doing is we're also inheriting the constructor into our contract. So this is our constructor for our random number consumer, but we can also use the constructor of the VRF consumer base. And this is actually how we go ahead and do that. We grab the constructor of the VRF consumer base and plop it in here. Now it's taking two addresses. It's taking the VRF coordinator and the link token. Like I said, the VRF coordinator is a contract that's been deployed on chain that's going to verify that the return of the Chainlink node is truly random. And we're going to use the link token as a payment to the Chainlink node for its services. And then we'll also have a key hash and a fee defined inside of this constructor as well. The key hash uniquely identifies the Chainlink node that we're going to use. And then the fee is how much link we're actually going to pay to the Chainlink node for delivering us this random number. Now let's talk about a couple things here. In Ethereum, whenever you make a transaction, you have to pay some ETH gas, right? Or transaction gas. This is to pay the smart contract platform a little bit of ETH for performing our transaction. With a smart contract that operates with an oracle, we have to pay some link gas or oracle gas. This is to pay the oracles a fee for their services for providing data or doing some type of external computation for our smart contract. The question that might then follow up is, oh, okay, well, how come I didn't have to pay when we did this price feeds thing? Well, for price feeds, somebody had actually already paid for the data to be returned. And if we go to data.chain.link and we scroll down, we can actually see a list of sponsors here that are paying to get this data delivered. So they're already paying the oracle gas to bring this data on chain for us. Since no other protocol is getting a random number for us, we're actually going to have to pay the oracle gas here. Now, in this contract, we have a function called getRandomNumber, which is going to return a bytes32. And what it's going to do, it's going to call this requestRandomness function, which is inherited from this VRF consumer base. If we look in here, we look for requestRandomness, we can see there's a function right here called requestRandomness. This function is going to send our oracle fee or the link token, and it's going to call this specific to the link token function called transfer and call. This function is going to call a Chainlink node. Now I'm not going to go into exactly how it's doing that right now, but we will talk about it in a little bit. So we call this requestRandomness function, and we send the key hash and the fee. Remember, the key hash uniquely identifies the Chainlink node, and the fee is going to be how much oracle gas we're going to pay. If you ever get lost on how much to pay or what the contract addresses are, you can always head over to this VRF contract section and see where the most recently deployed VRFs are, how much the fee is, etc. Now here's where it gets a little bit interesting. Getting a random number actually follows what's called the request and receive style of working with data. Let's go ahead and just try this out, and I'll explain what this means once we see it. Now we're going to save the answer to this random result variable here, and let's just go ahead and try this and see what happens. So we're going to switch to our injected Web3. And since we're now swapping to a new test network, this means that we have to get testnet ETH and testnet Link again. We can always look for the Link token contracts page to find the most up-to-date faucets. So we'll scroll down, we'll find Coven. Looks like this is the testnet Link faucet and the testnet ETH faucet. So here's our Coven faucet. We'll just want to switch from Rinkeby to Coven. We'll grab our address, paste it in, send me 100 test link. Here's our transaction. We can see we're transferring some ERC20. We'll take this contract address, we'll add it to our MetaMask by copying the address, scrolling down to add token, pasting it in here. I already have the address in here, so I'm just going to go ahead and hit cancel for now. And we'll also want some testnet Coven Ethereum, which looks like this faucet has it. So we'll paste the address in here. I'm not a robot. And we'll do send me 0.1 test ETH. And perfect. Now that we have some testnet Ethereum and some testnet Link, we can proceed. We're going to make sure we're on the Coven test network, and we're going to deploy our random number consumer gist here. Let's go ahead and hit deploy. MetaMask pops up. We're going to go ahead and confirm. I didn't explain this fulfill randomness function intentionally. You'll see why in a second. And great, our random number consumer comes up. Let's check what our random result is right now. It's obviously 0 because we haven't got a random number. So I'm going to do something intentionally wrong because there's a good chance that you'll run into this at some point. If I hit get random number right now, we see this error gas estimation failed. We have plenty of ETH. Why would this fail? The reason that it's failing is because the contract doesn't have any Oracle gas. So we got that gas estimation failed because we need to fund this contract address with some link to actually get a random number. So we're going to hit this copy button, and this is going to copy the address. And we're going to come into our MetaMask here, and we're going to send this address. We're going to paste it there, swap to link, and we'll send it one link. This is probably overkill because, as you saw, the fee is only 0.1, but we're just going to be overkill for now. And great, now that this contract has some testnet link, now we can call this get random number button because we can actually pay the Chainlink node to actually return our random number. So we're going to go ahead and do confirm. And this is fantastic. So we're paying a little bit of transaction gas to make this transaction, to make this request. And then we're paying a little bit of Oracle gas to make this transaction. Now, so the transaction confirmed, but if I hit random result now, it's still going to be 0. So why is that? What's going on? Well, getting a random number like this actually follows what's known as the request and receive cycle of getting data. You can read more about it here in this basic request model in the documentation. So in one transaction, we actually request some data, or in this case, a random number. And then in a second transaction, the Chainlink node itself will make a function call and return the data back to the smart contract. In this case, the function that we're calling is fulfill randomness. It calls this fulfill randomness with byte32 request ID, which is going to be the request number of when we call this, and it's going to return with this random number called randomness. So after we wait a little bit, if we hit random result now, we can see indeed our random number is in here. And again, the reason that it's in here is because we actually had 2 transactions occur. One paid by us when we called get random number, and one paid by the Chainlink node when it called fulfill randomness. Now, I lied to you a little bit. Technically, that VRF coordinator contract calls this function, and then the Chainlink node calls the VRF coordinator function, but for simplicity's sake, you can kind of just think of it as the Chainlink node itself is calling this fulfill randomness function. So now that we know how to do this in Remix, let's go ahead and add this to our Brownie project. So actually, before we even do that, we need to require. So before we even get a random number, let's change the state of our lottery. So now we'll do lottery state equals lottery state dot calculating winner. And while this is happening, no other functions can be called, right? This will lock out. Nobody can start a lottery and nobody can enter a lottery while we're calculating the winner. Awesome. So now that we know a little bit more about random numbers and everything that we're doing here, let's go ahead and try implementing this now. So in our Chainlink smart contract docs, of course, we're going to scroll down. We're going to go to our get a random number bit here. We can copy and paste all this code as well into our smart contracts. So the first thing that we're going to need to do, of course, is import the VRF consumer base code. Let's move back over, scroll to the top, and we'll just paste this in at Chainlink /contracts/src v0.6 VRF consumer base, and we'll inherit this into our lottery contract. So we'll say the lottery is VRF consumer base, and it's ownable. Let's take a look at this VRF consumer base in the Chainlink GitHub here. If we scroll down to the constructor of our VRF consumer base, we can see it takes these two parameters, the address of the VRF coordinator and the address of the Chainlink token. We can use a constructor of a contract inherited in our contract inside our constructor. So what we'll want to do is we'll want to come down to our constructor, and right after this public keyword, we can add any additional constructors from inherited smart contracts. So we'll say constructor, and this is our normal constructor, and then we'll put VRF consumer base. And we'll add the VRF consumer base addresses in here. We know that it's going to be a VRF coordinator address and a link token address. Similar to the price feed, these two addresses are going to change based on the blockchain that we're on. So it'll probably make sense for us to parameterize them the same way we parameterize the price feed address. So in our top level constructor parameters, we'll add an address for the VRF coordinator, and we'll pass this to the constructor of our VRF consumer base. Then we'll also grab an address for the link token. So we'll do address, link, and we'll pass this to the VRF consumer base constructor as well. Great. What else do we need to make this work? Well, back in the documentation, we can see we need a fee and a key hash. The fee is associated with the link token needed to pay for this request. So we'll make a public variable, uint256 public fee. Since this might change blockchain to blockchain, we'll have this as an input parameter as well. So we'll do uint256 underscore fee, and in our constructor, we'll do fee equals underscore fee. We'll set our global variable to fee. And I need a comma here and no semicolon here. What else do we need? Well, we need a key hash. The key hash is a way to uniquely identify the Chainlink VRF node. So we'll create another one. We'll do bytes32 public key hash. We'll add this as a parameter in here. Bytes32 key hash. And then we'll say key hash equals underscore key hash. Perfect. Our contract is coming along great here. Now that we have the main pieces that we need, how do we then request this random number? Well, if we scroll down in the documentation, we can see we have this request randomness function that we need to call. If we scroll back to our VRF consumer base contract, this request randomness function is a built-in function from the VRF consumer base. So our contract can natively call this request randomness function right in our contract. And you can see it takes a key hash and a fee as its parameters. So right in our end lottery function, we can add this function. And we can see this also returns a bytes32 called request ID. This return syntax is pretty powerful. You can actually identify the name of the variable you want to return right in your function declaration. So by saying bytes32 request ID, we're saying we're going to return a bytes32 variable named request ID. So right in our function here, we can do request randomness, because again, that's this function that we're importing, passing it the key hash and the fee. This will return a bytes32 called request ID. So this is actually doing this and having our function declaration tell us that there's going to be a variable named request ID is going to be exactly the same as if we did bytes32 request ID equals request randomness. Now, this function call follows, again, what we've talked about as the request and receive mentality, the request and receive architecture. This means that in this first transaction, we're going to request the data from the Chainlink Oracle. In a second callback transaction, the Chainlink node is going to return the data to this contract into another function called fulfill randomness. So again, if we look back in our VRF consumer base, we can see it has this function raw fulfill randomness. We can read some of the comments in here saying raw fulfill randomness is called by a VRF coordinator when it receives a valid VRF proof. Raw fulfill randomness will then call fulfill randomness. So there's a little bit of contract tag going on, but it's going to eventually call this fulfill randomness function, which is going to be what we define in here. And that's how our contract is going to know what to do once it gets the random number back. So in our first transaction, we're going to end the lottery, request a random number, and then in a second transaction later on, once the Chainlink node has created a provably random number, it's going to call a second transaction itself based off of what we define. We just have to call it fulfill randomness. And as you can see, it takes a byte 32 request ID and a random number. So in here, we'll do fulfill randomness, takes a byte 32 request ID, and then a uint 256 randomness. We don't want anyone else to be able to call this function. We only want our Chainlink node to call this function so we can return a truly random number. So we're going to make this an internal function. It's internal because actually the Chainlink node is calling the VRF coordinator, and then the VRF coordinator is calling our fulfill randomness. So we'll make this internal so that only the VRF coordinator can be the one to call and return this function. And then we're going to give it a keyword of override. This override keyword means that we're overriding the original declaration of the fulfill randomness function. Our VRF consumer base has a function fulfill randomness defined, but it doesn't have any parameters or anything about this function actually laid out. This function is meant to be overridden by us, and that's exactly what we're doing right here. So in this fulfill randomness function, let's go ahead and define what's going to happen once we get this random number back. So before we can process this random number, let's just check to make sure we're even in the right state. So we'll do require. Our lottery state is going to be equal to lottery state dot calculating winner. And if we're not in that state, we'll just say you aren't there yet. My auto format is on for this one, so it's jumping in. Then let's just do another check to make sure we actually get a response. So we'll do require underscore randomness is greater than 0. And if it's not, we'll just say random not found. Now we need to pick a random winner. Well, we need to pick a random winner specifically out of our list of players, our list of payable public players. So our players array is just a list of players. So it's like player 1, player 2, player 3, player 4, and they're each at a different index. What we can do then to pick a random winner is to do what's called a modulo function. In fact, let's even open Remix to do an example of this. Remix, let's pop open a new contract. We'll call it mod.sol. We'll do pragma Solidity caret 0.6.6. We'll do contract mod. And in here, we'll do a constructor, blank constructor, and we'll get a global variable, uint 256, number, and we'll set it equal to 5. And we'll go down to 0.6.6. We'll save, compile. And let's even just get rid of the constructor. Let's now create a function called doMod. We'll take a uint 256 mod value, make this a public function. Public view returns uint 256, and we'll just return 5 modulo mod value. Now let's go to JavaScript VM. We'll deploy this. We'll go in here. So our number is right now 5, and let's learn about how the modulo works. If we have this doMod function, what we're doing is the module divides by the number and returns the remainder. For example, if we did 5 mod 5, what do you think we're going to get? So we're going to do 5 divided by 5 and then return the remainder. Well, 5 divided by 5 is 1, and there's no remainder. There's no decimal there. So 5 mod 5 should be what? 0. Exactly. Well, what's 5 mod 4 then? Well, 4 can go into 5 evenly once, but there's one number left over. So 5 mod 4 is going to be 1. 5 mod 3 is going to be 2. 5 mod 1 is going to be 0, right? Since 1 goes with everything. This is how the mod function works, and it's this little percent here. We can use that mod function in our fulfill randomness with the length of our players. So we can say uint 256 index of winner is going to be equal to the random number that we got modded by the players dot length. So let's say, for example, we had 7 players sign up and our random number was 22. Well, we want to get one of these random 7 players. So we would do 22 mod 7. 7 divides evenly into 22 3 times with 1 left over. 7 times 3 equals 21. Difference between 21 and 22 is 1. 7 times 4 is 28. So we know, this is how we know we've reached our upper limit. So this is how we can get a random number based off of the index. Now that we have this index, what we can do is we can say the winner equals players of the index of winner. And just to keep track, let's make a new variable called recent winner at the top. We'll do address public recent winner. We'll grab this recent winner. Instead of winner, we'll say recent winner equals players in this index of winner here. Now that we've got a winner wallet, we want to pay them all of the money gathered from our enters here. So what we can do is we'll do this recent winner dot transfer the entire balance of this address. So we'll say address of this dot balance, and perfect. We'll transfer them everything that we have. Then of course, we're going to want to reset the lottery so that we can start from scratch. We can start blank again. So we'll do players equals new address payable array of size 0. So we're just resetting players to just be a brand new array. Then we're going to change our lottery state to being lottery state.closed because the lottery is now complete. And I often also like to keep track of the most recent random number. So at the top, I'll do a uint 256 public randomness variable. And in our fulfill randomness, I'll say randomness now equals underscore randomness. And perfect, we now have a contract here. Of course, we haven't actually tried it out, but we're assuming that it works great. So you know what this means. It's time to go into testing mode, testing and development mode. But let's even just try to do a Brownie compile first. Looks like we have an issue here. Send and transfer are only available for objects of type address payable, not address. Oops. Looks like we made our recent winner just an address, but it needs to be an address payable. So let's try Brownie compile again. And beautiful, we at least know it's compiling, so that's a great sign. Let's now move into our testing and development phase. As you are starting to figure out, we can ignore these file import callback not supported bugs in VS Code for now. I'm sure the Solidity linter will get better as time progresses. But great, so now let's go ahead and move into actually testing and working with everything here. So let's go ahead into our scripts, and we'll make a little deploy script first. Let's do a new file. We'll call it deploy lottery.py, and let's go ahead and deploy our lottery. So same as always, we'll do def main. we'll come up with a new function called deploy lottery. And then we'll do def deploy lottery. And then we'll just have it pass for now. And if we run this, Brownie runs scripts, deploy lottery.py. Our default network is not defined, which means the default is going to be development. We can even be verbose here, development, write that in our Brownie config. Run this, a ganache will get spun up, and nothing will happen because our deploy lottery function doesn't do anything right now. Awesome. The first thing we need always to deploy a contract is we need an account. So we'll do account equals, and we've been using this get account function for some time that we've been adding in a helpful script section so that it can pull from a real testnet or from a local development environment if we like. So to do this, of course, let's create our new helpful scripts.py. We'll create our init__init__.py so that Python recognizes it as a package. And in here, we'll create a new function, def get account. For now, we'll just have it pass. We'll copy this into our deploy lottery. We'll do from scripts.helpful scripts import get account. Now this is what our get account looked like in our last project. Along with that, we had these forked local environments. We also had from Brownie import accounts and network and config to make this look really nice, right? Let's flesh this out just a little bit more so it's even more robust. Right now, as we know, we have a way to use Brownie's ganache accounts, and we have a way to use our environment variables. However, there was a third method that we learned that isn't identified here, accounts.load. And this is with our ID. If you still have your account and you still have all your Brownie set up, if we do Brownie accounts list, you'll see we have a couple accounts here. We want our get account to be even more liberal so that if we wanted to use one of these as well, we could. So let's modify our get account script here a little bit. Let's first get rid of this else and rid of this indent. What this will do is this will be our default. If nothing that we define prior to this is defined, we'll just default to grab right from our config. Which, since we are doing that, let's create our .env. We'll paste our different variables in here, our private key, Web3 Infura, and Etherscan token. And in our Brownie config, of course, we'll do wallets, from key, private key. And now let's flesh this out a little bit. Let's add an index and an ID. Index equals none, and ID equals none. This way, if we pass an index to our getAccount function, we'll just use an index from this accounts variable. If we pass an ID, we'll have trying to do this accounts.load here. So now let's change this up a little bit. We'll say if an index was passed, we'll just return accounts on that index. Otherwise, if we're doing a local blockchain, we'll just return accounts 0. But if there's an ID, we'll return accounts.load ID. Whoops, we need to actually move this up a little bit so that it's before our local blockchain checking. So now in our deploy lottery, we could do something like get account ID equals free code camp. Whoops, and this is actually free code account. Free code camp account. Let's try one more time. It's going to ask for our password here. Now we have a much more liberal get account function. So now that we have account, we can actually deploy our lottery. So we'll say lottery equals lottery.deploy. And this is where we're going to import from Brownie, import our contract lottery. And we're going to have to add in all of these different variables. So if we go back over to our lottery contract. We need to give it a price feed address, a VRF coordinator, a Chainlink token, a fee, and a key hash. Now, the way we did that in FundMe is that we did it in a way where we checked to see if we were on a local chain or not. If we weren't on a local chain, then we would just pull our addresses directly from our config. If we weren't on a local chain, though, we'd deploy some mocks and use the address of those mocks. We're going to want to do the same thing here, but let's make our lives a little bit easier. We can take this whole process and put it into its own function. So let's make this a little bit easier mentally. The first thing that we're going to need is this price feed address. If we're on a real testnet, of course, we would just go into our Brownie config and add the address, which we will do. We'll add our RINC-B network here in a little bit. But for now, don't worry about that. But if we're not on a RINC-B chain, what we're going to need to do is deploy our mock. We're going to wrap all of this mocking and checking into a single function called getContract. And we're going to add this function in our helpful scripts. So let's create this function called getContract. So we'll do def getContract. Pass. And let's talk a little bit about what we want this function to do. Let's add 3 double quotes here and 3 double quotes here to start what's called a doc string. This will define everything about this contract. So we're just going to say this function will grab the contract addresses from the Brownie config if defined. Otherwise, it will deploy a mock version of that contract and return that mock contract. For the arguments of this chain, we're going to take a contract name. This is going to be a string, and it'll return a contract. Or in particular, it's going to return a brownie.network.contract.project contract, the most recently deployed version of this contract. So for example, if we have a mock v3 aggregator contract, it'll do the most recently deployed version of that with this -1 syntax. Now this getContract function, if this is a little confusing to you, again, we're going to go over this Chainlink mix in a little bit. And inside of this, it has a more robust description of what's going on in this getContract bit. So you can check that out if you want to learn more. But let's go ahead and actually define this. So we obviously want a contract name as an input parameter. So let's go ahead and add contract name in here. Meaning that this getContract function will get something like ETHUSD price feed, right? That's going to be the same as what's defined in our Brownie config. And from this name, we're going to get the type of contract that it is. Contract type. And to do that, we're going to have to create some mapping that'll map the contract names to their type. So right above, we're going to do contract to mock. And we're going to create a mapping in here, which will map everything out. So an ETHUSD price feed is going to be of type mock v3 aggregator. So we're going to have to import mock v3 aggregator from Brownie. So now we're saying anytime you see ETHUSD price feed, you know that that's going to be a mock v3 aggregator if we need to deploy a mock. So we'll say contract type is going to equal contract to mock of the contract name. Now we need to check, okay, do we actually even need to deploy a mock? So sure, let's check if we're on a local blockchain. So we'll say if network.showActive is in our local blockchain environments, and we'll skip the forked local environments because, again, we don't need to deploy a mock price feed address on a forked local environment. We'll say if network.showActive is in the local blockchain environments. Then we'll check to see if one of these contracts has already been deployed. We'll say if the length of contract type is less than or equal to 0, then we're going to go ahead and deploy mocks. So this is equivalent to doing something like mock v3 aggregator.length. We're checking how many mock v3 aggregators have actually been deployed. If none have been deployed, we're going to go ahead and deploy them. So we're going to have to create this deploy mocks function. So we'll do def deploy mocks. And this is going to be the same as what we did in our Brownie fund me, right? It's going to be the exact same. So we'll say account equals get account. I'm not going to put the prints in here, but you absolutely can. We'll say mock price feed equals mock v3 aggregator deploy. We'll need to give this some decimals and an initial value. So right above, we'll do decimals equals 8. Initial value equals 2000. 2000. 1, 2, 3, 4, 5, 6, 7, 8. And in our deploy mocks, we'll say decimals equals decimals. Initial value equals initial value. To deploy decimals and initial value. Of course, this is going to be from account. And for now, that's it. We'll just say print deployed. All right, great. So now we have a way to actually deploy the mock price feed here. So let's go back up to our get contract function. So we have a way to deploy the mock if one already isn't deployed. Now what we're going to want to do is we want to get that contract, right? We're going to want to get that mock. So we'll say contract equals contract type -1, right? So this is going to be equal to doing mock v3 aggregator -1. This is saying, hey, let's grab the most recent deployment of the mock v3 aggregator, which is exactly what we want. Perfect. So this will work perfectly for our development context. However, we're not always going to just want to deploy to a development network. We're also going to want to deploy to testnets. So then we'll say else, and this is where we'll just grab that contract from the Brownie config. For example, ETHUSD price feed. So we'll say contract address equals config networks network.show active, and that contract name. For example, again, if it's ETHUSD price feed, it'll be ETHUSD price feed here. And the way we're setting it up, it's got to be the same as what's in our contract to mock dictionary here. So up here, the way that we did it was we actually got the contract because we had its contract type based off of Brownie. For here, we're going to have to interact with the contract, getting those two pieces that we always need, which are going to be the address. We actually have the ABI from our mock v3 aggregator type right here, and we just got the address. So we can create this new contract type by saying contract equals contract dot from ABI, and this contract package can be imported right from Brownie, and it has this function from ABI that allows us to get a contract from its ABI and its address. So we'll just give it a name. We can say contract type dot underscore name. We can do the contract address, and then the contract type dot ABI. So these mock v3 aggregators and all these contracts have a .ABI attribute that returns the ABI. They also have a ._ name, which returns their name. So this is perfect. This is how we'll get the contract otherwise. And then at the end of all this, we'll just do return contract. Awesome. So this is an incredibly powerful function for us to get a contract based off of if it's already deployed as a mock or it's a real true contract. I know there's kind of a lot here, but definitely check the GitHub repository if you're a little bit confused on what's going on with this function. And let's also just deploy this to make our linter happy. Why not? Yay, VS Code's happy now. But now that we have this function, let's go back to our deploy lottery. Now we can do a comma, get account, and now we have a get account function. So let's go through this again. This lottery.deploy get account is going to get an ETHUSD price feed. If we don't have a mock deployed, it's going to deploy a mock price feed for us, and we're going to return that mock price feed. However, if we're on a test net, if we're on a real network, we're going to grab its actual address and return a mock contract of it. Our mock contract here has all the same functions of a regular contract, so we can just use it as the same. This way, we don't have to adjust this function for whether or not we're deploying to a testnet or to an actual address. The only additional piece we should put in here, just for clarity, is we should add .address here, because this is going to return the actual contract, and we really only want the address. This is going to make our coding a lot more robust for moving between development environments and testnet environments and working with scripts in a really effective manner. So now that we have this incredibly powerful function, let's go back to the lottery and figure out what are the different pieces we need in here. Okay, great. We also need a VRF coordinator. So to do this, we're going to go back to our docs.chain.link. We'll go to contract addresses, and we could do mainnet here, but let's also just set this up to work with RinkB. So we'll do Control F for RinkB. VRF coordinator is going to be this address right here. So we'll copy it. We'll go back, and we're going to have to do in our config is we're going to have to add a new network here for RinkB. We'll do VRF coordinator. Will be that address right there. And then while we're doing this, let's also get the RinkB address for our price feed. So Ethereum price feeds, RinkB. Let's scroll down for ETHUSD. ETHUSD, here we go. Grab that, enter. And this will be ETHUSD price feed. Paste that address in here. Perfect. So now we can do get contract VRF coordinator .address. Of course, we are going to have to go back to our helpful scripts because there's currently no mapping between what a VRF coordinator is and what its mock needs to be. So we'll add a comma here, and we'll do VRF coordinator, and we need to get a mock VRF coordinator. Well, first of all, we don't even have our mock v3 aggregator, so let's go grab that as well. So we can grab both of these. Again, I'm going to highly recommend going to the Chainlink mix, going into the contracts here, going to the test folder for these different mocks, because these are already set up to work with the Chainlink mix. However, you can definitely go into the Chainlink GitHub as well. Go to contracts, SRC 0.6, tests, and then look for the different mocks in here. So mock Oracle, VRF coordinator mock, etc. So I'm just gonna grab it though from this Chainlink mix. So let's go to VRF coordinator mock, and I'm just gonna grab this whole thing here. So do contracts, new folder, test, new file, VRF coordinator mock.sol. Paste it in here. And then while we're in here, we'll want to do a new file, mock v3 aggregator.sol. We'll grab this as well from our Chainlink mix. Again, it's got all the functions of a price feed, update answer, latest round, etc. VRF coordinator mock has different functions for actually working with the VRF coordinator. One of the specific ones in particular is this callback with randomness that we're going to use in our tests. So our VRF coordinator is going to get mapped to our VRF coordinator mock, which will also import this from Brownie. Great, and just to double check everything's working, we'll want to run just a quick Brownie compile to make sure we are importing our mocks correctly and everything's compiling, so it looks like we're good there. All right, so now we have get contract VRF coordinator.address. Perfect. What else do we need in here? We need a link token. The Chainlink token is, of course, just another smart contract. So we're going to do the exact same thing here. Get contract link token.address. Of course, this means in our config for RinkB, let's add a link token address. We'll go to the Chainlink documentation. We'll go to link token contracts. We'll look for RinkB. We'll grab this address. We'll drop it in here. Perfect. Now we have it in our Brownie config. We'll also need to add it to our helpful scripts. So we'll need a mock link token, which again, we can just go ahead and grab from our Chainlink mix here. So we can go to test. And as you can probably see, what I often normally do is literally just copy this entire test folder project to project. So I'm going to copy this whole thing, create a new file. We're just going to call this one link token.sol. Contract link token, perfect. And then in our helpful scripts, we're going to have this be link token. And of course, we're going to import this from Brownie. Great. Get contract link token.address. Perfect. What else do we need? We need a fee and a key hash. So the fee and the key hash are both just numbers, right? These aren't actually contracts. So we don't need to put this through that get contract bit. What we can do is just in our config, in our development network, we can just add a default for the key hash and for the fee. I'm just going to set my development key hash and fee equal to the RINKB ones. So to grab those, we'll go to the Chainlink docs once again. We'll scroll down to using randomness, contract addresses. We'll look up RINKB. We'll grab the key hash here, which we'll paste in for both our development and RINKB. And then the fee, it says 0.1 link. So we'll just do that in way here, which will be 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7. And we'll do this line for RINKB as well. Now in our deploy lottery, we can just grab this directly from our Brownie config because we're always just going to have this default key hash and this default fee here for our development network. So we'll do config networks network.show active. Which one's first? The fee. Of course, this means we're going to have to grab network from Brownie and also config. Then we'll do config networks network.show active key hash. And then of course, our last bit here, from account. And then additionally, as we learned last time, if we want to publish this, we'll do publish source equals config networks network.show active. We'll say .get verify, and then we'll add this false bit here. What this is saying is get that verify key, but if there's no verify key there, just default to false. This way, if we don't set a verify key in development, that's fine. It just won't get verified. For RINKB, let's go ahead and set verify to true. So we can actually verify this on the RINKB chain. And then we'll even do a print statement here. Deployed lottery. All right, lovely. Let's try this out. We'll do Brownie, run scripts, deploy lottery.py. We won't set a network flag, so it'll go to the default development network. Let's try this out. Things are compiling. Ganache is spinning up. It looks like we did run into a little issue here with our get contract function. Of course, we forgot to add deploying these mocks in our deploy mock script. Whoops. Let's go ahead and add that as well. Right now, our deploy mocks only deploys the mock v3 aggregator. So let's add the rest of our mocks in here. We're going to need to deploy a VRF coordinator mock and a Chainlink token mock. So let's open up those contracts, see what they need. The link token for a constructor doesn't have a constructor, so we can just have it be blank. So we'll do link token dot deploy, and all we need is a from account here. And then let's see what that VRF coordinator mock takes. VRF coordinator mock. It takes the link token as an address. Perfect. So then when we deploy the link token here, we'll say link token equals link token dot deploy, and then we'll do VRF coordinator mock dot deploy, and then we'll use the link token dot address as an input parameter, and then of course from account. All right, so now we're deploying all three of those mocks right away. Let's try this again. Brownie runs scripts, deploy lottery.py. Ganache is spinning up. Perfect. So we can see here that our mock v3 aggregator was deployed, then our mock link token was deployed, then our mock VRF coordinator was deployed, and then our lottery was deployed with those mocks defined. And we deployed the lottery. Awesome. Now we could 100% go ahead and then run this script on an actual testnet, right? Because our config is set up well. Let's write some more functionality for actually interacting with this lottery before we actually do that. And then we can actually just run a script which will do all this functionality end to end. Because again, deploying to a testnet takes a long time, and we really only want to do that when we're done and we're fairly confident that everything's working well. Let's even just delete this here. So now what's the next thing that we'd want to do here? What's the next thing we want to do in a script here? Well, we'd probably want to go ahead and start the lottery. So let's write a script that can actually do that. We'll do def start lottery. And in here, we'll get our account equals get account. We'll say the lottery is going to be the most recent deployment of the lottery. And we're going to call this start lottery function here. This is indeed changing state, so we do have to make a transaction. We'll do lottery. That's start lottery. We'll say from account. And then we'll do a little print and just say the lottery is started. And then in our main function down here, we can even call this start lottery function. So if we run this again on our development chain, we'll see if everything works smoothly here. Okay, we did run into an issue, and this is something that you'll see from time to time. Typically the workaround is you want to wait for that last transaction to actually go through. So we'll say starting transaction equals lottery.start lottery. Then we'll do starting transaction.wait 1. Brownie sometimes gets a little confused if you don't wait for the last transaction to go through. So let's try it again, and perfect. We do get this working as intended. So that is a really helpful tip if you run into those weird issues. You'll notice that even when we didn't have this, it still completed successfully. It just got a little confused at the end. All right, cool. So what do we want to do next? Well, we probably want to enter the lottery. Let's do def enter lottery. So how do we enter the lottery? We'll say account equals get account. Lottery is going to be lottery -1. We need to pick some value to send when we call the enter function, right? Because we need to send that entrance fee with it. So we'll say value equals lottery.get entrance fee. And just to be safe, I usually will tack on a little bit of way as well, because sometimes it might be off by like 1 or 2 or something like that. So we'll do lottery.get entrance fee plus, maybe something like this, which is like barely anything. Then we'll do transaction equals lottery.enter. We'll do from account. We'll send a value, which will be value. We'll do tx.wait, and then we'll do print. You entered the lottery. And we'll do this enter lottery bit down here too. Enter lottery. We'll run this, see if our enter script is working appropriately. You entered the lottery, looks great. And let's do our last function here. We'll do def end lottery. Count equals get account. Lottery equals lottery minus 1. We'll make a transaction, which will be lottery.end lottery. Now, before we actually end this lottery, we're going to need some link token in this contract. Because remember, our end lottery function calls this request randomness function. And we can only request some randomness if our contract has some Chainlink token associated with it. So we're going to need to first fund the contract and then end the lottery. Since funding our contracts with the link token is going to be a pretty common function that we use, let's go ahead and turn this also into a helpful script. So let's go to our helpful scripts. We'll make a new function called fund with link. And let's have this take a couple of parameters. So first, we'll want to have a contract address, of course. We'll want to know who we're going to fund with link. We'll set a default account to being none. So if you want, you can send an account, but you don't have to if you don't want to. We'll also do the same thing with a link token. We'll say if you want to use a specific link token, you can. Otherwise, we'll just grab it ourselves. And then we'll also do a default amount, which we'll set to 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, which is going to be 0.1 link. So first, let's get an account. We'll say account equals, and we're going to do a little clever Python stuff here. We'll say account equals the account if somebody sent it, if account. So we're saying the account that we use is going to be this account thing if this account thing even exists. Otherwise, we'll call our get account. Otherwise, we'll just do our regular get account function. Then we'll do the same thing with the link token. We'll say the link token is going to be equal to the link token that somebody supplies as a parameter if they applied something as a parameter. Otherwise, we'll just do that get contract stuff that we did before of the link token. Now that we have this link token contract from our get contract function, which again is basically the equivalent of doing this contract.from ABI on our link token, pulling from our config or from our mock, now we can just call the functions on this link token. So we can say our transaction equals link token.transfer. We're going to transfer token to the contract address with a certain amount. And of course, we'll do from account. We'll do tx.wait. And then we'll do print funded contract. And then we'll even return that transaction. I do, however, want to show you another way to work with this using the interfaces. Instead of doing this link token.transfer directly on the contract, we can use this interfaces section to actually interact with some contracts. So right now we have our mock link token in here, which is great because it has all the definitions and all the functionalities defined in here. Sometimes you're going to have contracts that you don't have everything. You don't have all the functionality, and maybe you only have the interface, maybe you only have some of the function definitions. So we can still interact with contracts with just an interface because, again, that interface will compile down to our ABI. So as another way of teaching us how to actually work with some of these contracts, what we can do is we can use the link token interface basically the same way as we use the link token contract here. So again, I'm in my Chainlink mix because there's already a link token interface in here. And this will compile down to a way that our Brownie package knows how to interact with these contracts. So if you wanted to, we could just grab this, go to our Brownie section. We'll do a new file in interfaces. We'll call it link token interface.sol. We'll paste it in here. Save my auto-formatted here. And what we can do in our helpful scripts instead is transaction equals interface. And we can also just import interfaces right from Brownie. Interface dot link token interface. And we just need to give it a contract address. So we can say link token dot address. We can say the link token contract equals interface dot link token interface link token dot address. So this is another way we can actually create contracts to actually interact with them. So we saw up here this contract.from API, which is great. This is another way we can do that exact same thing. So then we can just do link token contract.transfer contract address amount from account. So this is TX equals. So this is another way to actually interact with contracts that already exist. You're probably starting to see that Brownie has a lot of built-in tools that make it really easy for us to interact with contracts. If we have the ABI, we can just pop it into contract.fromABI. And again, with the address and the ABI, and then just give it some name. If we have the interface, we don't even need to compile down to the ABI ourselves because Brownie is smart enough to know that it can compile down to the ABI itself. And we can just work directly with that interface, which is incredibly powerful. For now, I'm going to comment these two lines though, and we'll just use the link token.transfer for now. Now that we have a funding script or a funding function, we can import this from our helpful scripts. From scripts.helpfulscripts, import get account, get contract, fund with link. And we can just call in our end lottery function, we'll do fund with link. And parameters, we only really need a contract address because the way we set this up, we'll just automatically grab a default otherwise. So we can say lottery.address, and that's it. And that's all we need. And then I know we're doing tx.wait right in the fund with link, but just to be verbose here, we'll get the transaction from the fund with link, and we'll do tx.wait here as well. And then once we're funded with link, then we can go ahead and call our end lottery function, because again, this is going to call that request randomness function from the Chainlink VRF. We'll do ending transaction equals lottery.end lottery. And all we have to do is from account, we'll do ending transaction.wait 1. So from our end, this is really all that we need to do, right? But remember, when we call this end lottery function, we're going to make a request to a Chainlink node, and that Chainlink node is going to respond by calling this fulfill randomness function. So we actually have to wait for that Chainlink node to finish. Now, typically it's within a few blocks. So normally what we can do is we can just do a time.sleep for something like 60 seconds. And typically in that time, the Chainlink node will have responded. So we'll just do import time at the top, time.sleep, and then we can see who that recent winner is, if that Chainlink node responded with a recent winner. So we can say print f lottery.recent winner is the new winner. All right, now, of course, for those of you who are thinking ahead a little bit, you might be thinking, hey, well, there's no Chainlink nodes watching our local ganache. And you're exactly correct. So what happens when we add our end lottery function to our main function here? Do you think that we're going to actually get a recent winner back? Why or why not? What do you actually think? Well, let's give it a shot. We'll do Brownie, run scripts, deploy lottery.py. So we're doing a lot of transactions here. We've started the lottery. We're entering the lottery. You entered the lottery. We're sending some link token. Now we just called the end lottery function. While we're waiting here, this is when the Chainlink node would go ahead and start responding with our randomness. However, as you probably astutely guessed, there's no Chainlink node that's going to call this fulfill randomness function right now. So for our Grenache chain, this will hypothetically end with nothing, right? Because there's no Chainlink node actually responding here. 0 is the new winner. Of course, this means that the Chainlink node actually didn't respond because there is no Chainlink node on our local Grenache. For our testing purposes, we're going to figure out how to actually get around that and deal with that. Awesome. It looks like we have everything set up to be successful in our lottery here. But we want to do our due diligence. We want to make sure that our tests are really solid on a development chain before we actually test this on an actual testnet. So let's jump into some of these tests. We've already started with this testlottery.py bit here, but we're going to iterate on this and make this even better. Now, before we get into these tests, there's a couple of things we want to talk about here. And that's going to be integration tests and unit tests. Unit test is a way of testing the smallest pieces of code in an isolated system. And we're going to use it to loosely define testing independent functions in our lottery contract. We also want to do what's called integration testing, which is going to be testing across multiple complex pieces. Typically, I like to run my unit tests exclusively on a development environment and my integration tests on a testnet. This is really helpful because we can test the majority of our application, like we said, on a development network, and then still be able to see what actually happens on a real testnet and see what happens on Etherscan and everything like that. Typically, what people do is inside their test folder, they'll create two different folders, one for unit and another folder for integration. Since for this demo, we're only going to have one file for both, I'm just going to go ahead and not create these folders, but it's a pretty common practice. Instead, what I'm going to do is I'm going to rename this. I'm going to hit enter to rename it. I'm going to do underscore, type unit for unit tests, and we're going to create a new file called test lottery integration.py. So this one, we'll do our integration tests, and in this one, we'll do our unit tests. Now, when writing unit tests, we really want to test, hypothetically, every single line of code in our smart contract. This is incredibly important, of course, because smart contracts are open to everybody to see and interact with. So we really want to test every single line of code we have in here. So let's go ahead and finish writing a get entrance fee test that will work on a local development network. As you can see, we're already going to have to refactor this from what we originally had. Let's go ahead and just delete everything under here for now. We already learned so much more from there. All right, so how are we going to test this get entrance fee function now? So first, we're going to want to deploy our lottery again. Since we have a deploy lottery script already, we can just use this deploy lottery script as well. If we wanted to, we could just copy paste this whole part into our test, but we're just going to go ahead and work from this deploy lottery script. So we're going to import this, and then we can actually even get rid of this from Web3 line for now. We can get rid of these two comments too. And we'll say from scripts.deploy lottery import deploy lottery. And on this deploy lottery function, we'll just say lottery equals deploy lottery, and we will return our lottery. Now, in a unit test, we'll say lottery equals deploy lottery. And this will give us our lottery contract. Once we have our lottery contract, we can just call this get entrance fee. So we can say entrance fee equals lottery.get entrance fee. And oops, let's just make sure we're doing the arrange act assert mentality here. And we're going to want to make sure this entrance fee is what we expect it to be. So what do we expect it to be? Well, again, our helpful scripts is going to deploy these mocks, right? It's going to deploy this mock, and the initial value is this 2000 number. So if the price of ETH here is $2,000 ETH feed, and the USD entry fee is 50, we'd say 2,000 over 1 is equal to 50 over X, which is going to be equal to 0.025. So we can go ahead and even do this math here. We can say expected entrance fee is going to be equal to 50 divided by 2,000. We'll just do 0.025, but we'll do this in way. So we'll do from Web3 import Web3. We'll say this is Web3.2 way 0.25 Ether. And now we'll assert our expected entrance fee equals the entrance fee. And now to test this, we'll do Brownie test-k. And perfect, this is working exactly as we anticipated. So that's awesome. Now, as we mentioned, since this is a unit test, we really only want to run this when we're working on a local environment, a local blockchain environment, or a local development network. So we'll go ahead and do this with PyTest again. Say if network.showActive is not in local blockchain environments, pytest.skip. Of course, we're going to have to import pytest. We're going to have to import this local blockchain environments from our scripts.helpful scripts. My VS Code automatically added that bit here. Now, if we try to run this, Brownie test -k get entrance fee -network rink eb. It should go ahead and skip this. Perfect, and that's what it does. What's the next piece that makes sense here? Enter is going to be one of the first things that these developers do. So let's do test def test enter. But let's even be more specific than that. We don't want people to be able to enter our lotteries unless the lottery is actually started. So let's make sure that this line actually works. So we'll call def test can't enter unless started. And again, we're only going to run this on a local development chain. So we'll just copy paste this section down here. We'll say lottery equals deploy lottery, because we're going to want to work with the lottery. And now we're going to want to, that when people try to enter a lottery that hasn't started yet, it's going to revert. So we can use what we've used before. We'll say with pytest.raises exceptions.virtual machine error lottery.enter from get account value lottery.get entrance fee. Of course, we're going to have to import both get account from our helpful scripts and exceptions from Brownie. Perfect. And this as well is following the arrange. And this is actually act/assert. So let's go ahead and test this. Brownie test-k. Test can't enter unless starter. Oops, let's do start ed. And great, that's passing as well. Let's go ahead and keep going down this list. What else? Now that we've tested whether or not they can't enter, let's test whether or not they can enter. So we'll do def test can start and enter lottery. So we're going to copy this again, paste it down here since we're going to work on a local blockchain. We'll do lottery equals deploy lottery. Account equals get account. We'll start the lottery. Lottery.start lottery. We'll do from account. We'll do lottery.enter from account. Say value is lottery.get entrance fee. And then we'll assert that we've correctly added a player to this lottery. So we'll assert lottery.players of 0 is going to be this account, right? Because we have our players array, and we're going to assert that we're pushing them onto our array correctly. Lottery.players of 0 equals account. So here's our act, and here's our assert. So let's try this now. Brownie test-k, test can start and enter lottery. And once again, awesome. Things are looking great. Now, let's test to see if we can actually end a lottery. So we've tested we can start a lottery. So we'll do def test can end lottery. We're going to copy this again, paste it down here. We'll do lottery equals deploy lottery. Account equals get account. We'll start the lottery with lottery.start lottery. Now we could 100% just import the rest of these functions in here, like end lottery, enter lottery, and start lottery. And similar to how we're just doing lottery equals deploy lottery, we could absolutely do that. For being very verbose here, I'm just going to go ahead and write all the functions and transactions myself. And this way, we'll actually be able to test a little bit more granularly. Anyways, we'll do lottery.start lottery from account. Do lottery.enter from account. We'll give it a value. Lottery.get entrance fee. Oops, I'm going to have to do account course equals get account. Now, to actually end the lottery, we do need to send this some link because we're calling request randomness. We use our fund with link script that we have in our helpful scripts. We'll import this from our helpful scripts. We'll call fund with link on our lottery contract. Once we fund with link, we'll then call lottery.endLottery from account. And then how do we actually know that this is being called correctly? Well, if we look back in our lottery contract here, when we call end lottery, we're not really doing a whole lot. All we're doing is changing our state. So let's go ahead and check to see if our calculating winner state is different. So we'll say assert lottery dot lottery state is equal to what? So calculating winner, if we scroll up to our enum, is in position 2. Open is 0, close is 1, calculating winner is 2. So we can say assert lottery.lottery state equals to 2. We can go ahead and test this as well. We'll do Brownie test-k, test can end lottery. We'll see if this works. And it does. Now let's test the most interesting piece of this entire lottery contract. We're going to test whether or not our fulfill function actually works correctly. Does this correctly choose a winner? Does it correctly pay the winner? And does it correctly reset? So let's go ahead and build our most complicated and most important test of this whole contract, choosing the winner. We'll do def test can pick winner correctly. Let's copy paste this bit about getting started. We'll do lottery equals deploy lottery. Account equals get account. We'll do lottery.start lottery from account. And then we'll enter with a couple different players. We'll do lottery.enter. Well, let's say from account value lottery.get entrance fee. Enter. And we'll copy this 2 more times, but instead we use some different IDs. We'll do index equals 1, and we'll do index equals 2. These are going to be different accounts here because we're going to use a different index because we want to just test for multiple different people here. This unit test is getting drastically close to being an integration test, but as I said, we're being a little bit loose with the definitions here. Now we're going to want to fund it with link. So we can just go ahead and copy this line here. Fund with link lottery. And now we're going to want to choose a winner here. And this is where we actually have to modify one more thing in our lottery contract. So in order to test actually calling this fulfill randomness function and testing everything in here, we're going to need to call this fulfill randomness function. Now, if we look at our VRF coordinator mock, we have this function called callback with randomness. And this is the function that actually calls this raw fulfill randomness.selector, which eventually will call that fulfill randomness function. But this is the entry point that the node actually calls. We have to pretend to be a Chainlink node and call this function. We're going to return a random number, of course. We're going to choose the contract we want to return to, but we also have to pass the original request ID associated with the original call. Now in our lottery contract, our end lottery function isn't going to return anything. And even if it did, it would be really difficult for us to get that return type in our Python. So what we want to do to keep track of when this contract actually entered the calculating winner state is we want to do what's called emitting an event. Events are pieces of data executed in the blockchain and stored in the blockchain, but are not accessible by any smart contracts. You can kind of think of them as the print lines of a blockchain or the print statements of a blockchain. We can go to this logs section, which also includes all the different events. Now, there's a lot of information here, so we're actually going to do an event ourselves just so that we can see what this really looks like. You can see here that when we call this end lottery function, in the logs, if we scroll to the bottom, there's an event here called randomness request. This was spit out by the VRF coordinator. This was spit out by the VRF consumer base that we inherited. And it even has some data that's already been decoded. One of those pieces of data is the request ID. Now, to add an event, we first need to create our event type. So at the top, we'll go ahead and do event requested randomness. We'll say bytes 32 request ID. So now we've identified a new type of event called requested randomness. It's really similar to the enum in this regard. To emit one of these events, all we have to do in our end lottery bit is we'll do emit requested randomness and then request ID. Because requested randomness takes a bytes 32 as an input parameter, and we're going to pass it that request ID as an input parameter. Now that we have this event being emitted, back in our test, when we call end lottery, it will actually emit one of these events to our transaction. So what we can say then is transaction equals lottery.end lottery. Same way we've always done it. But now we can look inside of this transaction object. Inside of this transaction object, there's actually an attribute called events, which stores all of our events. We can then look for a certain event name, which we know is requested randomness. So we'll say, out of all the events, look for the requested randomness event. And in there, in that requested randomness event, find the request ID. Request ID. Now we can say request ID is going to get grabbed from this event that we emit. So these events are going to be really helpful for writing tests. These events are also really helpful for a number of other reasons. One of the big ones is upgrading our smart contracts or understanding when a mapping is updated. But for now, we're going to be using them for testing. Now that we have this request ID, what we can do is pretend to be the Chainlink node and use this callback with randomness function to dummy getting a random number back from the Chainlink node. So what we're going to do is we're going to call our getContract function and get that VRF coordinator. Of course, we're going to have to import it from our helpful scripts. And we're going to call that callback with randomness function. So we're going to do dot callback with randomness. And we need to pass it this request ID, a random number, and then the contract to return to. So we'll do request ID. We'll do some random number, like we'll say static RNG equals 777. So we'll say the random number that we're going to return is going to be 777. And then we'll do lottery.address because we're going to return it to the lottery. Once again, we're going to say from account because this is making a state change. And now that we've got a callback, what we can do is do our asserts now. So this is us dummying getting a response from a Chainlink node. And this is how we mock responses in our tests to make our lives way, way easier. So now we can figure out who the winner of this lottery actually is. If these are our three entries, that means it's 777 mod 3. Since our random number is going to be 777, if we pull out a calculator, 777 divided by 3, it divides evenly. So we know that this means the answer to this is going to be 0, aka our account is going to be the winner. So let's assert the lottery dot recent winner is going to be equal to our account, right? Because we set a recent winner in here. We transfer them some money. We'll assert lottery.balance is now 0 because we're transferring this account all of the money. And let's even make sure that the account gets more money, right? So we'll do starting balance of our account. Starting balance of account equals account.balance, and we'll do balance of lottery equals lottery.balance. And then we'll assert account.balance is now going to be these two added together. Starting balance of account plus the balance of the lottery. Because we should get all of the lottery winnings here. Okay, so this is a long test, but this is probably the most important test. Let's make sure this is doing what we want it to do. So we'll do Brownie test-k. Test can pick winner correctly. Let's see if this works. Oops, I forgot to put some parentheses here, some parentheses here. Let's try this again. And perfect. We are actually updating, paying out, and running our lottery correctly and fairly with true randomness. This is incredibly exciting. And we've emitted events in our lottery contract to use in the off-chain event logging of Ethereum. I know we're getting antsy to actually run this on a real chain. So let's go ahead and do our last bit here. We'll create our integration test, which we will run on an actual chain. And then if we wanted to, we go ahead and try our deploy lottery function on a real chain as well. All right, so let's do our integration test here. This is where we're going to actually test on a real live chain. We're going to use Ringpy because that's the network that we've been using this whole time, which is great. Now, I'm being a little bit liberal in the way that we're doing our tests here. And we're just going to do one test for this integration test, but keep in mind, you're going to want to test every piece of your code. So let's just create a test called def test can pick winner. Now, this is going to be the opposite of our unit tests. Our unit tests are only going to be on our local blockchains, right? We're going to skip if it's not on our local blockchains. We're going to do the opposite of this one. So we can even just copy this, or we can type it out. We'll say if our network.showActive is in those local blockchain environments, then we're going to do pytest.skip. Of course, since we're grabbing these pieces, we're going to do from Brownie import network. We're going to import pytest. And we're going to do from scripts.helpful scripts import local blockchain environments. We're going to deploy our lottery. So lottery equals deploy lottery, which we're just going to grab from scripts.deploy lottery import deploy lottery. We'll do account equals get account. And of course, we're going to grab that from our helpful scripts as well. So we'll do lottery. Let's start lottery. This will be from account. We'll do lottery.enter. We'll say this will be from account. We'll do some value, which is going to be lottery.getEntrance fee And if we run into an issue here, sometimes, again, we can do lottery.get entrance fee plus like 100 or 1,000 or something like that. This is going to be barely anyway, but for now, let's keep it like this. Then let's just copy this line. Run it again. We'll have 2 people enter the lottery. Of course, it's going to be us both times. And great. Now we're going to want to actually end the lottery. So first we're going to want to fund it. So let's import that funding script. So we'll get fund with link, or that function. So we'll call our fund with link function on our lottery contract here. And then we'll go ahead and end the lottery. So we'll say lottery dot end lottery. We have to do this from our main account. We have to do this from the admin account. Now, this is where it's going to be a little bit different from our integration tests, or from our unit tests. In our unit tests, we pretended that we were the VRF coordinator, and we called the callback with randomness. We pretended that we were a Chainlink node. Here, we're not a Chainlink node because we're on an actual network, so we're actually just going to wait for that Chainlink node to respond. So for simplicity, we'll just do time.sleep, and we'll wait like a minute for it to respond. Of course, since we're using time, we're going to want to import time right at the top. And then, since account was the only one to actually be in this, we'll do assert lottery recent winner equals account. And we'll also assert lottery.balance equals 0. All right, great. So we have an integration test that we can run, which is going to run through pretty much the vast majority of our functionality here. So we can go ahead and test this with Brownie. Test will be a little bit verbose here. We'll say -k, test can pick winner. And then, of course, we'll do -- network rink B. Now, before we run this, per usual, we got to make sure, do we have any testnet rink B Ethereum? We do. Great. Do we have any testnet Chainlink? We do. Perfect. Do we have a .env? We do. It's got all of our pieces. Let's check our Brownie config. .env. Awesome. And again, if you don't want to use the .env, you can use that other method that we showed you guys, how to encrypt with a password that you can absolutely use. Oops, and before we run this, let's set this to start lottery, because that's the actual function here. And we'll also need to be lottery.balance with parentheses here. Sorry about that. And now we can run Brownie test -k, test can pick winner, -- network rink B. We'll also add this -s flag, which will print out whatever Brownie is going to be printing out. It'll make everything a little bit more verbose here. And if you want to, you absolutely should, because this is something that we'll have to do at some point anyways. However, if for this tutorial you want to skip it, go ahead, because we're actually going to run through this whole process of deploying and waiting again anyways. So now that we've added all of our tests, what we can do is run our entire test suite. So we'll do Brownie test. And this is going to run through all of our development tests here. You'll see it'll go really quickly. And you see how much faster it is for us to run our test on a local chain as opposed to doing everything on a testnet. So it's going to make your life way easier. And we have everything passed here. So we know that our contract code is doing approximately what we want it to do. So it's time for the moment of truth. Let's deploy this to an actual testnet. So we have our deploy lottery script, which oftentimes I'll have it be just this deploy lottery bit, and then I'll have some other scripts for these other pieces, or maybe I'll do it in the Brownie console. But just to demonstrate everything end to end, we'll have deploy lottery, start lottery, enter lottery, and end lottery all in this one script so that we can see everything end to end and see what it looks like on Etherscan. So let's go ahead and run this script on a RinkB network, and then we'll go jump onto Etherscan and see everything. So let's do it. Brownie, run scripts, deploy lottery, network RinkB. So first, we went ahead and we deployed our lottery. We got our addresses with our get contract method. We got our fee, we got our key hash, we got our published source and everything here. Then we went ahead and verified it because of this published source. So if we grab this address, lottery deployed it here, we jump over to RinkB Etherscan, we paste this address in here, we'll see this contract with the little check mark is verified. And again, we'll go to the read contract. We can see all the public variables and all the public functions. We can go to write contract and we'll see all the transacting functions that we can interact with. After we get verified and things get deployed, we went ahead and called our start lottery function to actually start the lottery. We got our little print line saying the lottery started. Then you entered the lottery. We then funded the contract with Link so that we could get our random winner back. And then right now our end lottery is confirmed. And we're just waiting this 60 seconds, right? Because we did this time.sleep. And if we sit on this contract, if we go to transactions and we refresh, we can actually see some of these different method calls over here. We can see we did a contract creation, we started the lottery, we entered the lottery, and then we recently ended the lottery. And you'll see in our script here, it says 0x blah, blah, blah is the new winner, which is perfect, right? That means that the Chainlink node actually responded. We can actually verify that by looking in the contract. We'll go to read contract. We can go to the recent winner and see somebody did indeed recently win. We can also go to events and we can see some of the events that we created. We can see this first event right here is this requested randomness event. This is the event that we called. And we have this end lottery here. We can also see an ownership transferred function that got called. This was called when we actually deployed this in the first place. Now, a little bit more on these events, aka these logs, right? So topic 0, this hash represents this entire event right here. And this bit is going to be our topic 1, our first topic, which represents that request ID. So this is going to be the request ID. Awesome. We have successfully created a working smart contract lottery with true provable randomness. This is absolutely insane, incredible job here. Now, one additional piece that I want to talk about before we jump off here is, again, in our testing. A file that you're often going to see is what's called conftest.py. Python automatically knows to look for this conftest file, and we'll grab different functions from it. We can also add external plugins, fixtures, hooks, testing root path. It adds a lot of really fantastic features and is a common thing that you'll see. We skipped over in here for simplicity, but in future projects, you'll probably see this conftest file, which has a lot of really nice testing configuration pieces in it. Now, that was a lot of stuff to code. And quite frankly, I don't think any of us want to have to do that every single time, have to code everything from scratch. Now, you can absolutely git clone all of these repositories right from their GitHub. But there's actually an even easier way for us to start with a blank project here. And this is with Brownie mixes. So if we Google Brownie mixes GitHub, we'll get this mixes organization, which just has a ton of boilerplate code for us to go ahead, get started, and start developing. The one we're going to be working with is this Chainlink mix piece, which is forked from this official one here. This gives us some wonderful contracts, some tests, a Brownie config, and really everything that we need to do to get started. So if you have Brownie installed, we can just bake this mix. So we'll do Brownie, bake, Chainlink mix, and in our new empty directory here, we'll get this new Chainlink folder with everything inside of it. So then we can cd the Chainlink, and we can see it has all of these pieces in here already. In the contracts, we have a whole bunch of different samples of working with the VRF, working with the price feed, working with this thing called keepers to automate our smart contracts, and making API calls and delivering any API call that we want to the blockchain. It also has a Brownie config, which already has a number of wonderful pieces in each one of these networks so that we don't have to go copy paste and add it in here. It's even got support for testnets like Avalanche, Polygon, Binance, and more. It has a number of really powerful tests, including testing some price feeds. It has a whole bunch of deployment scripts, some mocking scripts, some helpful scripts, and really everything that we need to get started and get going. For starters, we could run Brownie test. And it's going to compile everything. And then on a development chain, run all these unit tests. And if we wanted to test this on a real testnet, we could do Brownie test -- network ringp or any network that we wanted. If you're looking for a good starter place that has a lot of really powerful smart contracts for you to get started, I highly recommend using this mix as a boilerplate starting point for any of your contracts or any of your projects here. Now we are cooking. So we've learned a ton of the fundamentals of working with Brownie and working with smart contracts. Now that we have kind of all the building blocks though, we can actually code a lot of these much faster and much more efficiently than before. One of the things that we've seen over and over and over again is working with tokens and the ERC20 token standard. We're going to learn how to build our own token. But before we do that, let's understand why we'd even want to do this.
Now first, let's define even what are ERC20s. So ERC20s are tokens that are deployed on a chain using what's called the ERC20 token standard. You can read more about it in the ERC20 token standard here, link in the description as well. But basically, it's a smart contract that actually represents a token. So it's token, but it's a smart contract. It's both. It's really cool. Tether, Chainlink, UniToken, and DAI are all examples of ERC20s. Technically, Chainlink is in ERC677 as there are upgrades to the ERC20 that some tokens take that are still backwards compatible with ERC20s. And so basically you can think of them as ERC20s with a little additional functionality. Now, why would I even care to want to make an ERC20? Well, you can do a lot of really cool stuff with it. You can make a governance token, you can secure an underlying network, you can create some type of synthetic asset, or really anything else. In any case, how do we build one of these ERC20s? How do we build one of these tokens? Well, all we have to do is build a smart contract that follows the token standard. All we have to do is build a smart contract that has these functions. It has a name function, a symbol function, decimals function, etc. All these functions. We need to be able to transfer it. We need to be able to get the balance of it, etc. And again, if you want to check out some of the improvements that are still ERC20 compatible, like the ERC677 or the ERC777, you definitely go check those out and build one of those instead.
So let's create a new folder and get started. We're going to create our new Brownie file, of course, with Brownie in it. It's going to start up our repository and start up everything that we are going to work with here. We can kind of actually just jump in and start right with our contracts. So let's create a new file and we'll call it our token.sol. And this is where we're going to add all of our token code. Now, since this is an EIP, right, all this is a smart contract. So what we could do is we could grab all these functions, copy and paste them in here one at a time, grab the name, grab the symbol, grab the decimals, and then, code all these up, be like, all right, this does some stuff, blah, blah, blah. Or we could do it the much easier way, right? Since we're engineers, we don't always want to reinvent the wheel. So once again, our friends at OpenZeppelin have some amazing contract packages for actually building our own ERC20 token. So we can go right to the OpenZeppelin documentation. I'm working on the 4x version, but again, it doesn't matter the version that you use so long as in our config file, we add the version that we're going to use, which again, we've already gone over. So let's go over to their ERC20 documentation. And this is the entirety of the code that is needed to make an ERC20. So we can just go ahead and even copy this, paste it in here, and boom, we have some ERC20 code in here. Let's actually just change the name of everything in here though. So we're gonna call this our token.sol. We have this SPDX license identifier, MIT, great. We're gonna be using Solidity version 0.8, which I know I've done a lot of this code actually in 0.6, but I highly recommend working with 0.8 because it has a lot of really fantastic improvements to Solidity. You'll notice this is our first dive into using a different version of Solidity here. You'll notice that most of the syntax is exactly the same. There are, like I said, a couple of nice improvements with 0.8. The main one being you no longer have to use those safe math functions that we talked about before. But then we're going to go ahead and import OpenZeppelin contracts token ERC20.sol. Now, of course, since we're importing OpenZeppelin, we're importing this package. We got to add this to our Brownie config.yaml. And before we even get started, you technically have all the tools that you need to code and deploy your own ERC20 token. Now, I'm actually going to challenge you to go ahead and try to start a Brownie project, create your own token using OpenZeppelin packages, and then deploy it on a testnet. I'm going to show you how to do all of it here anyways, but challenging yourself and trying to do things your own and exploring is really one of the fastest ways to learn and grow in this space. Did you give it a shot? No, really, pause it now and give it a try. All right, welcome back. Now we'll go through it and we'll do it together. Of course, we need to add these dependencies. OpenZeppelin, OpenZeppelin Zeppelin contracts. Let's do their version 4. So let's even go to GitHub, open Zeppelin. And we'll do 4.2.0, which was released yesterday at this time, which is great. 4.2.0. And of course, again, compiler. We'll have Sulk. Oops. Remappings. We'll add at open Zeppelin equals this. And then we're going to go ahead and save. Now we can use this at open Zeppelin and it'll refer to the open Zeppelin contracts here. So great, now we can go ahead and import these. Let's change the contract name to our token. We're going to inherit this ERC20.sol from open Zeppelin. We can even go ahead to open Zeppelin contracts GitHub and we can even see what this ERC20 looks like. So we can go to their contracts, down to token, ERC20, ERC20.sol. And this is their initiation of an ERC20, which has all these functions like name, symbol, decimals, total supply, etc. In our constructor, we're going to add an initial supply, which is going to be in way, of course, so the initial supply of that token. And we're going to use the constructor of the ERC20.sol, which again, we can go ahead and check in the code here, and we can see the constructor uses a name and a symbol. So we have a name, we'll call it our token. And the symbol we'll do OT. And boom, that is literally all we need for our token here. I told you this was going to be a much faster project. Now, for scripts, all we have to do is create a new file. We'll add a one deploy token.sol, and we'll also add a helpful scripts.py. Excuse me, this deploy token.py. Excuse me. We'll just quickly add a get account function. We'll say def get account. And you can go ahead and just copy paste from the last one. And if you want, you can actually just copy paste from our last helpful scripts because it's pretty much going to be exactly the same. So that we have all these wonderful ifs statements so that we can deploy from really anything that we want. Now, in our deployment token script, we'll do from Brownie import our token. And then from scripts dot helpful scripts, import, get account, and just to make sure, let's add an init.py in here, just to make sure that our scripts can actually import. So, since we know that we need an initial supply here, let's go ahead and do initial supply equals, and then we can do, whatever we want here. If we want to make it a little bit more readable, we'll also do from web3. Import web3, and we can do web3.toWay, and we'll say 1000 is the initial supply, and this is in Ether. So our initial supply is going to be 1000 Ether. Then we just add our main function. We do account equals get account. We do our token equals our token dot deploy. We just add as a parameter this initial supply. We'll do from account, and then we'll do print our token dot name. And that's the whole function. Now, of course, if you don't have your environment variable set, we're going to add our .env file. This is where we can add our private key, our Web3 Infura project ID, and then if we want, our Etherscan token. I'm going to skip doing this for now because my environment variables are already set. And then, last but not least, we'll add .env. So private key equals OX blah, blah, blah. Web3 Infura project ID equals blah, blah, blah. Etherscan token equals blah, blah, blah. And perfect. Now, if we want to actually deploy this to a testnet, all we have to do, go into our config, we'll add wallets, from key, we'll add our environment variable private key. Now, Brownie knows where to grab this from because we've defined it in our helpful scripts. What I could do now, so Brownie runs scripts, deploy token.py. And we can go ahead and see that our token is printed out. We can see that we have this token deployed on our local ganache. We can see our token here, and this is great. Now I can go ahead and run this again. Network Rinkeby. Now if I grab this address, go to the Rinkeby Etherscan, pop it in. After a quick refresh, I can now see that my contract has indeed been added. And Etherscan even picks up that it's a token. What we could do is we can grab this contract address, go to Assets, add it in our MetaMask here. Next, add tokens, and you'll see we are the proud owners of 1,000 our tokens. Now, something else that you might want to do is add this to a liquidity pool, or add this to a place where you can actually go ahead and sell it and put it on the market. You can do something like that as easily as just popping onto Uniswap, going to Pool, hitting More, create a pool, and then adding our token in here. We'd have to manage the token list and be sure to add the token in here, but we could go ahead and add a token, create our own pool, and automatically put it on Uniswap. And that's how easy it is to actually sell it on one of these pools. But all right, so this was probably our easiest project of the course, but it really shows how far you've come along. Everything here. That we know a little bit more about DeFi and why it's such an amazing technology that only works in the blockchain world, let's look at this site DeFi Pulse. Or if you want to look at another one, there's another fantastic one out there called DeFi Llama, which also shows a lot of these different protocols in here. So DeFi Pulse is an application that shows some of the top DeFi projects based on how much total asset is locked into each protocol. Aave, which currently is the #1 ranked DeFi application with 9.32 billion in assets under management in terms of USD. Then we have some fantastic ones like Curve, Compound, Maker, Instadep, etc. Now we're going to be looking at 2 of these protocols in particular. The first one, of course, being Aave.
The second one is going to be a type of what's called a decentralized exchange.
To get started with Aave, we're going to go to testnet.aave.com/dashboard, and it'll bring us to a screen that looks something like this with please connect your wallet, and everything will be pretty empty. Paraswap is what's known as a DEX, or a decentralized exchange. It allows us to trade tokens incredibly easy on the blockchain. Now, there's not a whole lot of testnet DEXs that actually work, so we're just going to look at them and simulate as if we were working on them. For example, if I wanted to trade 1 ETH for some USDT, or maybe some wrapped Bitcoin, or some DAI, or some Aave, or Link, or really any token that we wanted, all we would need to do is connect our wallet here, and a swap button would show up, and we would go ahead and hit swap. Some other really powerful, these DEXs and really popular ones are going to be Curve Finance, Uniswap, and it's a really, really easy way to go ahead and swap your tokens for one another, depending on what you're looking to do. Aave is incredibly powerful, and it's going to be one that we're going to be working a lot with because it has pretty much all the fundamentals of working with the DeFi protocol that we're looking for. And it has a testnet that we can go ahead and test and simulate actually working with some of these protocols. So we're going to first work with the UI, or the user interface, and then we're going to do everything here programmatically. First things first, if you don't already have it, make sure you have some testnet Ethereum at least. And again, you can get some testnet Ethereum from looking at the link token contracts and going to Coven. This one, indeed, the testnet of Aave right now is only on Coven. So we're going to go ahead here. We're going to copy our address, paste it in. I'm not a robot. 70.0.1 test ETH. Remember, use this link token contracts page because this is going to have the most up-to-date faucets here. Once we see some ETH in our Coven testnet here, we can go back to Aave. So whereas Paraswap allows you to simply swap between assets and do a lot of buying and selling of tokens, Aave is a lending and borrowing application. So we can actually put down a token as collateral, and we can borrow, and we can generate some yield from interacting with this protocol. Borrowing and lending is a critical piece to doing any type of really interesting financial applications or financial instruments, such as short selling, being exposed to more assets, etc. You can also gain some percentage back. If you look at APY, it'll tell you how much percentage over a year you'll actually get in returns from staking or depositing an asset. So here's what we're going to go ahead and do. We're going to connect to the application using MetaMask, and you'll see on the deposit tab here, we'll see our balance be 0.1 ETH because that's how much I currently have in my wallet right now. What we can now do is click on ETH here, click this max button to deposit some Ethereum. We'll hit continue, and a little dashboard will pop up asking us, okay, would you like to deposit? Clicking this deposit button will actually have us deposit right onto the Aave contract on the Coven testnet. Make sure once you hit deposit here that you're actually on a testnet here. It looks like I actually have some insufficient funds, so I'm actually going to go borrow a little bit more from the faucet here. Grab a little bit more from the faucet here. We're going to come back. We're actually going to go back. We're going to refresh, and now it says I have 0.1. We're going to deposit 0.1, continue, deposit, and MetaMask is going to pop up saying, hey, are you sure you want to do this? Right? We can check our data. We can grab this address even if we want, pop it onto coven.etherscan, paste it in here. We can even double check to make sure that this is indeed the right contract that we want. Funnily enough, you'll see that this is the WETH gateway. When we deposit our Coven ETH, it actually gets transferred into an ERC20 version of our Ethereum, and then it'll go ahead and deposit it into the Aave contract. So we're going to hit confirm, and now we're going to get this pending here. We have a link to the Explorer, which shows us this transaction that's going through, and then we'll see that we've indeed successfully deposited our Ethereum. Now down here, you'll see a little button, add a ETH to your browser wallet. And we're going to go ahead and click this. And this will automatically add this token to our wallet. So we're going to hit add token. And we see now in assets, we have this a ETH down here. We could also have manually hit added token, got the contract address, but Aave was nice enough to just go ahead and add us a little button that does it for us. A ETH is what's called an interest-bearing token, and it goes up in real time. You'll see, if I sit here long enough, you'll see this number actually continually going up. This is the profit given to us from other people borrowing the ETH that we've deposited into Aave. If we go to our dashboard now, we can see we have 0.1 ETH deposited. And if we roll over it, you'll constantly see the amount go up and up and up. We can go ahead and withdraw our ETH, which will convert our A ETH back into ETH with the additional interest that we got from depositing. So depositing into Aave will give us interest back as a payment for other people borrowing the ETH that we've deposited. We can also use this ETH as what's called collateral. So if I go to this borrow tab, I can actually use the ETH to borrow some other asset. Maybe I want to borrow DAI, which is a stable coin meant to always equal $1. USDC and USDT also are meant to always reflect $1. We can borrow what's called wrapped Bitcoin, which represents the Bitcoin price. We could borrow some Aave token, some BAT token, some Link token. We can borrow all these different tokens. Now, borrowing an asset is incredibly powerful. By borrowing, you're allowed to obtain liquidity without selling your assets. And borrowing is one of the first pieces in order to actually short sell. Borrowing in DeFi protocols is absolutely massive because it allows you to frictionlessly short sell, obtain liquidity without closing your position, gain yield on some deposited collateral. You can do a massive number of new things only in the DeFi world, such as flash loans. Now, an important note on borrowing assets on mainnet. Since we're just borrowing it on testnet and this isn't real money, this is 100% okay to experiment with and work with. However, if you borrow an asset and you do not pay attention to how much you have for an underlying collateral, you could get liquidated and lose some of your funds. So be very careful and pay a lot of attention if you're going to do this on an actual network. Now, let's say we want to borrow the Aave token, for example. We click here and we can choose the amount that we want to borrow. Now, here's the thing. Since we've placed down some collateral, right, 0.1, if the amount that we borrow ends up being too high, we'll actually get what's called liquidated. Every time we borrow an asset, we get some type of health factor. The health factor represents how close to being liquidated you are. Once your health factor reaches 1, the collateral that you've actually deposited will get liquidated, and somebody else will get paid to take some of your collateral. This is so that the Aave application is always solvent. Being solvent means it's never in debt. So when I want to borrow, I want to choose some amount that might be a little bit safe here, and so that I'm not going to get liquidated. So Zoom in a little bit. I'm going to choose some number where I see a health factor, maybe like 5.6. We're going to continue. Now we'll have to choose our interest rate. When we borrow an asset, we actually have to pay some interest. This payment is actually going to go to the people who are depositing DAI or depositing the asset. The interest rate that we're going to pay is actually going to be paid to those who are depositing the asset that we're borrowing. So like how we're getting interest on our deposited collateral, others are getting interest on their deposited collateral based off of how often people are borrowing it. We can choose a stable APY, which will always be 4%, or a variable APY, which will change based off of how volatile and how in demand this asset is. For now, I'm going to choose variable, but you can pick whatever you want, especially for this demo. We're going to hit continue. I'm going to zoom out just a little bit. And this same interface is going to show up. We're going to go ahead and hit borrow. MetaMask is going to pop up and ask us if we really want to borrow. We're going to go ahead and hit confirm. And now we've successfully borrowed DAI into our application. We can even hit this little add DAI to your browser wallet to add the token to our wallet. Now, if we hit the button, we go to assets, we can now see DAI is indeed in our token assets here. Now, if we go back to our dashboard, you'll see we have a health factor score here. This is a really important score. If you click on this little eye thing, it says the health factor represents the safety of your loan derived from the proportion of collateral versus amount borrowed. Keep it above 1 to avoid liquidation. And we'll see all of our deposits here. So we still have 0.1 in ETH deposited. We also have 28 DAI deposited. You can see a whole lot of different stats here for working with our application. We can withdraw our DAI, we can withdraw our ETH, we can borrow more DAI, or we can go ahead and repay. We can either repay from our wallet balance or from our current collateral. Yes, we could repay with our collateral. Let's go ahead and do from our wallet balance. We'll hit max, continue, and we even get this little thing that says you don't have enough funds to repay the full amount. Well, why is this the case? We just borrowed this amount. It's because already since depositing, we've accrued a little bit of extra debt. Remember, we hit that variable APY, and every second it's going to tick up just a little bit. So let's go ahead and pay back what we can with our wallet. We're going to confirm. We're going to approve our DAI to be spent, and then we're going to go ahead and hit the repay button. And great. Now if we go back to our dashboard, you can see we've repaid almost everything here, but we have a little bit left. So let's just go ahead and hit repay with our current collateral. We'll hit max, continue. And this will use our ETH to pay back the collateral instead of the DAI. And then we'll hit repay. This way we'll have no more debt. Great. Now if we go back to our dashboard, we can see we have no more debt, which is fantastic. Aave is one of these applications that relies on the Chainlink price feeds in order to understand the ratio between how much you have deposited as collateral and then how much you can borrow and take out. If we look in our wallet now, we can see we still have some AETH. We also have some ETH, and now we have 0 DAI because everything's paid back, but we're still gaining interest on the ETH we have deposited. Let's go ahead, just reconnect. Let's go ahead back to testnet.aave.com. And let's just withdraw all of our ETH. Now keep in mind when working with some of this, this is a testnet, right? And working the way we're working right now is just on a testnet. So sometimes the testnet doesn't work quite as well as a mainnet because it's just for testing and doesn't have the exact same support. We were just working on the testnet. But if you want to go to Aave for real, you can go to app.aave.com, connect your wallet on the Ethereum mainnet, connect your wallet, move to the Ethereum mainnet, and interact with it exactly the way we just saw. Now, if we're on the mainnet here, we can see some additional pieces. When you deposit something like DAI, yes, you get 2.3% back as interest paid to you for depositing the DAI. You also get a little bit of what's called a governance token. You also get a little bit of Aave token. I know it's really small here, but this is an additional incentive that Aave has given the users for working with their protocol. Since Aave is a decentralized protocol, in order for anything to be improved or anything to be updated on the protocol, it actually has to go through a decentralized vote. So these governance tokens actually dictate and decide how the protocol improves moving forward. Now that we understand how to work with all of that through the UI, let's actually learn how to interact with Aave and interact with DeFi, all from our scripts. Learning how to do it this way will get us one step closer to being a quantitative DeFi engineer or DeFi researcher. This is someone who programmatically does algorithmic trades, algorithmic modeling, and just does everything in a programmatic sense, making them much more efficient and powerful interacting with DeFi. Now, all the code that we're going to be working with here is in this Aave Brownie Pi application, and you can always refer back to it in the link in the description or in the link in the GitHub repository and see all the code written yourself. So with that, create a new folder and open up your VS Code to that folder, and let's get into it. And Aave has some fantastic documentation that we're going to use as well. Link here is also in the description. Let's go ahead and start with our basic Brownie setup, just with Brownie init. And we got a new Brownie project, we got all our folders in here, and we are good to go. Now, if we're working with Brownie, we're actually not going to really be deploying any contracts because all the contracts that we're going to work with are already deployed on chain. All of them are just going to be working right with Aave here. Create a quick readme.md so we can know what we're doing here. Number one, we're going to try to deposit some ETH into Aave. Then we're going to borrow some asset with the ETH collateral. And then if you wanted to, I challenge you to actually sell that borrowed asset. This is what's known as short selling, but we're not going to do that here. And then we're just going to repay everything back. Great, and this will be the full functionality of working with Aave in this deployed contract. Everything that we're going to learn here will teach you how to work with other contracts as well, such as Paraswap or Uniswap, or any other type of swapping contract that will allow us to buy and sell. So let's just go ahead and create a script. We'll call it Aave borrow.py. Let's go ahead and create a function called def main, and we'll just do pass for now. The first thing that we need to figure out how to do is deposit some ETH into Aave. When we actually deposited our ETH via the UI, you can actually see when we call this deposit function, if I hit this deposit button here, oddly enough, if we go to this contract address on the Coven Etherscan, we'll see that this address is actually what's called a WETH gateway. What Aave is doing, like I was saying before, and let's go ahead and actually cancel this for now, reject. What Aave is actually doing here is swapping our Ethereum for WETH. Again, WETH is an ERC20 version of Ethereum, and this allows it to easily work with all the other ERC20s on the Aave protocol, like DAI, USD Coin, Ampleforth, Link, etc. So we actually have to do that as well. So the first thing we're going to need to do actually isn't deposit some of our ETH. The first thing we're going to need to do is going to swap our ETH for WETH. So let's even just put this in its own little script. We'll call it get weth.py. So we're going to have a function, def main. I'm just going to do pass for now. But we're actually going to want to use this get weth function in our Aave borrow.py. So we're going to actually have a main and we're going to have a def get weth. And our main function is just going to call get weth. So how do we actually convert our Ethereum to WETH or wrapped ether? We'll even do a little doc string here. Mince WETH by depositing ETH. Now to save gas, we could actually interact with this WETH gateway for Aave, but I'm going to teach you guys how to just get WETH in general. So we can look up the WETH contract Etherscan, the WETH Coven contract Etherscan, and we'll see here we have this wrapped ether page. And we can go to the contract and we can see that this is indeed verified. The way ETH works is there's a withdraw and deposit. We deposit ETH into this contract and it transfers us some WETH. So this is the first contract that we actually want to interact with. So we need our script to be able to call this deposit contract. So, per usual, the two things that we need to do this are going to be an ABI and an address for this WETH contract. I really like just doing everything directly from the interfaces. I've already copy pasted the interface into this here. So we're going to go to wethinterface.sol and we're just going to copy all this right here. So in our interfaces, we can create a new file. We're going to call it iweth.sol. We're going to paste it in. You can see this has all the exact same functions. It has our deposit contract, symbol, name, transfer, pretty much everything you would expect from an ERC20, plus this extra deposit piece. We'll call this IWETH. It's a common naming standard to just have I in the name of what your contract is when you're talking about an interface. So we have an interface now, and we also have an address. But again, this is our address on the Coven network. Since we know ahead of time that we're probably going to be using this on different networks like mainnet and Coven and etc., we're actually going to create a new file. We're going to add our Brownie config. Hopefully this is starting to look a little familiar to you now. We're going to go ahead and add our networks in here. In here, we're going to go ahead and add Coven. And in here, we're going to write WETH token. And we're going to add this address of the WETH token. Paste it in here. While we're in here, we're going to add the rest of our pieces. We're going to add wallets, from key, private key, and that's all we really need for now. Speaking of which, we probably are still going to want to test this locally. Now, since we've done some work with testing, we know that for testing, we can do our integration tests on Coven, because there's an integration test there. What about our local tests? Well, this is something good that we're thinking about right now. We know that Aave actually has all these same contracts on the mainnet as well. And we also know that we're not going to be working with any oracles. Because of that, we don't actually have to deploy any mocks ourselves. We can if we want to, but we don't have to. What we can do is for our unit tests, we can actually just use the mainnet fork network and just fork everything that's on the mainnet into our own local network. So instead of actually using mocks, we'll basically just mock the entire mainnet. And one more time, just so that we absolutely have it here, if you're not working with oracles and you don't need to mock responses, we can just go ahead and use a mainnet fork to run our unit tests. If you are using oracles, then it makes a lot more sense to do the development network where you can mock oracles and mock oracle responses. With this in mind, we know that we're going to be doing a lot of our tests on mainnet fork. We can go ahead and add a mainnet fork network here, and then we can just add the mainnet WETH token for mainnet fork. So we'll look up WETH token, Etherscan, WETH token, Etherscan, and we'll grab this contract address. Remember, absolutely positively, if you want to double check that the contract address that you're working with is correct, I highly recommend you do so. Because if you get it wrong, you could accidentally add some money to a contract address that you don't want. So we're going to have the mainnet fork address be the WETH token address. And in our terminal, we can do Brownie, networks list, and see that indeed we have a mainnet fork here. That's going to use the Ganache CLI to fork mainnet for us. There's a link in the description to refer back to the section where we actually set this up. So now that we have the interface, we know that we can actually compile it down to the ABI. So back in our get WETH here, first thing we need to do to make any transaction, obviously, is get an account. Well, this is where we can go back and make our helpful scripts. So we can go ahead, do def get account, index equals none, ID equals none, same as before. And if you have your get account function from our last demo, you can just go ahead and copy paste it in here. All right, great. Now we have our get account function. So we can do account now equals get account. Oh, but we have to import it in here. So we'll do from scripts dot helpful scripts import get account. And depending on your Python version, we'll add an init.py just so that Python recognizes that scripts is indeed a module. All right, cool. So we have our account where we can make some transactions with. Now let's go ahead and get our WETH contract. To do this, we can import interfaces from Brownie. Import interface, same as we did before. And we can do WETH equals interface dot I WETH, and the address here is going to be from our config. Config networks network.showActive, and then WETH token. And we also have to import config from Brownie. And network as well. Now you might be asking, why aren't we using the get contract function here? Well, you can absolutely 100% go ahead and use that get contract function. But since we're going to be testing on mainnet fork here, I know that we're always going to refer back to the config. So I'm confident that I'm not going to be deploying any mocks. It's better practice to go ahead and use that get contract function, but for this one, we'll just make it a little simpler and use the config. And now in our Brownie config, if we're on the Coven network, we're going to use this one. If we're on mainnet or mainnet fork, we're going to use this one. For going to mainnet or to real production, you could also have a mainnet network and it'll just be an exact copy of the mainnet fork. And remember, we're going to want our .env, our env file, our environment variables to get pulled from that .env file. So we can just set it like this. Now everything in our .env file will get pulled in automatically. Great. So we have an address and we have an ABI, which comes from the interface. Now we can just call this deposit function where we deposit Ethereum and we get WETH. So now we'll just do transaction equals WETH dot deposit. And we'll do from account value is going to be, let's just say 0.1. So 0.1 times 10 raised to the 18. So we'll deposit 0.1 and we should get 0.1 WETH in return. Do a printf string. Received 0.1 WETH. Oh, this doesn't even need to be a printf. And then we'll just return tx. Now, per usual, if your environment variables aren't set, such as private key, we're going to want to do that. So in our .env, we're going to do export private key equals 0x at the beginning, right here. We're going to export web3 Infura project ID. We'll want to add our web3 Infura project ID, which we've got before. If we want to use our Etherscan token, we absolutely can. And since we're putting a whole bunch of stuff into .env, we want to make sure in our git ignore we have .env so that we don't actually push this up to GitHub. Again, if you're nervous about having all these .envs in here, you can absolutely do the accounts.add or whatever other methodology you like to set your environment variables. Anyway, let's go ahead and run this script now. So we can do Brownie, run scripts, get weth.py, network, Coven, generating the ABIs from our interface. And we have a little transaction hash that we can use, pop into the Coven Etherscan, and we can see the transaction going through. In our wallets, we'll get minus 0.1 ETH and we'll get plus 0.1 WETH. We can see it's actually been successful. To add this and see this in our MetaMask, we're going to grab the contract address here. We're going to go back to MetaMask, add token, paste it in here, add tokens, and you can see we now have 0.1 WETH. If you want to switch back your WETH to Ethereum, you would just hit this withdraw function, or we could programmatically add a withdraw function in here. This withdraw function will withdraw our Ethereum, withdraw and take our Ethereum out of the contract and burn the WETH and replace it with WETH. So you need to swap your WETH back to get your ETH out. Awesome. We have some WETH, and now we have an ERC20 token. We have an ERC20 token that we can use to interact with the Aave application. Now that we've got this getWETH function, let's go ahead and start borrowing. So let's go ahead and start with our account. It's going to equal to getAccount, which now we're going to want to import right at the top, like so. Then we're going to get our WETH address, or we can even just do our ERC20 address because the WETH token is in ERC20, and maybe we want to deposit some other ERC20. We'll do config, networks, network.showActive, WETH token, and of course, we're going to have to now add from Brownie, import network. And now we'd want to call this getWETH contract, just in case we don't already have WETH. We would just add another from scripts, .getWETH, import, getWETH, but we don't actually need to call it right now because we already have some wrapped Ethereum in our Coven address. Now, if we want to test this though on our local mainnet fork, we probably will want to call this getWeth. So I'm just going to add a little if network.showActive is going to be our mainnet fork, we should go ahead and call this getWeth function. And for Brownie, we're also going to want to import this config. We'll also have to add mainnet fork to our local blockchain environments, like so that when we call get account in our scripts, it actually knows that it's a local environment that we're working with, and it will just return accounts 0, instead of us having to actually load a private key in every single time.
And we want to actually wait for our transaction to complete here. So we'll go ahead and add this wait.
And then do tx.wait and wait for this transaction to actually finish. Otherwise, Brownie will get a little bit mad. So now that we have that, we can run Brownie, run scripts, Aave borrow.py, network, mainnet fork. So you can see that actually in this case, testing everything on mainnet fork is going to give us a really, really accurate view of what doing this on mainnet actually is going to give us. We don't have to do any mocking. We can literally just fork all of mainnet and go from there. We are still going to test on Kovan though in a little bit, just so we can see all the transactions that go through, how long it takes for stuff to happen, and
etc.
So now that we've gotten some WETH here, we actually need to go into our second bit. We're going to deposit some ETH, or in our case, some WETH, into Aave. So how do we actually do that? Well, everything that we need is going to be in this Aave documentation here. Where we deposit and borrow from in Aave is in their contract, this lending pool. You can see here, the lending pool contract is the main contract for the protocol. It exposes the user-oriented actions that can be invoked in Solidity and Web3 libraries. And these have all of the functions that we need. It has deposit, where we deposit our asset as a collateral, withdraw, where we take it back, we have borrow, we have repay, and we have swap borrow rate, and a couple other interesting ones which we'll go into later. But for now, we just really need to focus on repaying, borrowing, withdrawing, and depositing. So as you probably guessed, deposit is the function that we're going to work on right now. And since this is the contract that we're going to work with, as always, the two things you need when working with a contract are going to be the ABI and the address. So we're going to get this lending pool contract. We're going to say lending pool equals, and we're actually going to even make a function called get lending pool. So down below, we're going to do def get lending pool, not poll, and we're going to get the lending pool address and the lending pool contract so we can interact with it down here. Now, something about this lending pool is that the lending pool address can actually change a little bit depending on a lot of different pieces. So there's actually this address provider, which gives us the address of a specific or particular market. If we go back to this Aave UI, there's actually different markets. So there's different types of ways we can interact with Aave. We're just going to work with the basic Aave v2 because it's easily the most used on mainnet as well. The address provider registry will give us, so this address provider will give us the address of the lending pool for our market. If we want to go across different markets, we'll have to go to the address provider registry to find it, but the addresses in here don't change and the addresses in here don't change. It's just the lending pool address itself might change. So we just have to go to this address provider here. And there's just one function that we need to work with. It's this get lending pool, which will give us the address of the actual lending pool. So don't let this confuse you too much. Basically, all we're trying to do is we're saying, hey, where is Aave located right now? And Aave has a contract that will always tell us where the main Aave contracts are. And that's this addresses provider right here. So this is another contract that we have to work with. And again, when we have a contract, what do we need? We need an ABI and we need an address. So we can absolutely, once again, we could go ahead and copy paste like ABI equals whatever the ABI is, but we're just going to use an interface because life is great with an interface. So a couple of great things about interfaces too. If we know we're only going to work with one or two functions, we can actually just make the interfaces ourselves. So in interface, we could do new file, we could do I, lending pool, address provider, .sol, and we could just add it in here ourselves. So we'll first do spdx license identifier, And we'll do like MIT or something. We'll do pragma solidity 0.6.6 or whatever we want to do. And then we'll do interface I lending pool addresses provider. Excuse me, this should be a lending pool addresses provider. And we know that there's only one function called get lending pool. And we're not exactly sure what get lending pool is defined as, but what we can do is we can go to Etherscan Aave lending pool addresses. You can see here, this is actually the lending pool. But what we can look at is the Aave protocol. We can go right to their GitHub. We can go to contracts. We can see they have an interfaces section. And they have this lending pool addresses provider, get lending pool, and kind of as we expected, it's an external view and it returns an address. So we can literally just copy paste this into here. And we could run with this and this would work perfectly fine. But this leads us to the next point. We might as well just grab the whole thing. This way we know for a fact we're not getting anything wrong. But yes, if we wanted to, our interface could be this, right? Because this is going to compile, it could be this. Because this interface is going to compile down to an ABI, and the ABI is going to say, hey, there's a function here, and that's all the ABI is really doing. It's just telling us how we can interact with a contract. But let's just go ahead and add everything so that if we want to interact with more things, we can. So now we have the ABI. We also now need an address, which we can definitely find from the Aave documentation. We can go to their deployed contract section. We can find lending pool addresses provider, which is going to be right here. We're going to copy that. And where are we going to put this? Well, as you know, we're going to put this in our Brownie config. We're going to do lending pool addresses provider. We're going to paste that right there. And since we know we're also going to do Coven, we can also grab from Coven here. So lending pool addresses provider. We're going to copy this here and we're going to add this addresses provider for Coven as well. Boom. And now we have it for both Coven and for mainnet fork. Awesome. So we can keep going now. Now that we have an ABI and we have an address for both Coven and for our mainnet/mainnet fork, what we can do now is we first get the lending pool addresses provider. It's going to be from our interface, which again, we're going to grab from Brownie. Interface.I lending pool addresses provider, which the address of that is going to be config network.showActive lending pool addresses provider. And then we're just going to say lending pool address is going to be equal to lending pool. I'm just going to copy and paste it instead of typing the whole thing. Address divider provider dot get lending pool. Right? Because again, this address provider has this get lending pool, which returns this address, which is the address of the lending pool. Then, now that we have this address, we can actually return the lending pool contract by once again getting the ABI and the address of the actual lending pool. So we have the address, check. We just now need the ABI, which once again, we can work with our wonderful interfaces here. Do new file, I lending pool, sol. And there's only going to be a couple of functions we're going to work with here, but Aave actually gives us the interface right here. And Aave actually even gives us the interface of the lending pool address provider for us. So we can go ahead and copy this, pop it over into here. Now we do need to actually change one thing in here as well. This interface imports locally with this .. So we actually just need to change these imports to actually import directly from GitHub instead of importing locally. Luckily, this is something we already know how to do. So let's go to our Brownie config. And up at the top, we're going to add this dependencies bit in. dependencies. So we're just going to work with Aave's protocol right from GitHub. So we're going to work with Aave/protocol v2. And let's see what their latest version is. Ooh, looks like they got a couple different versions here. 1.0.1. So let's go ahead and work with this one. At 1.0.1. And then with compiler, sulk, remappings, per usual, we're going to say at Aave is going to be equal to this dependency. This way, Brownie will download this right from GitHub, and now we can just use this at Aave instead. So back in our iLendingpool.sol, we can just change this to pull right from GitHub. And if we look in GitHub, we go to their contract section, we go to their interfaces section, iLendingpool. We know that we can pull this from at Aave/contracts/interfaces, because we see this iLendingpool addresses provider right in here. And then this data types bit, you can actually look in contracts. And this I know because I've been through it already. It's in protocol, libraries, types, and here it is, data type.sol. So we can just take this exact path again and do at Aave/contracts/protocol/libraries/types data type.sol. Okay, great. So now that we've actually imported this interface for us to use, we can go ahead and compile just to make sure that everything is working correctly. Brownie compile. And perfect. If these interfaces had an issue, they actually wouldn't compile through Brownie here. So we know that they're compiling correctly. But great. So now that we have an interface, we know that these interfaces compile down to the ABI, and we already have the address here. So to actually interact with the lending pool now, we can just do lending pool equals interface dot I lending pool, and we'll add this lending pool address, lending pool. And then we can return lending pool. So now we have a function that goes through the lending pool addresses provider from the Aave documentation and returns this lending pool contract that we can now interact with. And we can even test this out by just printing this lending pool address in our script. So we'll do Brownie, run, scripts, Aave borrow, network, mainnet fork. And perfect. We can see the address here is printed out and there are no errors. So we know we're doing it right. So now that we have the actual address, what we're going to do now is we're going to take this wrapped Ethereum that we've got, this ERC20 version of Ethereum, and we're going to deposit it into this contract, just like what we did in the user interface. In order to actually first deposit it, we need to approve this ERC20 token. ERC20 tokens have an approve function that makes sure that whenever we send a token to somebody or whenever a token calls a function that uses our tokens, we actually have given them permission to do so. So that's the first thing that we're going to actually have to do, is we're going to have to approve sending our ERC20 tokens. And this resembles, so since I know that we're going to have to approve a lot, I'm actually just going to go ahead and make an approve ERC20 token function, similar as to what we did with the get lending pool. So we're going to need to approve this ERC20. So we're going to need to approve this ERC20. So let's go ahead and make a function. We'll call it def approve ERC20. So how do we actually call this approve function on a token contract? Well, as always, we're going to need the ABI and the address of the token contract. Same as always. I told you I was going to be saying this a lot. Now we could create our interface ourselves, looking at all the functionalities of the ERC20 tokens. So we could go to EIP20, look at the token standard, find all the different functions and put them into our interface. Or we can go ahead and just cheat and just grab it from my GitHub repository here. So I already have an iERC20.sol right here. And we're just going to copy everything in here and add it in a new file called iERC20.sol. and paste it in here. So you can see there are a number of different functions in here. We can check the allowance. We can check the balance of different addresses, how many decimals a token has, the name, the symbol. We can do some transfers and transfer from. And then the function that we're going to be using is this approve function. So right here, we can already see the parameters this approve function takes. We're going to need to have a spender of who to approve can spend our tokens, and then how much they can actually spend. So if we come back over to approve ERC20, we know that for input parameters, we're probably going to need an amount, a spender address, the ERC20 token address, so which token we're actually allowing to spend, and then an account, right? Or this is going to be that from account bit. So we'll just have this be passed as part of the function parameters. So let's go ahead and code this. Let's first just do a quick print line so that people know what this transaction is doing. We'll say approving ERC20 token. And then we'll get the ERC20 token by saying ERC equals interface, same as always, .IERC20. And then we'll give it whatever ERC20 address that we pass to this function. And now we can actually interact with this contract, and we can call that approve function. So we'll say transaction TX, or again, TX usually stands for transaction, equals ERC20 dot approve. And we're going to approve this spender for an amount. And then we'll say from account. We'll do a TX.wait. We'll wait one block confirmation for it to finish. And then once it's done, we'll do print approved, and we'll return the transaction. Awesome. So now we have an approve ERC20 function that we can use to approve any ERC20 token. So back up at our main function, we can run approve ERC20 for some amount, which right now we don't have defined. The spender is going to be this lending pool, but the address of the lending pool, because remember, lending pool is the entire contract. We just want the address. The ERC20 address, of course, is going to be the ERC20 address, and the account, of course, is going to be our account. The only thing we don't have defined right now is some amount, which we can make it really whatever we want to be. To keep things standard, let's just go ahead and do 0.1. So I'm going to make this a global variable. I'm going to say amount equals 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7. And we can go ahead and do amount. We're going to import, now, of course, Web3. doing all these zeros So is from incredibly disgusting. Web3. So we're just going to
Import.
refactor to do from Web3, import Web3.
And then instead of always,
and we'll just do
Web3,
the
two-way,
0.1, Ether.
0.1, which is the amount that we actually want. And we'll say Ether.
Now we can run Brownie, run scripts, Aave borrow.py, network mainnet fork. And we can go ahead and see that our approval function is working as intended. Network that will now, always be doing this defined dash whenever we network run any type of fork Brownie flag script. Can get a little annoying. So we can do let's default. just go ahead and change our default network to mainnet fork.
Mainnet
so we don't have to
fork
do any network
in
flag.
our Brownie.
Let's go back to our Aave borrowing section now. So we have everything approved. Now we just need to go ahead and deposit it into Aave. Since we know we're probably going to use this a lot too, let's go ahead and create a deposit function. Since we have everything approved, we can now go ahead and use the lending pool deposit method. And we can check the documentation here or look on GitHub or Etherscan to see what the parameters that it takes are. So I'm even just going to go ahead and copy all this, bring it over here. So what we can do now is we can do lending pool dot deposit, and then all these parameters. Let's go ahead and walk through them one by one. So first thing is going to be the address of the asset, which we know is going to be our ERC20 address. Boom. The amount of the token, which we can go ahead with our amount variable. Address on behalf of is just going to be our account.address. We're depositing this collateral for ourselves, and then referral code. So referral code is, the referral code is actually deprecated, and referral codes don't actually work anymore, so we're just always going to pass 0 here. And just to make sure we know that this is what we're doing, we're going to go ahead and print depositing 1, 2, 3, and then after we're done, we're going to do print deposited. And whoops, looks like we forgot to add that final dictionary here of from account. One more thing here. Let's go ahead and do TX for transaction equals lending pool.deposit. And we're going to go ahead and once again, we're going to wait for one block confirmation. Wait one. Transactions still being processed. So now if we run Brownie run scripts, ave_borrow.py, we can see that this actually went through fine. All right, now that we have some collateral deposited, we can go ahead and actually take out a borrow. We can go ahead and borrow some other asset. The question is going to be, how much? How much can we actually borrow? How much should we borrow? What would result in a positive health factor? Well, maybe we should actually pull off chain some of our stats. How much do we actually have deposited? How much collateral we have? How much debt we have? And so on and so forth. That way in the future, when we don't start clean, we can take some inventory of where we stand with our collateral and our debts. At the Aave documentation, we can go ahead and see this function called get user account data. This is going to return the user account data across all reserves. So it's going to get the total collateral that we've deposited in terms of Ethereum. It's going to get our total debt in terms of Ethereum, how much we can borrow, the borrowing power that we have, the liquidation threshold or how close to that liquidation threshold will be, the loan to value ratio, and again, this health factor. This health factor is obviously incredibly important because if it drops below 1 or reaches 1, users can call this liquidation call. Now this function returns all these variables, but for now, we really only care about how much collateral we have, how much debt we have, and how much we're available to borrow. So let's go ahead and write a function that will actually sort that out for us. We'll call it get borrowable data. Borrowable data. So let's go ahead and create this. Def get borrowable data. And we're going to pass in the lending pool as a first parameter and then the account as a second parameter, because we're looking to call this function on the lending pool from an account. So let's go ahead and just call that function. So we'll do lending pool dot get user account data, and we'll pass in account.address. Because if we look at the API again, all that it needs is a user's address to get started here. And it returns 1, 2, 3, 4, 5, 6 variables. So we can go ahead and get all of them with this tuple syntax here. So we'll say total collateral ETH, total debt ETH, available borrow ETH, current liquidation threshold, loan to value, and then the health factor. So it's with this syntax here that we can actually get all of these variables with this one call. And again, this get user account data is a view function, so we don't need to spend any gas. All of these variables are going to get returned in terms of way. So let's just go ahead and convert these from way to something that makes a little bit more sense to us. So we want to get this available borrow ETH so we can figure out how much we can borrow. Let's get that in terms that we can actually understand. So we'll do from way, available borrow ETH in terms of Ether. We'll do total collateral ETH equals web3 dot from way. And we'll do total collateral ETH, Ether. And then we'll do total debt ETH equals same thing, web3 dot from way. Total debt ETH in terms of Ethers. And let's even do a little printf statement for each one of these. So we'll do print f. This f allows us to put variables inside the print function. And we'll say you have total collateral ETH worth of ETH deposited. We'll even copy paste that a couple times, and we'll change this one to total debt ETH, and we'll change this one to available borrow ETH. So we'll say you have worth of ETH deposited, you have total debt ETH worth of ETH borrowed, and you can borrow available borrow ETH worth of ETH. and then we're going to go ahead and return. Again, we're going to use this tuple syntax so we can return two variables. And we're going to say a float of this available borrow ETH and a float of the total debt ETH. The reason that we have to add this float variable here is that without it, some of the math that we're going to try to do later won't pan out as well. So now we have this function, get borrowable data. We're going to pass the lending pool, and we're going to pass our account here. Since we're returning the borrowable ETH and the total debt, we can say borrowable ETH and then total debt equals that function right there. So let's go ahead and try this out with Brownie run scripts, Aave borrowed a pi. Again, because in our config, we have a default network of mainnet fork. Things seem to be approving, things seem to be depositing, and awesome. We have our output here. We deposited 0.1 worth of ETH. We have 0 ETH borrowed, and we can borrow 0.8 worth of ETH. Yes, this is correct. Even though we have 0.1 ETH deposited, we can only borrow 0.08. This is because the liquidation thresholds of different assets are different. In this risk parameters documentation here, we can see the different liquidation thresholds on the different assets. We can see that Ethereum has an 80% loan to value. So with Ethereum, we can only borrow up to 80% of the deposit assets that we have. And if we have more than 82.5% borrowed, we'll actually get liquidated. It also tells about the liquidation bonus, reserve factor, and some other helpful pieces in here as well. But now that we have this borrowable ETH amount, we can go ahead and actually borrow some DAI. So let's do a quick print saying, let's borrow. Now, in order for us to borrow some DAI, we also need to get the conversion rate. We need to get DAI in terms of ETH. So we're going to have to use some price feed here. Luckily, we already know how to work with Chainlink and how to get price feeds. Aave uses the Chainlink price feeds as well, so we're using the exact same conversion rate tools that Aave is going to use. So let's go ahead and create a function to get us this conversion rate. We'll say the DAI to ETH price is equal to get asset price. And then in here, we'll pass the DAI ETH price feed. This will be the address of the DAI Ethereum conversion rate. Let's go ahead and create this function. Call it def get asset price. And the parameter it needs is going to be price feed address. So the first thing that we're going to need is we're going to need to get this DAI ETH price feed. Where can we get this? Well, as we know, per usual, we'll head over to the Chainlink documentation. We'll go to Ethereum price feeds. We'll find DAI ETH. We'll grab this and we'll paste it into our config for mainnet. So we can go ahead and add the DAI ETH price feed in here and paste it into our config. Again, if we want to test this with Kovan, we can obviously just scroll down, look for Kovan, find the DAI ETH right here, grab that address, and pop it in for Kovan. And then we can get this the same way that we got the address of the WETH token. So I'm just going to go ahead and copy this, paste it here, but instead of having WETH token in here, we'll do DAI ETH price feed. And now we have a way to change the price feed address depending on what network we're on. So in our get asset price function, we're going to do the same exact thing that we always do. We're going to grab an ABI and an address to work with the contract. So again, we can get the ABI by just working directly with the interface. So we'll say DAI ETH price feed equals interface dot aggregator v3 interface, because this is the name of the price feed interface, which again, if we look at our interfaces, it looks like we don't actually have. So what we can do is we can go to the Chainlink GitHub, or as you guys are already starting to figure out, all my example code has all these interfaces as well, but we can go right to the source too. What we can do, we go here, we go to contracts, we get at source, we'll do 0.6, we'll do interfaces, and right here is the aggregator v3 interface. So if we want, we can just copy this whole thing, move back over to our interfaces, new file, and this file is actually named aggregator v3 interface You could call it iAggregator v3 or aggregator v3 interface. You could keep it with iAggregator v3.sol to keep with the convention that we have, or you can just call it aggregator v3 interface.sol to keep in line with what the Chainlink code is actually called. I'm going to call mine aggregator v3 interface. You'll notice a couple different projects have a couple different conventions. But now that we have it saved, we can do interface to aggregator v3 interface, and we'll pass it this price feed address. Now, this DAI-ETH price feed is going to be a contract that we can call a function on. And again, we can always refer back to the get the latest price documentation to see how to actually work with it. There's even some Python code here for working with it in Web3. We're going to go ahead and call this latest round data function, which we can also find in our aggregator v3 interface, this latest round data, which returns a round ID, answer, started at, ended at, and answered in round. All we're really concerned with is this answer bit here. So the way we can do this is we can say latest price equals DAI-ETH price feed, that latest round data. And instead of grabbing all 5 of these, 1, 2, 3, 4, 5, what we can do is we can actually just grab the price, which is at the 1 index. So round ID is at 0, price is at 1, start at 2, etc. So we can just say at the first index, and then we can return a float of this latest price. We can even print another printf statement. The DAI-ETH price is latest price. So let's go ahead and run this. And great, we have the DAI-ETH price feed here, which of course we know that looking at this right now, this isn't in the right units. We know that DAI-ETH price feed has 18 decimal places. So what we can do then is we know that this number would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. This number is really 0.0004 blah, 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 blah. So maybe we don't want to return it like so. Maybe we want to say the DAI-ETH price feed is, and we add a little bit of web3.py to make this make a little bit more sense. So we'll say web3.from way, and we'll add this latest price bit in here, comma, ether. Maybe we'll even do a converted latest price, which is going to be equal to web3.from way, latest price, ether. And we'll print that out instead. So let's go ahead and run this again. All right, that looks a little bit more accurate. Perfect. Okay, great. Now we have the DAI-ETH price. We're getting really close to being able to borrow this actual asset. And let's even return this converted latest price here, just so that we're always working in units that we understand. Okay, now we're getting somewhere. Now we can calculate the amount of DAI that we want to borrow. We can find this by doing a little bit of math. We're going to do the reciprocal of the DAI-ETH price times our borrowable ETH. And just to be safe, we're going to times it by 0.95. So this line, we're converting our borrowable ETH to borrowable DAI, and then we're timesing it by 95%. We're timing it by 95% because we don't want to get liquidated. So we're going to be a little bit more cautious. Remember how we slid that sliding scale around to make it safer and less safe? Well, the lower percentage that we actually borrow, maybe we even borrow 50% of our collateral, the safer that we're going to be. So keep that in mind when you're deciding how much to actually borrow if you want to run this in a production environment. So now that we have this amount to borrow, let's even print it out. Let's say print f, we are going to borrow amount to borrow, DAI, and then we're finally going to do it. Now we will borrow. Looking at the Aave documentation, we can look at their borrow function, and we can see the API here. Let's go ahead and call this function. So we'll do borrow transaction. It's going to be equal to lending pool.borrow. Let's look at those parameters. So the asset that we want to borrow, DAI address. So first we should get a DAI address, which we can, once again, we'll want to put in our config. So we'll go over to our config and we'll add a DAI address or a DAI token here, which we can find on Etherscan, DAI token. It looks like this is the token right here. So we'll copy this address for mainnet. Remember, if you want to run this on Kovan, you're also going to need to have a DAI token for Kovan. Now, on testnets, Aave actually changes up where the tokens for its testnets are actually going to be. So if we go to their documentation, we go to deployed contracts, and we go to Kovan here, you'll always see this little flag thing pop up. Say, always ensure you're using the latest lending pool address, since Kovan is updated from time to time. It's going to be the same thing if we scroll down for tokens. They have an up-to-date list of Kovan addresses in a JSON file here. So it looks kind of gross, but if we look up DAI, we can see symbol, DAI, and the address of DAI on the Kovan testnet. So sometimes this does change. So if you run into an issue, maybe it's because the DAI token that you were working with on their Kovan testnet has actually changed. Then we're going to do config, networks, network.showActive, DAI token. Great. Now let's move on to the next parameter. The amount, which we just figured out here, amount DAI to borrow, which we do need to change back to way. So we're going to do web3.toWay, amount DAI to borrow, Ether. Because right now, amount DAI to borrow is in our human readable version, which we need it in way. Then our interest rate mode, which is going to be stable or variable. Stable is where the interest rate will always be exactly the same. Variable will change depending on a lot of different things going on with Aave. For safety, we're just going to go ahead and add one here. Then we're going to do a referral code and on behalf of. So referral codes no longer exist, so we'll leave 0. And it's going to be on behalf of ourselves. So we'll do account.address. And then, of course, we have to do a from account. Then we'll wait for this transaction to complete. And if we've done this right, we should have borrowed some DAI programmatically from the Aave protocol. So let's even print, we borrowed some DAI. And we can once again call our getBorrowableData function, since this getBorrowableData function will print out our new account information for how much we borrowed. So let's go ahead and run this on mainnet fork again. Awesome. So if we've done this correctly, we now see that we've borrowed some DAI. So we can see here, we now have 0.1 worth of ETH deposited, 0.059999 worth of ETH borrowed, and we can borrow a little bit more worth of ETH. This 0.75999 is actually the DAI that we've borrowed. So we've deposited some ETH and we've borrowed some DAI, and Aave is telling us how much that DAI converted to ETH is there. So we actually borrowed 160 DAI, which is great. All right, we've now learned how to borrow everything, which is fantastic. Let's go ahead and actually repay that back. So we're going to call their repay function. And let's just put this into its own function called repay all. And we'll give it the amount that we want to repay, the lending pool address, and our account. So let's define repay all, where we're just going to repay everything that we have. And again, we're going to add an amount, lending pool, and account for parameters. So if we're going to pay back this network, first thing that we need to do is actually call the approve function and approve that we're going to pay back. So the first thing we're going to have to do, per usual, is we're going to actually have to approve that ERC20. So let's say how much we're going to approve, web3.toWay, amount, Ether, to the lending pool, and we'll grab it from the config, networks, network.showActive. And this is going to be the DAI token again. And of course, with our account. I believe our approve ERC20 already calls wait, so we don't have to call it here. So once we approve, we're going to be using this DAI that we borrowed to pay most of what we have borrowed back. Now we're going to call the repay function. So we'll say repay tx equals lending pool.repay. First, we need the asset that we're going to use to repay, which we're going to use config, networks, network.showActive, DAI token, the amount, which is going to be passed in here, amount, the rate mode, which we've hard coded to 1, and the address on behalf of, which is going to be account.address. And then, of course, we always have to do from account. Then we're going to do repay tx.wait. We're going to wait 1 block confirmation, and then we'll print repaid. Whew. And if we've done all this right, we'll do one more print line saying you just deposited, borrowed, and repaid with Aave, Brownie, and Chainlink. Whew. All right, moment of truth. Let's see if this works. Whew, we did it. Repaid. You just deposited, borrowed, and repaid with Aave, Brownie, and Chainlink. Awesome work. Now, if you want to, what we can also do is we can see if this will work with our wallet address here. So what I can do is I can copy my address, go to Coven Etherscan, and paste it in here. And right now we can see that I have a whole bunch of Link and some Ether. What I can do is actually test everything that we just ran through on the Coven testnet and see everything happen right on this Etherscan address. So if we've been following along correctly and we've added contract addresses appropriately, we should be able to run the exact same script on the Coven testnet. I'm going to do one additional thing here though. I'm going to have us not repay so we can see us with a little bit of debt. So let's go ahead and run Brownie, run scripts, Aave bar to pi, and we'll change to network Coven. And now it's going to take a lot longer, as we've seen before, because we're actually making these transactions on a real network. Whoops, it looks like I got one of the DAI ETH price feeds wrong for Coven. So I can once again just go over to the documentation, DAI ETH, and it looks like this is the real address for Coven. So we'll copy that, paste it in here. Whoops. We should also probably have some WETH token. So first, let's go ahead and run our get WETH script for Coven. And we're going to change this account to get account. Brownie, run scripts, get WETH.py, network Coven from our helpful scripts. That way we can actually use our wallets correctly. All right, great. So now we have 0.1 WETH. And actually, again, what we can do is grab this address here, add token, paste it in, add tokens for the WETH token. And now we can see we have 0.1 WETH, which is perfect. So now that we have some WETH, we can run the borrow script. Aave, Brownie, run, scripts, Aave borrow, network, Coven. And wow, we can see that everything went through correctly and successfully. So since I actually commented out this repay function, we still should have DAI in our address here, in our wallet here. And again, we can see that by going to our Brownie config, grabbing this DAI token address, add token, custom tokens, next, add tokens. And we can see we do indeed have 160 DAI in our wallet. We have no WETH since it'll be in Aave now, and we have borrowed DAI instead. You can also see that we now have this AWETH if we added it from when we were working with the UI. We have this interest-bearing WETH instead of regular wrapped Ethereum. Let's look at one of these transactions. We can see that our borrow transaction gave us some stable debt-bearing DAI and also some DAI. So we owe Aave some DAI from this debt. We got some debt, we got some DAI, and we gave out some Aave interest-bearing DAI to the rest of the Aave protocol. You'll notice now, if we go to testnet.aave.com/dashboard, we'll see exactly what our script just did. We have 160 DAI borrowed, and we have 0.1 ETH deposited. If we want to repay our funds, we can do it with our current collateral or from our wallet balance. And you'll notice something. If I try to repay everything from my wallet, all the DAI that I've actually borrowed, you'll notice we don't have enough funds to repay the full amount. This is because since we actually borrowed a little bit, we've accrued some of that interest. So we actually owe more back than we originally borrowed. That's how the loans work. So when you're designing this repay functions, be sure to have that in mind. You can also have your repay be -1 to repay the entire debt. It's recommended to send an amount slightly higher than the current amount borrowed. But in any case, maybe we say we want to do from our current wallet, we'll hit max, but maybe we want to actually just repay with our current collateral. We can go ahead and repay the maximum amount. Again, we could do this all from the UI. We'll approve. And this is exactly what our repay function actually did. And now we're all repaid up. If we go back to our dashboard and we hit refresh, we'll see we just have a tiny bit of Ethereum and no more borrowed assets. Awesome. You've essentially learned everything that we need to go through for here. This is a massive step forward in teaching you how to become quantitative DeFi wizards and build really robust applications and really robust financial applications in the DeFi world. Now, something I want to point out, even though this isn't a Python course and we're teaching more about Solidity and smart contracts, it's still in your best interest to test these functions. Yes, I know they're Python functions, but it's still going to be in your best interest to test them to make sure your application always works as you expect it to. Now, I'm not going to go through this testing suite that I put here, but it's a really simple testing suite to test some of the different functions that we created. It can be really helpful, especially for something like get asset price, where the math might be a little bit off and you want to make sure it's correctly. Again, link in the description to seeing some of these tests. This is actually going to be even easier than that lottery contract that we did, since we're just testing Python functions. And again, you can test these all with Brownie test. All right, you are all doing fantastically. Now is another fantastic time to take a break, go for a walk, get some food, because our next session, our next lesson, we're going to be learning about NFTs, how to build them, use them, and deploy them.
Look, NFTs are hot right now. NFTs, also known as ERC-721s, are a token standard that was created on the Ethereum platform. NFT stands for non-fungible token and is a token standard similar to the ERC-20. Again, ERC-20 is like Link, Aave, Maker, all those goodies that are found on the Ethereum chain. An NFT, or a non-fungible token, is a token that is non-fungible. This means that they are starkly unique from each other, and one token isn't interchangeable with any other token of its class. A good way to think about it is $1 is interchangeable with any other dollar. $1 is going to have the same value of another dollar. Those are fungible tokens. That's like ERC-20s. One link is always going to be equivalent to one other link. By contrast is going to be NFTs. Those of you nerds out there would know, like a Pokemon would be a good example of an NFT. Your one Pokemon is going to have different stats, different move sets, and isn't interchangeable with any other Pokemon. Or maybe a more relatable one is like a trading card, a unique piece of art, or the like. So that's what these NFTs are. They are non-fungible, non-interchangeable tokens that, for the moment, are best represented or thought about as digital pieces of art that are incorruptible and have a permanent history of who's owned them, who's deployed them, etc. Now, like I said, NFTs are just a token standard, so you can actually make them do much more than just be art. You can give them stats, you can make them battle, you can do really unique things with them, you can do pretty much whatever you want with them, but right now the easiest way to think about it, and the most popular way to think about it, is by calling them art. 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 It's art! Or some type of collectible, or just anything that's unique. Now, they've been getting a ton of buzz recently because we've been seeing more and more of these being sold at insane prices. Like we saw Axie Infinity sell 9 plots of their land, 9 plots of their unique land, for $1.5 million. We also saw the original creator of the Neon Cat, you know this cat, sold for like 300 ETH. So like I said, they're just tokens that are deployed on a smart contract platform, and you can view them on different NFT platforms like OpenSea or Rarible. And these are the NFT marketplaces that let people buy and sell them. You obviously can do that without these marketplaces because it's decentralized, but they help and give a good user interface. So that's the basic gist of it. Let's talk some more about the standards. The ERC-721 standard, or the NFT standard. This is the basis of it all. There is another standard that's semi-fungible tokens, the 1155. We're not going to talk about that here, but you can check it out. The main differences between a 721 and an ERC-20, on ERC-20s they have a really simple mapping between an address, and how much that address holds. 721s have unique token IDs. Each token ID has a unique owner. And in addition, they have what's called a token URI, which we'll talk about in a minute. Each token is unique. Each token ID represents a unique asset. So since these assets are unique and we want to be able to visualize them and show what they actually look like, we need to define those attributes of the object. If it's a piece of art, we need a way to define what that art looks like. If it's some type of character in a game, we need a way to define that character's stats in the NFT. This is where metadata and token URIs come in. So if you know anything about Ethereum, you know that sometimes gas prices can get pretty high, especially when it comes to storing a lot of space. It can get really, really expensive. So one of your first questions might be, well, are they storing these images and these art pieces on chain? And the answer is sometimes. Back when they were coming up with NFTs and artists were deploying stuff, the ETH devs and the artists were like, yeah, art, let's do that art. I'm just gonna deploy this 1 megabyte image onto the Ethereum chain, and oh God, it's so much gas expensive. How do I hit the delete button? How do I? It's not deleting. And they realized that if they put all this art on chain, it was going to be incredibly expensive. So to get around this, what they did is they put in the standard what's called a token URI. This is a universally unique indicator of what that asset or what that token looks like and what the attributes of that token are. And you can use something like a centralized API or IPFS to actually get that token URI. Typical token URI has to return something in this format like this, where it has the name, the image location, the description, and then any attributes below. Now, if you're like me, your first question would probably be,
we pull from a single source seems pretty centralized.
This is a current limitation of the NFT ecosystem. There is often this talk of on-chain metadata versus off-chain metadata. Because it is so much easier and cheaper to store all your metadata off-chain, a lot of people will use something like IPFS that is decentralized, but does take a little bit of centrality to keep persisting, but they can also use their own centralized API. However, obviously, if that goes down, then you lose your image, you lose everything associated with your NFT. Because of this, most NFT marketplaces actually can't and won't read off on-chain attributes or on-chain metadata because they're so used to looking for the token URI. Obviously, if you do off-chain metadata, you can't do anything really cool or really interesting or have any games with your NFTs. For example, if you wanted to create an on-chain Pokemon game, all your attributes would need to be on-chain in order for your Pokemon to interact with each other. Because if it was off-chain, then that becomes a lot harder to cryptographically prove. So if you're new with NFTs and you're like, wait, this is kind of a lot of information, I'll make it easy for you. If you're looking to render an image of an NFT, add your image to IPFS, add a metadata file pointing to that image file on IPFS, and then grab that token URI and put it and set it as your NFT. The Chainlink D&D article does a great job of walking you through this and showing you how to do this, so be sure to read that if you're looking to learn how to do that.
So all the code that we're going to be working with is actually available for you in this NFT mix, Brownie mix. It's an official Brownie mix, and it allows us to deploy these 3 adorably cute dogs. And there are 2 different types of contracts that we're going to be working with. We're going to be first working with a simple collectible, and then we're going to work with an advanced collectible. The simple collectible is going to be a very simple ERC 721 standard. We're not going to really add any bells and whistles other than give it like a name. And then our advanced collectible is going to take advantage of some of those more advanced true scarcity features that we were talking about. So protocols like Avagochi and Ether cards use Chainlink VRF to get verifiably random numbers to create verifiably scarce NFTs. Something that's important to keep in mind is that in the real world, when companies create trading cards, there's no way to prove how scarce or how valuable these trading cards actually are. If we use a verifiable random number, then whoever is deploying these NFTs can't even control how rare these NFTs really are. So we get this verifiable scarcity and this verifiable rarity, which adds some value to the tokens. If you want to just go ahead and work right from the Brownie mix, you can absolutely just run Brownie bake NFT mix and then CD into NFT. And all of our code is going to be right in here. We're going to go through and deploy and develop everything from scratch because we're going to actually take some previous concepts that we've learned, improve on them, and we're going to learn a lot of nitty-gritty, interesting pieces about making this hybrid smart contract because these NFTs really are a perfect example of a hybrid smart contract. They have some off-chain component interaction with a random number and we're storing their metadata with IPFS. And I'll explain IPFS a little bit more in depth as we go on here. So let's go ahead and get to it. I'm going to go ahead and make a new directory called NFT demo. I'm going to CD into it, code, period. And perfect. I have a blank project here, and you already know what the first step we're going to do is do Brownie init to create our blank Brownie repository. Now let's go ahead and create our first contract. We'll call this simple collectible.sol. Since this is going to be a simple collectible, a simple NFT that we're going to get started with. Now, similar to the ERC20, this ERC721 standard has a number of functions that we can actually work with. We can go ahead and even look at the ERC721 non-fungible token standard on the eips.ethereum.org website. And we can see a sample interface and some sample events and some functions and kind of everything that we've grown to know and love. And once again, instead of us kind of recoding, copy pasting all of this from scratch, we're going to be using OpenZeppelin's ERC721 documentation for this. Now, we're going to be working with version 3.x. There is a version 4.x that has come out. Using version 3.x of their OpenZeppelin contracts is also, I think, a little bit easier to explain. But again, those of you who want to challenge yourself, definitely try their 4.x version. So let's go ahead and jump right into it. First, we'll do our SPDX license identifier, MIT. Then we'll choose our Solidity version. We're going to use Pragma Solidity 0.6.6. But again, most of this should work for 0.8 moving forward. And then we're going to go ahead and look at the OpenZeppelin ERC721 documentation. And we're going to go ahead and grab this line right here. Import OpenZeppelin/contracts token ERC721, ERC721.sol. You can even see a sample ERC721 that they give you. And this is actually going to be similar to the ERC721 that we're going to make. So we're going to go ahead and paste that. And of course, since we're doing this at OpenZeppelin/contracts, we're going to need to create our Brownie config. And same as always, dependencies. It's going to be OpenZeppelin/OpenZeppelin contracts. And again, like I said, we're using version 3. So 3.4.0 again. And then we'll do compiler, sulk, remappings, and we'll say at OpenZeppelin equals this. And great, let's even try to just compile this right now. Brownie compile. And perfect, it has been compiled. Now, similarly to our ERC20 that we did with OpenZeppelin, we're gonna do the same startup here. So we're gonna say contract, simple collectible is ERC721. And this is how we're going to inherit all of those functions in the ERC721 token standard here. And we can start coding our simple ERC721. Now for our ERC721, we're gonna make it be a couple of these cute, adorable dogs. So it's gonna be one of these 3 dogs. For our simple collectible, we're just gonna go ahead and use the pug here. So you can use any image that you want for this demo. However, if you want to just follow along with us, we can just download this dog and we'll call it pug, create a new folder here called img, and then I'm just going to add pug.png to this img folder. So this is going to be the NFT that we're going to deploy. We're going to deploy this very simple pug for our smart contract. So we're going to be deploying this pug. This is the image that we're going to use for our NFT. It's going to be this adorable pug. So let's go ahead and create the rest of the contract for this pug. So the first thing we're going to make is our constructor. It's going to take no input parameters. It's going to be a public constructor. And then we're going to go ahead and use the ERC721 constructor, which if we look at the documentation, we give it a name and then a symbol. We're going to use the ERC721 constructor parameters, which is going to be a name, which we're going to say is doggy, and a symbol, which we're going to say is dog. And perfect. That's all we really need to do for the first part. This NFT contract is actually what's known as a factory contract. There's a main contract, and in it, it has a list of all the NFTs and the owners that are of this type of NFT. So in this example, all of the type of NFT is just going to be this pug, and it's just going to be this dog. And we actually need a function to mint new NFTs based off of this pug. Now we can absolutely have an NFT factory contract that only creates one single NFT, but we're going to use this factory implementation to create multiple NFTs. We're going to do it with a function called create collectible. This will create a new NFT and assign it to whoever called this function. So anybody can come here and create a new puppy for themselves, or in other words, adopt a puppy. So we're going to say function create collectible public, and we're going to say returns uint256. You'll see why we need to do this in a minute. Now, when we create this collectible, all we're doing is we're assigning a new token ID to a new owner. And if we look at the Open Zeppelin ERC721 GitHub, we can see they have this safe mint function. This is the function that they use to mint or create a new NFT. This function, it takes a new address to, which is going to be the new owner of the NFT, and a token ID. Every NFT in this factory contract has a unique token ID. We're going to have our token IDs start from 0 and just increment every time we have a new token minted. This safe mint function calls this safe mint function, which calls this minting function. So if you're looking at the code here, this mint function is really the function that calls and creates this NFT. You'll see actually that they just have two mappings that they update. They update this owner's mapping, which is just a mapping of token IDs to the owners of the token IDs. And then they update this balances mapping, which is a mapping of owner address to the token count. So the number of tokens that an owner actually has. And that's all that's happening when we call this mint, or in our case, safe mint function. The difference between safe mint and mint is safe mint checks to see if a token ID has already been used or not. And this way we don't actually override who owns tokens and who owns token IDs. So we're going to use the safe mint function. So first we need to think, okay, well, we're going to need a way to count these token IDs so that every single person has a unique token ID. So let's create a global variable, uint256 public token counter, and we'll initialize it, token counter, to 0. Of course, this is the same as initializing token counter to 0, but let's just make it very explicit. So when we create a new collectible, we're going to say uint256 new token ID is going to be equal to this token counter. And we're going to iterate this every time we mint a new token. So for example, we're going to iterate that in this create collectible here. So new token ID equals token counter. We're going to call this safe mint function, since we're inheriting it from Open Zeppelin's ERC721. We need to give it this new NFT, an owner, which is going to be message.sender, so whoever calls this function. And then we need to give it a unique token ID, which is going to be this new token ID. Now, whenever we mint one, we're going to want to increment this token counter. So then we can say token counter equals token counter plus 1. And we can then return this new token ID. So we'll return the token ID of the token that we just created. And boom, if you're looking for an incredibly minimalistic contract to deploy NFTs, this is all that you need. So we can run Brownie compile to make sure we did everything right. And product has been compiled. We can see it in the build, so great job. Obviously, this might be a little dissatisfying to you after the breakdown that we just gave. How do we view this token? What does this token look like? I thought we wanted this to be a doggy. How do we know that this looks like a dog? How do we get this image on the blockchain? This is where metadata is going to come into play. Now, if we look at the original ERC721, there is this part called the metadata extension is optional for ERC721 smart contracts. As we've talked about, anytime you make a transaction on chain, it costs some gas. Even very tiny amounts of data can cost more and more gas. Images are much bigger than these little bits of data here, and they can cost a lot more gas. So when this standard was being created, the developers kept this in mind and knew that storing entire images and entire GIFs and entire videos on chain was going to be incredibly costly. So they added this piece about metadatas and token URIs. The token URI is a distinct uniform resource identifier for a given asset. This is an example of a URI and the metadata that we're going to be demoing today. A URI is just a unique resource identifier. So this can be something like HTTPS or IPFS or any URL string that uniquely points to some metadata. Your metadata file is going to look like this. It's going to have a title for the title of the NFT. It can have a type, and it can have all these different properties or stats or attributes. For example, we're going to have our pug NFT, which is going to be defined like this. It's going to have a name as pug. Description is going to be an adorable pug pup, and it's going to have what's called the image URI, which defines what the token actually looks like. And if we copy paste this into another browser, we get returned this. It's this token URI with this metadata JSON object that's going to enable different NFT platforms to actually render our NFT. So this is an example of what this pug is going to look like on different NFT marketplaces like OpenSea. Platforms like OpenSea understand that they need to show this image, they need to use this name, they need to use this description and have these traits. So if we look back at this NFT on OpenSea, we can see the name is pug. We can see the description here. If we go to levels, we see its cuteness is 100 out of 100. Now this of course leads us to a really interesting point. If we're storing the image off-chain, then how is this image decentralized? If we're storing this image off-chain, how can we guarantee this NFT is going to stay forever? Now, this leads us into a little tidbit about storing data on the blockchain. As of current recording, storing a lot of data on-chain can get incredibly expensive. The more data that you store, the more transactions that you have to make to store that data on-chain, and the more gas that you're going to have to spend. At the time of recording, Ethereum is about little less than 900 gigabytes in size. If a ton of people were to put full videos or movies or massive images, Ethereum would grow exponentially out of proportion. And this would become unsustainable for the blockchain network as a whole. So Ethereum isn't great for actually storing a ton of data. It can store a lot of data, but it's a lot better for doing the logic and the smart contracts. So there are a lot of different platforms that are actually working on this problem of storage. These platforms allow people to store data in a decentralized way that isn't going to exponentially explode the size of Ethereum or different smart contract platforms. The decentralized storage methodology we're going to work with is going to be IPFS, or Interplanetary File System. And this is where we're actually going to store our image, and this is actually where we're going to store our image so that NFT marketplaces know what our NFT looks like. Now, here's what some protocols do. Some protocols just set up a server and set this token URI to instead be from a decentralized service like IPFS and use just maybe their own centralized server. This is obviously a massive issue because if their server goes down or if they want to change the image or they want to change the stats, all they have to do is change it in their server. And this is why a protocol like IPFS is going to be a lot easier, quicker, and more decentralized version of doing this. The full solution is going to be using something with IPFS and Filecoin, but easy solutions to do that are still being built out. So for now, we're just going to use IPFS because it's free, it's quick, and it's easy. And it can be expanded to combine with Filecoin to be even easier to work with. Now, something else that I want to touch on too. When it comes to this metadata, right now, all these NFT marketplaces only know how to pull attributes from this token URI. Now, if we want to build really cool NFTs that can interact with each other, having some attributes or maybe some like attack stats or attack moves like in Pokemon, for example, or trading cards, we can't just store these in this token URI because the blockchain doesn't know anything about this token URI. So we actually need to store these attributes on chain. I'm really hoping in the future, a lot of these NFT marketplaces are going to get better at and pulling metadata from on chain. But right now, any attribute that we give our NFTs, we actually have to reproduce in the token metadata and the token URI as well. So we've just learned a lot about metadata, IPFS, token URIs, and everything like that. Let's update this simple NFT to be able to render on OpenSea and render on these NFT platforms. Because right now, if we were to deploy this, nobody would know what this doggy looks like. So let's give it a token URI. So in this create collectible, let's do string memory token URI. And after we call this safe mint function, there's another function that we're importing called set token URI. And we're going to set the token URI for the token ID and we're going to give it this token URI. This will allow our NFT to actually have an image associated with it that we can actually see. So let's go ahead and create a script that's going to deploy this NFT factory contract and then create us a collectible. So we're going to do new file. We'll call it deploy and create.py. And let's jump into our script. So we'll do def main. First, we need to start with an account. And once again, we can go ahead and create helpful scripts.py. We can go ahead and copy paste this get account function in here if you want. But of course, since we added this config wallet from key, we're going to go to our Brownie config. We'll add wallets from key, and we're going to grab our private key environment variable. Since we're using a private key, again, we're going to create a .env, and we need to export private key, and we're also going to need to export our Web3 Infura project ID. So we can just copy paste from our last project, the private key, Web3 Infura project ID, and our Etherscan token so that we can actually verify this on chain. And we'll add a new file, init.py, so that older versions of Python know that this is indeed a package. So we'll go ahead and do from scripts.helpful scripts import get account. Now all we have to do is import our simple collectible and run simple collectible equals simple collectible dot deploy. And if we look at our simple collectible, we have no constructor parameters here. So we can just do from account. And now this will have our simple collectible deployed. Now we need to actually call this create collectible function, and we're going to pass it a string, which is going to be this token URI. I'm going to go ahead and use this sample token URI that is included in our NFT mix. So if you're looking to get this token URI, look up NFT mix, Patrick Collins. Hopefully the GitHub will show right up, and we can just go right to the scripts in here in the simple collectible folder, create collectible. That was the big free. And we're going to grab this, and in our script, we're going to do sample token URI equals this. Now, when you paste this token URI in your browser, if you can't see it, you might have to add something like IPFS companion to your browser like this. Some browsers don't natively have it. So there is a link to IPFS companion for this project in the GitHub repo. But now that we have a token URI, we can call this create collectible function. So we'll do transaction equals simple collectible dot create collectible, and we'll pass in this sample token URI, and then of course we'll do from account. We'll do tx.wait. We'll wait for one block, and then if we've done this correctly, we'll actually be able to see this NFT on an NFT marketplace like OpenSea. So let's do a quick print line here. We'll do print. Awesome. You can view your NFT at, and we'll do this in F string. And this is where we're going to put the OpenSea URL for this RinkB. So we're going to say OpenSea URL, which is going to be equal to, if we pop over to OpenSea, if we pop over to this OpenSea pug here on the RinkB testnet, we can go ahead and grab this first start of the string. So it's going to be https testnets.opensea.io/assets. And then this is the address of the contract. So we can say OpenSea URL is going to be this / and we'll put this little brackets here / and then another one of these. And this is because the URL for here, testnets.opensea.io/assets, it's the contract address and then the token ID on the end here. So this is what it's going to look like. So in our print line, awesome, you can view your NFT, OpenSea.format, simplecollectible.address, comma, and we can do simplecollectible dot token counter -1 for the most recently deployed one. And then we'll run this now. Brownie runs scripts, deploy and create, network, Rinkeby. And awesome, we get this print line here saying, awesome, you can view your NFT at https://testnets.opensea.io. Just keep in mind, obviously for mainnet, we can't use this testnets.opensea.io, but assets, the address of the NFT contract, and then the token ID as well. So if we go ahead and click this, and it looks like it's already actually been rendered here in OpenSea. We could even go ahead and hit refresh metadata just in case it doesn't show up right away, but it looks like for us, it did show up right away, which is awesome. Some other kind of fun parts about OpenSea is if we go to our profile here, we'll actually be able to see all of the NFTs that we own on this testnet. I've actually deployed this doggy twice here, once to test and then once to actually do it. Great, we've created our simple collectible. Of course, no project is complete without some tests. So let's create some tests. Since we're also going to be doing an advanced collectible, I'm going to skip the integration test and I'm just going to write a really simple unit test. So we'll create a new folder, we'll call it unit. And in here, we'll do a new file, test, simple collectible.py. So let's create our first test. We'll do def test can create simple collectible. We'll just make sure that we can actually create a simple collectible. Now we'll make sure that this is our unit tests. So we'll do from scripts.helpful scripts, import local blockchain environments. And then we'll do if network.show active, not in local blockchain environments, pytest.skip. So of course we need to do from Brownie, import network, and then also import pytest. Now, something that we could do here is actually in our test, we could go ahead and even test our scripts by importing deploy and create here and testing this. We could do something like return simple collectible. And in our test, then we could do from scripts dot deploy and create, import, deploy and create. And then back in our deploy and create script, we can modify this a little bit. Instead of main here, we'll call this deploy and create. And then we'll have our main function just call deploy and create. And you'll see Brownie runs scripts, deploy and create to Pi. If we go ahead and run this, again, we can just run this on the development network real quick instead of on Rinkeby. You'll see that this does also work. Obviously, we won't actually be able to see our NFT on OpenSea because this is deployed to the Brownie temporary Ganache chain as opposed to a persistent Rinkeby chain. In our test here, we could then just run simple collectible equals deploy and create. And then we'll do an assert here. We'll assert simple collectible dot owner of 0 is going to be equal to get account. And then we'll also import get account. So we can run Brownie test, make sure this works, and perfect. Now, this was all fun and dandy, but there's a couple of things that we didn't go over and that we didn't do. So let's create a quick readme.md for a couple of notes. So number one, we didn't upload an image to IPFS ourselves. So we just used a token URI that was already existing, right? We didn't actually upload something to IPFS. We didn't go over why is IPFS decentralized. We didn't really talk too much about what IPFS is. Number three, anyone can mint an NFT here with any type of stats, right? It's not verifiably scarce or random, right? This isn't that cool. So we want to actually build an NFT project that has all these pieces where we upload the image to IPFS ourselves. We're going to talk a little bit more about why IPFS is decentralized and it's the preferred solution for storing NFT metadata. And we're going to make our NFT more verifiably random and verifiably scarce, like for things like Ether cards and Avagochi. Let's go ahead and do this project again, but we'll integrate the Chainlink VRF to make this NFT verifiably scarce and verifiably random. And then we'll also teach you guys how to upload to IPFS and work with IPFS ourselves. So let's go ahead and do this. So let's create a new file in our contracts, and we'll call it advanced collectible.sol. And what we're going to do here is we're going to make, again, an NFT contract where the token URI can be one of 3 different dogs. So if we look at this NFT mix, in the images section, there's a pug, a Shiba Inu, and a Saint Bernard, or one of these 3 dogs. We're going to make it so that when you mint one of these NFTs, you're going to get a random one of these 3 dogs. Now, I'm not going to go over stat generation and like creating battling NFTs or really games out of these NFTs. If you guys want to see a version of those contracts, check out this Dungeons and Dragons NFT. There's a link in the GitHub to see this, and it actually creates characters that can do battle and have like stats and attributes like attack, constitution, and different things you'd find in Dungeons and Dragons. This one's done actually with Truffle as opposed to being done with Brownie, but all the contracts are going to be the same other than this migrations.sol. So if you're looking to check this out, you absolutely can. It is a ton of fun. And they have some really cool images as well. So be sure to check that out if you're looking for more. Anyways, here's what we're going to be looking to do. We're going to make an NFT contract where the token URI can be one of 3 different types of dogs, and it's going to be randomly selected. So let's go ahead and do it. So first, again, we're going to do this SPX license identifier right at the top. So we can go ahead and put that there. And we're going to even use same Solidity version, and we're going to use OpenZeppelin again. So we can literally just copy and paste that from our last project. Now we're going to create our contract, advanced collectible. We're going to say is ERC 721. Great. And then, since we're going to want to work with Chainlink VRF to get a provably random NFT, we're also going to want to import at chainlink/contracts/src v0.6 VRF consumer base.sol. And of course, that means we're going to go back to here and we're going to add smart contract kit /chainlink Brownie contracts at 1.1.1. And then we're going to go ahead and add the remapping in. We'll say at Chainlink equals, boom. Awesome. So we've imported the Chainlink bit. Our advanced collectible is ERC 721, and it's going to be VRF consumer base. So same as always, let's go ahead and start with the constructor. We know from our lottery smart contract that we're actually going to want to parameterize a lot of these pieces for working with the VRF coordinator for working on different chains and different testnets. So we're going to do address VRF coordinator. We're going to do address link token bytes 32 key hash. And we can always head back over to docs.chain.link, go to get a random number just in case we forget what some of the parameters are. VRF coordinator, link token, key hash, and fee. Great. You went 256 feet. And we'll make this public as well. Add a little curly bracket there. And we can go ahead and start doing the rest of this. Of course, we need to do the VRF consumer base constructor and the ERC 721 constructor. So VRF consumer base is going to be this VRF coordinator and this link token and the ERC 721. We could parameterize these as well, but we know it's going to be a dog, so we'll do doggy and the symbol of dog, which is the same as our simple collectible here. We know we're also going to need to do this token counter bit. So we'll do UN256 token counter. And right in here, we're going to do token counter equals 0. Of course, we're going to need a key hash. So let's make this UN256 public token counter. Excuse me. We're going to do a bytes 32 public key hash. And we're going to do a uint 256 public fee. And we'll set key hash equals key hash and fee equals fee. Great. So this is a combination of a lot of the stuff we did in our lottery smart contract and some of the pieces that from our ERC 721. We need the key hash, the fee, VRF coordinator, link token, all for the VRF consumer base. Oops, I should put an extra quote here. And then we need dog, doggy, and a token counter for our ERC 721. So now we're going to create our function create collectible. So we're going to do function create collectible. And again, we're going to do a string memory token URI. But this time in our Python scripts, we're actually going to define where we're getting this token URI from, and we're going to create it ourselves. But we're going to make this public, and it's going to return a bytes 32. Remember way back in our lottery, when we did this event requested lottery winner, when we called the Chainlink VRF, we're going to do a similar thing here where we're going to make an event for whenever we request one of these new dogs. And that is also what we're going to return. We're going to return that request ID here. So since we're using the Chainlink VRF here, we can go ahead and call that request randomness function, which again, head over to the docs.chain.link. This is imported from the ERC 721. And then in that request and receive model, it's going to call back with our fulfill randomness function. We're going to need to do a couple of different things here because we want the user who called to create collectible to be the same user who gets assigned the token ID. So first we'll do bytes 32 request ID equals request randomness. And we're going to pass obviously the key hash and the fee. This is going to create our randomness request to get a random breed for our dogs. So let's go ahead and just define a little bit of the fulfill randomness function so we can figure out how we're actually going to pick a random dog. Well, the first thing that we're going to need is we're going to need some definition of what the different breeds that the dog can actually be. And again, similar to the lottery, we're going to create a new type called breed using the enum. So we're going to do enum breed, and then we're going to give it 3 types. Pug, which is going to be state 0, Shiba Inu, which is going to be state 1, and Saint Bernard, which is going to be state 3. So our breed is going to be one of these 3 breeds here. So then in our function fulfill randomness, when we get that random number back, we can use that random number to pick one of these 3 breeds. So of course we need to have a bytes 32 request ID and uint 256 random number, and we're going to make this internal override so that only the VRF coordinator can call this. And what we're going to do now is we're going to select a breed based off of this random number. So we're going to say breed, which we're saying this breed variable is of type breed. It's going to be equal to breed generated from that random number mod 3. Since we have 1, 2, 3 different breeds. Awesome. So this is how we're going to get our random breed. However, we do need to assign this breed to its token ID. So now that we have a random breed back, how do we actually go ahead and assign this? Well, we're going to have to create a mapping to do this. It'll look something like token ID to breed. We're going to have to get our token ID somehow, and we're going to have to equal it to the breed. So then our first question is, okay, well, in order for us to assign this breed to the token ID, how do we actually get the token ID? Well, we're going to grab the token ID by doing uint 256 new token ID equals token counter. And then we'll just set the token ID to breed using this new token ID equal to the breed. So we're going to want to make this token ID to breed mapping up here, to which we can do mapping uint 256 map to breed, and we'll call it token ID to breed. This way, each token ID is going to have a very specific breed based off of this mapping's results. Perfect. Okay, what else do we need in this fulfillment? We need to mint the NFT, and we need to set a token URI. Well, when we minted it before, we called this safe mint function. However, message.sender here is always going to be the VRF coordinator, since the VRF coordinator is actually the one calling this fulfill randomness. So we can't actually have this just be message.sender. We need to figure out how we can get the original caller of create collectible here. How do we get the original message.sender of create collectible? Well, the answer there is actually going to be in another mapping. When we call create collectible, we can create a mapping of request ID to sender. And this is going to take the request ID as a key, and then whoever sent it as the value. So we're going to create this new mapping at the top. And then actually let's make this other mapping public as well. We'll do mapping bytes 32 to address. And we'll call this public request ID to sender. Now in our fulfill function, the same request ID that requested the random breed is returned. So what we can do is we can say address owner or sender is going to equal request ID to sender of request ID. And then this address owner is who we're going to safe mint the NFT to. And of course, while we're matching up the functions, we don't want to forget to always do token counter equals token counter plus 1 at the end. Awesome. Now we still need to set the token URI here. So back in our advanced collectible, we're going to have to do this set token URI at some point. So let's actually think about this for a second. We're only going to know breed of our dog once this random number is returned. And we know the breed of the dog is going to be one of these three breeds. It's going to be a pug, a Shiba Inu, or a Saint Bernard. And let's actually, for now, let's even just go ahead and add those three images to our project here. Create a new folder. We'll call it image. And you can put whatever images you want in here. I'm actually just going to download the three images right from the NFT mix. Boom. And now I have my pug, my Shiba Inu, and my Saint Bernard in here. So anyways, it's going to be a pug, a Shiba Inu, or a Saint Bernard here. We're only going to know what the breed is once the random number is returned. And the breed is actually going to govern if it's a pug, Shiba Inu, or a Saint Bernard. So we technically could actually just get rid of the input parameters for create collectible, since there's going to be no token URI initially created. What we could do is we could create a new set token URI function that sets the token URI based on the breed of the dog. For the simplicity of this project, we're actually just going to create our own set token URI function that we're going to update based off the breed of the dog. A challenge for you after we finish this project is to make this even more decentralized and have the fulfill randomness function actually be the one to decide what the token URI is. But for now, in our fulfill randomness function, we're going to skip setting the token URI, and we're actually going to call it in a separate function. We're going to create our own function called set token URI. And we're going to pass it a uint256 token ID, a string memory token URI. And we're going to make this a public function. Once this fulfill randomness function is responded, the breed of the dog is going to be set, right? This token ID to breed is going to say, hey, this token ID now is associated with this breed, which is going to be pug, Shiba Inu, or Saint Bernard. All we want to do then is, now that we have the on-chain metadata, we're just going to reciprocate that with the off-chain metadata. So we're going to need 3 token URIs for those 3 dogs. We're going to need one for pug, Shiba Inu, and then obviously Saint Bernard. However, we want to make it so that only the owner of the token ID can actually be the one to update the token URI. So we can use a require function for this. We can say require, and we're going to use an imported OpenZeppelin function called isApproved or owner message sender token ID. And we're going to do a comma here, ERC721 caller is not owner nor approved. This is approved or owner function, if we go into the ERC721 GitHub for OpenZeppelin, we can find this function is approved or owner which checks the owner of the ERC-721 of that token ID. And it makes it so that only the owner or somebody approved to work with this token ID can actually change the token URI. So then we're just going to call that function called set token URI of the token ID and the token URI. Now we're actually manually going to be the ones to call this set token URI once the breed has been decided. We could, of course, like I said, use a mapping at the top that automatically routes it there, but so that we can experiment a little bit more and learn a little bit more about IPFS, we're going to leave it a little bit more general like this. And perfect. This is pretty much the majority of what we're going to need for our ERC-721 contract. Obviously, we still need to work with IPFS and getting our token URI, but for the most part, this is everything that we need. Now, I am going to introduce a new best practice here. Whenever we update a mapping, typically a good best practice is going to actually be to emit an event. So let's create an event for each one of these mapping updates. We'll call it event requested collectible. And we'll do a bytes 32 indexed request ID. And we'll also do a address requester. This requested collectible event is going to be emitted when we request ID to sender because we're updating the mapping here. This is also going to be really helpful when we run our tests so we can get this request ID, similar to what we did with the lottery. So down here, we're going to do emit requested collectible. Let's collectible here. Let's use an I instead of an A here. Collectible. And we'll pass it this request ID and then message.sender. We also update a mapping down here with token ID to breed. So we're going to do a new event. We're going to call event breed assigned. And we'll do a uint 256 indexed token ID. And then we'll do a breed. And then when we assign the breed here, we're going to emit breed assigned with new token ID and breed. So let's see if we did everything right. Let's do Brownie compile. Looks like we have a quick error here. Did you mean fee or fee? Let's do a quick underscore there. Now let's try to compile. Much nicer. All right, great. Let's move on. All right, so now let's take a little look-see at our scripts here. So we have this deploy and create script, which is going to work for our simple collectible. So let's go ahead and actually give them both their own folder. So we're going to do a new folder. We'll call one simple collectible. And we'll do another new folder called advanced collectible. And we'll grab this original deploy and create, and we'll place it into this simple collectible folder here. Awesome. Now, if we wanted to run this, we would do Brownie run scripts, simple collectible, deploy and create, and we can go ahead and test this out on our local ganache here. And cool, looks like it's working correctly. Great. So now let's create our advanced collectible script. And a lot of what we're going to do is going to be the same as this simple one, deploy and create. So I'm actually going to copy this. We're going to create a new file called deploy and create.py. We're going to paste everything in here. But we are going to change a couple things up. So let's do a little bit of refactoring first. So this OpenCRL, we're going to be accessing in a couple of different scripts. So we're actually going to take this, copy it, get rid of it in our deploy and create here. And we're going to move it to our helpful scripts and place it under here. OpenCRL equals this script right here. And now what we do in our simple deploy and create is we're going to do from scripts.helpfulscripts import OpenCRL. We're going to delete that here. So now in this script, this OpenCRL is going to come from our helpful scripts, which is what we want. And we're going to do the same thing for our deploy and create for advanced. Okay, great. So I've now copied and pasted all the code from deploy and create into this deploy and create for our advanced collectible. So let's go ahead and modify this now. So instead of from Brownie import simple collectible, we're going to import advanced collectible. And we're going to do the same thing down here. And I'm even just going to go ahead and delete everything before this. We're going to change this to advanced collectible. And awesome. Okay, this is going to be our starting point. And we can even get rid of this sample token URI. Great. So this is going to be our new starting point. We've done a little bit of refactoring. Now OpenSea URL is going to be in the helpful scripts. We're pulling in advanced collectible instead of simple collectible. And the rest applies. We're still using our get account to get the account. And now we have this advanced collectible equals advanced collectible dot deploy. Of course, our advanced collectible has a different constructor. It's got a VRF coordinator, a link token, a key hash, and a fee. So we're going to have to add those as the parameters in here. We want to work with Rinkeby for this because the OpenSea marketplace right now for testnets only works with Rinkeby. So that's why we're going to work with Rinkeby here. So let's get started and just grab those Rinkeby addresses first. So our advanced collectible needs a VRF coordinator and a link token. So if we head over to the Chainlink documentation, we go to contract addresses for the VRF. We can scroll down to Rinkeby, grab the VRF coordinator here, and same as before, we'll jump into our Brownie config. We'll do networks, Rinkeby, and we'll do VRF coordinator. We're also going to need the link token here. So we'll do link token. We need the key hash. And we need the fee, which is going to be 0.1 link, which we can do fee as 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, which is going to be 0.1. You can, of course, just copy and paste Brownie configs over to different projects because these values are always going to be the same. Now in our advanced collectible deploy and create, we can go ahead and add those variables in here. Since we're going to be interacting with actual contracts that are on chain, and we're going to want to be able to flip back and forth between the mock versions of them, we're going to bring back that get contract function that we used before. This is the function that's going to be smart enough to know if we need to deploy a mock or just grab from an actual contract. I'm going to show a little fast forward of me rebuilding this function, but feel free to copy and paste it from our last project. Now, something that we do need to talk about though is our deploy mocks function. The syntax here is going to be basically exactly the same. However, we do need to deploy a couple of mocks, so make sure you have these in your deploy mocks function. Specifically, we're going to need a mock link token and a mock VRF coordinator. And again, feel free to just grab these from our last projects. And then, of course, be sure to add your contract to mock dictionary, where the link token is mapped to the link token, and the VRF coordinator is mapped to the VRF coordinator. If you guys look in the GitHub repo, there's a couple try catches there that just make it a little bit nicer for error handling. But this is basically the entire script. So now what we can do, we can go back to our advanced collectible deploy and create, import this get contract from our helpful scripts, and we'll just replace this with get contract VRF coordinator. Get contract link token. And then for key hash and fee, since these don't really matter, these can be whatever we want, and these aren't really contracts, we can go back to our config. We'll add the development network, and we'll just add key hash and fee. And again, since it's just testing, we can just go ahead and make them exactly the same as Rinkeby. Whew, done a lot of work. Now, let's go ahead and run this on the development network again. So we'll do Brownie, run scripts, advanced, deploy and create, no network, so it's going to default to development. Let's see what happens here. And awesome. So we can see we actually did a couple of things here. So first, we deployed this mock link token. Then we deployed our mock VRF coordinator. We finished that. And then we deployed our advanced collectible all on a local network. So let's go ahead and continue here. Once we deploy this code, we're going to want to fund this contract with some link. The reason we're going to want to fund it with some link, of course, is so that we can call the random number. I like to have my funding with link also in a function. So we'll do fund with link, and we'll give an address, advancedcollectible.address. And let's go ahead and create this function in fast forward. We're going to fast forward this as well, but feel free to copy and paste your fund with link functions from past projects. Or if you want to slow this down and follow along, feel free to do that too. Let's go back to our deploy and create. We now have this fund with link that we're going to do right here. And then all we have to do now is call our create collectible function here. So we'll just do advanced collectible dot create collectible. Of course, from account. And we'll do creating TX. We'll wait one block confirmation. And then we'll print new token has been created. So we are definitely going to want to test this because we have a number of custom scripts here, right? So let's go ahead and just do a manual test. So we'll do Brownie, run scripts, advanced collectible, deploy and create, and we'll do it on a development network. Whoops, we got to add Ether here. Sorry about that. In the Web 3.2 way, 1 Ether. So let's go ahead and run the script again. And all right, it looks like everything worked. Everything was deployed. New token has been created. Great, this is fantastic. Now, ideally, before we do an integration test, we would, of course, write some tests. But I want to teach some things that are easier to demonstrate on an actual testnet. So we're going to go ahead and deploy this to an actual testnet before we write our tests. So we're just going to run the script again and do -- network rank B. And awesome, a new token has been created. So what we can do is we can grab the contract address once again. We'll paste it into the rank B Etherscan, and we can see everything in here. We can see we've given it a little bit of link. We can see our 2 function calls. One is going to be the contract creation. One is going to be create collectible. Our contract has already been auto-verified, actually, because I verified this contract on rank B already, and Etherscan says, this bytecode is the exact same of another contract that we've already verified. And if we go to read contract and we go to token counter, we'll see 1 token has been created. We've actually created our first token. Now what we can do in our advanced collectible scripts, we can create a new script and just call it create collectible. .py. And in here, we'll just create a collectible. So all we have to do is we'll do def main per usual. We'll have to do from Brownie, import advanced collectible. We'll import account from our helpful scripts. We'll import fund with link. In our main function, we'll do account equals get account. Of course, we need to import this as well from our helpful scripts. Then we'll do advanced collectible equals advanced collectible -1, because we just want to get the most recently deployed. We'll fund this contract with link. So we'll do advanced collectible.address. And we'll also choose an amount here. We'll just do web 3.2 way of 0.1 with Ether. So that means we also have to do from web3 import web3. Then we'll do transaction. Then we'll do creation transaction equals advanced collectible dot create collectible from account. We'll do creation transaction dot wait. We'll wait 1 block confirmation, and then we'll print collectible created. Oops, sorry, I actually don't have to import account here, or accounts, excuse me. And sorry, this actually needs to be amount equals, excuse me. Now let's go ahead and run this. And what we're going to do is we're going to fund our advanced collectible with link, which is 0.1 link. And then we're going to create a new NFT. Awesome, collectible created. So if once again, we take this address, go back over to Etherscan, do a quick refresh here. We go to our contract, read contract. We look at the token counter. It may still be 1, so you might have to give it a second for the Chainlink VRF to respond. Once the Chainlink VRF responds, we'll see 2 in here. We can also check the token ID to breed. If we look at the 0th one, we'll see the breed is 2. And if we look back at our contract, the advanced collectible without soul, we know that if the breed is 2, that means it's a Saint Bernard. See the token ID of 1, it has a breed of 1, so it got randomly assigned a Shiba Inu. Awesome, so we have tokens and they get randomly assigned breeds. Fantastic. As you can see, we're doing kind of a lot of manual testing work here, right? So what we're probably going to want to do instead is, you guessed it, automate these tests. Now we can go ahead and want to deploy advanced collectible. So we can go ahead and import that deploy script that we just wrote. So we would do from scripts dot advanced collectible dot deploy and create, import deploy and create. And then all we have to do is call deploy and create. In this function, we'd probably want to then return the advanced collectible contract so we can make sure that we actually get what we want here. So we'll say advanced collectible equals deploy and create. And that'll be our acting step. At the beginning, we'll do arrange. And then we'll do an assert of, we'll just check to see that the token counter has been increased. We'll do assert advanced collectible. The token counter is equal to 1. All right, great. So this will return our advanced collectible. However, we know that since we're actually going to be working with a mock VRF coordinator, if we look at our advanced collectible, we know that the bulk of the work actually comes in this fulfill randomness function. And we're going to have to tell our mock to actually return and call this function. So in order to do that, we should probably also return this creating transaction here so that we can get the request ID. Remember how in our lottery, we actually just directly called everything. And we needed this request ID to call this callback with randomness function. In our tests here, we're actually using our scripts a little bit. So we could either just go ahead and write out all the steps similar to what we did in the lottery, or we could adjust our scripts a little bit. For simplicity here, we're just going to go ahead and have this deploy and create function also return the creating transaction. This way, we can go ahead and get the request ID. So back in our test here, that means we have to do deploy and create equals advanced collectible and creation transaction. Now that we have this creation transaction, we can use it to get our events. And again, if we look back in our advanced collectible, we can see here that we're emitting this requested collectible with request ID. So we can go ahead and do request ID equals creation transaction dot events. We'll add the name of our event here, which is requested collectible, and then we'll get that request ID. Once we have this request ID, we can then go ahead and grab the VRF coordinator. So from our scripts, we'll grab this get contract, and we've coded our get contract in a way that if the mock has already been deployed, again, if we go back to our helpful scripts, if the contract has already been deployed, then we're just going to go ahead and grab it. So since here, our mock will have already been deployed, so we don't have to redeploy it. So we can just do get contract, VRF coordinator dot callback with randomness. And we'll use the request ID. We'll pick some number like 777. We'll give it to the address of our advanced collectible. And remember, we're going to be calling the callback with randomness. This is what a real Chainlink node is actually going to call back. And it just needs the request ID, the randomness number, and a consumer contract. So request ID, random number, and then the consumer contract. And then of course, we have to do a from account, from get account, and we'll import get account as well. And now we can move into our cert phase. So first, if this is correct, then our token counter should be at least 1. So we can assert advanced collectible dot token counter is greater than 0. Or we can be a little bit more specific here, equals 1. We also should technically be able to get the breed and figure out the breed of this first token, of this first collectible. Let's go ahead and parameterize this 777. We'll call it random number equals 777. We'll place that here. And then what we can do is we can say assert advanced collectible dot token ID to breed of 0, right? In our fulfill randomness, we're going to assign the token ID to being the breed. And the breed is going to be this random number mod 3. So in our test, we can say the token ID to breed of dog 0 is going to be equal to random number mod 3. And this is pretty much our full test. So let's go ahead and run this. We can do that test with -k. Whoops, it looks like our simple test has actually got an error now. We're getting this module not found. No module named scripts.deploy.create. This now, since we actually changed it, is going to be scripts.simple collectible.deploy and create. So now if we rerun our test, we'll see Brownie isn't going to error out anymore. So even though we skipped this test, Brownie still compiles it to make sure that everything makes sense. But what we see here is fantastic. Our advanced collectible unit test has worked perfectly. Let's go ahead and make an integration test for our advanced collectible here. So now we'll have our test folder here, and we'll have unit, and we'll have integration. Our integration test is actually going to look really similar to our advanced collectible here. So I'm just going to go ahead and copy everything. New file, test, advanced collectible, integration.py. And we'll just paste everything in here. Now, the only thing that we're going to have to change is that we're not going to be the ones to call back with randomness here. So we can remove this part. We also don't need the request ID anymore since the Chainlink node is going to be responding. This means that the breed that we're going to get is actually going to be random. So we can get rid of that assert as well. All we need to do is wait for the transaction to get called back. So we're going to import time. And instead of us calling back with randomness, we're just going to do time.sleep. Then we'll wait 60 seconds. Test can create collectible. We should also give this a different name. Integration. Now we should be able to test this on a RINKB chain, and our token counter should indeed increase with the Chainlink node actually responding. So now we can run Brownie test -k, just that test, --network RINKB. Oh, whoops. Right now we're skipping this because we're saying only for local testing. Now, since this is going to be our integration test, we're going to do the opposite. If network.showActive is in these local blockchain environments, then we're going to skip it and say only for integration testing. All right, great. So now we have a quick and dirty integration test that we can run. We're not going to run it for now because we're going to be working a lot with this RINKB chain and we're going to be deploying a lot of different things. And we don't want to wait so long. So this is fantastic. We have a way to deploy this. We have a way to get these new collectible tokens and create them. But if we were to take this address right now and try to view this token on something like OpenSea, we would get nothing back. We wouldn't get any result. Right now, our token doesn't have a way to be viewed or be visible by everybody else. These NFT platforms don't know what they look like. And again, this is where that set token URI is going to come into play. So we have to figure out a way to host an image and host all the metadata for our token URI. And the way that we're going to do this is by using IPFS. And this is a lot better than actually hosting this on our own server because anybody can then go ahead and host this image or this metadata themselves. Now there's further improvements to this with something like Filecoin, where you actually pay to have your image hosted forever. However, IPFS can hook into Filecoin in the future and is going to be a good enough solution for what we're looking to do here. Just keep in mind that what we do not want to do is run this on a centralized server. When we spin up our IPFS node, we will be the only node that actually runs and actually hosts our image. However, the image is open for anyone to pin to their nodes as well. So it's much easier for us to host our images in a decentralized manner. What's bad, obviously, is if we just had the image stored on our own centralized server, because if our server goes down, then that URL no longer exists. If at least one node on the IPFS network is hosting this image, it will be available for anybody to see. So that's why it's going to be a much better solution than some centralized server. As I mentioned, decentralized storage is a topic that's getting better and better, and we're looking forward to seeing more and more ways to interact with them. In any case, we need to create an IPFS node that's going to host some data that looks like this. Or, like what we saw with our simple collectible, it needs to host metadata that will look like this. We both have to host a metadata file and an image URI file, which will host the actual image. Both of these need to be stored on IPFS. So let's go ahead and create a new script called create metadata, which will read off-chain and create our metadata file. So we'll start our scripts, per usual, with def main. And we'll get the most recently deployed advanced collectible using this -1 syntax. Of course, we're going to do from Brownie import advanced collectible. Once we have this advanced collectible, we can then loop through all of the tokens and actually figure out the metadata for each one of them. So we'll do number of advanced collectibles equals advanced collectible dot token counter. Because we want this create metadata to create the metadata for every single token that we've created. Do a quick print line here, just saying print, you have created number of collectibles. We even run this really quick. Brownie runs scripts, advanced, create metadata, network Rinkeby. Since we've already run this on the Rinkeby chain, we'll see you've created one collectible. If I were to run our create collectible script again, and then our create metadata script, we'd of course get more. But right now we only have one collectible. Now let's loop through all these collectibles and create their metadata. So we're going to create that file that looks like this, and it's going to have the name, which is going to be based off of the random breed that I got. It's going to have the description, which is based off of, again, the random breed that I got. It's going to have an image, which will also be based on the random breed that I got. And I just put some attributes in here, but again, these attributes. So we're going to say for each token ID in the range of number of advanced collectibles. For each one of these advanced collectibles, first we need to get the breed. So we're going to say the breed. The breed is going to be equal to advanced collectible dot token ID to breed of the token ID. Now, advanced collectible dot token ID to breed, this is going to return an integer, right? Because again, in our advanced collectible, this enum breed is going to be 0, 1, or 2. So we actually want to create a quick mapping that represents that 0 is Pug, 1 is Shiba Inu, and 2 is St. Bernard. So I actually like to create this in a helpful script called def get breed. And then it takes, as an input, it takes a breed number, and it uses a switch statement. So up top, we'll say breed mapping equals 0 is going to be Pug, 1 is going to be Shiba Inu, and 2 is going to be St. Bernard. So in this get breed function now, we can just do return breed mapping of that breed number that we get. So Instead of doing advanced collectible, the token ID to breed, we can now just do get breed. And this will return the number, and this will return the actual string. So we can just do from scripts .helpful scripts import get breed. Now that we have the breed, we can start creating this metadata file. Now what we're going to want to do is we're going to want to have some type of format for our contract to always pull from. So what I like to do here is I'll create a new folder called metadata. And in this folder, I'll have a new file. Called sample metadata.py. And then I just have metadata template equals, and then I just have this template that we're always going to use. Now in here, we're going to need a name, and then we're going to leave the name blank because we're going to want to fix it later. We're going to have a description, which we're also going to leave blank for now. We're going to have that image URI, which we'll also leave blank. And then we're going to have some attributes, which should be blank for this dog because we don't actually have any on-chain attributes, but I'm just going to go ahead and add some to show you what you could do if you wanted to give your dog some stats. You know, maybe cuteness, maybe raw power, maybe speed, agility, you know, whatever you want to do. So we'll do trait type, going to be cuteness, and then value is going to be 100. This would basically say, hey, there's a trait type called cuteness, and the value of that is 100. So the cuteness of the dog is 100. So now once we have this sample metadata file, we can import this into our script here. So we'll say from metadata dot sample metadata import metadata template. And another quick note, you might have to put a __init__.py file in that metadata folder if you're working on older versions of Python. And we can start creating our new metadata file for this breed, for this dog. We'll want to save each collectible under their network and with their token ID. So let's go ahead and create a new folder. We'll call it RinkB, and this is where we'll save all of the RinkB metadata for all these collectibles, for all these token IDs. Now, before we actually save it though, we should just check to make sure that the file doesn't already exist, right? Because if the file already exists, that means we've already created the metadata for that token and we don't need to. So we can just go ahead and get the metadata file name, which is going to be equal to /metadata /network.show active. Of course, this means we need to import network from Brownie / the token ID with a hyphen with the breed.json. Just to make sure we're doing this right, we can even just print this out. Do a quick manual test. Brownie runs scripts, advanced, create metadata, network RinkB. So this will be the name of the file. So metadata, RinkB, token ID, and then the breed.json. Okay, cool. Now we can actually check this to see if this already exists. And we're going to use a Python library called path. So we're going to say from pathlib import path. And we're going to say if that path, this metadata file name .exists, if that path exists, we'll do a quick print saying metadata file name already exists. Delete it to overwrite. This way we won't accidentally overwrite metadata that we've already created and do extra work. So if it exists, we'll print that out. Great. Otherwise, we can go ahead and printf, creating metadata file name. We can even run this real quick. Great, you have one collectible, creating metadata file. Perfect. So let's go ahead and start creating this metadata file. So we're gonna have to give it a name, description, image URI, and we're not gonna give it any attributes though. So just name, description, and image URI. So name is easy enough. Since this is a dictionary or a mapping in Python, we can actually just go ahead and start mapping. So up above before this if, we'll do collectible metadata. It's going to be equal to this template. So this is going to be where we store all of our metadata. We'll say collectible metadata of name is just going to be the breed. So if it's a pug, the name will be pug. If it's a Shiba Inu, name will be Shiba Inu. If it's St. Bernard, name will be St. Bernard. And we'll give it collection metadata description is going to be equal to, we're going to do an F string here, and adorable breed pup. Now, if we print out this collectible metadata, we should see at least the start of the metadata, which we do. Great. Name, St. Bernard, description, and adorable St. Bernard pup. Of course, you'll have a different random breed, but it should look something like this. Now, we're going to need collectible metadata image URI. This is where we're going to have our image already uploaded to IPFS so we can assign it to our metadata here. So how are we going to do this? Well, we're probably going to need some upload to IPFS function that's going to return our image URI. And then we can just set that image URI to the collectible metadata of image. So let's go ahead and start doing that. Let's create our upload to IPFS function. Now, in order to upload to IPFS, we of course need to have the images ourselves. I already have them downloaded here. And again, you can download them right from the GitHub yourselves if you like. To make this a little bit generic, we'll have this upload to IPFS take a file path. That way we can pass this image URI upload to IPFS. We're going to give it some type of file path here. We're going to have to grab that image path. So we'll grab that image file name by just doing breed dot lower, because right now our breeds are all uppercase. So we're going to want to make it lowercase. Then we're going to replace the underscores with hyphens .png. So we'll say plus .png. And then, you know what, let's just go ahead and add the full path here. So we'll say /image / plus breed.lower. Perfect. So, and then we'll even change this to image path. And then we can pass this to our upload to IPFS. So this file path now is going to be the location of the object that we're going to upload to IPFS. We're going to use this path library to actually grab that path to upload it to IPFS. So we're going to say with path, file path, dot open RB as file path. Now this is a little bit of sophisticated Python here. What we're doing is we're taking this path here, we're opening the file. RB means we're going to open it in binary. Since these are images, that's how we're going to actually open it. And we're going to upload the binary actually to IPFS. And then as FP, so we're saying this opened file is going to be named FP or file path. We're going to do image binary equals fp.read. And that's how we actually read the whole binary. And now this whole image is stored as binary in this image binary here. Now here's where we're going to do the upload stuff. Now to get started here, we're actually going to have to download the command line for IPFS. Download command line IPFS. We'll come right to the docs here. And again, there's going to be a link in that GitHub. And in here, there are instructions to download it for whatever system that you're working on, right? If you're working on Windows, if you're on Linux, if you're on Mac, these are the different ways to actually download this IPFS command line. You'll know you've done it right if you can type IPFS -- version and you see something like IPFS version 0.9.0. It's important to note that we could also do the IPFS download desktop, and we could download the desktop version of this, and we'd see a user interface which looks something like this. We could upload our files manually and then manually go ahead and grab those files and place it into our scripts. But we're engineers, we want to do this programmatically. In any case, once we have this API downloaded, we can actually follow the documentation here, the HTTP API reference, for actually uploading our code. We're going to be mainly working with this endpoint API v0/add, as this is the endpoint that's actually going to add our file or directory to IPFS. Now, what we're going to want to do is we're going to actually upload our images to our own IPFS node. We can run our own IPFS node by doing IPFS daemon, and we'll see an output that looks something like this. We can even see a web UI using this web UI URL here. This will look similar to what the IPFS desktop looks like. But again, we're going to work just mainly from this daemon from our own IPFS node. Congratulations, you're running your own IPFS node right now. As you can see, it's currently running on our own local host right here, HTTP 127.0.0.1 at port 5001. So to actually upload this, we first need to get that IPFS URL, which is going to be equal to this URL right here. Paste. Now we want to make an API call or a post request to this endpoint using this API v0 add. And these are all the different parameters that this add can actually take in so that we can actually post it to IPFS. For those of you familiar with curl and you want to test this out using a curl, I've added a curl into this create metadata file as a comment so that you can actually go ahead and test this if you want to use this. Now, what we're going to want to do to keep working with our scripts is you should have like a little plus button somewhere on your VS Code. We're going to hit that plus button, and now we're actually going to have two different shells. One which is running our IPFS node, and one which is running our bash or ZCH or whatever other shell that your OS natively works with. Now that we have this IPFS URL, we're going to grab the endpoint, which is going to be, again, this right here, -API -v0 add, and we can make a post request to it. So for us to do that, we're going to say response equals requests.post. We're going to do the IPFS URL plus the endpoint, and we're going to say the files that we're going to upload is going to be equal to file image binary. Requests is a Python package that we're going to import. So we're just going to say import requests. Now, if we go back to the IPFS documentation, we can scroll down to see what the response looks like. It's going to return a bytes, a hash, a name, and a size. Now, if we look at this sample token URI, we can see the API call here. IPFS stores all its data using a hash. And if we're looking at this, the simple collectible, this hash here is the hash that represents this pug.json file. Everything in IPFS gets hashed, and every single piece of data has a unique hash, which is why it's so fantastic. If we were to change anything with this image, this hash would be drastically different. All we need to do is get the hash that IPFS gives the image that we upload, and we can go ahead and plug it into a template URL like this one here. So what we're going to do then is we're going to say IPFS hash is going to be equal to this response.json, since we're just going to JSONify the response to make it look like this response here. And we're going to grab that hash, right? Since it's going to return this dictionary. And we just want the hash here. Then we're going to give it a file name by saying it's going to be that file path dot split. We're going to do some fancy Python stuff here. We're going to say -1 to 0, which basically all this line is doing is saying, if we have ./image/pug.png, we're going to split it up by these slashes into an array, and we're going to grab the last part of the array. So we're basically just changing this to this with this line right here. Then with this, we can get the image URI, which is going to be equal to an F string again, https ipfs.io/ipfs/ipfs hash file name equals file name. And it's this format right here which will give us this. So if I go ahead and even just copy paste this under as a comment to show you guys, we see this part's exactly the same And then this is that hash here, represented here. And then we have question mark file name equals, and then the file name. So excuse me, this is actually going to be like 0-pug. 0-pug. And that's exactly what we need. We need this image URI. So we'll do a quick print image URI. And then we'll go ahead and return the image URI. Now, since we're actually going to be testing this with IPFS, we can add a new integration test. So we'll call this test IPFS upload.py. Now, you might want to write a test for this, and we're not going to do one, but I challenge you to later on maybe come back and write your own test for this upload to IPFS. For now, we're actually just going to manually test it. So we're going to go back up to our script here, and we're going to run image URI equals upload to IPFS image path, and then we're going to get printed an image URL. Since we're working with the St. Bernard here, we should get a St. Bernard image URI. So if I run Brownie, run scripts, advanced, create metadata, network Rinkeby. Let's see what happens. I needed to add brackets here. Sorry about that. Now let's try it again. Awesome. We were able to create this metadata file. Now, if we go ahead and copy this and paste it, perfect. We see exactly what we're looking for. We see our St. Bernard. Awesome job. And this has been uploaded to our own IPFS node. Now, I want to show you guys actually another service and another way we can actually upload these to IPFS. Some people don't want to run their own IPFS node because they're not actually going to be keeping it running the whole time. Anytime their node goes down, this means that nobody will be able to see your image unless somebody else pins your image or uses your image. So what I also like to do is I like to upload it to some other third-party service as well as uploading it to my own IPFS node. So I like to create another script actually called deploy to Pinata. So let's go to scripts, new file, upload to pinata.py. So Pinata is an IPFS file management service, and they actually will pin whatever files that we're working with as well. So we'll have it pinned in our node, and they will have it pinned as well. So we can go ahead and register. Awesome. This is what Pinata looks like. It's a way to upload and work with IPFS, and they'll give us some extra support. And they have a free tier, which is fantastic as well. They have some wonderful documentation as well under this documentation section. So let's go ahead and upload this to IPFS so that when our node goes down, our images don't go down. So we'll do Pinata base URL is going to be equal to https://api.pinata.cloud. And you can find all this in the documentation as well. If we scroll down the documentation, we're going to be using this pin file to IPFS endpoint here. And you can see that entire endpoint right here with the base and then the endpoint. So we're going to copy that endpoint. We're going to say endpoint equals pinning/pin file to IPFS. We're going to choose some file path. And for us, we're just going to do ./image/pug.png. Of course, if you want to upload some other image, you could, change this file path, or you could even do some type of for loop to pin everything in the image section here. Again, we're going to do file name. We're going to use that same syntax as before. We're doing file path .split / some fancy Python stuff just to get this last part. And we also need to use some headers in this post request. So it's a type post request. We need to use some headers here. So we're going to say headers equals, copy this, Pinata API key, which is going to be some API key. And then we also have this Pinata secret API key, Pinata secret API key, which is going to be something else. We can find these two API keys. If we scroll all the way down, we hit API keys, create a new API key. I'm going to call this, you can make this an admin key. I'm just going to do limit max users, limit max uses. I'm going to set this to 200. because I'm going to make this a public key, so I don't want people using this a million times. Please make sure you select at least one permission. Pin file to IPFS. For those of you guys watching, you can absolutely just grab all of these if you want. You can make this an admin, do whatever you want to do here. Since I'm only going to be using this pin file to IPFS, that's all I'm going to do. Hit create key, and here are our tokens here. So our API key is going to be right here, and we're going to copy that. We're going to open back up that .env and add this as one of our environment variables here. So we're going to export Pinata API key equal to that key there. This API secret we're going to copy, and we're going to do export Pinata API secret equals that key there. And we actually don't need this JWT, but if you guys wanted to, you could copy it as well. So now that we have them in our .env file, these are now going to be environment variables that we can use. And Brownie is going to automatically put them into our environment. So what we can do then is we could do os.getEnv Pinata API key. And then, of course, we're going to have to import os. And then for our secret key, we're going to do the same thing, os.getEnv Pinata API secret. And this is how we get those two headers for uploading to Pinata. Then we're going to do a lot of the same code we did before. We're going to say with path of file path.open RB for the binary as FP. Of course, since we're using path, we're going to do from pathlib import path. We're going to do the same piece, image binary equals fp.read. Response is going to be equal to requests, which we have to import requests. Import requests. Dot post Pinata base URL plus that endpoint that we have. And for files, it's going to be equal to file. And we're going to upload a couple of things here, though. We're going to give it a file name. We're going to do the image binary, and that is getting really annoying when it keeps getting in the way. File name, image binary, and then outside of these brackets here, we're going to do comma, headers equals headers. And then we're just going to print response.json. So to have this run in Brownie, we're just going to do a def main function here. A nice little trick we can do is we can select all this text and just hit tab and it'll move it over one. And perfect, we can now run this inside of Brownie. So we can do Brownie run scripts, upload to Pinata, and perfect. We get a little output that's going to look something like this. It's going to give our IPFS hash, the pin size, the timestamp. So now if we go back to Pinata, we go to pin manager, do a little refresh here. We now see our pug has actually been uploaded to Pinata. Awesome work. We're going to keep going using the IPFS daemon to actually upload things. But if you want, you could totally swap out this upload to IPFS to use that script that we just created to upload it via Pinata instead of our own IPFS node. Anyways, this upload to IPFS is going to return this image URI. So we can go ahead then and set the image URI. It's going to be set on this collectible metadata image. And then all we have to do is dump this collectible metadata into its own file and then upload that as well to IPFS. We'll dump this to its own file by doing with open metadata file name, and we open it with a W, which means that we're going to write as file json.dump collectible metadata to the file. So we're going to have to import JSON to do this. And what this is going to do is just going to dump this dictionary as JSON to this collectible metadata file. Then we can upload to IPFS also this metadata file name. And this upload to IPFS should print out the image URI, or in this case, the metadata URI. So let's go ahead and try this out. So remember, we do need our IPFS daemon running. And let's go back to our scripts and we'll do Brownie, run scripts, advanced, create metadata, network, rank B. And boom, okay, so here is our image URI, which if we click this, we'll be able to see looks just like this. And then here is our uploaded St. Bernard metadata file, which is fantastic. So now we have both a metadata file and we have an image URI. This is fantastic. We've uploaded both of these to our IPFS. And if we scroll over, go to our metadata file in RinkB, we'll see we have this new file in here because we've gone ahead and saved it in here. It has everything that we need. It has St. Bernard, it has the description, it has this image URI that we just created, and it has some attributes that, again, we're basically ignoring. Now, to make our lives a little bit easier, and since I've already actually uploaded these to IPFS myself a couple times, and since the hashes of these are going to be the exact same for all of us when we upload this, we're going to go ahead and just quickly refactor this to make it a little bit easier so we don't always have to have IPFS running. So in our .env, I'm going to add a new environment variable called upload IPFS, and we're going to set it equal to false. So now down here, I'm just going to say if os.getEnv upload IPFS equals true. Anyway, since we're going to do OS here, we're going to do import OS. And before this, I'm even going to do image URI equals none. And we're going to say image URI equals image URI if image URI, which again, I know this could be a little confusing, but we're saying we're setting image URI to whatever image URI is. If image URI isn't none, else we're going to create a mapping called breed to image URI of the breed. So again, since I've already uploaded them, I already know what all these image URIs for these 3 dogs are going to be. So up at the top, we're just going to create a new mapping called breed to image URI equals, I'm actually just going to go ahead and copy paste this whole thing. Now you can skip this. You don't have to refactor here. And you can just always have your daemon running and always upload to IPFS. It's a little bit quicker to not always have to do that. Again, this brief image URI is in the GitHub repo. Feel free to just copy paste it to use it. You can even click the links to check it, to check to see that those image URIs are really there. And this is what we'll use. So back down here, brief image URI, perfect. And then we're also going to add if, again, os.getEnv upload IPFS equals true. Then we're also going to upload to IPFS down here. But this is to go and actually just show you how exactly we could upload all this stuff to IPFS. Since I've already done it, we're going to make it a little bit easier on ourselves. Another thing that you might do is you might actually save all these URLs to their own file, to their own JSON object, maybe inside of the metadata folder, maybe under RinkB or something. And then you could go ahead and just pull directly from those files. Same thing with the metadata. Once we upload to IPFS, we're not actually going to save these URLs anywhere. You could absolutely 100% after you run this upload to IPFS script, we could go ahead and save it to a file and pull directly from there moving forward. But awesome. Okay, so we've done a lot of work here. We have uploaded to IPFS our metadata and our image URIs. So we have everything that we need to actually just set the token URI finally for our advanced collectible. We finally can call this set token URI function. So let's go ahead and do this last bit here, this last set token URI function. So let's go to scripts, advanced scripts, create a new file. We'll call it set token URI, uri.py. And this is where we're going to set the token URI. So we'll do def main. And then here we'll do a quick printf, working on network.showActive. Of course, since we're using network, we'll do from Brownie import network. We need to close that there. And let's grab the most recent advanced collectible. It's going to be equal to advanced collectible -1. Since we're using advanced collectible contract, let's import that from Brownie. Let's once again loop through all the tokens that have been deployed. So we'll do number of collectibles equals advanced collectible dot token counter. Do a quick print. You have printf, excuse me, number of collectibles, token IDs, and let's loop through this list of collectibles again. So we'll say for each token ID in range, number of collectibles. First, we'll get the breed, saying breed equals advanced collectible dot token ID to breed of the token ID. We actually have to call this get breed function again, which luckily we generalize, so we can do from scripts dot helpful scripts import get breed. And now let's first, before we actually set the token URI, let's check to see if it already has a token URI set. So we're going to say if not advanced collectible dot token URI of token ID dot starts with HTTPS. So what this line is doing, I know it's a little bit long, is we're grabbing advanced collectible dot token URI of the token ID. So we're grabbing this token ID's token URI, and we're saying if it doesn't start with HTTPS, that means we know that it hasn't been set. So we can go ahead and print setting token URI. Let's actually make this a printf of token ID, and then we can set the token URI. So I'm actually going to generalize this out into its own function. So let's go ahead and we'll do def set token URI. And as inputs, this is going to take the token ID, the NFT contract, which is going to be our advanced collectible contract, and the token URI. So the first thing that we're going to do, we're going to say account equals get account. So we're going to grab this get account, of course, from our helpful scripts, because this set token URI is actually going to call that set token URI function. We're going to say NFT contract dot set token URI of the token ID and the token URI. Remember, this is a function that we added to our advanced collectible right here, set token URI. It takes a token ID and a token URI. And this is going to be from, of course, the account we just created. So we're going to say transaction equals that. We'll do transaction.wait. We'll wait 1 second for it, or 1 block for it. And then we'll print. We'll do printf. Awesome. You can view your NFT at, we use that OpenSea URL, .format, NFT contract .address, comma, token ID. Then I'm just going to add another print here saying, please wait up to 20 minutes and hit refresh metadata. Hit the refresh metadata button. So now we have our set token URI function. We can add the token ID in here, the advanced collectible contract, and then we just have to add the token URI here. So since we've already uploaded, and since I've already actually uploaded all three, what you could do, and what I like to do, is just have a dictionary here so we don't always have to be pulling from something. So I have a dog metadata dictionary. It's going to be equal to, and we're going to add those different dogs in here. So St. Bernard, this St. Bernard URL. We're going to paste it here. I've actually gone ahead, like I said, and uploaded this metadata for all 3 dogs. So I'm just going to go ahead and copy paste all 3 in here. Again, we're shortcutting a little bit here, But what you could do is you could save all these metadatas to their own file, and you could just pull from that file instead of doing kind of this dog metadata dictionary. So in any case though, we're going to do dog metadata dictionary of breed, right? Because dog metadata dictionary of St. Bernard is going to be this, which again has our image URI, has everything about our dog, and is perfect. What we also might want to do is write some tests around our set token URI function, of course, but I'm just going to move on. So in any case, we've done a lot here. I'm actually going to even close down my IPFS node, and we should be just about ready for everything. So of course, we'll run our Brownie test. Want to make sure that all our unit tests are working great, which they look like they are working fantastically. But we are ready to do a full end-to-end manual test here. And you could 100%, and I actually highly encourage you to 100%, we're just going to run these scripts in order and look to see if our stuff shows up on the OpenSea NFT marketplace. So are you guys ready? Let's do this. So make sure, of course, your environment variables are set here. Make sure that your MetaMask for RinkB has some ETH and has some link, and then we can go ahead and start running some of these scripts. So we'll do Brownie, run, scripts, advanced collectible, deploy and create, network, RinkB. Integration test moment of truth. And perfect, a new token has been created. Awesome. We can even go grab this address. Let's delete all these tabs that we have opened up. And we'll go to rinkb.etherscan.io. We'll paste it in here. And we can see contract has been verified, even though we didn't verify it because it matches some other source code. We can see token counter is 1. And we can even go to token ID to breed of 0, see what breed it is. So it's breed 2. And it looks like we're getting a St. Bernard again, which is incredibly adorable. We can even go to events here and we can see the different events. Since this is verified, we can even see the name of the events. So we have our breed assigned event and we have our requested collectible event. First is an index topic of token ID, and then there's the UN8 breed. And then we have the bytes32 request ID and the address requester. Now let's run our create metadata script here. So we'll do Brownie, run scripts, advanced, create metadata, network, RinkB. We don't have to run create collectible since our deploy and create already does that. So now if we run our create metadata, since this is a St. Bernard again, I'm going to go ahead and get this already exists, delete to overwrite. So what I'm going to do is I'm actually going to even create another one so that I get a new NFT. So I am actually going to run this create collectible script. So we're going to do Brownie, run scripts, advanced collectible, create collectible, network RinkB. And what this is going to do, all it's going to do is it's going to fund with some link, which it's going to be a little bit overkill with the link, but that's fine. And then we're going to do advanced collectible.create collectible. So we're just going to do 2 transactions here. Perfect. Collectible has now been created. Now I'm going to wait a solid 30 seconds to have that Chainlink VRF respond. And I'm even going to go to the contract, give it a quick refresh. Look at this token counter. Once the Chainlink VRF responds, this token counter will then be 2. Now that I see a token counter of 2 here, that means that it actually has responded. So we can now run the create metadata script. And we should have a new metadata file now. You have 2 collectibles. 0 St. Bernard already exists, delete it to overwrite, create a metadata file, metadata RinkB pug. So now if we look in metadata for RinkB, we have a St. Bernard and we now have a pug. Awesome. So we're going to set the token URI of both of these. If I grab this contract and I go to testnets.OpenSea, I can paste this address in and I'll get this doggy and then this random hash here, right? And we see there are 2 token URIs deployed. Again, if they're not here, you might have to refresh, but they don't have the images, right? Because we haven't set the token URI. So we'll go back, look at the advanced collectible. We've deployed and created. We've created another collectible. We've created their metadata. Now all we have to do is set the token URI. So Brownie, run scripts, advanced collectible, set token URI, network rank B. And the script, it's going to loop through all of them and actually going to set those token URIs. So we have setting token URI of 0. So this transaction is doing exactly that. And it's going to go ahead and say, awesome, here's your output. And then it's going to say setting token URI of token ID 1. And that's that second transaction. And it also gives us an output to that one as well. So if we've done this correctly, and we hit refresh metadata on this testnet.opensea.io, and we do a little refresh here, we can now see our St. Bernard, which is fantastic. And then if we change this from 0 to 1, since I've deployed 2, and I refresh this one's metadata, and then refresh the page, we can now see the pug as well. Again, just keep in mind, sometimes the refreshing metadata does take some time, and you might have to wait up to 20 minutes. But for all intents and purposes, we have just deployed our NFTs, given them token URIs that aren't around centralized servers. We can now see them on an NFT marketplace like OpenSea. You can let out a big sigh of relief because you just did something fantastic that not a lot of other engineers can do. You should be incredibly proud of yourself at this point. Let's take a minute, go back over some of the new things that we've learned here.
When deploying your smart contracts on chain, we all know that those smart contracts are immutable or unchangeable. But what if I told you that they were mutable? Well, technically that wouldn't be correct. However, smart contracts actually can change all the time. When people transfer tokens, when people stake in a contract, or really do any type of functionality, those smart contracts have to update their balances and update their mappings and update their variables to reflect this. The reason that they're immutable is that the logic itself never changes and will be on-chain like that forever. So technically, yes, once they are deployed, they are immutable. And this is actually one of the major benefits of smart contracts in the first place, that nobody can tamper with or screw with our smart contracts once we deploy them. However, this can be an issue if, for example, we want to upgrade our smart contract or protocol to do more things, or we want to fix some glaring bug or issue that we have. Now, even though we can't change the specific code that's been deployed to an address, we can actually do a lot more than you think. We're going to explain the different methodologies behind upgrading your smart contracts, and then we're going to show you how to do it. Now, at first glance, you might be thinking, if you can upgrade your smart contracts, then they're not really immutable then. And in a way, you'd be right. So when explaining kind of the different philosophies and patterns that we can use here, we do need to keep in mind the philosophies and decentralization implications that each one of these patterns have, as they do all have different advantages and disadvantages. And yes, some of the disadvantages here are going to affect decentrality. So we need to keep that in mind. And this is why it's so important that before you go ahead and jump in and start deploying upgradable smart contracts, you understand the trade-offs. We're going to look at 3 different ways to upgrade your smart contracts. The not really upgrading method, the social yeet, aka migrating method, and then the method that you're probably here for, which is proxies. So let's talk about the not really upgrading method, or the parameterization method, or whatever you want to call it. This is the simplest way to think about upgrading your smart contracts. And it really isn't upgrading our smart contracts because we can't really change the logic of the smart contract. Whatever logic that we've written is there. We also can't add new storage or state variables, so this is really not really upgrading, but it is something to think about. Upgrades is just parameterizing everything. Whatever logic that we've deployed is there, and that's what we're interacting with. This function means we just have a whole bunch of setter functions and we can update certain parameters. Like maybe we have a reward parameter that gives out a token at 1% every year or something like that. Maybe we have a setter function that says, hey, update that to 2% or update that to 4%. It's just a setter function that changes some variable. Now, the advantages here are obviously this is really simple to implement. The disadvantage is that if you didn't think of some logic or some functionality the first time you deployed their smart contract, that's too bad. You're stuck with it. You can't update the logic or really update anything with the parameterization, aka not really method. And the other thing you have to think about is who the admins are. Who has access to these setter functions, to these updating functions? If it's a single person, guess what? You have a centralized smart contract. Now, of course, you can add a governance contract to be the admin contract of your protocol, and that would be a decentralized way of doing this. So just keep that in mind. You can do this method, just need a governance protocol to do so. Another example of this might be a contract registry, and this is something actually that early versions of Aave used. Before you call a function, you actually check some contract registry that is updated as a parameter by somebody, and you get routed to that contract and you do your call there. Again, this really doesn't allow us to have the full functionality of upgrades here. You can argue that this registry is a mix of one of the later versions, but for all intents and purposes, this doesn't really give us that flexibility that we want for our upgrades. But some people might even think that upgrading your smart contract is ruining the decentrality. And one of the things that makes smart contracts so potent is that they are immutable, and that this is one of the benefits that they have. So there are some people who think that you shouldn't add any customization or any upgradability. You should deploy your contract and then that's it. Trilobits has actually argued that if you deploy your contract knowing that it can't be changed later, you take a little bit extra time making sure you get everything right, and there are often less security vulnerabilities because you're just setting it, forgetting it, and not looking at it again. Now, if I were to deploy a smart contract and I wanted to upgrade it with this philosophy in mind that, hey, we got to keep it immutable, we could use the social yeet method to actually upgrade to new versions. The social yeet method, or the migration method, is just when you deploy your new contract not connected to the old contract in any way, and by social convention, you tell everybody, hey, this new contract, this new one that we just deployed, yeah, this is the real one now. And it's just by convention of people migrating and over into using this new one that the upgrade is done. Hence my slang name of social yeet, because you yeet the first one out of the way and you move to the second one. I think I'm funny. This has the advantage of truly always saying, hey, this is our immutable smart contract, and this is our new one. This is really the truest definition of immutable, because since you give it no way of being upgraded in place, then if somebody calls that contract in 50,000 years in the future, it'll respond exactly the same. Another huge disadvantage here is that you have to have a totally new contract address. So if you're an ERC20 token, for example, you have to go convince all the exchanges to list your new contract address as the actual address. Keep in mind that when we do this, we do have to move the state of the first one over to the second one. So for example, if you're an ERC token moving to a new version of that ERC token, you do have to have a way to take all those mappings from the first contract and move it to the second one. Obviously, there are ways to do this since everything is on chain, but if you have a million transfer calls, I don't want to have to write the script that updates everyone's balance and figures out what everyone's balance is just so I can migrate to my new version of the contract. So there is a ton of social convention work here to do. Trilobits has actually written a fantastic blog on upgrading from a V1 to a V2 or etc. with this yeet methodology. And they give a lot of steps for moving your storage and your state variables over to the new contract. So link in the description if you want to read that. Now let's get to our big ticket item. So in order to have a really robust upgrading mentality or philosophy, we need to have some type of methodology or framework that can update our state, keep our contract address, and allow us to update any type of logic in our smart contracts in an easy way. Which leads us to our big ticket item, the proxies. Proxies are the truest form of upgrades, since a user can keep interacting with the protocols through these proxies and not even notice that anything changed or even got updated. Now, these are also the places where you can screw up the easiest. Proxies use a lot of low-level functionality, and the main one being the delegate call functionality. Delegate call is a low-level function where the code in the target contract is executed in the context of the calling contract. And message.sender and message.value also don't change. So you understand what delegate call means now, right? Great. And in English, this means if I delegate call a function in contract B from contract A, I will do contract B's logic in contract A. So if contract B has a function that says, hey, store this value in a variable up top, I'm going to store that variable in contract A. This is the powerhouse, and this combined with the fallback function allows us to delegate all calls through a proxy contract address to some other contract. This means that I can have one proxy contract that will have the same address forever, and I can just point and route people to the correct implementation contract that has the logic. Whenever I want to upgrade, I just deploy a new implementation contract and point my proxy to that new implementation. Now, whenever a user calls a function on the proxy contract, I'm going to delegate call it to the new contract. I can just call an admin-only function on my proxy contract. Let's call it upgrade or something, and I make all the contract calls go to this new contract. When we're talking about proxies, there are 4 pieces of terminology that we want to keep in mind. First is the implementation contract. The implementation contract has all of our logic and all the pieces of our protocol. Whenever we upgrade, we actually launch a brand new implementation contract, the proxy contract. Proxy points to which implementation is the correct one and routes everyone's calls to the correct implementation contract. You can think the proxy contract sits on top of The implementations. The user. The user is going to be making contract and function calls through the proxy contract. And then some type of admin. The admin is the one who's going to decide when to upgrade and which contract to point to. In this scenario, the other cool thing about the proxy and delegate call is that all my storage variables are going to be stored in the proxy contract and not in the implementation contract. This way, when I upgrade to a new logic contract, all of my data will stay on the proxy contract. So whenever I want to update my logic, just point to a new implementation contract. If I want to add a new storage variable or a new type of storage, I just add it in my logic contract and the proxy contract will pick it up. Now, using proxies has a couple of gotchas, and we're going to talk about the gotchas, and then we're going to talk about the different proxy contract methodologies, because yes, there are many proxy contract methodologies as well. And this is why Trilobits doesn't really recommend using upgradable proxies for your smart contracts, because they're fraught with a lot of these potential issues. Not to mention, again, you do still have some type of admin who's going to be upgrading your smart contracts. Now, if this is a governance protocol, then great, you're decentralized. But if this is a single group or entity, then we have a problem. The two biggest gotchas are storage clashes and function selector clashes. Now, what does this mean? When we use delegate call, remember, we do the logic of contract B inside contract A. So if contract B says we need to set value to 2, we go ahead and set value to 2. But these smart contracts are actually kind of dumb. We actually set the value of whatever is in the same storage location on contract A as contract B. So if our contract looks like this, and we have 2 variables in contract A, we're still going to set the first storage spot on contract A to the new value. This is really important to know because this means we can only append new storage variables in new implementation contracts, and we can't reorder or change old ones. This is called storage clashing, and in the implementations we're going to talk about, they all address this issue. The next one is called function selector clashes. When we tell our proxies to delegate call to one of these implementations, it uses what's called a function selector to find a function. The function selector is a 4-byte hash of the function name and the function signature. Don't worry about the function signature for now. Now, it's possible that a function in the implementation contract has the same function selector as an admin function in the proxy contract, which may cause you to do accidentally a whole bunch of weird stuff. For example, in this sample code in front of you, even though these functions are totally different, they actually have the same function selector. So yes, we could run into an issue where some harmless function like getPrice has the same function selector as upgrade proxy or destroy proxy or something like that. This leads to our first out of the 3 implementations of the proxy contracts. This is called the transparent proxy pattern, and this is actually going to be the pattern that we're going to be demoing to you today. In this methodology, admins are only allowed to call admin functions, and they can't call any functions in the implementation contract. And users can only call functions in the implementation contract and not any admin contracts. This way, you can't ever accidentally have one of the two swapping and having a function selector clash and you running into a big issue where you call a function you probably shouldn't have. If you're an admin, you're calling admin functions. If you're a user, you're calling implementation functions. So if you're an admin and you build some crazy awesome DeFi protocol, you better come up with a new wallet address because you can't participate. The second type of proxy we're going to talk about is the universal upgradable proxy, or the UPS. This version of upgradable contracts actually puts all the logic of upgrading in the implementation itself. This way, the Solidity compiler will actually kick out and say, hey, we got 2 functions in here that have the same function selector. This is also advantageous because we have one less read that we have to do. We no longer have to check in the proxy contract if someone is an admin or not. This saves on gas, of course. And the proxy is also a little bit smaller because of this. The issue is that if you deploy an implementation contract without any upgradable functionality, you're stuck, and it's back to the yeet method with you. And the last pattern or methodology that we're going to talk about is the diamond pattern, which does a number of things. But one of the biggest things that it does, it actually allows for multiple implementation contracts. This addresses a couple different issues. For example, if your contract is so big and it doesn't fit into the one contract maximum size, you can just have multiple contracts through this multi-implementation method. It also allows you to make more granular upgrades. Like, you don't have to always deploy and upgrade your entire smart contract. You can just upgrade little pieces of it if you've chunked them out. The disadvantages here really only seem like you have a lot more complicated code. All the proxies mentioned here have some type of Ethereum improvement proposal, and most of them are in the draft phase. There isn't really a standard here for the proxy that the whole community has landed on and says, yes, This is great, let's do it. So for all these, be sure to jump in the discussion and give your thoughts.
All right, so now that we know a lot more about upgrades and how they actually work and some different methodologies behind them, let's go ahead and learn how to actually implement some of these strategies and implement our contracts so that we can upgrade them. Now, there is a Brownie upgrades mix directly in the Brownie mixes organization that if you want to use, you absolutely can. Once again, to do that, it's just Brownie bake upgrades mix, and this will have all the code that we're going to teach you how to use right now. But let's go ahead and build this up from scratch ourselves. So we're going to go ahead and run Brownie init. This, of course, we're going to create our new Brownie project here. We're going to be using the OpenZeppelin proxy contracts to actually work with this and run with this. The methodology that we're going to be working with is the transparent upgradable proxy. Now, they've been using the universal upgradable proxies a little bit more. However, the transparent upgradable proxy is really fantastic and easy to understand. So that's going to be the one that we're going to be working with here. And these are the two contracts that we're going to be importing directly from OpenZeppelin. So let's get to it. We're going to create a really simple contract that we can easily tell if it's upgraded or not. We're going to be using the exact same ones that OpenZeppelin actually uses. So let's create a new file, and this is going to be called box.sol. We're just going to have it store and retrieve some type of value. So let's give it the SPDX license identifier of MIT. So let's pick our Solidity version. And for this, we're actually going to use 0.8.0. Oftentimes, you're going to have to quickly pick up new versions of Solidity anyways. We're going to do contract box, and we're going to give it a uint256 private value. We're going to do an event called value changed. I'm going to give it a uint256 new value. Give it a function store uint256 new value. And this is going to be a public function that anybody can call. And all we're going to do is we're going to set value to be new value. And we're going to emit this value changed event. Then we're going to have a function retrieve, and this will be a public view. And it's just going to return a uint256 value, return value. And this is going to be our whole contract. Hopefully you can understand everything that's going on in this contract. I should spell license right, shouldn't I? Now we're going to copy all of this code and create a new contract called box v2.sol. And we're going to paste it in. And box version 2 is going to be exactly the same, except we're going to add one more function called increment. This is going to be a public function, and we're going to set value equals value plus 1. And we're also going to emit a value changed event with that new value. Now this is going to be really easy for us to check to see if a contract has been upgraded or not. If we can call increment on the same address that we originally deployed box to, then this means that the contract has been upgraded. We shouldn't be able to call increment on this box contract, but we should be able to call it on box v2. Perfect. So that's all we need to do to get started. Now to actually work with the proxies and the transparent proxy that we're going to be working with, we do need to add them to our Brownie project. So we're going to create a new folder, and we're going to call it transparent proxy. And in here, we're going to add those two contracts. We're going to add one called proxyadmin.sol. And all we're going to do is we're going to grab all the code from the OpenZeppelin proxy contract and paste it right in here. Since this code is pulling directly from an OpenZeppelin package, we are going to have to fiddle with the imports a little bit to make it match so Brownie can actually compile it. And of course, since we're going to be working with another package, we have to add this dependencies to our Brownie config. So dependencies, OpenZeppelin / OpenZeppelin -contracts. And for this one, we are going to actually use 4.1.0. Then we have to do compiler, soak, remappings at OpenZeppelin is going to be equal to this dependency. Now, while we're in here, we might as well do our .env so we can get our environment variables, and we'll add our wallet in here. Wallets from key, private key. We can now just have this be at open Zeppelin /contracts access ownable.sol. And we don't need to change this at all because we're actually going to keep this transparent upgradable proxy.sol. Because this is the second contract that we're actually going to grab from OpenZeppelin. So let's create a new file. It's going to be called transparent upgradable proxy.sol. This exact text here. And we're going to copy paste this whole thing from OpenZeppelin. Boom. Paste it in here. Awesome. And then same thing here. We just have to little reverse engineer this at open Zeppelin /contracts/proxy ERC 1967 ERC 1967 proxy. And perfect. That is exactly where we are. So great. Now, if we've done this right, we should be able to run a quick Brownie compile. Whoops, I got to change this to box v2. Now let's run a Brownie compile. And perfect. Looks like we have compiled. We've got some stuff in build. Great, everything's working correctly. So, okay, so we have our box here, our box v2, and we have our proxy contracts as well that we can use to upgrade this box to a new version. We can even look, if we go back to proxy of OpenZeppelin, if we look at our proxy admin here, we see it has this function upgrade and call. And this call is the upgrade to and call on the proxy contract. If we look in the transparent proxy, this upgrade to and call calls upgrade to and call, which has been imported actually. So we can actually even go back, go to ERC 1967, proxy upgrade, look for that again. And this is the function that it's actually going to call. And it calls this upgrade to function, which calls this set implementation function. And all we're doing is we're doing storage slot.get address slot of this implementation slot. That value is going to be this new implementation. All it's doing is it's setting the implementation slot to being the new address that we want it to use. And we can see now, if we look in the proxy contract, the way that it actually works is it has this fallback function where it's always going to delegate all of our calls to whatever the implementation contract is. This delegate function, if we look at it, does a little bit of low-level assembly here. And it uses this low-level delegate call to send any function call or any call to this contract to the implementation contract. So this is exactly the function doing all that delegation. All right, so now that we've dug deep into the code, let's actually script this out and turn this into a script. So let's create a new file, and we'll call it 01 deploy box.sol. And this is going to be how we're actually going to deploy the box. So since this is a Brownie script, we're going to do def main, of course. Our account is going to be equal to get account, which we're going to do from scripts.helpful scripts import get account. So let's go ahead, create a new file, helpful scripts. Oops. Scripts.py. And again, we're just going to paste in that get account function from our past helpful scripts. All right, we have our get account script again. So we can just do account equals get account. Oh, this should be, sorry, it should be .py, excuse me. Do a quick print. Deploying to, we'll do network.show active. That means we got to do from Brownie import network. And then we'll do box equals box dot deploy from account. Do the little brackets here. Of course, since we're going to be deploying this contract, we also have to import that from Brownie. And perfect. This alone should just deploy the box contract, right? So this means we could do something like print box dot retrieve, and it should be 0, right? So if we run Brownie, run scripts 01 deploy, it'll deploy that. Whoops, we also got to add our .env. We don't have to put anything in here yet because we're not actually deploying to a real network. But let's go ahead and run this. I spelled retrieve wrong. It's probably good to spell things right. Let's try it again. And great. So we get 0 here. Perfect. That's exactly what we'd expect. So cool. However, though, if we run box.increment, this should error out, right? Boom, exactly. It has no attribute increment. So this is what's known as our implementation contract. This box is implemented. It's the implementation contract. Now we have to hook it up to a proxy. So let's first give it a proxy admin. And proxy admins are optional. And it's also recommended that if you do have a proxy admin and you're going to use some type of DeFi protocol, sometimes it's great to have your proxy admin be something like a multi-sig, like a Gnosis Safe, which is really fantastic. There's going to be a link in the GitHub for learning how to actually spin one of those up. Let's go ahead and do a proxy admin because they're really helpful anyways. We could, optionally, just set ourselves to be the proxy admin, but let's set it to be this contract. So we'll do proxy admin equals proxy admin.deploy. And again, this will be from account. And since we're using this proxy admin, we got to import that as well. So if we look at the proxy admin, we see a couple functions here. We see like get proxy implementation, which is just going to return the address of the implementation. We have get proxy admin, who's going to be us. Change proxy admin. We have this upgrade, which is just going to call that upgrade function on the proxy. And then we have upgrade and call. Upgrade and call changes the implementation to the new implementation and then calls that initializer function. Since we want these to be proxies, you can see here that we don't have a constructor. This is intentional. Instead, we could have some type of initializer function. For example, maybe we want to have this store be our constructor. Instead of having a constructor, what we do is we call what's called our initializer function the instant we deploy this contract. For the demo here, we're just not going to have an initializer. Anyways, so now we have this proxy admin. We have the implementation contract, we have the proxy admin. Let's now hook them up to the actual proxy. First thing that we need to do actually is we need to encode the initializer function. If we wanted store to be our initializer function, like I said, we could do something like initializer equals box.store, 1. And this would be our initializer, box.store combined with 1. What we then have to do is we'd have to encode this for our proxy. If we look at our transparent upgradable proxy, if we look at the constructor, we have address logic, address admin, and data here. The logic is that implementation, right? This is going to be the address of our box. The admin is going to be ourselves, or in our case, it's going to be that proxy admin contract. And then data is going to be that initializer function. If we go into the ERC 721 proxy contract, go back to proxy, ERC 1967 upgrade, and we look at this as one's constructor, we can see that this data bit here, once this is built with this constructor, it's immediately going to call this upgrade to and call. So it's going to call this initializer. If we go to upgrade to and call, if we go back to this upgrade contract, we can see this upgrade to and call. It's going to call this address.function delegate call, new implementation data. And this is how it actually calls that initializer function. We have to actually encode this into bytes. So we have to say box.store is the function to call, and then 1 is going to be the first parameter, right? If this is what we'd want to do. So we do box encoded initializer function equals encode function data. And this is where it gets a little bit tricky, but I usually have this encode function data once again in my helpful scripts. So we'll do quick def encode function data, and it's going to take an initializer, which we're going to start off as none, and then any number of arguments after that. So again, this could be like, initializer equals box.store, and then the arguments could be 1, 2, 3, 4, 5, etc., or whatever, right? For us, we only have one variable that can be put into store, but this is how you would do it. And to do this, Brownie actually has a built-in function that can actually do this. We can just return initializer.encode input star args, and that's all we'd have to do. However, there is a bit of an issue when the length of the args is 0. So I've already hacked away at it for you guys. So we're just going to do if the length of the args is 0, or we're not using an initializer. Then we're going to return ethutils.2bytes hex string equals OX. And then we do have to import ethutil, import ethutils, and of course we'd have to pip install it with pip install ethutils. So I know I kind of rushed through that, but basically what we're doing, like I said, is we're encoding this into bytes so that our smart contracts actually know what function to call. So we're just encoding it. That's all we're doing. And if it's blank or there's no initializer, we're going to return an empty hex string. And our smart contract will understand, okay, arguments are blank here. Perfect. I've got a nice doc string in the upgrades mix that explains this even better. I'm even just going to paste it in here for now. If you'd like to pause and read this a little bit more to kind of get the full depth of what this function is really doing, feel free to do that. This is a little bit lower level Solidity and EVM stuff that we're getting into here, but it can be good to know anyways. Whew, okay, great. So now that we have this, we can go ahead and run box encoded initializer function equals encode function data, which we would import from our helpful scripts. And this is what we use when we call the constructor for our transparent upgradable proxy. I'm just going to have it be blank for now, but feel free to fiddle around and try to actually use an initializer after we run through this demo. So this box encoded initializer function is going to be blank. We're saying, hey, don't use an initializer, and that's totally fine. If we were to add some stuff to here, we would say, hey, use an initializer. So now we can actually deploy this transparent upgradable proxy. If we open this up with the constructor, we can see what we need here. So we're going to say proxy equals transparent upgradable proxy.deploy. Of course, import this from Brownie. And what are those variables that we need? Okay, we're going to need the address of the logic. This is going to be our implementation contract address. So we just say box.address because we've already deployed this, which is great. Then we're going to need our admin, which we could just say is us, but we're going to use the proxy admin .address. And then last, we need that function selector. We need that encoded function call, which for us is just blank, but we still need that. So box encoded initializer function. And then we have to add from account, of course. And I've also noticed that sometimes it's helpful to add some type of gas limit. So I'll even add a gas limit of 1, 1, 2, 3, 1, 2, 3. That's 6 zeros there, but sometimes you might be fine. But with the proxies, they sometimes have a hard time figuring out the gas limit. So I've just manually put it in here. You can if you want to. It might work fine without it. And then great, let's do a quick print function. We'll print f proxy deployed to proxy. You can now upgrade to v2. Now what we can do is on the proxy's address, we can call functions. So typically, right, if we wanted to call a function on this box contract, we do box.retrieve, or however you spell it, box.store. Let's just do box.store, right? You'd call it like this. However, we want to actually call these on the proxies, right? Because this box contract address, this box contract is always going to be the same address and can't change. The proxy code can change. We want to always call these functions to the proxy and not to the box here, right? So the way we do that is we can do proxy box equals contract.from ABI, we'll call it box, on the proxy.address, box.abi. And of course, we'll import this from Brownie. What we're doing here is we're assigning this proxy address the ABI of the box contract. And this is going to work because the proxy is going to delegate all of its calls to the box contract. Typically, if you put an ABI on top of an address that doesn't have those functions that the ABI defines, it would just error, right? But the proxy is actually going to delegate all those calls to the box. So we could actually go ahead and try something like print proxy box dot retrieve. Hopefully I spelled that right. And even though we're using the proxy address here, we are going to delegate the call to box. So let's go ahead and run this. So we'll do Brownie, run scripts, deploy box. It's going to deploy the box. It's going to deploy the admin. It's going to encode that initializer function, which we've set to nothing. Then it's going to deploy our transparent upgradable proxy. And then it's going to call retrieve on the transparent upgradable proxy instead of our box. So let's do this. And perfect. We did it, right? It's returning 0 here. That's awesome. What we could also do is we could also do proxybox.store 1, and then we'll call retrieve. We'll see what happens here. Whoops, it's yelling at me because I got to do from account. Now let's go ahead and run it. And perfect. See, so after we stored on the proxy box, on this proxy, we're able to retrieve the value there. So this is fantastic. All right, now that we've deployed it, let's learn how to upgrade it. We're going to change this to deploy and upgrade.py. And we're just going to do everything in here. So now that everything's deployed, let's go ahead and now upgrade this. So now we can always point to this proxy box address, and it's going to be the most recent upgrade. It's always going to have the code that we want it to have. So let's go ahead and upgrade from box that doesn't have that increment to box v2 that does indeed have this increment function. So let's try this out. So first thing we need to do is we actually need to deploy that box v2. So we'll do box v2 equals box v2 dot deploy. We'll say from account, and we'll leave it like that. Of course, we're going to have to import box v2 from Brownie. And right now, actually, let's even do proxy box increment. Right? If we call proxy box that increment from account, this should error, right? It shouldn't be able to call this increment function because that doesn't exist. Oh, and then we also changed the name of the script. Sorry. This is actually going to be deploy and upgrade. And perfect. We see it actually errors out here. It says, hey, box object doesn't have this increment function. You're crazy. I don't know what you're talking about. Well, good. That's what we want to do. So let's delete that line. Box v2. And we'll even do a quick little upgrade here. Now, all we need to do is call an upgrade function. Now, basically all we have to do is call this upgrade2 function, right? But depending on if we've added a proxy admin contract, if we're using an initializer function, there might be a couple of different ways to go about this. So I like to just wrap everything up into its own upgrade function. You'll see what I mean in just a second. So what I like to do, again, we're going to pop into our helpful scripts, and we're going to create a new one called upgrade. Now for parameters in here, of course, we're going to take some type of account so that we have something to account to deploy from. We're going to use the proxy, which is, again, going to be that proxy contract, which is going to be our proxy contract here. We're going to need a new implementation address. We're going to need the proxy admin contract, which could be none. For us, we're going to have one, but it could be none. And then we're going to have an initializer, which also could be none. And then we're going to have the args for the initializer, which also could be none. Again, this star is a special thing in Python, which says any number of arguments will just get stored into this list called args. And perfect. This is going to be our function that's just going to take care of everything for us. So first thing, let's check to see if there is a proxy admin contract. So we'll say if there is a proxy admin contract, then we want to check to see if there's an initializer. What we're going to do is we're first going to want to encode that function data, of course. So we'll say encoded function call equals encode function data with the initializer and those star args. This is going to be the encoded initializer function here. Then all we have to do, and actually let's start with a blank transaction equals none. We'll say transaction equals proxy admin contract, since we're using one of these proxy admin contracts, since we've detected one, dot upgrade and call, since we also have an initializer. We're going to pass the proxy.address, new implementation address, and the encoded function call. And then, of course, from account. So this upgrade and call, if we look in that proxy admin, there's this upgrade and call function right on the proxy admin, and it just calls upgrade to and call of the proxy contract. So hopefully don't let this bog you down a little bit, that there's kind of a lot of mix and matching going on, but this is what's going on. Oops, sorry, this is encoded function call, not encoded function data. Great. Now, if they don't have an initializer, well, what do? Well, we don't need to encode any function call here. We can just say transaction equals that proxy admin contract dot upgrade. So it has an upgrade and call. It also just has a regular old upgrade. So we'll just call upgrade, and we'll give it the proxy.address, the new implementation address, and then from account. Now, if it doesn't have a proxy admin contract, this means that the admin is just going to be a regular old wallet. Well, what do we do then? Well, first, check to see if it has an initializer still. And if it does, we need again to encode that function call. We can just copy and paste that there. And then once that's encoded, we can just call directly off the proxy contract. We're going to call exactly what the proxy admin contract is calling, which is going to be proxy.upgrade to and call. We're going to give it the new implementation address, the encoded function call, and then from account. And let's wrap this all up in a big else. So if proxy admin contract, do this stuff, else do this stuff. If initializer, do that. Otherwise, we can just do transaction equals proxy dot upgrade to, and then we just add that new implementation address from account. And then we'll finally return transaction. Whew. So I know that there's a lot here, but we're really just making this upgrade function really general. We could always just know, okay, if we're going to use a proxy admin, let's just do it like this. Okay, no, we're not going to use a proxy admin. We're also not going to use an initializer. Great, it would just look like this. But this is essentially all that we have to do. Whew. So now that we have our upgrade function, we can go ahead and use it here. So we need to give it an account, a proxy, a new implementation address. So we'll say account. So we'll say upgrade transaction equals upgrade account. We need a proxy and a new implementation address. We're going to give it the proxy. And we're going to give it box v2.address for that new address. We do have a proxy admin contract. So we'll say proxy admin contract equals proxy admin. And we don't have an initializer. So we can leave that part blank. Of course, we need to import this upgrade function from our helpful scripts. And this is all that we need. So now we can do print proxy has been upgraded. And what we can do now is we can do proxy box equals contract dot from ABI. We'll call it box v2. We'll give it the proxy.address, box v2.abi. And now we should be able to call proxy box.increment from account. And then we can print proxy box.retrieve. And this should now be 1. And what we'll actually see is that this will return 2. Why does it return 2? Well, in our original proxy box, we stored 1. So it started with 1. We then upgraded to this new contract. And then let's actually just do a .wait, of course. We upgraded to a new contract right here. However, the storage of that contract stayed in the proxy. So that 1 stayed in the proxy. So even though we upgraded the contract, there's still 1 stored at the location in storage. So then when we call increment now, and then we call retrieve, it's going to go from 1 to 2. So let's go ahead and run this. Brownie runs scripts, deploy and upgrade, enter. And boom, that is exactly what we see output here. This is an incredibly, incredibly powerful and advanced feature. And if you've gotten to this point, you are on the border of being one of the most powerful smart contract engineers on the planet. Huge congratulations for getting this far. But we're not quite done. We, of course, need to write some tests because that is what's going to make sure our project always stays in sync and always stays up to date. So let's write a couple of tests here. So let's create a new file. We'll call test box proxy.py. And for this, we're really just going to test to see that our contracts work. We're going to see that this box actually is going to work correctly. So let's create a new test. Def proxy delegates calls. So we're going to make sure that we actually can delegate calls to our contract. We're going to say account equals get account, which means we got to do from scripts.helpful scripts import get account. Then we're going to do box equals box.deploy. Of course, this is going to be from account. Since we're using box, we're going to do from Brownie import box. We're going to do this proxy admin. So we're going to say proxy admin equals proxy admin dot deploy. Of course, from account. Let's import proxy admin from Brownie. All right, so now we'll do the box encoded initializer function, or whatever we called it before. This is going to be that encode function data, which my VS Code actually automatically imported. Thanks, VS Code. And again, we're leaving it blank because we're not actually going to have a store there. And then we're just going to go ahead and run that deployment. So we're going to say proxy equals transparent upgradable proxy. And we're going to grab this from Brownie.deploy. Say again the box.address, proxy admin.address, box encoded initializer function. We're going to say from account, and then we'll give this a gas limit of 123. Now we're going to put the ABI on top of this proxy. So we're going to say proxy box equals contract.from-ABI. We're going to name it box. This is going to be with the proxy.address and the box.ABI. Of course, we're going to need to import contract from Brownie. And okay, so now we can assert proxy box dot retrieve, if I spelled that right, is equal to 0. Then we're going to do proxy box dot store. We'll do 1, and this will be from account. And then we're going to assert again this proxy box dot retrieve should now equal 1. So we're using this proxy contract. We've slapped the ABI on top of it, and this should work. So we're just testing to see that our proxy is working correctly. So we can go ahead and test this then with Brownie test. And beautiful, it passed. Now let's go ahead and create a new script for testing the upgrades. Create a new file, call it test box v2 upgrades.py, and let's do it. Called def test proxy upgrades. So account is going to be equal to get account. Hopefully at this point you're getting pretty good at writing these tests. From scripts.helpful scripts import And of course, we want to add this init.py just in case you forgot. So now we're going to import get account. Perfect. So we have our account here. Now, as you can see, we're doing a lot of this box equals box.deploy, deploy the proxy admin. It would probably make sense in one of your scripts to just write a write a function called like deploy all or something like that. So again, if you guys want to learn more, if you want to improve upon this, I would highly recommend you go back and you make some of those improvements to really modularize this up. But for the time being, let's just keep going. So box.deploy from account. And since we're doing this, we're going to do from Brownie import box. I'm going to say proxy admin equals proxy admin.deploy. This will also be from account, comma, proxy admin. We're going to get those initializer functions. So we'll say box encoded initializer function equals encode function data, which we're going to grab from our helpful scripts as well. And then we're going to do the proxy again. Proxy equals transparent upgradable proxy deploy. We've got to import this from Brownie as well. Whoops, not twice though. Deploy. It's going to have the box.address, proxy admin.address, box encoded initializer function from account, gas limit 123 123. All right. So we have the proxy deployed. We've already tested that this proxy works in this test box proxy, so we're not going to go ahead and test that again. What we're going to do instead now is we're going to deploy box v2. And we're going to update the proxy and make sure that everything still works. So we're going to do box v2 equals box v2 dot deploy. It's going to be from account, of course. Now we're going to say proxy box equals contract dot from ABI box v2 proxy dot address box v2 dot ABI, and we're going to grab both this and this from Brownie. And what we're going to try to do is slapping this ABI onto this proxy address, we're going to try to call a function only box v2 can call. However, we know that, like what we tested before, it actually should revert. So we can actually check for reverts by importing PyTest. And we can say with PyTest.raises, and I know that this is a Brownie exception. I know what type of exception this is. It's an exceptions.virtual machine error. You can figure out what type of error this is by just running it and getting the error. So this is actually from Brownie, this exceptions thing. So we're going to actually also import exceptions from Brownie. We're going to say proxybox.increment from account. And I saved and everything, sorry, got formatted here. But calling proxybox.increment should throw this exceptions.virtual machine error. So this test will pass if this throws an error. And that's how we test that. So we want this to throw an error the first time we call it. Then we're going to upgrade and then we'll call it again and it'll actually work. Now we're going to call upgrade on account, proxy, box v2, proxy admin, contract equals proxy admin. We're going to need to grab upgrade from our helpful scripts. And now we should actually be able to call increment with our proxy box. So first we'll do a quick assert, proxybox.retrieve equals 0. Then we'll do proxybox.increment from account. And then we'll assert proxybox retrieve is 1. So we're deploying our box, we're deploying our proxy and everything around it. Then we're deploying our v2 implementation. We're trying to call increment, which won't work. We then upgrade our proxy to this new address, and then we can go ahead and call increment, and it should actually increment our box here. So let's go ahead and run this test. Brownie run test dash, Brownie test dash K. Grab this, paste it in. And we've done it. Our tests are working correctly, so we know that our box is working correctly. Awesome. Great job. Like I said, this is an incredibly powerful feature to be able to do these upgrades. With these, there comes a lot of risk, at least in the form of centralization risk. If you're the only wallet that controls the proxy, that means your application is centralized, full stop. So if you're going to deploy anything with proxies to mainnet, absolutely be sure to get it audited beforehand. Now, before we close this project up, let's actually deploy this to an actual testnet so that we can see everything that goes on when we call this deploy and upgrade. Let's go ahead and do it. So let's pop into our .env file and let's paste the variables that we have in here. We need the private key, Web3 Infura project ID, the Etherscan token. Awesome. Let's even publish the source of all these contracts so that we can see them on Etherscan. So for box, we're gonna do a little comma here. We'll say publish source equals true. I'm just gonna copy this comma to publish source equals true and paste it on all of my deployments. Publish source equals true. Publish source equals true on the admin, on the initial transparent upgradable proxy, on the box v2 deployment, and that's it. I've got my Etherscan token, my Web3 Infura, my private key, my Brownie config is indeed pulling from the private key, my .env has .env. Let's check to see my wallet. We have some RINKB in here, perfect. Let's do this. Brownie runs scripts, deploy and upgrade, network, RINKB. All right, so it looks like a couple of our contracts weren't able to actually verify. There are a couple bugs being worked out with some of the verifications, so we're going to ignore the ones that weren't able to be verified here. But let's go ahead, grab these addresses, pop them onto the RINKB Etherscan, and see what just happened. This is our box implementation. Let's grab this address. Let's paste it into the RINKB testnet Etherscan. Awesome. This is exactly what we have. Contract has been verified. This is exactly the code that we have here. And we can see all we have is a contract creation. And this is exactly correct. Because when we call the store function on this, it's actually going to get stored. We never actually called any functions directly on this contract. All we did was deploy it, which makes perfect sense. Let's go check out this proxy admin now. This second address, the second contract that we deployed. Sadly, this one didn't get verified. However, we can see we did indeed call this upgrade function at some point, which makes a lot of sense. If we look at our script, proxy admin, in our upgrade code, since we did have a proxy admin contract, we did call that upgrade function. Perfect, makes sense. Now let's go to this transparent upgradable proxy. This is going to be the most interesting one out of all of our applications. Interestingly enough, we look at this contract, we can see store and increment both have been called on this contract, not on the box. Because again, this is the proxy that we're going to call all the functions on to make our contracts upgradable. Internal transactions are calls that another smart contract made to this transaction. And if we look at a couple of these, we can see, if we click more, we had increment called from another contract, which makes sense. We had upgrade called from the proxy admin. And then we also, of course, we had store called from another contract. And if we verified this, we would be able to see Etherscan recognize this as a proxy contract as well. Hopefully when you work with this, you'll be able to verify it as well. But if not, not a big deal. You can always just manually do it later yourself. So this was an incredibly powerful project that we just did here and that we worked on. And all right, maybe take a nap, maybe go for a walk, get some food, get a drink, because we are on to our last coding project. Now, I do want to say that this project is considered a bonus because we're going to be going very quickly over the front end pieces. We're going to take all the building blocks that we've learned and build an amazing full stack application. Gear up, get ready, let's jump into this bonus project. And then after we finish this up, we're going to close everything out with a final quick section about security, the future, and thank you for joining this course. So let's do this last one. All right, and now we are moving on to our final project. This is going to be the most advanced projects and combine all the knowledge that we've learned so far into one project. Then we're additionally going to put a front end or a user interface onto this project. When we build our own applications, we're going to need a way for non-devs to actually interact with it in a meaningful way. So now this isn't a front end or React tutorial course, although we will be explaining some of the choices that we've made and how to actually do them. You should be able to follow along fine, even if you don't have any front end experience here. If you're looking for a full front end tutorial, FreeCodeCamp has some amazing videos that you can absolutely try out. All right, welcome back, everybody. And now we're going to be embarking on the most exciting, the most end-to-end. We're going to take everything that we've learned and wrap it all together in this single last application here. And we're also going to be learning about front-end development. And we're going to be building a front end on top of our application, on top of our contracts here. Now, this isn't a front-end tutorial. However, FreeCodeCamp has some wonderful, wonderful React tutorials. We're going to be teaching you guys just enough so that you can go ahead, jump in, and build your own simple, but also kind of nice looking front ends on top of whatever contracts that you have. For those of you who want users to actually interact with your applications and interact with your contracts, building a usable front end is a really important piece. So let's take a quick walkthrough of what this application is going to look like. So here is our front end here. And what this application is going to allow users to do is it's going to allow users to stake or deposit their tokens into what's called our token farm contract. Once they have some token deposited, that's when you can kind of go get creative with what you want those tokens to do. You could use it as staking in some governance. You could go ahead and invest it in something like Aave or another DeFi protocol to gain interest. You could build a yield aggregator. There's a ton of different features that you can actually do once you have users stake their tokens. And here's how they would do it on their UI side. So we have this little button here, which we go ahead and click connect on. MetaMask is going to pop up and we're automatically going to sign in. That's going to connect our MetaMask to this user interface now. So if I look at my MetaMask, I'm on the Coven test network, and we can see that I am indeed connected. Now what I can do is I can now stake some of my tokens into this contract. We currently have 3 different types of tokens that this platform allows for you to stake. Wrapped Ether, FAU, which is mimicking DAI on the test network, and our DApp token. This DApp token is going to be the reward token that our platform gives users as an incentive for staking on our platform. Once we stake, we can actually then unstake. And that's really it. So we'll go ahead and stake. Maybe we'll stake 10 DApp. We'll hit stake. MetaMask will pop up. This is the approve function, this first approve function that gets called. We get a really nice little waiting bar here. And once it's been approved, we get a notification saying the transfer has been approved. We then go ahead and we'll confirm staking. We'll get this little loading bar while it's being staked. And we'll see that pop up that says tokens staked successfully. Now, if we go to the token farm contract, we can see that we have 10 of this DApp token staked. We can also unstake it. The other thing that we can do is, as admins of this wallet, we can actually issue a reward to our users based on how much they've staked. So you see right now we have 95 DApp token. We have 10 DApp tokens staked. On the back end, I'm going to run an issue token script. It's going to send all users that have some stake a little bit of a DApp token reward. Now you can see it's been updated and we've been given a little bit of DApp token that resembles the amount of DApp token that we have staked. The way that we figure out the value of all of our different tokens is using, of course, Chainlink price feeds. We can then, of course, unstake everything. And we see tokens unstaked successfully. And that's it. And this is what we're going to build. Now, we aren't going to go over the unstaking portion of the front end application here, but here's what it would look like if you were to go ahead and finish building out the front end yourself. There is a full repository with the entire front end with this unstaking piece, but for simplicity, we're just going to skip over this unstaking bit. So let's go ahead and get started. I'm going to go ahead and make a new directory called DeFi stake yield Brownie. And then I'm going to open this up in a new text editor. Now, the first thing, of course, that we want to work with is going to be our contract. So we're in here, remember, always start with Brownie init, or you can start with the Chainlink mix. I'm just going to go ahead and start with Brownie init. And perfect. Here is our setup. All right, first thing we're going to do is we're going to make our daptoken.sol. This is going to be the token that we're going to give out to users who are staking on our platform. This is our reward token. You might have heard of yield farming or liquidity mining. This is our token that allows users to actually engage and participate in that. And this is just a regular old ERC20. So you guys already know we've done this before. And for this one, we're even going to use the latest and greatest in Solidity. Remember, I said that you're going to have to get really good at bouncing around between Solidity versions. So for this one, we're going to do everything in 0.8. So let's go ahead and do that. So we're going to do pragma Solidity 0.8.0. And we're going to do this the exact same way we made our other ERC20 token. We're going to go ahead and use OpenZeppelin again. We can even just copy paste the import from their documentation, or we can just write it out. Import at OpenZeppelin /contracts /token /ERC20 /ERC20.sol. And you guessed it, because we're using this at OpenZeppelin syntax. We're going to make a new file. Brownie.config.yaml. We're going to make some dependencies. We'll do OpenZeppelin /OpenZeppelin contracts. This time, we're going to actually use version 4 of these at 4.2.0. And again, you can find out everything about this package by going to OpenZeppelin /OpenZeppelin contracts on GitHub. And then compiler, sulk, remappings at OpenZeppelin equals this part right here. Paste it in. Okay, great. Then what we can do, we can go back to our dApp token and just do some basic ERC20 bits here. So we'll do contract dApp token is ERC20, and we'll give it our constructor, public ERC20. We'll call it dApp token, and we'll give it a symbol of dApp. And we'll give it an initial supply as well. So we'll call the mint function. And we'll set the message.sender as the owner. Give it an initial supply of 1 million, which will be 1, 1, 2, 3, 1, 2, 3, plus those 18 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8. And now that we have our first contract, we can try to compile it. Brownie, compile. And looks like it worked. Great. Now we're going to go on to create our more interesting contract, our token farm. We can even take a quick second and figure out what we want this to be able to do. Well, we want to be able to stake tokens, unstake tokens, issue tokens. This is going to be issuing those token rewards. We're probably going to want to add allowed tokens to add more tokens to be allowed to be staked on our contract. And we're probably going to want some type of get ETH value function where we can actually get the value of the underlying staked tokens in the platform. With that in mind, let's move on. So, you know the drill. Pragma Solidity, caret 0.8.0. And we're going to be here for a while, so I'm going to close those out. And this will be our contract token farm. Contract token farm. Oh, and let's not forget our SPDX license identifier of MIT. Well, let's go ahead and start with the staking of the tokens, right? Because that's going to be the most important piece of our application. So we're going to do function, stake tokens. They'll probably want to stake an amount of token, and they'll probably want to stake a certain address of the token. So some amount of some token. Now there's a couple things we need to keep in mind here. What tokens can they stake? How much can they stake? So these are our first two questions. For our application, we're just going to say you can stake any amount greater than 0. So we can even add that. We'll do require amount is greater than 0. And if it's not, we'll just say amount must be more than 0. And since we're using version 8, we don't have to worry about anything to do with safe math, which is awesome. So we can just go ahead and do stuff like this. Now we only want certain specific tokens to be staked on our platform. So we could say require token is allowed or something to this effect. So we might have to actually create a token is allowed function. So let's go ahead and create that function. Token is allowed. It'll take some token address, make it a public function, and it'll return a Boolean. It'll return true if that token's allowed, or false if it's not allowed. So how do we know if a token is actually allowed? We probably want some list or some mapping of these tokens and whether or not they're allowed. After all we've learned, you'll probably learn that there definitely are some trade-offs between lists and mappings here. For simplicity's sake, we're just going to stick with a list for now. So we're going to create an address array. We'll make it public, called allowed token. And this will just be a list of all the different allowed tokens. For our token is allowed function, we'll just loop through this list and see if that token is in there. So we'll do a for loop. For uint256 allowed tokens index equals 0. Allowed tokens index is less than allowed tokens dot length. Allowed tokens index plus plus. So we're going to loop through this list and we're just going to say if allowed tokens of allowed token index equals this token, then we're going to return true. Otherwise, if we get through this whole for loop and we don't find this token in here, we're just going to return false. Now we have a way to check to see if allowed tokens are there. Let's actually write a function to add allowed tokens. So we can do function add allowed tokens, address token, public function, and we'll do allowed tokens, and we'll just push it onto that array. Now adding allowed tokens is probably something we only want the admin wallet or the owner of this contract to do. So we'll add only owner as a modifier to this function, and we'll make this token farm ownable, is ownable, and we'll import from OpenZeppelin here too. Import at OpenZeppelin/contracts/access ownable.sol. Let's do a quick compile. Great, things are being compiled fantastically. Now that we have a little bit of functionality here, now might be a good time to actually go ahead and start writing some tests, if you want to. Since I know that we're going to change the constructor a little bit and we're going to change a little bit of how this is actually formatted, I'm just going to keep going. But now might be a great time, should I start writing some tests for my application? You know we're going to do those tests later on anyways, though. All right, great. But in any case, now that we have these two functions, we can go ahead and actually start checking to see if the tokens that these stakers are going to stake is actually allowed. So what we can do now is we can add this require statement in. We can require token is allowed of token. Otherwise, we'll just say token is currently not allowed. And perfect. Now we have two require statements that answer these questions. What tokens can they stake? And how much can they stake? So now all we have to do is we just have to call the transfer from function on the ERC20. Remember, ERC20s have these two transfer type functions. They have transfer, and they also have transfer from. Transfer only works if it's being called from the wallet who owns the tokens. If we don't own the token, we have to do transfer from, and they have to call approve first. So we're going to call the transfer from. So we're going to call the transfer from function on the ERC20 since our token farm contract isn't the one that owns the ERC20. We also have to have the ABI to actually call this transfer from function. So we're going to need the iERC20 interface. We could go ahead and pop it in here. We could also make an ERC20 contract. We could also just grab it from OpenZeppelin. So we'll do import at OpenZeppelin/contracts/token/ERC20/iERC20.sol. We're using the interface here because we don't need the whole contract. Anyways, let's now wrap iERC20. Let's wrap this token address as an ERC20 token. So now we have the ABI via this interface and the address, and we'll call .transfer from the message.sender, and we'll send it to this token farm contract. So from whoever calls stake tokens to this token farm contract, and we'll send the amount. And perfect. Now we just need to keep track of how much of these tokens they've actually sent us. So we're going to want to create some type of mapping here. And this mapping is going to map token address to staker address to the amount. This way we can keep track of how much of each token each staker has staked. So it's a mapping per token, per staker, per amount. So we'll just call this mapping of that token address, which is going to get mapped to another mapping of those user addresses, which then gets mapped to a UN256. So we're mapping the token address to the staker address to the amount. We'll make this a public mapping. And we'll call it staking balance. Now that we have this mapping in our stake token function, what we can do is we can say staking balance of this token from message.sender is now going to equal whatever balance that they had before plus the amount. All right, this is great. Now we have a way for users to stake different tokens that we've actually allowed them to stake on our platform. Awesome work. So what do we want them to be able to do next? We want them to unstake tokens. We want to be able to issue some reward. We want to be able to get the ETH value based on that reward. Typically, you might want to do this unstake tokens bit first. However, I know that we're actually going to need some additional functionality in our stake tokens function for us to actually issue tokens properly. So let's just go ahead and do this issue tokens bit. Remember, this issue tokens is a reward we're giving to the users who use our platform. So we want to issue some tokens based off the value of the underlying tokens that they've given us. So for example, maybe they've deposited 100 ETH, and we want to do a ratio of 1:1. For every 1 ETH, we give 1 DApp token. That's pretty easy for us to figure out. However, let's say they have 50 ETH and 50 DAI staked, and we want to give a reward of 1 DApp token per 1 DAI. Well, then we'd have to convert all of our ETH into DAI so that we know that conversion ratio for the DApp token. So that's the problem that we're going to work on now. Let's create this function called issue tokens. And this is going to be a function only callable, again, by the owner or the admin of this contract. So how do we actually go ahead and issue tokens here? Well, the first thought would be to loop through a list of all the stakers that we have. But right now, we don't have a list of stakers. What do we have? We have a mapping of stakers, and we have a list of allowed tokens. Well, we're probably going to need to have a list of stakers. So we'll do an address array, because again, we can't loop through a mapping. So we'll do an address array, we'll make it public, called stakers. This is just a list of all the different stakers on our platform. Now, when somebody stakes a token, we're going to have to update this list. We want to make sure they're only added if they're not already on the list. So in order for us to do this, we should get an idea of how many unique tokens a user actually has. So I'm going to create a function called update unique tokens staked with message.sender and the token. And what this function is going to do, it's going to get a good idea of how many unique tokens a user has. And if a user has one unique token, we can add them to the list. If they have more than one, we know that they've already been added to the list, so we don't need to add them there. So let's create this function, update unique token staked. We'll have it input an address user and an address token. And we'll make this an internal function so that only this contract can call this function. And what we'll say is if staking balance, let's even do a little underscores here, of token of user is less than or equal to 0, we're going to update some unique tokens staked mapping. So we'll say unique tokens staked of the user is going to equal the unique token staker of the user plus 1. And since we have this new mapping called unique token staked, we'll make that as well. So we'll do a mapping of an address to a uint256 public called unique tokens staked. So this way we know how many different tokens each one of these addresses actually has staked. Now that we have a better idea of the unique tokens each one of these users has staked, what we can do is we can figure out whether or not we want to push them onto this stakers list. If they're already on there, we don't want to push them on there. If they're not on there, then we do want to push them on there. So what we can just do is say if unique token staked of message.sender is equal to 1 if they have one unique token staked. If this is their first unique token, we're going to add them to that stakers list. So we'll say stakers.push message.sender. And this is going to be our completed stake tokens function here. So we had to add this little extra functionality between the unique tokens to figure out how to actually issue some reward for them. But now that we have this list and it's going to get updated here, and it'll also get updated when we unstake, what we can do now is just loop through this list of stakers. So we can say for uint256 stakers index equals 0, stakers index is less than stakers dot length, stakers index plus plus, and now we're going to issue some of these tokens here. So we're going to say the address recipient equals stakers index. So one at a time, we're going to loop through, grab these recipients, and then we're going to send them a token reward based on their total value locked. So we got to do a couple things here. We have to send them a token reward. We have to figure out how to actually send them this token. And then we also have to get their total value locked. So let's do this. To send them a token reward, this is going to be this DApp token that we created in the beginning. This is going to be our DApp token. So right when we deploy this contract, we need to know what a reward token is actually going to be. So what we can do right at the top, and then I'm actually just going to move this array up here so that they're all kind of nicely together. What we need to do is we need to create a constructor. Right when we deploy this contract, we need to know what is the address of the DApp token. What's the address of the reward token that we're going to give out? So we can say constructor. It will be passed an address of the DApp token address. This will be a public function. And we'll store this DApp token as a global variable. So we can say IERC20, since we're already importing it here, public dApp token. What we can do now is set dApp token equals IERC20 underscore dApp token address. So now we have this dApp token with its associated address. And what we can do now is call functions on it. For example, we can call dApp token.transfer. We can call transfer here because our token farm contract is going to be the contract that actually holds all these dApp tokens. And we're going to send this token to the recipient, of course. But how much are we going to send? Right? How much of this token are we going to send to them? Well, we need some function to get the total value. So we're going to say uint256 user total value equals some function, right? And we can go ahead and define that right now. We'll call this function get user total value, right? Or get recipient total value, or whatever you want to say. So we'll pop recipient in here, and let's go ahead and create this function. So we'll call function get user total value address user. And this is where we do a lot of looping, right? We gotta find out how much each of these tokens actually has. Now, what a lot of protocols do, instead of actually them sending and them issuing the tokens, is they actually just have some internal method that allows people to go and claim their tokens, right? You've probably seen that before, people claiming airdrops. That's because it's a lot more gas efficient to have users claim the airdrop instead of the application actually issuing the tokens, right? It's going to be very gas expensive to do looping through all these addresses and checking all these addresses, right? We're going to do it though, because we are a wonderful, amazing protocol and we want to give our users the best experience. But in any case, this is going to be a public view function that will return a uint256, right? Because we want to return this total value to our issue tokens function up here. So how do we actually get started here? Well, let's create a uint256 total value, and we'll set it off to, start it to be 0 here. And let's even start it off with a quick require statement, right? We want to require that the unique token staked of this user is going to be greater than 0, right? And if it's not, we'll say they don't have any tokens staked, right? So the value is going to be nothing. Now, if this is true, if they have some tokens staked, we'll go ahead and find it. So we're going to loop through those allowed tokens up here, the allowed tokens, and we're going to find how much this user has for each one of these allowed tokens. So we're going to say for uint256 allowed tokens index equals 0. Allowed tokens index is less than allowed tokens dot length. Allowed tokens index plus plus. And let's go ahead and we'll add the total value. And now we'll say the total value is going to be equal to the total value plus however much value this person has in these tokens, in this single token. So get user total value is the total value across all the different tokens. We need a way to get the total value across one token. So we're going to create a new function called get user single token value, and we'll pass it our user, and we'll also pass it this single token that we're on right now. So we'll pass it allowed tokens, allowed token index. So we got to create a new function here. Function get user single token value. This is going to take an address of a user and an address of a token. It's going to be a public function. I'm just going to put this on a new line to make it a little easier to see. It's going to be a view function, and it's going to return a uint256. We want to get the value of how much this person staked of this single token. So for example, if they've staked 1 ETH and the price of 1 ETH is $2,000, we want to make sure that this returns 2,000. Or if they have 200 DAI staked and the price of 200 DAI is $200, we want to make sure this returns 200, right? So we're getting that conversion rate. We're getting exactly how much value this person has staked in our application. Now we'll do a quick if. We'll say if unique token staked of the user is less than or equal to 0, then we'll just go ahead and return 0, right? We don't want to do a require here, right, as we did up here, because we want this to actually keep going, right? If this is 0, we don't want the transaction to actually revert, okay? We want this to keep going. So how do we actually get the value of a single token? Well, we're going to need to get the staking balance, right? But we also need the price of that token. So we're going to need to get the price of the token and then multiply that by the staking balance of the token of the user. So once again, we need to create another function. We'll call this one get token value. So in another function, we're going to call get token value. Get past an address of a token. We'll make this a public view function that will return a uint256. And this, of course, is where we need some pricing information. And this is where we're going to actually work with the Chainlink price feeds once again. And hopefully this part is going to be a little bit more familiar for you. So what we're going to need is a price feed address. That's the first thing that we're going to need. So we're going to actually have to map each token to their associated price feed addresses. So we're going to need some mapping that does that, right? So we're going to need some mapping that's going to map an address to an address. It's going to be a public one, and this is going to be token price feed mapping, right? It's going to map the token to their associated price feeds. And with that, that means we're going to have a function called set price feed contract, where we actually set the price feed associated with a token. So this will take an address of a token and an address of a price feed. This will be a public, and this will be only owner. We don't want anybody to be able to set what these price feeds should be. We just want the owner to be able to do this. So we'll do token price feed mapping of the token is going to equal the price feed. And that's it. So now we have a way to set the price feed contracts. We have a way to map the tokens to their price feeds, right? And again, we go to docs.chain.link. We can go to price feeds, Ethereum price feeds. We can find these different price feeds here. And this is where we're going to set those price feeds. Now back down in our get token value, we can grab that price feed address now by saying address price feed address is going to equal that token price feed mapping of that token parameter. And now that we have this, we can use it on an aggregator v3 interface. Again, we can always go back to the docs here. We can grab this bit right here. Of course, we're going to change it to be 0.8. And for those of you who would rather I just wrote it out, we're going to import at chainlink/contracts/src/interfaces/aggregator v3 interface.sol. And since we're doing this import, we're going to go to our Brownie config, SmartContract kit/Chainlink Brownie contracts. And we're going to see what's the latest version of these. Now I'm going to point something out. This package recently changed to mirror the NPM package versions. So it does look like it went backwards in versions, and there's even a little update here. But this is the newest version, even though it says 0.2.1. It's literally just to match the NPM contract tags. So this is what we're going to use. So we're going to do at 0.2.1. And then in our remappings, we'll also do at Chainlink equals this bit right here. Now that we've imported that, we can now grab that aggregator v3 interface or that price feed and say aggregator v3 interface of price feed address and grab that price feed contract. Then once we have this price feed contract, we can call .latest round data. And again, you can always check back to the documentation to see what that function actually looks like. And this is going to return, it's going to return a whole bunch of stuff. But we only care about the price. So the first thing it returns is round ID. We don't care about that, so we'll just put a comma. We do care about the int256 price, so we'll put that in there. But we don't care about the rest of these. So we'll just do comma, 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 because we only care about the price here. We also care about the decimals. We need to know how many decimals the price feed contract has. That way we can match everything up to be using the same units. So we'll say uint 256 decimals equals price feed dot decimals. And what we can do now is we can return both of these. So this actually needs to return a uint 256 and another uint 256 for the decimals here. And we can do return. We can return both of these. So we'll do a uint 256 price. We'll wrap that price into a uint 256. And then we also need to wrap the decimals in a uint 256. Since decimals actually returns a uint 8. So we'll return the price and the decimals. All right, now we're cooking. Now we can go ahead and start scrolling back up and adding all this stuff in. So we can say uint 256 price, uint 256 decimals equals this get token value that we just created right here. And then we can just have this return staking balance of the token of the user times the price. We're going to do some interesting math here, divided by those decimals. 10 raised to decimals. Whew. And I know there's a little bit of math here, right? And so you might be going, wait, what are we doing here? Wrap that up like that, just so that we're absolutely certain we're doing correct order of operations here. So we're taking the amount of token that the user has staked, right? Let's say, for example, 10 DAI. And we're taking the price of that DAI. Maybe we have all of our contracts, all of these tokens get converted back to the USD price. So we have DAI USD. Or actually, better yet, let's say we have 10 ETH, right? Our price feed contract is going to be ETH USD. Let's say the price is $100 per USD. So this first bit is we're going to do that 10 ETH times $100. So we're going to do 10 times 100, which is going to equal to 1,000 value. The only thing is we also have to divide by the decimals. So our staking balance is going to be in 18 decimals. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But let's say our ETHUSD only has 8. So 1, 2, 3, 4, 5, 6, 7, 8. So we need to multiply these first and then divide by the decimals. That way we can arrive at a price that actually makes sense. It's going to be a function that we're definitely going to need to test to make sure that we're doing everything right, so that we're doing all the math correctly. But okay, now that we have this user single token value, we go ahead and come back up to our user total value, and we can literally finish this function by just calling return total value. And then we can pull up to our issue tokens. Now that we have the total value that this user has actually locked, we can just transfer the amount of tokens that they have in total value. So we can say dApp token transfer this recipient. We can transfer them the total value, right? We'll say however much they have in total value staked on our platform, we'll issue them as a reward. And that is our issue tokens function. We are making great progress. All right, so we have a way to stake. Done. We have a way to issue. Done. We have a way to get value, or just get value. Done. We've added a way to add allowed tokens, and all we have to do now is add some way to unstake the tokens. So let's go ahead and create this function. I'm going to make it right underneath the stake token one. We'll do function unstake tokens. We'll pass it the token address. We'll make this a public function so anybody can call this. The first thing we're going to want to do is fetch the staking balance. How much of this token does this user have? So we'll say uint 256 balance equals staking balance of the token from message.sender. And we're going to require the balance is greater than 0. Otherwise, we'll say staking balance cannot be 0. And then we're going to do a transfer. So we'll do IERC20 of the token dot transfer message dot sender balance. Once we actually transfer the token, we'll do staking balance of this token of message dot sender. We're going to update this balance to now be 0, right? Because we're going to transfer the entire balance here. And then we're going to update how many of those unique tokens that they have. Now, a quick note here. Later on, we're going to learn about reentrancy attacks. So at some point, come back here and figure out, hey, is this vulnerable to reentrancy attacks? So we'll say unique token staked of message.sender is going to equal unique token staked message.sender -1. Now, the last thing that we could do is we probably should actually update our stakers array to remove this person if they no longer have anything staked. This is a little bit sloppy, but we're just going to skip doing that for the time being. However, if you want to go back and add the functionality to remove the stakers from the stakers list as they unstake, please go for it. It's not a big deal if we don't actually do this because our issue tokens function is actually going to check to see how much they actually have staked. And if they don't have anything staked, then they're not going to get sent any tokens. But all right, that's basically all of the functionality here. Let's just try a quick sanity check with the Brownie compile. Whoops, I forgot to add v0.8 in here. Let's try again. That little bit. This needs to be token, and this needs to be user. Whoops. And then it looks like I did the same thing down here. This is actually staking balance. Let's try it again. And perfect. Everything is at least compiling correctly. Just because it's compiling correctly, though, doesn't necessarily mean that we're doing everything correctly. So this is fantastic. Typically now we'd want to go ahead and start doing our tests. I'm actually going to go ahead and build one of our scripts first. The reason I'm going to build one of the scripts first is because I'm going to use my deploy script pretty regularly in my tests. I'm going to use it as part of my testing. This way, I can also test some of my scripts as well in addition to the contracts. So let's go ahead and make our deploy script. So let's create a new file in here. We'll call it deploy.py. We'll also create an init.py for those of you who want older versions of Python. And let's go ahead and do this. So we're going to have a main function in here. And in our main function, we're actually just going to call deploy token farm and dep token. And then we're going to have a function def deploy token farm and dep token. Right, and I should be able to run Brownie run scripts deploy.py. And great, everything's compiling right, and we're running our scripts here. So first thing that we're going to want to do, as always, is get our account. And I am going to copy a couple of those helpful scripts from our past projects. So I'm actually going to pull up our NFT demo that we did. So I'm actually going to go to our Chainlink mix that we did. And I'm going to grab our helpful scripts. Remember, we can always jump onto the Chainlink mix here and we can just grab some of the scripts from here. So we could go to scripts, helpful scripts, and just copy paste this whole thing, or just grab it like I did, right? These are going to be those exact same scripts that we built previously. So now we have our helpful scripts in here, right? We're going to have this contract to mock for running our tests. We have get account so that we can get our accounts easily. We have encode function data, which we're not going to have to work with since we're not doing upgradable contracts, but we have it here anyways. We have upgrade, which we're also not going to use, but we have it here anyways. We have get contract, which returns mocks if they're not already deployed, or it just returns whatever contract that we're looking for. And then, of course, we have our deploy mocks script here. So now we can do from scripts.helpful scripts import get account. And perfect, we can get our account like that, no problem now. And now we're going to want to start deploying some contracts. So we're going to deploy that dap token first. So we'll do from Brownie, import dap token. And we'll do dap token equals dap token dot deploy. And this takes no parameters, so we can just do from account. Then we're going to want to deploy our token farm. So we could say token farm equals token farm dot deploy. And this tags one parameter, which is the dApp token address, right? Because we need that address so we can give it out as a reward. So we're going to say dApp token dot address. We'll do a comma, and then we'll say from account. And we'll need to import this from Brownie as well. And while we're here, we might as well add some publish source bits on here. So we can say publish source equals config. We'll grab this from the config. Networks. Do network.show active. Verify. We'll grab network from Brownie. We'll grab config from Brownie. And in our config here, let's do networks. We'll add development. We'll set the verify here to be false. And then we're going to work with the Coven chain. So we'll say Coven. Verify will also be false. Actually, Coven will be true. And then we'll do a persistent ganache. Our verify for this will be false. And I'm even just going to put this up here so that all these ganache chains are kind of with each other. So we'll verify in Coven, but we won't on development or ganache. Now, once we've deployed this token farm contract, we need a couple things, right? We're going to need to send this some dApp tokens, right? We're going to need to send pretty much all the dApp tokens so that I can actually give those tokens out as a reward. So we're going to want to do a transaction is going to equal to dApp token dot transfer. We'll send it to the token farm dot address. And then we have to choose how much we're going to send, and we'll send the total supply. But we'll keep a little bit for ourselves so we can do some testing, and so just in case. So we'll also do minus kept balance, some static kept balance, which we can say add at the top. We'll say the kept balance is, let's keep like 100. So this will be equal to web3.2way 100 ether. So we'll do from web3 import web3. So in our transfer, we'll do dApp token.total supply minus the kept balance. And then of course, we're gonna have to do a from account. So now we're sending our token farm basically 99.9% of the total supply of this dApp token so that it has this token to actually give out as a reward. We'll do a tx.wait. We'll wait for one block confirmation there. Now what do we want to do? Well, if we look at our token farm, we know at our stake tokens function, we can only stake tokens that are allowed. And each one of these tokens also is going to need to have some price feed associated with it, right? In our token price feed mapping. So we're going to have to add those. So what we're going to want to do is we're going to want to create a function called add allowed tokens. And what this is going to do, it's going to add the tokens that we want to allow, and it's going to give them a price feed contract associated with them. So let's create this function. We'll call it def add allowed tokens. And this is going to take a couple things. We're going to want to take that token farm because we're going to need to call the add allowed tokens function on it. We're going to take a dictionary of allowed tokens, and this is going to be the names. This is going to be a dictionary of the different token addresses and their associated price feeds. So we're just going to price everything in USD so that we can figure out the value of everything in USD. And then last, of course, we're going to need an account. For now, I'm just going to do pass here. Let's look at the different inputs that we're going to put into this. So obviously we're going to do token farm, but then we're going to need to make this dictionary of allowed tokens. So we're going to need the address of the different tokens that we want to have. Now, how do we get the addresses of the different tokens that we're going to use? And what are the tokens that we're even going to use here? For simplicity, we're just going to start with 3 tokens. We're going to allow our platform to allow 3 different tokens to be staked. We'll use the dApp token as one. We use WETH token or wrapped ETH because that's pretty much a standard in most smart contract platforms. And then we're also going to use an FAU token, which stands for faucet token. And we're going to pretend that this faucet token is DAI or DAI. The reason we're going to use this faucet token is because there's this erc20faucet.com, which allows us to get this fake faucet token. We can get unlimited amounts of this faucet token on different testnets. We're going to pretend that this faucet token is going to be DAI, right? So FAU token /DAI. So how do we actually get these addresses? Well, DApp token, we know. WETH token, what we can do in our config is we can actually add those addresses here. So for Coven, the WETH token address is going to be this right here, which again, you can go check this out and you can find it on Etherscan. You can write your own if you want. We're just going to use this already deployed one on Coven. FAU token, which is going to be this token here, which I know is going to be this address right here. And if you want, you can come here and grab your address, paste it into this erc20faucet.com, put an amount of 10 in here, we'll connect to MetaMask. Oh, it even tells us the token address right here, which we can just copy paste. We can do mint free tokens, confirm. Great, it says success. If we don't already have it, we can take this token address, go to our MetaMask, assets, add token, paste it in. I've already got it. We could see right now I have 5 FAU. Once this confirms, I'll have an additional 10, and now you can see 15 here. This is going to be this FAU token that we're going to use. We have WETH here, and then we know what the DApp token address is going to be from when we deploy it here. Now we could do, again, we could do the config, networks, etc., and just always get it from our config. Or we could use our get contract method that we grab from our helpful scripts, which will deploy a mock WETH token. It doesn't exist in one of these. And that's what we want, because we're going to want to test this locally. So we're going to want to deploy our own fake WETH token. So we'll say the WETH token equals get contract WETH token. And then the FAU token, it's going to be get contract FAU token. And remember, what we put in here, our string that we put in here needs to match our string in our config. Now, in order for this get contract to work for WETH token and the FAU token, we're actually going to have to modify our helpful scripts here. So if we copied and pasted it directly from our Chainlink mix, this is basically what we're going to have here. We're importing all of our mocks, which we can go ahead and copy paste these as well from the Chainlink mix, our test, our mock contracts here. We have some forking implementations. We have contracts to mock, which tells us based off of the key, what token or what contract we're going to use to mock. We have get account, which we use all the time. In order for us to do this contract to mock correctly, we're going to have to mock WETH and FAU. And actually, we don't even need all these in here. We don't even need this whole contract to mock. In fact, we can get rid of mock Oracle. We can get rid of VRF coordinator, and we can even get rid of the link token for this. We do need this SDUSD price feed later on, so I'm just going to leave it in here for now. We definitely do need, though, FAU token, which is going to be mocked to something, and we need WETH token, which was going to be mocked to something else. So what are these tokens going to be mocked to? Well, they're each an ERC20 mock, but we want to give them kind of their own identity. So what we're going to do is we're actually going to make a mock ERC20 for both FAU and for WETH. So we're going to come in here, we're going to do a new file. We'll call it mockDai.sol. And this is going to mock that FAU token. So it could be mockDai, it could be mock FAU, whatever we want it to be. And we're just going to make this a basic ERC20. So we'll do pragma, solidity, 0.8.0. We'll import at open Zeppelin contracts token ERC20, ERC20.sol. Obviously, this is going to look very familiar. This should spell pragma, not whatever I just spelled. This is going to look really similar to that DApp token. So now we can call it contract. MockDai is ERC20, and we'll do constructor public ERC20. MockDai will be the name of this, and the symbol will be DAI. And perfect. And that's all we need. We'll copy this whole thing, and then we'll do the same thing for mockweth.sol. We'll paste this whole thing in here, and we'll just change the name. We'll call this mockweth. It's ERC20, mockweth, and this will be WETH token. Great. So now that we have those mocks in here, we can change FAU token to mockDai and WETH token to mockweth. We can import those from Brownie, and in fact, we can get rid of the mock Oracle here and the VRF coordinator, and instead we'll do mockDai and mockweth. Now, of course, since we have DAI-USD price feed and ETH-USD price feed, we're going to make sure we have these in our mocks here. And then we're also going to have to deploy these in our deploy mocks script below. So if we scroll down to deploy mocks, we can see this is what it currently has, which is pulling directly from the Chainlink mix. So we can just go ahead, delete the VRF coordinator mock and the mock oracle, and instead we'll deploy that mock weth and that mock die. So we'll do print deploying mock die token equals mock die dot deploy from account, and then we'll do print f statement deployed to die token dot address, and then we'll do print deploying mock weth, and then we'll do weth token equals mock weth dot deploy. We'll say from account, and then we'll print deployed to. This will be another printf weth token dot address. Now, additionally, we have our ETHUSD price feed left over from the Chainlink mix. We also need this DAI USD price feed. So we can go ahead in here. We'll add DAI USD price feed, and we'll set this as a mock v3 aggregator. We could do is we could parameterize this up so that the mock v3 aggregator takes maybe some different decimals, a different initial value, so that these could be different. But for the sake of testing, we're just going to leave them being the same here. So great. So we have the address of the weth token. We have the addresses of the FAU token. And if those don't exist on the network we're working on, we're going to deploy a mock. So now that we have all these addresses, we can do a dictionary of allowed tokens is going to be equal to this dictionary that we make. So we're just going to route each one of these contracts, like the DApp token, to its equivalent price feed. For the DApp token, we're just going to say that the DApp is going to be equal to DAI. We're going to say the FAU token is also equal to DAI, and our weth token, of course, is going to be equal to ETH. So we're going to want to get a DAI USD price feed, another DAI USD price feed, and an ETH USD price feed. So in our config, we can add DAI USD price feed. And since we're going to be doing our integration tests on Coven here, we'll come to the Chainlink docs. We'll go to Ethereum price feeds. We're on Coven. And we'll scroll down to DAI USD, which is this address right here. We'll pop that in. And then we'll also want the ETH USD price feed, which we'll also go grab that from here on the Coven network, and we'll grab that from right here, and we'll paste it in. So now to complete this dict, we can do this get contract again, and we'll deploy mock price feeds if they don't exist. So now we can just do get contract DAI USD price feed. FAU token is also going to be DAI USD price feed, and then our weth token is going to be ETH USD price feed. And awesome, now we have our dictionary of allowed tokens that we can pass to our add allowed tokens. This will map the tokens and their addresses with their associated price feeds so that we can get them all to equal the same value in our contracts. So we can go ahead and create this function called add allowed tokens. We'll pass it this token farm, we'll pass it the dictionary of allowed tokens, and then of course, we'll pass it the account. Now in our add allowed tokens function, we're going to loop through all these different tokens and call the add allowed tokens function on it. So we're going to do for each token in the dictionary of allowed tokens. We're going to do token farm dot add allowed tokens, and we'll do the token dot address, and we'll do from account. We'll say add tx equals that. We'll do add tx dot wait 1. Then we're going to call this set price feed contract. So we're actually going to set the price feed associated with that token. So we'll do set tx equals token farm dot set price feed contract. And we'll do token dot address, the dictionary of allowed tokens of that token that we're for looping, and then of course from account. And we'll do set tx dot wait 1. And then we'll just return the token farm. But we probably don't have to return anything. And great, that deploy script looks pretty good. And in fact, we're going to end our deploy script here with returning the token farm and the DApp token. This way, we can actually use this deploy script in our tests. So I'm just going to do a quick little zoom out, and we can see our wonderful deploy script right here. And awesome, it looks like we have just about everything here. Let's give this an initial test on a local Ganache chain. See if our mocks all work, see if everything at least makes sense. We can call our functions. Awesome, it looks like we can call all of our functions and we can deploy our mocks, and the mocking is working at least somewhat correctly here. This is great. We'll zoom out a little bit here. We've got our deploy scripts. We've got our add allowed token scripts. We've got all of our mock contracts added under tests. Things are looking good. Now, what do we want to do here? Well, of course, we want to run some tests. We want to make sure our contract is actually going to do what we say it's going to do. You guys ready? Let's jump into it. So in our tests, let's make a new folder called unit. We'll add a new file. We'll call it test token farm.py. Let's do some tests. Now, ideally, we would also write some tests for our DApp token. However, we're going to skip over those because we're basically just doing OpenZeppelin's implementation. But in a full-scale production here, you probably would want to write some tests on your tokens as well. So let's get into this. Let's look at our token farm and see what we need to test. Remember, ideally, every piece of code in our smart contract here should be tested in some form or another. So with that in mind, let's get started. So one of the first functions that we see is set price feed contract. So let's make a test for that. So we'll do def test set price feed contract. And we're literally going to test just this one function. So how do we test that? Well, first, let's make sure we're on a local network, right? Because we only want to be doing this on our local network since this is one of our unit tests. So in our arrange stage, we're going to do if network.showActive is not in local blockchain environments. Then we're going to run pytest.skip and say only for local testing. Of course, we got a number of pieces here that we need to import. We're going to have to do from Brownie, import network. We're going to do from scripts.helpful scripts, import local blockchain environments, and then we're going to import pytest. All right, so now we're going to get an account to make these transactions. We'll say account equals get account, and let's grab that from our helpful scripts as well. So now we have an account we can use. Let's even grab a non-owner account. So we'll say non-owner equals get account, and we'll do index equals 1. This will give us a different account rather than this account, and we'll use this to check some only owner functions. And then what we're going to do is we're going to get the token farm and the DApp token based off of our deploy script. So we're going to use this deploy token farm and DApp token. And we're going to import that by saying from scripts.deploy import deploy token farm and DApp token. And we're just going to call this function in our test right here. So we're going to say token farm DApp token equals deploy token farm and DApp token. Awesome. This is how we're going to do this a lot, this arrange step for a lot of these tests here, because this is how we're going to set them up. We could even hypothetically turn this into a conf test or into a wrapper if we wanted to, but we're just going to leave it in here like this for now. Now we can move on to our act phase. So we're going to want to do token farm dot set price feed contract. Because remember, this is what we're testing right now, and we're going to use a token and a price feed address. So we use the DApp token dot address. We'll use get contract to actually get an ETHUSD price feed address, which we can also grab from our helpful scripts, get contract. And an important note here, if you try to set a contract as an address parameter like this, Brownie will know, okay, that you're looking for an address instead of the actual contract. In any case, then we'll do from account. Save it and it reshifts over here. Now, this should work perfectly. So we're going to assert this. We're going to move into our assert stage, right? If we check our price feed mapping, this should now be updated. So we can do assert token farm dot token price feed mapping. And remember, token price feed mapping is an address to an address. So we'll say dap token dot address. This should be equal to get contract of ETHUSD price feed. This should be updated with exactly what get contract of ETHUSD price feed returns. In fact, we can even make this a little bit better. Copy this. We'll say price feed address equals get contract, and then we'll pop this in here, and we'll pop this here. That way now we're just using this single variable for both. All right, that's our first test. Let's run it. Brownie test. This will run the whole test suite. And we're passing. Awesome. Now, let's also do a test to make sure that non-owners can't call this function. We want to make sure that somebody other than the owner who deployed this, right? Because deploy token farm and dap token is going to be run by get account. We want to make sure that somebody else can't call this function. So we'll do with pytest.raises exceptions.virtual machine error. Oh, excuse me for that getting in the way. And then we'll try to call this exact same function here, right? We can even just copy paste it, but instead we'll call it from non-owner, right? And then we do also have to import exceptions from Brownie. So this should also pass. It's expecting this contract call to actually revert. So let's try this. Perfect, it passes, right? And we can double check to make sure that this pytest.raises is working, because what if we did account here, right? This now should fail, because this isn't going to revert. And that's exactly what happens. Perfect. So we can leave this as non-owner. And our first test is looking great. Let's even zoom out just a hair here. We can sleep easy that this function is going to work as we intended. Isn't that a wonderful feeling? Yes, it is. Great. Let's move on. So let's look at our token farm. What's the next function? Aha. Issue tokens. All right, great. Let's write some tests for issue tokens. So what are we going to do? Def test issue tokens. So how are we actually going to do this? Well, in order to test issuing tokens, we actually need to stake some tokens first. So for now, I'm actually just going to do pass here. And before we test issuing the staking tokens, we need to write a test for staking those tokens, right? Because in order to issue tokens, you need to have some tokens staked. So let's write a test stake tokens first, and then we'll write this test issue tokens. So we'll do def test stake tokens. Now let's set this up. So we're going to copy this bit here because we are going to be working on a local network with this. We'll do account equals get account, and then we'll go ahead and deploy the token farm and the dap token. So this initial bit is going to be exactly the same, making sure we're on a local network, getting the account, deploying the token farm and the dap token. So now let's move into the act phase. Let's go ahead and act. Let's go ahead and actually send some tokens to our token farm. So first, we obviously need to call approve on the dap token contract. So we'll do dap token dot approve to the token farm dot address. And again, you can see, and again, we can go to the Open Zeppelin docs to figure out what the parameters of this are, but it's going to be an address and it's going to be some amount, and then obviously from account. Now I put a couple question marks here because we're going to constantly be using an amount, right? We're going to be using an amount staked for a lot of our tests here. So what we're going to do is we're actually going to turn that into a fixture. We're going to call it amount staked. And we're going to define this in our conf test folder. So we're going to make our conf test file. So in here, we're going to do new file, conftest.py, and whoops, it's in the wrong directory. So we're going to go cd tests, unit, we're going to do move conftest.py, down one directory, and it should be in here now. If that didn't work, you should be able to drag and drop it into test. You just want to pull it out of unit is what we're doing here, right? Just want to get it so that it's just in this test directory here. In any case, in our conftest.py, we're going to create our first fixture. So we're going to do @pytest.fixture. We'll do def amount staked, and then we're just going to return web3.2way 1 ether. Now, of course, we need to import PyTest here. Then we're going to need to import. Then we're going to do from web3, import web3, and now it saves perfectly. So now we can use this amount staked fixture as basically a static variable, right? We could have done at the top, we could do something like amount staked equals, that exact same thing, but we're going to get into the habit of working with these fixtures. So we have our def test stake tokens, and we're going to pass it this amount staked fixture. PyTest and Brownie will automatically grab all this stuff from the conftest folder and put it into here. So now we can just use amount staked as a parameter in our test here. So once we approve, we can then do token farm dot stake tokens. We can now call our stake tokens function right here. And it takes an amount and then a token address. So of course, we're going to do amount staked as the amount, and then we'll do dep token address as the address, and of course, from account. And perfect. This is going to be our basic action of testing the staking functionality. So we can go ahead and down here and move into our assert phase, and we can just assert a number of things, right? We can do a little bracket here. We're going to do a couple of things here. We're going to assert the token farm, that staking balance of dap token dot address of account dot address equals amount staked. So let's talk about this really quickly. What is this actually doing? So if we go to our token farm, we know that we have this mapping called staking balance. And this is a mapping of a mapping, right? So we need to actually pass two variables, the first address and then the second address, to get this amount. This is how you do that syntactically with Brownie. You just pass it as additional parameters in here. So we pass the dap token address, which is going to be the token address here, and then the account address, which is going to be the address here. And perfect. So we can even run this by doing Brownie test -k test stake tokens. And great, looks like that passed perfectly. But we have a couple of other assertions to make, right? Because if we look at our stake tokens function, it does a lot of things. So let's check all of these and make sure that they all are working correctly. So we'll also assert that the token farm dot unique token staked of account.address is going to be equal to 1, right? This is going to be the first token, so it should have a unique token staked. We should also assert that the token farm dot stakers at the 0th index is going to be this account that we're using. We update our unique token staked, we update our staking balance, and then we add stakers.push, right? So we're going to be the first address in this array now. And then I'm going to do one other thing here too. I'm going to do return token farm and dap token. The reason I'm doing this is because now we can actually use this test in some of our other tests. Now we're getting a little bit integration-y here. We're kind of mixing and matching some stuff. We could even probably put this whole thing in a function in our regular scripts directory. But for simplicity's sake, this is how we're going to architect it. But great, let's test the rest of those. We'll just hit up, Brownie test -k, test stake tokens. We'll hit enter, and perfect. This is passing correctly as well. Awesome. Let's keep going. Now we're moving into this test issue tokens phase here. And we're going to use our test stake tokens test here. So the way that we're going to use this is we're going to grab this amount staked parameter, place it in here, and we're going to set this up exactly the same way. And we're going to set this up almost exactly the same way. So we can even just copy these few lines here, paste it. We're going to do an arrange. We're going to check to make sure we're on a local network. We're going to get our account. But instead of doing deploy token farm and DApp token, we're going to do token farm, comma DApp token equals test stake tokens, and we're going to pass it that amount staked. So this is why we're returning the token farm and the DApp token in our test stake tokens. That way we can use that function now in our test issue tokens. And perfect. Now we can test issuing these tokens. So to test issuing tokens, to issue this reward, we want to first take some inventory of the current starting balances of our address here. So we'll say starting balance equals DApp token dot balance of account dot address. And great. This is how we're going to start off in our arrange phase. Now let's move to acting, move in our act phase, and we'll just do token farm dot issue tokens. We'll say from account. And this is really the only thing that we're testing here. So now we can move into the arrange stage, and we'll do assert. I'm going to do a little parenthesis here, because this is going to be a long thing. And we're going to assert that the DApp token dot balance of the account dot address should equal the starting balance plus some new amount. What's that new amount going to be? Well, if we look at our issue tokens function, if we're staking in our conf test, if we're staking 1 ether, right, or 1 DAI, right, because we're staking the DApp token, we're just staking 1, our mocks are going to be this FUSD price feed, right? Our mock V3 aggregator, when we deploy it, the initial value is going to be this 2000 right here. And we're saying in our mock, in our sample here, we're saying we are staking 1 DApp token, which is equal in price to 1 ETH. So we should get 2000 DApp tokens in reward. Since we're saying, since the price of ETH is 2000 USD. So there's a little bit of math here, but the initial value is going to be 2000, right? You can almost think of it like this, with 18 decimals. And our application pays us reward based off of the total USD value that we have locked. So we actually can know that this is going to be that 2000 price. So what I'm even going to do is and if this isn't already in the Chainlink mix, shame on me, I should add this in here, is we're going to add a new variable called initial price feed value. It's going to be equal to 2000. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. It's going to be that super big number. And we're going to take that and we're going to set that here to our initial value is going to be now this initial price feed value. And what we can do in our test is we can then import that from our helpful scripts. And we can just assume that our starting balance is going to be now our starting balance plus that initial price feed balance. And if we've done our math correctly, and if we've done our issue tokens, and if we've done all of our get value correctly, this should work. We should have done our testing already on the things like get user total value, right? Because get user total value is a subset of issue tokens, but we're jumping the gun a little bit here. And we're going to test this later on anyways. So with that being said, let's run this test. Brownie test-k. Test issue tokens, and lovely. So our math is correct. Awesome. We are doing wonderfully with our tests here. We've even gotten some of the harder ones out of the way early, which isn't too bad either. Now, as far as this video goes, we're actually going to stop rating the test because we're literally just going to keep going down that Solidity file and grabbing functions and adding tests to them. We've got all the tests located in the GitHub repository associated with this lesson. There is both a unit test file and an integration test file in the GitHub repository. If you want to just go ahead and check that, feel free to do so. We're going to move on to the next section to keep things moving forward. But I highly, highly recommend you trying to write all these tests yourself. So good luck. We're going to have to make our now we're going to move
file.
into
We're going to have to add our private key
end
and our
so
web.
before we run this, make sure that your integration
project
tests work well. Make
D,
sure that
to get started.
if you run your deploy
If you want,
script
you
on
can
an
copy
actual
paste
network
this
directly
directly
like
from our
Coven,
last
because that's what we're
project.
going to be testing, everything works
We'll
correctly.
say dot
So of course,
env
you're going to want to get out your
dot
.env file. You're going
Great.
to want to add that to your Brownie config, add your
Great. Now
private
we have-
key in, add your Web3 inferior project ID, and make sure you have plenty of testnet Coven so that you can actually run these deploy scripts.
We can always find the latest faucets from the link token contracts page under our Coven or RinkB networks here. We're also going to need our wallets section. We'll do from key, and this is where we'll put the $, private key. Because
And now let's move into something
now that we've done all the
brand new
contract
here.
work, we're going to learn something totally new that we haven't covered yet. We're going to learn to do some front end development. Now, like I said, this isn't a front end course, and the focus isn't going to be on front end.
And I want to point out right away that this is considered a bonus section. There are a ton of pieces in this section that we're not going to have the time to go over thoroughly because we're not going to be going into what's going on the front end side. The editing is a little bit choppier, and I highly recommend having the documentation, having the GitHub associated with this front end with you while you're going through this.
FreeCodeCamp has an awesome video on doing front-end work. And if you want to learn more about React and TypeScript and some of the technologies that we're going to go over, definitely check out those videos after this. We're going to make this, though, so that you should be able to follow along with everything that we're doing. If you're not interested in front-end, feel free to go ahead and skip this part. However, understanding how these front-end applications work is really helpful, and it'll give you a massive, incredible skill to actually build front ends for your smart contracts. Having a really solid user interface is really important in the Web3 and the blockchain world. If people can't use your contracts, then what good is your application? So with that being said, let's jump on and let's build our front end. And I know we said we didn't like JavaScript. We're going to be working with TypeScript here, which is an improved version of JavaScript and catches a ton of the different bugs and allows us to be much more explicit with how we're working with our front end. We're also going to be working with React. We're going to be working with Create React App. This is a front end framework that allows us to quickly spin up a front end to build for our applications here. We're also going to be working with this tool called UseDApp. It's a framework for rapid dApp development and works great with React here. So let's get started building this front end. The first thing that we're going to want to do to build a front end for our full stack application, create React App boilerplate. So you should have npx installed. If you run npx -- version, it should show up. This should be installed from when we installed npm. If you don't have npx installed, you can run npm install -g npx. Additionally, we're going to want to install yarn here. To install yarn, again, you just run npm install -- global or -g yarn. You'll know you have yarn installed correctly if you can run yarn -- version. You see a version of yarn. And I have a link to install both npx and yarn in our GitHub repo. But great, once you have those, we can actually create a folder with all of our boilerplate code in it. We're going to run npx create React App. We're going to call it front end. And this is going to create a new folder called front end. And we're going to do -- template TypeScript, because we're going to want to work, like I said, with TypeScript instead of JavaScript. For those of you who've never worked with TypeScript before and who have worked with JavaScript, don't worry, the syntax is nearly identical. For those of you who have never worked with either, don't worry, we're going to walk through everything that we do. And then we'll hit enter here. And what's going to happen is you'll see we're going to create this new React app in this new front end folder in our project here. Awesome. Now that we've downloaded our Create React app, we have this new folder called front end, and it's got a whole bunch of stuff in it. Now, typically what different applications will actually do is they'll have one repository for all their Python and for all their contracts, but they'll additionally have a different folder or a different repository for their front-end application and their front-end work. This is really good practice. We're just going to bundle everything up into the same repo here just to get started and just to make it easier for us getting started here. However, what you will see across different projects is they'll have a totally separate repo for their front-end. So let's take some inventory on what's actually going on inside this folder. So the first folder you'll see is node modules. These are basically the pip installs. These are the different packages pulled in from JavaScript and TypeScript. We can pretty much ignore this folder for the majority of what we're working with here. Next, we have our public folder. We're also not really going to go in here.
but it's got some nice little images. It's got our basic index.html, which has the HTML that we're going to be running with. It has a couple logo images, and it has a manifest. The manifest is something that we want to change. This tells our browsers a little bit about what our app is and what our app actually does. So this is something that we would change, but everything in here is pretty self-explanatory. The short name of our application, the long name of our application, some icons, start URL. This is something that if you want to fiddle with it later, absolutely please go for it. And then robots.text. We're not going to talk about this at all. This helps web searchers and indexers learn a little bit more about your site. We can ignore this one as well. So for the most part, we're not really going to do anything in the public folder or the node modules folder. Our source folder, however, we are going to be spending a lot of time in. It has our app.css, which includes a whole bunch of formatting for HTML. We have app.test.tsx. This is going to be testing our front end. Yes, you can even test your front end. We're going to totally skip over testing the front end, which, yes, I know we've spent a lot of time testing our contracts. If you want to learn more about testing your front ends, there's some fantastic links in the GitHub and in the description to go over this. App.tsx, which we are going to be spending some time in, and it's one of the main places for us to write some code. Index.css, again, a formatting and styling file. Anything that ends in CSS is some type of formatting and styling. All these TSX are going to be typescripts. Index.tsx, we're going to pretty much ignore. We are going to change the logo, and we can ignore all these last bits here. A package.json. This file tells our project what dependencies it needs and Node.js packages it actually needs to get started. We have a README, which of course is a README. We have a TypeScript config, which gives us some options on how to work with TypeScript. We're going to ignore this. And then we have our yarn.lock, which is an auto-generated file. We're not going to touch it at all because Yarn is going to automatically create this. If you're unfamiliar with yarn.lock and unfamiliar with a lot of this stuff, don't worry too much about it. This isn't going to be a file you're really going to need to pay attention to. But okay, now that we've created the basic Create React app, we can actually go ahead and right now we can see what a front end would look like. So we'll CD to the front end. We'll run yarn just to make sure we have everything installed. What yarn does is it actually installs all of our dependencies. Anything in this package.json, yarn's going to go out and download these dependencies and store them into node modules. And then yarn.lock is going to tell us exactly what it downloaded. Once running yarn now, it just checks to see, it says, it looks like you already have everything installed. Because when we run Create React App, it already goes ahead and downloads everything. But now we can just run yarn start. And if you want to know where this is coming from, if you go in your package.json and you look under scripts, these are the 4 different scripts that we actually run. Running yarn start runs this mpx react scripts start, which will actually start our front end. So we'll do yarn start. You'll see react script start. You'll see it says starting the development server. And after a little bit of time, we'll get something that looks like this. Edit source /app.tsx and save and reload. And this is a super simple front end. Obviously, this isn't at all what we're looking for, but we've now started a front end, which is fantastic. It'll say compiled successfully. It'll say you can now view front end in the browser. It'll tell you exactly where it's located on our local host, on the network, and it'll give you any outputs from the front end down below. So we're just going to stop the front end for now by hitting Command C or Control C and closing it down. Of course, if we reload now on the front end, it's going to be blank. But great. So we have a really basic setup for working with a front end. Awesome. If we look at an application like app.aave.com, you'll see they have like this really fun connect button that pops up, and they've got some nice user interface tools for actually working with the blockchain. We don't want to have to reinvent the wheel and build all these custom tools for doing this. So we're going to use this application called UsedApp, or this framework called UsedApp, which has a whole lot of these already built in. To get started installing, all we have to do is run this command right here, yarn add usedapp/core. So here in our front end, we'll do yarn add at usedapp/core. And this will go ahead and install all the UsedApp pieces into our front end so we can actually work with UsedApp and not reinvent the wheel with working with wallets and working with Ethereum and other smart contract applications. Awesome. Now we have that installed. We can actually go ahead and start building our front end now. What we're going to do is we're going to go to app.tsx folder, and we're going to start in here. We're going to start adjusting some bits in here. So what we can do is we can do yarn start, and we'll get our little React front end here. Now what we could do is we can go ahead and do something like change anything in here, right? See how this line says edit source.app, source/app, and save to reload. What we could do, we change this whole line being something just like hello. We'll save it. It'll recompile. We can go back, and now it just says hello, right? So this is how we can actually upload and update our front end. We have these wonderful return pieces here, these return sections here, which will return the HTML to actually render the front end. And this is also our starting point for allowing our application to be Web3 compatible. So if we go to this use dApp documentation, right, we go to our getting started section, we have a little example here that shows kind of what something should look like, right? But it's not exactly clear where we put all this code. So they do have this wonderful step-by-step bit. And this is probably the most helpful bit here. It says the first thing you need to do is set up dApp provider with optional config and wrap your whole app in it. So we're going to use these dApp provider tags, right? This is the open tag and this is the closing tag. And we just wrap it around our app. So we can see here, this whole thing right now is our app. So we could take this whole thing, delete it, right? And if we save right now, we can go and see our front end's going to have nothing. It's going to be blank. This function app here that's getting exported, export default app, and this is getting rendered in this index.tsx. We have this cool little app HTML tag thing, right? But in any case, we want to wrap this whole thing with this tag here, right? So we can even just copy this, paste it in. I can do dApp provider, and then my VS Code even auto adds a second dApp provider here. We can delete this div class name equals app. I'll just put a little divider in here and just say hi. And at the top, we'll just import this dApp provider thing. Like what is this weird tag? We're going to import it. So we'll do import dApp provider from and use dApp/core. Now, if we hit save, we'll get this weird error saying, hey, property config is missing in our dApp provider. And that's because this dApp provider needs a config associated with it. So we need to add this config bit into this dApp provider. So we're going to do config equals, this first bracket says we're going to type in TypeScript, and this second bracket is saying we're an object here. So in this config, we're going to tell our application a couple of different things. So we're going to tell it what supported chains there are. What are the networks that our application can actually work with? The default value for supported chain in UseDApp is going to be mainnet, Reli, Kovan, Rinkeby, Ropsten, and XDAI. Since we're going to be testing only on Kovan and Rinkeby, we could just do chainid.kovan and chainid.chainid is another term that we can pull right from our UseDApp/core. Right, and now if we wanted some other chain ID, we could just go ahead and put it in here, right? Like if we wanted to work with our ganache, we could just do 1337. If we wanted some other random chain, we could just put the other number in there, right? But chainid.kovan is going to be 42, and chainid.rinkeby is going to be, what is it, 3? Yeah, 3 or whatever it is. And this is all we need to get started working with a Web3, a blockchain compatible application. So let's go back, let's save, and we'll refresh, and now it just says, hi. How's it going? So we're going to spend a lot of time in this source folder. And since we're going to be here in a lot, let's do some cleanup just to cut down on the amount of fat that we have with that create React app. So app.css, we're going to toss this. App.test, yes, tests are great, but we're going to toss it. We're going to leave index.css. We do need index.tsx. We don't need this logo bit anymore because we're going to use our own logo. We do need this. We also need this. And since we're not running tests anymore, we don't need this, but I'm going to leave it in here just in case you guys want to later on go back and add some tests. Great. So now we're looking a little bit lighter. And in our app, let's just remove app.css. Let's remove logo.svg, logo.svg. Goodbye. Now, okay, so we're going to create what's called a component. We're going to create a header component. Now in React, components are basically where you put modular parts of your front end. And we're going to create one of these components is going to be our header component. To do this, we're going to create a new folder, call it components. And in here, we're going to create a new file called header.tsx. And this is where we're going to put our header stuff. And we're looking to make a little button up here, right? We're looking to make a little button in this header. So what we're going to do is we're going to import some stuff. So we're going to import use ethers from at usedap/core. And again, if we look at the documentation real quick, this use ethers thing has got some cool stuff. It's got this activate browser wallet thing, got this account thing. It's got some cool stuff. So what do those actually do? We're going to start by exporting a constant variable called header. This is going to be a function, and this is some really fancy TypeScript syntax. What this is meaning is that we're saying header is a function, and here's what the function is going to do. We're going to use this use ethers thing to get a couple variables. So we're going to say constant variable account activate browser wallet deactivate equals use ethers. In order for us to actually use these, though, we need to figure out first if the user is connected. So we're going to create another constant variable. We'll call it is connected. And this is going to equal an account. It's going to equal an account. It's going to equal account does not equal undefined. So we're saying if the account is undefined, we're not connected. If it's not undefined, then great, we're connected. So we're literally just looking to see if there's an account here. And whether or not we're connected will decide if we show a connect button or not. So to do that, we're going to return a div. This is where we're going to return some HTML stuff. And we got to check to see if we're connected. So we'll do is connected. And we're going to use this question mark, which is known as a tertiary operator, which means if this is true, we're going to do something. And if it's false, we're going to do something else. So we're saying, okay, if we are connected, right, what do we do if we're connected here? Well, we're going to create a button. We'll have the color equal primary. Create this button here. And then my VS Code auto makes these closing tags. We could even leave this button blank if we want, or we're actually going to put some fancy stuff in here. And then we'll put a little function in it. We'll say onClick equals deactivate. This is this deactivate function pulled in from our use ethers thing. I should spell it right though. And we're going to call this button disconnect. Oops, there's a little parenthesis next to this. So this is what this is connect thing does. So we're saying if we are connected, great, do this. Now we're going to do a little colon here. And this is going to represent what we're going to do if we're not connected. Okay, if we're not connected, what we're going to show is a different button. Color can still be primary. And we're going to do onClick. We're going to do a function of activate browser wallet. And then we close up the button tag with another \button. And we'll call this one though. So if we are connected, we're going to show a disconnect button. And then if we're not connected, we're going to show a connect button. And that's it, right? Just make sure all of your divs, all your tags are matched up. And we can go ahead and save this. And if we look at our UI, you'll see nothing's changed, right? Okay, well, why isn't anything changed? Well, this component that we just made, it's living inside of this components folder. And we've exported this header variable, this header function, right? However, it's actually not in our app here, right? So if we look at our index.tsx, this is what's actually getting rendered. So we're just rendering this app variable, which is pulled in from ./app, right? This app.tsx. So index.tsx is really our true ground zero. This is where everything really comes from. This is kind of our entry point, right? This is our main function. You kind of think of it that way. That pulls from this app file that we have here. You can see in here, we don't have any reference to this header, right? We have our dApp provider, we have our div tag saying hi, but we don't have the header in here. So what we need to do is we need to import this component we just made into our app.tsx. So what we're going to do is we're going to do import header from /components/header. And now we can take this header bit, we can place it inside our header tags here. We can just do header, and we'll close the tag by adding it right here. We'll save, and we'll head back. And now we can see a little connect button here, which is great. Obviously, it doesn't look great, but we have the functionality here, which is what we want. And if we hit the connect button, our MetaMask will actually pop up and say, hey, would you like to connect? Which account would you like to connect? I'm going to go ahead, select my first one, next, connect. It's connecting. And now I'm actually going to be connected. Let's go to one of the supported networks like Coven. And now we can see here, we have this on click equals disconnect. If I click this now, oops, I need to put this inside the tag here. So we just moved on click to being inside of this little button here. Now we can see it actually says disconnect. And if I click it, I get disconnected. And if I hit connect, I get automatically connected, right? So if we look at our MetaMask, we can see we're connected right here, right? That little green thing. We can also manually disconnect by going right into our MetaMasks, click this connected thing here, click the account and hit disconnect the account, and you'll see our front end does indeed update. Awesome. This is how we can take our MetaMasks and actually inject it into our front ends so we can actually use the front ends. Great job. This is absolutely massive where we are so far. Now, you might be saying to yourself, hey, Patrick, this is cool, but it doesn't look very good. That's kind of a gross button in the top right corner. Can we style this up? Can we make this look a lot nicer? And the answer is absolutely yes. So there's a lot of different styling packages out there. You can 100% write your own custom ones. We're going to be using one called Material UI. It's a popular React framework for creating components and doing a lot of styling and doing a lot of really nice work here. So we're going to be adding this to our project as well. So to add it, we're just going to use this line. And I'm just going to go ahead and do it myself. I'm going to come in here. We're going to cancel this with Control C. We're going to do yarn add at material -UI/core. And this will give us access to some really nice libraries for styling all these buttons and styling a lot of the things that we're going to be working with. Back in our header, we can add this styling here. So we're going to do import button make styles from at material-UI/core. And we're going to use their button and their make styles. If we look in the documentation here, we can find their buttons. This is documentation, kind of like what their default buttons look like. And this looks pretty good. Looks a lot better than what we currently have. We're also going to be taking advantage of their make styles bit here. So make styles is a way to actually do styles based off of different themes that you can actually use with Materials UI. We're not going to be working with CSS files because we're going to be working with this make styles instead. If you prefer CSS, you can absolutely easily translate these to CSS files. So we are going to add some use styles first of all using make styles. So in here, we're going to do const use styles equals make styles. And this is where we put a theme in here. We're just going to set it to be a default theme. There's some documentation if you want to go ahead and add your own themes though. So this make styles function is going to have a container. And in this container, we're going to add some padding of theme.spacing. We're going to add display flex. We're going to add justify content, flex end, and then we're going to add gap, theme.spacing 1. So this is really just some typical CSS stuff. Now we're going to take this use styles constant that we just made, and down here we're going to do const classes equals use styles. So now we have this classes object that we can start working with. We're going to take this classes object in our little is connected thing. We're going to do div class name equals a little JavaScript in here, classes.container. And we're going to wrap this whole thing in this div, right? And this is going to style this whole button div here. So now if we go ahead and do yarn start again, because we shut it off, we come back here, we're going to see it's going to look a little bit different. Now it's been moved over here. We have this like fun little disconnect connect button where there's some padding and it looks a little bit nicer. And we're going to change all of our buttons to being kind of this built-in button from the Materials UI. Right, so we're going to swap out all those buttons with our new button here. And if we go back, we can see it looks even nicer now that we've swapped it out with that new type of button, right? It's got a nice little clicky feel to it. And then we can also do another line called variant equals contained for each of our buttons. So right next to the color primary, we'll do variant contained. And then now we go back and we have a really nice button now. So awesome. Now we have like a really nice button. Let's create a component that will contain the meat of our application now though. From Materials UI, we're going to use what's called containers, right? And these are nice little containers that are going to allow us to style and make these different sections? Well, we can import this container bit from this materials UI by doing import container from at material -UI/core in our app.tsx. And what we'll do to our header, we'll make a little container here. Container, we'll give it a closing tag, container. And then maybe in here, we'll put this little div high, right? So we'll remove that div, we'll paste it in here. And now we can see that it's been formatted a little bit, right? It's been pushed over from the side. It still says high. We're gonna wanna do one more thing. We're gonna give it a max width of being MD. Oops, max width equals MD. And this max width, now if we look in the docs again on materials UI, these are the different sizes. We have large, medium, small, extra large, extra small, and then false, right? These are the different options we can have for max width. We're just going to do medium. So if we save this now, go to our app, we can see it's been pushed over a little bit more. It's time to add our main pieces, right? We're going to need that top piece for staking and the bottom piece for unstaking. So we're actually going to create a new component called main, and this is going to be our main component. So we're going to create a new file in components called main.tsx. So let's start by just showing some information about our wallet, right? Showing what we have in our wallet associated with what we have in their smart contracts. So we'll say export a constant variable called main, and this will be a function. Here's that syntax for functions in TypeScript and JavaScript. In order for us to show what amounts that we have in our current wallet, we're going to need to know what chain that we're even on, because the network that we're on is going to determine where the addresses are, right? Because it's going to be different if you're on Coven or Mainnet, etc. Now, this is where it gets a little bit interesting, because obviously with Brownie, we know where these addresses are, right? And Brownie keeps track of this for us, right? It does it in our builds folder, in our deployments folder. If we look there now, if you actually deployed something to Coven, you'll see this 42. You'll see some stuff in here. You'll see this map.json, which has the most recent deployments of our tokens and our token farm, if you actually deployed it to Coven. If you haven't deployed it to Coven, I highly recommend you doing that now as well. This way, we can test our front ends against a real testnet. So in order to get these addresses, we're going to have to ask Brownie, hey Brownie, what are these addresses? Where are these coming from? So we're going to need to grab some information from this Brownie config. We're basically going to need to get all the information that's in this Brownie config, right? Because it has these addresses already, and this is what we want. However, it's really hard for Node.js to work outside of this source folder. So what we're going to want to do is we're going to want to send that Brownie config to our front end. So the way we're going to do that is we're going to actually modify by adding a new function called def update front end. Now, the only reason that this works is because we have both our contracts and our front end in the same repository. In the real world, once you deploy your contracts, those addresses are pretty much set, so you can just copy paste them over to your front end repository. But for us, we don't have set contracts yet, so we need a way to update our front end. So what we're going to do is we're going to send that Brownie config over to the front end, right? That way our main can know where those addresses are. We're also going to need to send the Brownie config to our source folder. We're also going to need to send the build folder. Why? Because this will have access to the dApp token address or any other mock addresses that we're using. We're going to open up our Brownie config, and we're going to paste, and we're going to dump the config into that source folder. Now, TypeScript doesn't work with YAML so well. It works with JSON really well. So we're actually going to convert it from YAML to JSON and dump it into the front end. So we're going to open up our Brownie config. We're going to say with open Brownie config.yaml. We're going to open it in read format. And we're going to say as Brownie config. We're going to say config dictionary equals yaml.load Brownie config loader equals yaml.full loader. So we're going to have to import this YAML from the top. We're going to do import YAML. And what this YAML is going to do is it's going to allow us to load our YAML into a dictionary. That's really it. So you probably don't have it right now. You're going to want to run pip install PyYAML to actually get it. Now we'll be able to have that. Now that we've got this in a dictionary, we're going to want to send this to the front end, right? We're going to want to write this dictionary as a JSON object to our front end. So we're going to say with open, and we're going to open that front end source folder, and that's just where we're going to dump this file. We're going to call it Brownie config.json. We're going to open this new file in write mode. We'll say it's as Brownie config JSON. What we're going to do is just do what's called a JSON dump. We're just going to take this dictionary and dump it as JSON into this file. So we're going to say json.dump config dic Brownie config JSON. Of course, we're going to have to import JSON. And then at the end, we'll even print front end updated. So now that we have this update front end script, what we can do when we run our deploy token and dap token, we can just add this update front end bit. Now, we don't want to always update the front end, right? We only want to do it when we're working with the front end. So in our deploy token farm and dap token, we're going to set update front end equals false. So by default, this is false. This way, when we run our tests, the front end won't get updated, right? And down here, we'll just say if update front end, then we'll update the front end. Otherwise, we won't. And in our main function here, we'll just say update front end equals true. Now, if we deploy this to Kovan or Rinkeby, we'll automatically update and send this Brownie config. And then let's actually change this to front end update instead of update front end so that we don't have the same method name as our Boolean here. So we'll do front end update instead. So now when we deploy, we'll actually go ahead and update our front end here. But we're not always going to redeploy. So let's also create an update front end.py script. And this will just call that function that we just made. So we'll do def main update front end. And then we'll do from scripts.deploy import update front end, semicolon there. Great. Let's open up a new shell by hitting a little plus button here. Now we have two shells, and we can just do Brownie, run scripts, update front end, doesn't matter the network. And what this is just going to do, it's just going to run that copy script, right? It's going to run our update front end script, which we made right here. So if we did this right, we should now have a brownie config.json in our front end /source directory. So if we go in here, we go into our source directory, we can indeed see it's right in here. Do we need anything else? Well, so that's going to give us those addresses, right? It's going to give us some of the addresses, but it's not going to give us everything. What about dap token, right? Dap token isn't going to be something in our brownie config. WETH token and FAU token, sure, they'll be in our config, but dap token is going to be something that only is going to be deployed by us. So we need to send that to the front end too. We need to send basically our whole build folder. So we're going to need to update this update front end script to also send the build folder. I know that we're actually going to be copying a number of different folders. So I'm just going to go ahead and make a new function called copy folders to front end. And in here, so we're going to make this copy folders to front end function here. We're going to do a couple of clever Python things. This is going to take a source and a destination. So we want a source folder and then a destination folder. So we're going to copy this build folder and move it to some folder in the front end. First, we're going to check that that destination exists. And if it exists, we're going to kill it. We're just going to remove it. So we're going to say if os.path.exists destination. We're going to do this shuttle.rmtree dest. And this is going to kill everything. So we need to import both of those. We're going to import os. And we're going to import shuttle or shutil. I actually have no idea how to pronounce that. But we're going to remove that whole bit. And we're just going to copy everything over from our build folder. So we're going to do shuttle.copytree src dest. So we're going to say, hey, if that build folder exists in the front end, just delete it. And we're just going to copy everything over from the build folder. And we're going to do this copy folders to front end a few times. The first thing, of course, like I said, is going to be with this build folder. So we're going to do this copy folders to front end. The source is going to be /build. So we're going to take this whole build thing and we're going to move it to /front end /src And we're going to create a new folder in here called chain info, right? And this is just going to have all of the build information. And all right, cool. So now we can run that. Brownie runs scripts, update front end. We'll go ahead and run that. And great, front end is now updated. So if we look in our front end, we look in source, we now have this chain info folder, which is literally just the build folder, which is awesome. Now we can actually start working with these pieces in our front end. So let's figure out how to get the dApp token address. Well, to get this dApp token address, we're going to need that map that we just got from chain info in our deployments, but we're also going to need to know what chain that we're currently on. Like what we saw before, we have this chain ID from useDApp/core, which will tell us what the chain ID of the current network that we're on. So we can go ahead and import that in here as well. So what we're going to do is we're going to import use ethers again from at useDApp/core. And what we're going to do here is use ethers allows us to get the chain ID that we're working on. So we can say const chain ID equals use ethers. Now that we have the chain ID, we're going to have to map it to the name of the network, right? Because our Brownie config has this network section, but it's mapped by the name of the network, not by the ID. So what we're actually going to do is we're going to create a helper config in our SRC. So we're just going to create a new file, helper config.json, and it's literally just going to be a JSON object that maps numbers to their associated chain names. So 42, for example, is going to be Coven. 4 is going to be RinkB. 1337 going to be Dev, or it could also be Ganache, right? 1 is going to be mainnet, etc. Now that we have this helper config, we can do import helper config from /helper config.json. And before we even get the dApp token address, we can do const network name is going to equal that helper config at the chain ID. Now TypeScript is actually going to get a little bit mad at us here. So we need to add a little bit more to this line actually. So we need to say, okay, only grab from this helper config if chain ID exists, right? Because there might be a chance that chain ID is nothing or it's something really weird. So we're going to say chain ID, and we're going to use this tertiary operator again. We're going to say if this chain ID exists, then go ahead and use the helper config. However, if it doesn't exist, just use dev. I should spell chain ID right so it doesn't get really confused on me. And whenever we return one of these components or try to use one of these components, we're always going to have to return some type of HTML or div tag like this. We head over to our app. We add our little main bit here. Of course, we're going to want to import this. We'll say import main from ./components/main. We save it. We'll add our main tag here. Our main opening. When we do the syntax, we're basically saying in it. Now, depending on your setup, you might actually run into this error here saying element implicitly has an any type because expression, blah, blah, blah. And you might be saying, okay, well, what's going on here? Now, to make our lives easier, we're going to tone down TypeScript's strictness here. So what we're going to do is in our TypeScript config.json, we're actually going to add suppress implicit any index errors. So we're basically suppressing when we get this type of error because it's not ever actually going to affect anything. I should probably spell this correctly. We'll save it. Now, if we save this file here, we're going to actually get this saying everything's compiled, everything looks good. And if we refresh our front end, we're going to get back to exactly where we are before. Now, what we can also do is we can also console.log these out. We can also see in the console exactly what these are going to look like. So if we do console.log chain ID and console.log network name, we save and we go back. We can go hit inspect, go to the console, and we'll see 42 and Coven gets printed out in the console over here. So that's 42 is the chain ID and Coven is the network name. So we know that we're doing this right. Okay, great. So we have our network name and we have a chain ID. We've got a way for us to update our front end with a new script. Let's finally get those different addresses that we need. We'll say the constant variable dApp token address is going to equal something from that build folder or that chain info folder that we created. Inside here, inside deployments, we have this map.json. And since I've already deployed this to Kovan, we have dApp token and token farm on the Kovan network. So we can then use that and say, if we are connected to a chain ID, and that's what this question mark is doing, saying if this chain ID exists, then look into that mapping, else we're just going to use a 0 address, right? So how do we actually get this mapping in here though? So I'm going to say import network mapping from, this is going to be in that chain info folder inside the deployments, and it's just going to be map.json. So we're going to take this network mapping object, and we're going to say if the chain ID exists, then inside this network mapping JSON object, we're going to cast that chain ID as a string, and then we're going to grab the name of the dApp token, which is going to be dApp token, and we're going to grab whatever address is at the top, right? So this is going to be a big list. The more times we deploy, the more times Brownie is going to keep track of it, and there's going to be all these different addresses, and we just want this one right at the top, right? We want the most recent one here. So we're just going to say at position 0. Otherwise, if we're not on a chain ID, we're just going to use a 0 address. And Ethers.js actually has a really nice package to give us what's called constants. So we're going to do constants dot address 0. And we can import that from Ethers. So we'll do import constants from Ethers. If you don't already have Ethers installed here, we're going to do cd front end. We're going to do yarn add Ethers. And now we have the Ethers package in here. Now, we're not going to do the same thing for the WETH token or the FAU token, because those tokens are defined in the Brownie config as opposed to being defined in our map.json here. So to get those ones, we're going to say const WETH token address. It's going to equal, let's check first if the chain ID exists, and if it does, we're going to grab it from the Brownie config. So to grab that, we're going to do import Brownie config from, again, now that we've imported it, Brownie config.json. And now we can work with this Brownie config inside of our front end. So we'll say Brownie config of networks, of that network name of the WETH token. And if chain ID does not exist, then once again, we're going to do constants.address 0. So we're just going to leave it blank. And then we're going to do the exact same thing for the FAU/the DAI token. So we'll do const FAU token address equals chain ID question mark. So if the chain ID does exist, it'll be the Brownie config networks network name FAU token. And if chain ID doesn't exist, it'll be constants dot address 0. Okay, awesome. And if we save it, oops, looks like I put an extra comma in there by accident. Just going to get rid of that and resave. And then refresh here. So I'm getting an issue because I'm on the Rinkby chain right now, and it's saying, hey, there's nothing for Rink. There's no dApp token for Rinkby. You got to be on Kovan. So if I go back to Kovan here and I refresh, now it works out fine, right? This might still break for you if you're on Kovan and you haven't deployed anything to Kovan. We can fix this in our config for the dApp provider by changing the supported chains for this. Now, typically, a lot of the times you're going to want to test using a Ganache chain or some type of local chain so that your front-end testing can be a lot faster. For this, we're just going to do everything on Kovan, but a nice little challenge for you would be to refactor this so that it also works with something like Ganache. And we're going to not use Ganache. So I'm just going to go back to app.tsx. We're going to remove Ganache. We're going to even remove Rinkby for now. We're just going to work with Kovan just to make it simple. If I go to our React page now, refresh, I can connect. Awesome. If I go to Rinkeby, it's not going to freak out because it says, hey, Rinkeby is not even supported. So I don't care what you're doing. However, Coven is supported. So we're connected and we're looking good. And the thing is, we really don't want to couple our front end with our contracts, right? We really want to code the contracts independently and the front end independently anyways. So let's get back into our main.tsx. So we're going to be in here for a while, but we've already done some great things. We've gotten what network we're on, what chain ID we're on, and we've gotten the different addresses for these different tokens. So as you can probably see, the place that we're actually going to put stuff on the front end is in this little return statement here, right? Right now we're just returning I'm main, and we just see I'm main right here. To do this, we're actually going to make another component. We're going to make a component called your wallet. This component is going to be a part of this main component here. It's a component inside of a component that is literally only going to address our wallet needs. So on our little components tab here, we're going to go ahead and create a new folder, and we're going to call it your wallet. And this is just going to have everything to do with our wallet in here. So let's get in here. We'll create a new file because we're going to actually make a couple files. And our first one is just going to be your wallet.tsx. And this is going to be our component that is just going to deal with getting our wallet, getting the token balances of the different tokens that we have. Since we know we're going to put this component in main, and main is in our home base, our app.tsx, you know that we're going to do an export const your wallet in here, and we'll make this a function. Now, in order to actually show these tokens, we do need to get some information from our other component. We need to get some information on what the supported tokens even are. So we're going to have our main actually pass a variable to our wallet here. We're going to call it the supported tokens. And this is going to be of type your wallet props. And this is going to be your wallet props here. Just to tell TypeScript what this supported tokens is going to look like, we're going to say interface your wallet props. It's going to look like this. Supported tokens, and it's going to be an array of token. It's going to be an array of some token. We're going to grab that token type from main as well. So actually we're going to do import token from main. And in our main, we're going to pass this token, and we're going to pass some supported tokens to our wallet. So right underneath those 3 token addresses, back in main, we're going to do const supported tokens is going to be an array of token, this token type. So above here, we're going to do export type token equals, and we're going to say a token type is going to involve an image, which is going to be a string, an address, which is also going to be a string, and a name, which will also be a string. So we're creating a new type called token here in our main function. We're creating this supported tokens object, which is an array of tokens. And this is, and this is going to equal that array syntax. So our first token is going to have an image that we haven't defined yet. The address is going to be this DApp token address. And the name, of course, is going to be DApp for DApp token. Now we're going to need a couple images. So at this point, you should see where we're going with this. We'll create this array of supported tokens. First is our DApp token, and we need an image for this DApp token. So if you're following along, you can just grab this image right off of the GitHub, and we're going to grab that DApp token, and we're going to pop it into src, and we're going to change this to dapp.png. Now we can import this by doing import dapp from /dapp.png. Now we can take this dapp image, and under image, now let's do the other tokens. So we'll do a comma, we'll do image, will be eth, address will be weth token address, name will be weth. And again, we can either, and let's close this off. And again, we can either grab right from my GitHub or pop it into my SRC here. We'll change this to eth.png. We'll scroll up and we'll import this as well. Import eth from /eth.png. And boom, that looks good. One more comma to image. It's going to be FAU, or this is going to be our DAI token. Address is going to be FAU, token address. Name is going to be FAU, or DAI. This will be our DAI token. We'll pop it into our SRC, change the name to DAI.png. Then we'll import DAI from ./DAI.png. Grab DAI, and it looks like we're going to name it DAI actually instead. And if your VS Code starts yelling at you about this can't find module, it's really confused, what we're going to do at the top here. So we're just going to add a little comment, /* ESLint disable spaced comment * reference types equals React scripts. And we'll save, and that issue will go away. All right. Well, now that we have our supported tokens token array, we can actually pass this to that your wallet bit. Right. So now we're going to go to this return bit. We're going to remove that div on main, and we're going to actually start getting to some meat here. So we're going to pass this to our your wallet component that we're going to import in just a second, and we're going to send it our supported tokens. We're going to say supported tokens equals supported tokens / like this. And of course, we're going to have to import your wallet here. So we'll scroll up to the top. We'll do import your wallet from / your wallet. We're actually going to make a new file in our your wallet folder called index.ts. And we're just going to export your wallet from / your wallet. And we'll save that. And we're getting an issue saying you wallet is not defined. It's because this should be your wallet. Okay, cool. So we're getting another issue, but I'm going to fix that in a second. Great. So now we have some supported tokens. We have a wallet here. We're exporting our wallet with our index.ts in our your wallet folder. Now let's finish our your wallet implementation. And this needs a little equal sign here. Whoops. And we're going to get this little error basically because we don't have a return here. So we could just do return just to make it happy. Div hi. We'll even change this to I'm your wallet. And we'll save, and now everything's happy. We'll go to our front end, we'll do a quick refresh, and now we see I'm your wallet. So let's keep diving into your wallet here, right? Because this is going to be where we're doing all of this stuff about what's in your wallet. Now, we're going to use a couple of these components from the Materials UI here to get started. To start, we're just going to use this box. The box component, it serves just as a wrapper component for most of the CSS utility needs. It's just a box, right? It's a box that we can put on our front end. So we're going to come over into our your wallet, and we'll start working with this box. We're going to put everything inside of this little box here. We're going to have to import this box. Do import box from @material UI/core. We'll give this a little header. H1. We'll say your wallet. H1. Get a little header. Your wallet. I'm your wallet. Great. Now we'll get rid of this little I'm your wallet, and we'll create another box. And in here, we're going to add all of our functionality for what is in our wallet. Now we're going to use some tabs here from the Materials UI to swap between the tokens, right? We're going to have one tab for FAU token, another tab for DApp token, and for wrapped ether. We're going to use this tabs thing here. So to work with tabs, we're going to need to import some tab stuff. So we're going to import tab context, tab list, and tab panel from material UI/lab. So material UI/lab, these are some components that they're not quite ready to move to the core. So we do have to add these as well. So we'll go to our front end in our other shell, and we'll do yarn add material UI/lab. These are kind of their testy ones, but they have some really nice features that we're going to use. But let's get into this box and let's make our first tab context value equal to, now in our box here, the first tab that we're going to have to use is going to be whatever token that we have selected. And to select tokens, we're going to use what's called a state hook. So we're going to create a state hook here inside of this. We're going to do const selected token index set selected token index equals use state number 0. So use state, we're going to grab from React. It looks like I've already imported it here. Import React, comma, brackets use state from React. And what this is going to do, it's going to create one variable, selected token index. This is going to be whatever token that we're on. And then set selected token index is going to update this selected token index. This use state components thing is a way of saving state between renders of components. So in our little box here, we're going to start with a tab context. We're going to start basically with our own tab, and the value is going to be equal to whatever token we currently have selected .toString. And we're going to have to make a list of these tokens in our tab context. We're going to have to add some way to change between the tabs, right? When we change between the tabs, we want a different token to be selected. And we're going to make a tab list that's going to change whenever we click the different tab. So we're going to add some functionality to this, but for now we're just going to give it an ARIA label. Call this our stake form tabs. And based off the supported tokens in a mapping of the token to index, we're going to call a function in here where we return a tab, which will have a label equal to the token.name. The value would be equal to the index.string, or excuse me, .toString. And the key is going to be equal to the index. Tab is something that is just from the material UI/core. So we're going to import tab from material UI/core. I should probably spell supported tokens correctly. Supported tokens. And now, if we look at our UI, we can now see we got a couple different buttons here, which is great. We have DApp, WETH, and DAI, right? These are the different supported tokens that we're mapping here. Now, of course, if we click the different buttons, nothing actually happens. So we do need to handle a change. We do need to code some functionality to handle a change whenever we do something different. So in our tab list, we're going to add onChange equals handle change. And we're going to code a little functionality at the top to actually handle a change. So we'll say const handle change. It's going to be equal to an event, a react.change event. We'll do a new value. It's going to be a string, and this is a function. So we're going to do this little function syntax again. And all we're going to do is we're going to use our little state hook here. So we're going to do set selected token index, and we're going to parse the int of the new value that we get. So what's happening here? We've added this new functionality where whenever we change one of those tabs, we're going to change the selected token, right? This selected token number is going to be different. And what we do is we map the indexes to a token, right? So each one of these tokens is going to represent a certain number. So now when we save, when we go check out our front end, you can now see that we do indeed swap between tabs here, which is really nice. All right, let's keep going. So that's cool. We have a way to swap between the different tokens visually here, but we need a big stake button, right? The reason that we need to swap between the tokens is because we need a way to stake between them. So when we're on one of these tabs, we're going to add a stake form here. We're going to add a big button that allows us to stake. So we're going to do some TypeScript. We're going to do supported tokens.map. We're going to map that token and index again. It's going to be another function. Use that. And in here, we're going to return a different tab panel. The value in here is going to be the index.toString. Key is going to be the index. We'll make a little div in here. And we're going to need to put two pieces in here. We're going to need to be putting our wallet balance in here, and then also a big stake button, right? Of course, if we look at it right now, it's just going to say our wallet balance and a big stake button. But how do we actually do this? How do we actually get our wallet balance and one of these big stake buttons? Well, we're probably going to need some type of component to get our actual wallet balance that we're going to stick in here. So, yep, you already know, we're going to go in here into our your wallet component. We're going to create a new file, and this is where we're going to define that wallet balance component. And we're going to import our wallet balance into our wallet here so that we can actually see the balance of our wallet right in the front end. And this is where we're going to actually be reading off chain finally after a lot of TypeScript and React setup. Since we're going to be importing this into our your wallet component here, of course, we're going to start with export const wallet balance. And we're going to make this a function. So we'll do this really weird function syntax. And we're probably going to want to pass this the token, right? The token that we want to get the balance of. So we're even going to set that up like this, a token in here, and we'll define what this looks like with the interface called wallet balance props. So we'll say export interface wallet balance props. And this will be a token, right? This will be that same token type that we defined before. So we're going to have to import that. So we'll say import token from main. All right, great. And that's our initial setup here. We'll grab from the token that we pass to this, we'll get the image, address, and the name from that token. Address and name. We'll grab the account, right? Because we're going to need the account along with the token. So we'll say const account equals use ethers. And of course, we're going to have to import account from, import not account, use ethers from @usedap/core. We're going to need the account, we're going to need the address, and usedap/core has a nice little hook called use token balance that we're going to use. You can check it out in the documentation. It provides a way to fetch the balance of ERC20 tokens specified by a token address. It makes our lives a lot easier. So we'll just import that as well, use token balance. And all we have to do really is do const token balance equals use token balance of the address of the token and our account here. We could even do a quick console.log token balance to see if we're doing it correctly. And we take this wallet balance and import it into our wallet here. We should be able to see something. So we'll import it into our wallet now. Let's scroll to the top. We'll do import wallet balance from /wallet balance. And down inside our very large return function here, we'll add this new tab or this new component. We'll say wallet balance. We still, remember, we need to send it the token. So we'll send it tokens at the index of the selected token index. I should spell supported tokens right. I should spell wallet balance right with a capital B. We do need to do a return so that it's actually a JSX component. We'll do a div. We'll just have this say, I'm the wallet balance. If we go to our front end, we do a quick refresh. We do indeed see this little print line here. This is JavaScript's big number. So if we really want to see this token balance, we'll do .toString. And we have to put this question mark here to tell TypeScript, hey, turn it to a string if it's not undefined. And now if we save, we go to our front end, we do a refresh. Since we are connected to Coven here, we can see we got an amount printed out here. And if we switch tabs, you'll see the different amounts being printed here, which is fantastic. Cool. So let's remove this little console.log. We want to show this token balance, obviously, in our UI, right? We don't want to have people to have to go to the console.log, right, to actually see it. We want it to represent, we want it to show up where it says, I'm the wallet balance. So what we're going to do, first, we should probably format it, right? Because this is in units of way. So we're going to do const formatted token balance. This will be a number, which will equal to token balance. If token balance does exist, again, we're using this tertiary operator. We're going to parse float format units token balance 18. Otherwise, we're just going to use 0. Format units is a nice little import that we're going to grab from the Ethers project. So we'll do import format units from at Ethers project /units. And of course, yarn add at Ethers project. And of course, we're going to do a yarn add on this here. We'll do yarn add at Ethers project /units. And now this formatted token balance is going to be this token balance that we just got, but formatted much nicer. And in our little div here, what we could just do is we could just add this formatted token balance. We'll save and we'll look at the front end now. And aha! We now see we have 100 DApp, 0 WETH, and 15 DAI, right? These numbers might be a little bit different depending on how much you actually got, but this is perfect. This is exactly what we're looking for. So let's close out the console and let's flesh this out a little bit. Let's make this look a little bit nicer here. So instead of just returning a little div like this, let's actually make a new component called balance message. And we'll use this instead. We'll create a new component called balance message, and it'll format up the way we actually show these formatted tokens. And here we'll pass it a couple variables. We'll pass this component an amount. We'll pass it a label. We'll say the label is going to be your unstaked name balance, right? We're grabbing name from the token. And we'll pass it a token image SRC, which is going to be that image. So we're going to pass it a label, or excuse me, not IMG, it's going to be image. We're going to pass it a label, token image, and an amount, right? And this component is just going to make us have this balance look a little bit nicer. So in our Your Wallet section, we're going to do a new file called balanceMessage.tsx. Oops, not tsxx. TSX, and we can kind of rip through this pretty quickly. So, per usual, we're going to do export const balance message is going to equal a function where it's going to take those parameters, a label, an amount, and a token image SRC. And this will be an interface of balance message props. This will be a function, of course, so we'll do this weird function syntax. Of course, we need to tell TypeScript what this looks like. So we'll say interface, balance message props. What are those inputs? We'll say the label is going to be a string. The amount is going to be a number. And the token image SRC is going to be a string. And in here, we're going to once again do that use styles bit from Materials UI, because we want to style this up a little bit. So we're going to import make styles from at material /UI/core. We'll do a const use styles. It's going to equal make styles theme, which we're going to skip doing a theme, but let's make some styles for the different pieces. Let's give it balance message be surrounded mainly by a container, which will have a couple of styles in here. We'll say the display is going to be an inline grid. The grid template columns are going to be auto, auto, auto. Again, you can check out all these parameters in the documentation. There's going to be a gap, which will be theme.spacing 1. Again, we're skipping theme, but this will just be a way to add some spacing. And then align items in the center. We'll also give the token image its own styling. We'll give it a width of 32px, 32 pixels, and then the amount, we'll give it a font weight of 700. So we'll make that a little thick. So now that we have our use styles, we have our styling here. We can go into our export below. We'll do const classes equals use styles. And we're going to return a div. Class name is going to be equal to that main container, classes.container. We'll do another div just for that label that we're looking for. We'll do another div for class name. Equals classes.amount. So have that nice font weight. And in here, we'll just have the amount. And then we'll grab that image of the token. Class name is going to equal to classes.tokenImage. We'll grab the source of that image is just going to be that token image src that we get passed. And we'll give it an alt called token logo. And we'll close that tab out. Great. So what we're going to want to do is in our wallet balance here, this balance message that we just created, we'll do import balance message from ... components / your wallet, capital W. And actually, I know we're going to use this balance message a little bit later. So I'm actually going to grab it and drag it into components, move it into components, and move it out of your wallet. Because I know that we're actually going to use it a little bit later. So that means in our wallet balance, we're just going to pull it right from components / balance message. And whoops, we actually need to make this look like this. Close it out here. Remove this part. Like this. Boom, right like that. And now let's try out the front end. Okay, we're looking a little bit nicer, right? We have a really thick number here explaining how much of the token we have. We have the images popping up. This is starting to look great. Let's add this stake button, right? So that when they see this, they can actually stake and interact with our contract here. So to do this, we do need to create another component called our stake form. So in your wallet, we're going to create a new file called stakeform.tsx. And this is where we're going to add a little button and an amount for the users to actually stake on our contract. So you already know we're going to start with export const stakeform equals, and we're going to have our wallet pass the token just like we passed the token to wallet balance. So we'll say token, and we'll have this be stakeform props, which is an interface we're going to define in a second. This is a function, so we'll do this fun function syntax here. And then stakeform props, as you know, is just going to be a token. So we'll do export interface stakeform props. And this is just going to be a token of type token, which again, we're going to import token from main. Great. And that is our starting point for this. So we're going to create a stake form with a big button that says stake, and the user can actually choose how much they want to stake on our smart contract. So we're going to do some similar stuff as we did before. We're going to grab some variables. We're going to say the address is going to be that token address that we get from the past token. We're also going to get a name of the token from that token. We're going to get our account from use ethers again. So we can import that. We'll say from, or whoops, import. Use ethers from at use dApp/core. We're going to want to grab the token balance. So we'll do const token balance. Once again, we can grab that with the use token balance with the token address and the account. So we're going to use token balance. This will also grab from use dApp/core. We're going to want to format this token balance. So we'll do const formatted token balance. This is going to be a number. Again, this is going to be the exact same as we did before. We'll say token balance. Do parse float. We'll do format units. Token balance. 18 or 0. And format units, once again, we're going to import that. Import format units from at ethers project/units. Perfect. Importing here, we've gotten some starter boilerplate. Let's just go ahead and grab those buttons, right? Because those are really the things that we're going to care about here. Let's just return some stuff here so something can show up on our front end, right? So let's do return. I'll start returning something here. And whenever we return something, it's all got to be in one tag, right? So I know I'm going to be doing a whole bunch of different tags. So I'm just going to go ahead and make an open and close tag here. And this is where I'm going to put all my stuff. Now we know we're going to want to have a big stake button, right? So let's go ahead and just do, let's get a button tag in here. And of course, since we're going to have a button, we're going to pull this in from that material UI, right? So we'll do import button from material UI/core, just so we can get started with something here. And then back in our your wallet.tsx, let's add this button in here inside of our tab panel. Right below our wallet balance, we'll add this stake form thing. We'll open and close. Of course, we've got to import it. So we'll say import stake form from /stake form. And we need to pass that token object. So back in our your wallet, we're going to say, okay, token equals supported tokens of that selected token index. Selected token index. And let's not have this. Let's just do a little backslash here to close that out. Let's be sure to close this bracket here. And we'll give this button some stuff, right? We'll do color equals primary. We'll say size equals large. And then we'll give it some text called stake, double exclamation point, or however many you want to put in there. And now if we look at our front end, we got this big stake button. Nice. Okay, we're looking a little bit better. Currently doesn't do anything, but we have a stake button. Great. Now we can start adding some implementation, right? We can have it do some stuff now. When we hit this stake button, what do we want it to do? We want it to do two things. We want it to approve whatever token that we have, and then we want it to stake that amount. We also need to have some type of form here. We need to know how much we want to stake, right? So we're going to need some little input box that we can add a certain amount in. Well, we can do that too with a little input box from Materials UI. So there's another package we're going to grab, which is called input from Materials UI/core. And then we're going to use this little input box before the button. So we're going to do input, a little slash here. And now if we save, refresh the front end, awesome. Now we can do some typing in here. We can click this stake button. Now to do this though, we're going to need to keep track of how much amount is in here, right? We're going to need to keep track of how much amount's in here. So we're going to inspect on the front end, and we're going to go to the console and see if we can follow along with how much is in here. or what amount is in here. And to do this, we're going to make another one of those state hooks, and we're going to track that amount in there. So we're going to say const amount, set amount for one of these stake hooks equals use state, which is going to be a number or a string or an array, number or string, 0. And we're going to import this use state here from React. So we're going to do import React, use state from React. And now we have this state hook that we can use to keep track of the amount that's going to be put in there. And with our input tag here, we're going to say on change. Whenever this changes, we're going to have some handle function, right? We're going to call it handle input change. And this is going to handle the input change. So we're going to create that function. We're going to do const handle input change equals, and we're going to use some events stuff in here. We're going to say this is going to take an event, a React dot change event of HTML input element. This is going to be a function that's going to set amount. It's going to say const new amount equals event.target.value. Whenever we change that value in that field, if it's equal to nothing, then we're just going to say, okay, we're going to do nothing. Otherwise, we're going to cast it as a number, event.target.value. We're going to cast whatever is in there as a number. And then we're going to do set amount to this new amount. And what we could do is we can even do a console.log new amount. And we can start using it, right? So if I go back here and I do 1, 2, 3, right, you can see it's console.logging every time I change something in here. So now we have a way to actually get that amount with this input. Now we're going to need a way to send that amount as part of our stake, right? So we're going to first have to call that approve function with this amount. And then we're going to have to call from our token farm, then we're going to have to call this stake method. So how do we get it to call this approve function here? Well, to do these, we're actually going to make some new state hooks that we're going to use in our staking farm here. We're going to make state hooks for approving and for staking and even for unstaking. So back in our folder here, we're going to create a new folder called hooks. And this is where we're going to add some different hooks. First hook that we're going to make is going to be called use stake tokens dot TypeScript. And this is something that we're going to import into our stake form here so that we can actually stake some tokens. And the way we want to do it too is that once we hit our stake button, it kicks off the approve, and then actually right afterwards, it kicks off a send. It kicks off a stake token. We want to run these two functions sequentially. And we're going to make this use stake token hook clever enough to do it in that order. So let's do it. Hooks are basically just like components, except for they're more functionality wise. So since we know we're just like components, we're going to do export const use stake tokens. And this is going to be a function, just like our other components. And as input, we're going to take a token address. That's going to be a string. And inside of this, we're going to have some intelligent scripts to know if it's already been approved, if it's not already been approved, and what we need to do. Right? We know we're going to need some approve thing, and we know we're going to need some stake tokens thing. So let's at least try to approach this approve thing first before we get too creative, right? How do we approve this transaction? To get an approve, we're going to need a couple things. We're going to need the address, as you guys know. We're probably going to need the ABI. We're probably going to need the chain ID, so we know which chain it's on. So let's go ahead and let's grab those. So we'll do const chain ID equals use ethers. And since we're using use ethers here, we're going to import this. So we'll do import use ethers from at use dep /core. We're also going to want the ABI of the token farm. So we'll do const ABI equals, well, where do we get this ABI from? Aha, that's right. We've imported it in our little chain info piece. And it should be right in here. We should be able to do import token farm from down a directory. It'll be in chain info /contracts /token farm.json. And now we can say ABI is going to be equal to this token farm, right? Because in token farm, we have an ABI key, so we can just abstract that away and just pull out the ABI. Perfect. We're going to need the token address, of course. We're also going to need our token farm address, and we can find that the exact same way we found it before with const token farm address. It's going to be equal to, depending on if the chain ID exists. Once again, we're going to want to use that network mapping. So we can even go back to main.tsx and see how we did it here for the dApp token address. We can copy this as like a frame of reference. We'll say, if this chain ID exists, we'll pull right from that network mapping. Right, we'll pull right from the network mapping, so we got to import that too, which we can grab from import network mapping from chain info /deployments /map.json. So once again, we're going to say if that chain ID exists in the network mapping, we're going to use that string chain ID. So we'll do string chain ID of the token farm at position 0, right? Because we obviously want the most recent one. Otherwise, again, we'll do constants.address 0. And since we're going to do that, of course, we're going to have to do import constants from ethers. And this hooks folder should be in source, so let's just make sure that we have hooks in source here. Now we're going to want to interact with this token farm address contract, right? We're going to want to run that approve function. First, we want to create like an interface, so we can do const token farm interface. We'll say this equals new utils.interface with the ABI. This utils we can again grab from the ethers project, or excuse me, from ethers. So we'll do comma utils. Now we can create a token farm interface here. And now that we have an interface, we'll create a contract. So we'll do const token farm contract equals new contract. And this will be a combination of this token farm interface and the token farm address. Actually, it's address first. And contract is something we can grab from import contract from @ethers project /contracts. All right. You're probably starting to follow along and figure out, okay, cool, I have a token farm contract. Now that we have a contract, we can actually call some functions, which we totally can, but right, we need to call the approve first. So let's get the token contract before we even work with the stake token, right? So to work with the token, we're going to want to do the same thing. So we'll do const ERC20 interface equals new utils.interface interface. And this will be from ERC20 ABI, which we should probably make first. So we'll do const ERC20 ABI equals, we'll do it the same way we did up here, except for instead of token farm, we'll do something else. We'll do, look in our contracts here, we'll do mock ERC20 instead. And then we'll just call this ERC20. Or yeah, we'll just call this ERC20. We'll grab it from our mock ERC20.json. So now that we have this ERC20, we do const ERC20 ABI equals ERC20.ABI. And we can just pop this ABI to create our interface. We'll now do const ERC20 contract equals new contract of the token address, comma, the ERC20 interface. Boom. Okay. Now we have both of these contracts. We have the ERC20 contract. We have the token farm contract. Now we should be able to go ahead and call some functions, right? Now to actually send one of these, we're going to use this thing called useContract function. It's a hook in useDApp that returns an object with two variables, a state and a send. This state bit is used to represent the status of the transaction. And that's how we're actually going to automatically kick off the stake after we approve. To send a transaction, we actually have to use this send function here. So we're going to use this use contract function to get a state and a send. So that's what we're going to first need to do. So we're going to do const send, and then we're going to call this approve ERC20 send, and state, because this is what it's returning. It's returning a send and a state. And we're going to say state is going to be approve ERC20 state equals use contract function. We pass the token contract, the ERC20 contract, comma, the name of the function, which is going to be approve. Then we do a comma, and then we'll do a little object here. We'll call this transaction name, and this will just be approve ERC20 transfer. Then, of course, we have to import this from useDApp, this use contract function. Now, oddly enough, whoops, and I got rid of the closing tag here. But great. So now, in a weird way, we actually have these two new pieces here. We have this send function, this approve ERC20 send, and this approve ERC20 state. This is going to be the status of our transaction, and this is going to be the actual function that we use. And if we want to call this approve function, what we can do is now we can return calling this approve function. So we'll do const approve. We'll have this be a function. We'll say it'll take a string amount as an input parameter, and we'll just have it return this approve ERC20 send, and we'll give it the token farm contract address as a first input parameter, token farm address, and we'll use this input amount as a second parameter. And then we'll just have this use stake tokens return this approve function, and then also this state here. So it's going to return approve, and it's going to return state. We could also just have it return this if we wanted, but we're going to wrap it just all up in this approve thing here. We also probably want to return this state, right? So we're going to turn this into a hook as well. So we're going to do const state set state equals, use state, and we'll have this be the approved ERC20 state as the input. And of course, since we're using use state, we're going to grab this from React as well. We also want to return the state, so we'll return this approve ERC20 state here. So now we have a way to actually do all this. So in our stake form, what we're going to have is we're going to create a const that's going to grab those two variables. So we'll do const approve, and approve ERC20 state is going to be equal to use stake tokens with that token address pulled down from the token as the input parameter. And this is our new hook. So we're going to import use stake tokens from ... hooks. Now that we have these two functions, we have the approve function, and then we have the state of that function. Now we can add a handle submit functionality for our button here. So now we can say, okay, on click, when we click this button, we're going to do a handle stake submit, right? Because this is our big, well, it's not going to show up now because I broke everything, but this is our big button, right? This is our stake button. So we're going to create this function called handle stake submit. So let's go ahead and do const handle stake submit. This will be a function. And what it's going to do is we'll get this amount here. So we'll do const amount, which we're going to actually have to convert it from the string to way. So we'll call it amount as way. We'll do equals utils.parse ether. We'll grab parse ether. We'll grab utils, again from ethers, utils from ethers, and we'll do the amount.toString. So we're going to grab this amount this state hook amount here. We'll turn it into a string. And then what we can do is we can return this approve function with this amount as way. Okay. Oh, and then we're getting a fail to compile. So in our hooks section, we're just going to do an index.typescript, and we're going to export this use stake. So we'll do export use stake tokens from /use stake tokens. Close that. We'll restart the server, and then I should import this from the right place. And I should import this from the right place as well. And let's get rid of the brackets here. Whoops, sorry. And let's do this as a .toString. Whoops, because you can't do a big number. Now let's save. It'll recompile. We'll pop into our front end here. We'll do a refresh. Our stuff is up. That's cool. Our stuff is getting logged out. Now, if we hit stake, we should call the approve function here. MetaMask pops up. We do get allow localhost to spend your dApp. This is amazing. We're going to reject this for now, though, because we don't want to bother testing it. So amazing job getting this far. We're hitting a button. MetaMask is popping up, and we're doing it. We're actually sending a transaction. This is incredibly exciting. Great work so far. Let's keep going. The approve function is working perfectly. It's working as intended, or we're kind of assuming it's working as intended, but that's great. This is perfect. So now we got to go one step further. We need to have this call stake after it's been approved. This is where we're going to do a little something called use effect. We can import it in here. We'll just do use effect, comma. What use effect does, it allows us to do something if some variable has changed. So the way that we're going to do that is we're going to say, okay, use effect, and it takes one of these functions as an input, and then we'll do a little comma here, and similar to those state hooks, we'll do an array of different things we want to track. And if anything in this array changes, we'll kick off this use effect and we'll do something in here. So one of these things that we definitely want to track is this approve ERC20 state. If approve ERC20 state, if this transaction comes back successful, then we want to do some stuff. So we'll say, we'll track this state, and we'll go ahead and say if approve ERC20 state dot status equals success, then we're going to go ahead and do like a stake function. And to do a stake function, we're going to follow this exact same methodology that we did for the approve. So first, we're going to use this use contract function thing. So we'll do const. Send is going to be stake send, and then state will be stake state. And this is going to be equal to, again, we're going to use contract function. This is going to be on our token farm contract. This is going to be our stake tokens function. And this will be transaction name. It's just going to be stake tokens. And that's it. So let's make this look a little bit more readable here. Lovely. So we have our little use contract bit here. And now this stake send, we can just call this right in this approve ERC20.state.status. We can just do stake send. And if we look back in our token farm, if we do stake tokens, we have an amount and a token address. So that's what we're going to have to put in here. We have to put some amount, and then token address will just be token address. Where do we actually get this amount from? Well, when we originally called this approve function, this is when we should actually do it. And you might be asking, hey, how come we wrapped this approve ERC20 into a function here, but we're not going to do that here? I'll tell you why in just a second. So what we're going to have is we're going to have a state hook for how much we want to actually stake. So we'll do const amount to stake and set amount to stake. It's going to be equal to use state. And we're going to start with 0. We're just going to get this defaulted right to 0. And what we're going to do actually is once we call this approve function the first time, we're going to set amount to stake to be this amount. And what we should do instead of calling this approve is we should call this approve and stake. Since it's this function that's going to kick off, yes, it's going to kick off our approve ERC20, but it's also going to change the amount that we're going to stake. And later on, once the transaction succeeds, it will also then kick off our stake send or our staking function. So we're going to change this to approve and stake. That means below we have to actually return approve and stake and not just approve. And for stake send, the amount is going to be this amount to stake, which we got from our original approve and stake. And then we just have to change this to approve and stake. And we'll change this from approve to approve and stake. And realistically, that's all we really need to do here. So if we save, we go back to our front end. Let's go to one of these that I actually have some of. I'll type in 1 for in here. I'll hit the stake button. And what should happen is approve will come up. I'll confirm. And once this actually confirms, then I'll be able to, another transaction should pop up telling us to actually stake. And that's exactly what happens here. So we've approved, now we can stake. We'll even watch MetaMask really quick here. I'm doing this on Coven, right? I just called this stake tokens function. For those of you doing this on Ganache, it'll be a lot quicker. But perfect, that was fantastic. Our balance even got deducted by 1. Now we have 1 of these tokens actually staked, and this is fantastic. However, there's obviously a couple issues here, right? What was happening during that whole section, right? There was no indication for us of what was really going on. We got no notifications. We're totally left in the dark here. Additionally, this page still looks disgusting. So we want to clean this up. We want to make this look a lot nicer. So how can we actually do this? So for switching between these, we want to actually just change our use effect here. So we do want to check this approve ERC20 state, but we also want to see if we switch the token address. We want to just check to see if approve ERC20 is done, if we switch our token address. And we also want to just check to see this if amount to stake actually changes. So if we do amount to stake, we want to check kind of during all these 3. If any of these 3 changes, we'll just do a quick check. Hey, is approve ERC20 done? If yes, great. Then we'll stake some tokens. So this is great, but we're going to want to get some notifications that these transactions are going through, these transactions are pending, and these transactions finish. So how do we actually add those pieces to this? Well, UseDApp has this thing called use notifications. This notifications bit will help us actually get notified on whether or not our transactions are completing. So to use these notifications, we're going to do a couple of different things in here. First, all the way back in our app.tsx, we're actually going to change our config here. We're going to add some notifications in here to check periodically if our things are done. And there's a couple of different parameters. There's a expiration period, and then we'll set it to be 1,000. This is in milliseconds, so we'll set it to be 1,000, which is just 1 second. And we'll do a check interval, also of 1,000. So basically we're saying, hey, every second, check the blockchain on our transactions that we send, please. Thank you. And now that we have this notifications bit identified, in our staking form, we can add this bit. So from use.core, we'll do comma, use notifications. And now we can actually start using some of these notifications. So right here at the top, we'll do const notifications equals use notifications. We can actually start working with some of these notifications now. We're going to want to see if anything in any of these notifications actually change. And if these notifications change, we're going to want to do something. So since we're going to want to check to see if notification changes, those of you who have been following along with what I've been explaining for use effect, you know that means we're going to want to use a use effect. We're going to say use effect. It's going to be this function. And if we don't have it imported, let's go ahead and import this from React, this use effect. We're going to be looking to see if these notifications change. We're going to be looking to see if our transaction has completed. So in our little watching array here, we're going to say, let's watch the notifications here. Let's make sure If any of those notifications changes, if anything on our MetaMask changes, we're going to want to do something, right? So we're going to say if there are any notifications that are approve ERC20 or transaction succeeded, we want to show, hey, good job, it's been approved. So to do this, we're going to say if notifications.filter. This is going to be a function based off the notification. On this notification, we're going to say notification.type. It's going to be transaction.succeed, and that notification.transaction name, then this is why we needed to give them names before, in our use state, is going to be approve ERC20 transfer dot length is greater than 0. Then we're going to do some stuff. Or transaction succeed. So we're saying if in these notifications, we're going to filter on a notification. If the type is transaction succeeded and the name is approve ERC20 transfer, then we're going to do some stuff. And for now, we're just going to do console.log approved. We can also then do the same thing for if notifications.filter on the notification.type. If that notification.type is going to be, again, that transaction succeed, and notification.transaction name equals stake tokens, capital T, stake tokens, and there are more than one dot length is greater than 0, then we'll do console.log tokens staked. Okay, so we've got some notifications put in. We're going to do a little console logging. Let's see if our use effect stuff is actually going to work. So let's go to our front end. We'll do a quick refresh. We'll go to where we have some tokens. I'm going to type 1 in here. I'm going to hit stake. I'm going to hit confirm. And we're going to wait a little bit. And if this confirms correctly, then we're going to see a little console.log printout that says approved. And we do indeed. And that's perfect. MetaMask pops up again for our stake tokens. We hit approve there as well. And we should see a little console.log out here for staked, token staked. And we do. Perfect. So now we have a way to actually track some of these notifications and track what actually happens on the blockchain. Console.logging stuff is great, but we want to actually see it in our UI here. What we're going to want to do is show a little waiting thing here while we're waiting for it to be approved, and then show a pop-up when it actually does get approved. We can add a little constant called isMining, which will be based off of whether or not the transactions are approved. So we'll do const isMining, and this will be equal to the state of these transactions. So this should actually instead be approve ERC20. This should be approve and stake ERC20 state. Now we'll say, isMining will be equal to approve and stake ERC20 state dot status equals mining. Should probably have it look like this. Then back in our use stake, instead of approve ERC20, I'm going to change this to approve and stake ERC20 state. And then we're also going to return approve and stake ERC20 stake to make this make a little bit more sense here. Get that little red line to go away. And now what we can do with this isMining thing is we can add this to our button. Now we have this isMining thing. It's going to be based off of whether or not approve and stake are done. So we can scroll down to our button and we can add a little disabled flag. So we'll say disabled equals, and it'll be equal to dependent on whether or not it's done. So we'll just add isMining. And if this is true, then disabled will be true. And if this isn't mining, then this will be false. We can also add this to be kind of like a little loading thing. So instead of just saying stake all the time, we'll do a tertiary operator. We'll say if it is mining, then we'll do like a little loading thing. Material UI has this thing called circular progress that we can use. It's like a little loading thing. So we can do, if it is mining, we'll do a circular progress. We'll say the size is 26 or whatever we want it to be. We'll close the tag out. And if it's not mining, again, we'll do this stake with a bunch of exclamation marks here. So now, if we save that, we'll go to our front end. It looks like I need to fix something. Can't find name approve ERC20 state. That's because we changed it. This is now approve and stake ERC20 state. So let's change it to that. Now let's save, go back to the front end, and okay, cool. Let's go to one of these that we have some stuff with. We have a little die. We'll do one here. We'll hit stake. And if we did this right, this should show a little loading thing while the transaction's going through. So we're going to hit approve. And perfect. We do see a little loading thing, and it should stay like this until the transaction finishes. This is a good way to indicate to the user that we've actually approved. Now I'll hit confirm for staking. So we didn't actually see the loading thing go back up again. So this probably means that we didn't actually reload this is mining correctly. And the reason we don't see the little spinny thing is because this approve and stake ERC20 state is really only tracking the approve, right? We have our const approve and stake, which does all this good stuff here. But our staking part, this stake state, we actually never use, right? And we need to pass this back to our stake form so it can actually know, what's going on. So what we can do is we can add a new state hook. We'll do const. We'll just call this one state. And then we'll do set state. It's going to be equal to use state. And this will be that approve and stake ERC20 state. We'll start it off there. And this will represent kind of the overall state, right? This will be the true approve and stake ERC20 state. But what we're going to do now is we're going to have to track both of those states. We're going to have to track both the approving and the staking. So we're going to do use effect, and we're going to track both of those with our little wonderful use effect stuff. So we're going to track them by doing, of course, approve and stake ERC20 state, and then stake state. So if either one of these change now, we're going to want to change this overall state function, and that is going to get pushed back to our stake form here. So what we're going to say is if approve and stake ERC20 state dot status equals success, then we're going to set state to be the stake state. Otherwise, we're going to set this overall state. We're going to do set state to be this approve and stake bit, or really just kind of approve here. Now we're going to pass this just kind of overall state variable here to our front end like this. To our stake form. And in our stake form, we're just going to map this state variable to the approve and stake ERC20 state. We'll save here. That should work perfectly. Great. Now if we go back to our front end, we'll go to die or whatever. We'll do one. We'll hit stake. MetaMask will pop up. We'll confirm. We do indeed get this little loading thing, which is perfect. Once it's done, once it's approved, we'll confirm again, and we get loading again. And this is perfect. This is exactly what we want, because now the user has a good idea. Okay, I need to wait, right? The transaction is going through. The transaction is being built. And once it's done, it's all set. So this is fantastic. We now have basically all the functionality for staking, right? We have approve. We have it doing some waiting. We have it actually staking. Let's clean this up a little bit, right? Let's make this look a little bit nicer. So first, we're going to go to index.css. We're going to add some bits in here. For a body, we're just going to do background color. We're going to set this to set a background color to HSL. We'll do 227, 61%, 26%. There's a whole bunch of tools. The background color doesn't really matter, but we'll save. We'll refresh our front end, and we'll get a nice little background color here, which is cool. But let's actually be even more creative than just this. Let's do a nice little linear gradient in here. We'll just get rid of this. Actually, we'll do background. We'll do linear gradient. We'll do 135 right here. We'll do HSL 227, 61%, 13%. Then we'll do HSL 227, 61%, 26%. We'll do one more. We'll do HSL again. This will be 227, 61%, 39% for some colors in here. Semicolon there. And let's look at our front and okay. We're getting somewhere. We got some cool double gradients going on in here. We'll go to our main section here and we'll do that use styles bits again. So right in our, looks like we don't have any material UI in here. So we'll do a little import, make styles from at material -UI -core. And right at the top, we'll do const use styles equals make styles, some theme, which we're ignoring. Nice little function thing here. And then for our titles in here, we'll do a little, make the color be theme.palette.common.white, which again, we're ignoring theme, but if we did have a theme, we would do it like that. We'll do text align center, do some padding, theme.spacing 4. And in our main, of course, we'll just add this in here, const classes equals use styles. And then we'll just put like a little section in here. We'll do an H2 where class name is going to be equal to classes.title. And we'll just call this DApp token app. We'll go back to the front end. We got like a nice little DApp token app. Nice and white right at the top. That looks good. We'll go to your wallet component. We'll add some styles in here. Looks like we don't have any styles in here, so we'll do the same thing. We'll grab make styles in here. We'll do a little const use styles equals make styles. A theme that we're going to ignore. Some fun little function syntax stuff here. We'll say tab content. Give this some styling. We'll say all the tab content stuff will have display of flex direction will be column, align items in the center. And then we'll do a gap for this, which will be theme.spacing of 4. We'll give our boxes some stuff. So we'll say box. We'll say background color is going to be white. We'll say border radius is going to be 25px. So give it some roundness here. Then we'll also do a header, which we'll just do color of white. And we're going to grab tab content. We're going to scroll down. This is going to be inside this little tab panel bit here. This div is going to have class name equals classes dot tab content. Oops, we got to add classes in here right before the return. So do const classes equals that use styles. We'll say this box. Well, we're not going to do the overarching box. This could actually just be this if we wanted to. We'll just say it's this first box. So this will be class name equals classes dot box. And then our H1 is going to be class name equals classes dot header. Let's save it and let's take a look. Whoa, this is already starting to look a lot better. Now, as you guys can kind of see, the functionality is really the important part behind the application, and doing a lot of this use style stuff is what's really going to make it look a lot prettier, right? So if you're like, hey, how do I do this pretty stuff? Now, I know I didn't really explain what any of this prettiness was doing. There's a ton of tutorials on doing CSS. That's basically what this is, that you guys can learn a little bit more to make your stuff look pretty. Now, it looks like for the most part, we have everything that we need to stake. I know we have the spinning wheel, which is great, but let's also add a little bit of an alert at the bottom to say, hey, your transaction has gone through successfully. So what we're going to do is we're going to pop back over to our stake form. We're going to wrap our input and our button into their own little div here, right? And that is going to put a little bit of space actually between our little component here and some other stuff, which is kind of nice. But what we're going to do is the reason that we're doing this is so that we can add some alerts. This section down here is where we're going to add some alerting. To do that, we're going to use what's called a snack bar and alerts from Material UI. You can look at both of these in the documentation. Provides a brief message about app processes and something like this. And we're just going to say, hey, you did it. Transaction has come through. So what we're going to do is we're going to import snack bar from Material UI. slash core. So we're going to do comma, snack bar. We're also going to import alerting, like a little alert box. Import alert from at material UI-lab/alert. And what this is going to do is it's also going to make these alerts basically. Down below our button and our input, we're going to do a little snack bar in here. Snack bar. And we're going to say this is going to open when we want to show that the ERC20 is done, which we're not exactly sure how to do that quite yet. We'll have it auto hide. Auto hide duration is going to be equal to about 5 seconds or 5,000 milliseconds. And then on close, we're also going to do some stuff. Inside this little snack bar, yes, I know we haven't filled this out yet. Actually, let's just do this for now. Have them blanks for now. Inside this snack bar, we're going to have some alerts where we say on close. We're also going to do some stuff. Severity is going to be success. And this alert is what's going to have our text in here. So we'll say ERC20 token transfer approved. Now approve the second transaction. And we're going to have 2 of these little snack bars. One is going to be for the ERC20, and one is going to be for staking tokens. So we're going to call this one token staked. Or excuse me, tokens staked. Now we need to define when these open and also when they close and what to do when they close. So this ERC20 thing should pop up when ERC20 has been approved. So we're going to want to create some variable that's going to track whether or not it's actually been approved. So we'll create another state hook here. We'll do const show ERC20 approval success, comma set show ERC20 approval success. This is going to be equal to use state. And we're going to start with false, right? We don't want to show this thing right away. And then we're going to want to do the same thing for staking tokens. So we'll do const show stake token success, and then set stake token success. And this will be also use state. And we will start this out with false. And what we're going to do is right now we're doing this console.log in here, right? And this is cute, but we want to actually turn this into changing show ERC20 approval success, right? So when this actually goes through, when notification says, hey, it's been approved, we want to say, okay, great, show that approval status. So instead of doing console.log here, we're going to say set show ERC20 approval success to true. And then we're also going to set show stake token success to false. Hopefully I'm spelling this right. Set show stake token success, and let's make sure that's spelled right. Great. And then we're going to do the same thing, but the opposite for staking token. So we'll get rid of console.log. We'll do set show ERC20 approval success to false and set show stake ERC20 to true. Now we'll say the ERC21 is going to open. And now we can also have these notifications thing track these two. If these ever change, we'll also run through this. So we'll grab both of these in here. So this use effect will now track these as well. And we'll say show ERC20 approval status. We'll open up the ERC20 alert. And then the show stake token success will open up the stake tokens alert. And then for both of these, we'll add a new function called handle close snack, which will just close it out and turn those variables that we just made to false. So we'll do const handle close snack. This will be a function, and we'll just say set show ERC20 approval status to false, and then set show stake token. I'm just going to copy paste it. This one also to false. Awesome. Now, if we go back, we refresh our front ends here. Looks like I forgot to do an on close. Okay, yep. We'll do handle on close snack here for the alerts as well. And there are no tags there. There are no brackets there, so I got to change that. But now, if we go to our front end, we'll do a quick refresh. We see everything in here looking great. Let's add one in here. We'll hit stake. This will pop up. We'll hit confirm. We'll get the little progress bar, which is exactly what we want. And you see here, now we get this little pop-up. It says ERC20 token transfer approved. Now approve the second transaction. This should go away after a few seconds or not. Let's just approve the second one. Oh, it looks like it now went away. So maybe it was a little bit longer than 5 seconds. And now we see the token stake popped up. Perfect. So we have some pop-ups. We have a little bit of ways to show the user how to do everything. Now you'll notice this doesn't look exactly like what we see in the GitHub repo, right? And this GitHub repo looks a little bit different. It's got this little slidey bar. It's got this second token farm contract for unstaking. However, a lot of what we're going to keep doing is just going to be a lot of more front-end stuff. And at this point, you pretty much should have everything that you need to build the rest of the contract. So what we're going to do is we're going to have the rest of this be a challenge if you want it. If you would like to complete it, you can absolutely add this second token farm contract with this unstake all WETH bit or unstake all FAU, DApp, etc. We're going to have two versions of this front end in here. We're going to have kind of this more cleaned up version, and then we're going to have a little bit more raw version. This one's the more raw version. All the code is going to be there. So if you want to say, I don't really want to code and follow this along, you can just copy paste the code. Or you can say, you know what, I'm going to do this unstaking part all myself, and that will be awesome. Also fantastic. You should be incredibly proud of yourself because at the end of the day, at this point, you have a way to stake tokens into a smart contract and build a front end, which is absolutely massive, absolutely fantastic. You should be patting yourself on the back. Excellent job, excellent job.
Let's go ahead and wrap this course up. Welcome back, friends. How do you feel? Good? Smarter? Empowered? Ready to take on the world? Excellent. Well, you absolutely 100% should be, and you deserve a massive round of applause because you have just done something fantastic. You have started your journey and equipped yourself with the tools to become an incredibly powerful, intelligent, smart contract engineer in this space. Now, I would be remiss if I didn't comment on security and audits when it comes to doing your smart contracts. As you know, all these smart contracts are available on-chain for anybody to see and anybody to work with. This means that having a security mindset is incredibly, incredibly important. And I highly recommend, if you're going to go mainnet, if you're going to take your application onto a real network where it's going to be securing a lot of people's money and a lot of people's assets, you absolutely need to get an audit. There is no excuse for not getting an audit and having an application that's securing a lot of people's money. Getting an audit is essentially just having somebody else peer review your code, looking for any vulnerabilities that could be exploited. An audit can be the difference between your protocol skyrocketing into the future and doing fantastically successfully, or dwindling, getting hacked, and everyone losing faith in your abilities. Audits are essential. We've got some helpful links in the GitHub repository associated with this course to learn more about audits, who to get them from, and some helpful tips on setting your smart contracts up to make auditors' lives easier. While we're talking about security, it's also helpful to know some of the most common attacks in this space. We've got another wonderful link in the GitHub repository that will show you some of these attacks and how to get around them and what they actually look like. Two of them that are big enough that I think I need to mention here are going to be Oracle attacks and re-entrancy attacks. These are the two attacks that I see happen most often. Unfortunately, right now in the state of DeFi, protocols get hacked for millions of dollars literally almost every day, and it is a travesty to the space that this is happening. Most of the time, these attacks are preventable. So understanding some of these security tips, doing your due diligence, and getting an audit is going to make both you as a smart contract developer and as a dApp developer and as a protocol better, but also the entire space is going to be more safe, secure, and easier for newcomers to get into. Thankfully, you can sleep a lot easier on those Oracle manipulation attacks because you've learned some best practices for working with oracles. You've learned how to work with a Chainlink decentralized Oracle network to get your data and do your external computation. Using a Chainlink decentralized Oracle network, or a DON, will solve these Oracle manipulation attacks so that you don't have to deal with people manipulating a centralized Oracle because you are going to be using a decentralized one. Reentrancy attacks are a little bit trickier to detect, but whenever you call an external smart contract, a smart contract outside your project, you especially should think, does somebody in that smart contract have access to changing some variables that I don't want them to change? Again, we have some wonderful examples in that GitHub repository associated with this course to teach you more about that. Additionally, I highly recommend everybody check out both Ethernaut and Damn Vulnerable DeFi. These are two games that show you some of the exploits and some of the low-level Solidity things you can do that you might want to look out for when you're writing your smart contracts. All right, so now that we've got the security piece out of the way, once again, huge congratulations for getting this far. You now have the tools to build a better world, to build these smart contract applications, and to empower yourself and your community with these blockchain applications. Now, the first question you might be asking is, Patrick, this is great, but where do I go now? What do I do? I have all these tools, I want to go use them. Absolutely. My first bit of advice here is going to say you can always learn more, and there's always going to be more places to learn and grow. And even though this course gave you a full setup of everything that you're going to need to get going and get off to the races and start building, it's good to know where else you can learn more and where else you can grow. Some amazing places are going to be Crypto Zombies, Dapp University, Ivan on Tech, ChainShot, Eat the Blocks, Patrick Collins, my YouTube channel, Austin Griffith's YouTube channel, Natter's YouTube channel, the Ethereum.org website, Chainlink blogs, and really any other material you can get your hands on. While you're learning, you should 100% be growing with the community. This is something that I've been pushing from the start. Blockchain and smart contract world is different from these corporate worlds. We are a decentralized open source group, open source ecosystem where we flourish if the people around us flourish. So growing and connecting with the community is an absolute must, and it's a way to really accelerate all the momentum that you're getting after taking this course. Twitter, the Reddit, Brownie Discord, the Ethereum Discord, the Chainlink Discord, there are all these Discords and all these communities that you can jump in, you can grow, ask questions, chat, spread ideas. Then once you're in these communities, then you can start really coding and tinkering more. Hackathons are some of the best places to put your stuff to the test and also really learn and build and grow. In the blockchain space, there are hackathons happening all the time. And these are places where you can show up, you can learn from some of the sponsors, you can build really cool things, and you can win prizes as well. We've seen some projects win a hackathon, go on to raise millions in seed funding and become $1 billion protocol. Some have gotten advisors from top investors like Mark Cuban. And these projects do wildly successful, but at the same time, we also see a huge uptick and a huge number of the newcomers in this space. People have never written a smart contract, never written any of the code, come in, try, learn, grow, and come out an incredibly powerful engineer with more networking and with more people around them who they know they can lean on and talk to in this community. So whether or not you want to win a hackathon doesn't really matter. Hackathons are a great place to sharpen your coding skills, get better, meet some people, maybe win some prizes. And a lot of these decentralized projects do look at the hackathon winners looking for some talent to pick up for their teams. A lot of the engineers that I work with right now, I work with them because they got picked up from a hackathon. So hackathons are great places to go. ETH Global, ETH India, and the Chainlink Hackathon are some of the best hackathons in the business, so be sure to check those out. All these decentralized protocols have a ton of work that people can be doing to help grow their protocol in some way. And they all have community grant projects where people can come in, propose some grant, propose something to the community, and that person builds it out. So if you have an idea on how to improve one of these decentralized applications, you can go ahead, propose what you want to improve, and if you get approved, you could be awarded a grant to work on that as well. You could become a smart contract consultant here. You can start offering your services to people who are looking for really strong Solidity and smart contract developers. You can start reaching out to some of these projects now that you have these skills. You can start reaching out to other people saying, hey, I've got a great idea of something I want to build, and I'm looking to take it to the next level. And that's the most important piece of advice I have for you here. Just build. Just have a good time and build things that you enjoy building. You'll learn the most, the fastest by building, tinkering, and trying new things. And this is also one of the best ways to meet people in the industry. Everybody that I work with in my life in this space, I work with them because I was building something and we became close because we were working on the same things. I feel incredibly lucky to have met and interacted with so many fantastic people in this space. And I hope that one day I'll get to meet and interact with you too. So good luck to you all, and let's rebuild this world. Let's make a world where there's more economic opportunity, there's more equality, and let's rebuild some of this institutional trust while having an absolute blast in this wild west that is cryptocurrency, smart contracts, and blockchain. Like I said, I hope to meet you all one day, and just do me a favor and make today an amazing day. Take care, everybody.